Dr. Charles Severance is one of the world's most popular programming instructors. In this course, he'll teach you C programming and object orientation with a little help from the classic C book from Kernighan and Ritchie. This is definitely the place to start if you want to learn C.
Welcome to C Programming for Everybody. My name is Charles Severance, and I'm your instructor for this course. This course and website is dedicated to learning the classic version of C programming language from the 1978 book, written by Brian W. Kernighan and Dennis M. Ritchie. This book places the reader in the middle of the 1970s transition from a hardware-centered computer science to a focus on writing portable and efficient software. C was used to develop operating systems like Unix, Minix, and Linux. Programming languages like Perl, Python, Java, and JavaScript and Ruby are all written in C. Software like early TCP/IP networking stack implementations that made the internet possible were written in C. And the first web browsers and web servers were written in C. Writing software in C enabled major advances in computer architecture and performance. Operating systems, compilers, and utilities could be recompiled to work on a new hardware platform once we had a C compiler for the new hardware. So much software has been written in C over the past 40 years that there's a very good chance that much of the software that you use every day was either written in C or written in a programming language that was written in C. So we study C less as a programming language to use on a daily basis and more as the foundation of modern software and computing. In many ways, C is the technology equivalent of the Rosetta Stone in that it provides a connection between the programming languages of the past and the programming languages of the present. The name CC4E in www.cc4e.com refers to the original Unix command cc, which was the command that you used to compile your C program. CC stood for C compiler, and it is featured on the first page of the first chapter of the K&R-C book. Programmers like me from the 1970s and 1980s typed CC on Unix systems like the AT&T 3B2 to compile and run their first Hello World program in C. This material is being presented under fair use as we are making use of material from a copyrighted work that is out of print and not broadly available in any format. The book is also not available in any accessible format. We are making use of this material in a teaching and research context with a focus on studying its contribution to computing history. The material is available for free and online to anyone who wants to learn about the history of the C language, computing, and computer architecture. Welcome to the course. Welcome to C Programming for Everybody. My name is Charles Severance, and I'm your instructor for this course. This course and website is dedicated to learning the classic version of C programming language from the 1978 book, written by Brian W. Kernighan and Dennis M. Ritchie. This book places the reader in the middle of the 1970s transition from a hardware-centered computer science to a focus on writing portable and efficient software. C was used to develop operating systems like Unix, Minix, and Linux. Programming languages like Perl, Python, Java, and JavaScript and Ruby are all written in C. Software like early TCP/IP networking stack implementations that made the internet possible were written in C. And the first web browsers and web servers were written in C. Writing software in C enabled major advances in computer architecture and performance. Operating systems, compilers, and utilities could be recompiled to work on a new hardware platform once we had a C compiler for the new hardware. So much software has been written in C over the past 40 years that there's a very good chance that much of the software that you use every day was either written in C or written in a programming language that was written in C. So we study C less as a programming language to use on a daily basis and more as the foundation of modern software and computing. In many ways, C is the technology equivalent of the Rosetta Stone in that it provides a connection between the programming languages of the past and the programming languages of the present. The name CC4E in www.cc4e.com refers to the original Unix command cc, which was the command that you used to compile your C program. CC stood for C compiler, and it is featured on the first page of the first chapter of the K&R-C book. Programmers like me from the 1970s and 1980s typed CC on Unix systems like the AT&T 3B2, to compile and run their first Hello World program in C. This material is being presented under fair use, as we are making use of material from a copyrighted work that is out of print and not broadly available in any format. The book is also not available in any accessible format. We are making use of this material in a teaching and research context with a focus on studying its contribution to computing history. The material is available for free and online to anyone who wants to learn about the history of the C language, computing, and computer architecture. Welcome to the course. Hello, and welcome to C Programming for Everybody. This lecture is putting C in a bit of a historical context. Now, if you're watching this lecture, you're probably familiar with some of my other classes. I just want to kind of let you know that I've been building a lot of classes. Most of you probably took Python for Everybody, available on Coursera, edX, and many other platforms. But I have a whole series of classes that are designed what I call the path of the master programmer, where I try to start people that no matter where you start, I want you to be able to learn to be a really good programmer and follow along as far as you want. These are all my materials. They're all 100% free, open, and online. And they're really aimed at teaching everybody how to program. I mean, I started doing this back in 2012 with Coursera, and I have dedicated myself to making all my materials free and to create a path that anyone can take anywhere in the world, regardless of economic challenges or other things in your life. I want everybody to have an opportunity to be a professional developer. So I encourage you, and frankly, if you haven't taken Python yet, like my Python for Everybody class, this course is going to be a little bit difficult. So let's start with a history of C. The book we're looking at, the Kernighan and Ritchie, the C Programming Language by Brian W. Kernighan and Dennis M. Ritchie, was published in 1978. And the key thing is that it is a moment in history where everything changed. And so we're looking at this textbook and the text in this textbook and the language itself in the context of how it has impacted history. The C programming language itself has a long history. There was a language called B, and they were using it at AT&T Bell Labs to build utilities and operating system stuff. But it was a little too word-oriented. And so this language C was, as new computer hardware came out that supported byte addressing and the ability to load a string of bytes and store a string of bytes rather than a set of words, words being larger than a byte and more than one character were packed into words, and kind of like the 60s and early 70s. C wanted to make a character a sort of core, low-level kind of data that the language would happen. And from the early and mid 70s, the C and Unix kind of co-evolved. They wanted to build something that would make Unix work well on a PDP 1120, and at the same time make it so they could port Unix to other systems. But really, it was about the PDP 1120's cool memory architecture having to do with byte addressability. And what happened was they were carefully rewriting Unix in C, but then fixing C, laying the groundwork for Unix portability. And so by 1978, this K&R C book was published, and at that point you could think of it as a summary of over a decade of research in how to build a portable programming language and then use that portable programming language to build a portable operating system, C and Unix, of course. By 1989, the C had become popular and there was a need to standardize it, so there's a variant of C called C89 that is the ANSI, and then that same version was called C90 as ISO, the International Organization of Standards, also standardized that. And so that was our first version of the C that we could all agree on. The ANSI did not intend to go too far away from what we call K&R C, but instead it just sort of nailed down a few things that by then were important to nail down. And C has continued to evolve from sort of 1990 to the present, and there's a number of major revisions, but the key thing that these revisions don't do in the modern version of C is they do not attempt to make C easy to use language, say like Python or JavaScript, and C knows its place in the panoply of languages and does a good job of that. So if we look at sort of what's the future, C is a difficult language to use as a general purpose language. Python is a great general purpose language, but it's not a great systems programming language. And the two things that are missing from C are the lack of really solid dynamic memory support in the core types and libraries. And then there is no safe string type. There's no string in C. It's character arrays, and arrays have sizes. And if you start putting stuff beyond the boundary of that array, things just blow up. And C++ is, to me, not the sort of future version of C. It's really a more powerful, intricate, and flexible version of C for programmers who are doing really professional, intricate systems applications. Writing good C++ in some ways is more difficult than writing good C. The languages that sort of take on in C's mantle in the general purpose are things like Java, JavaScript, C#, or Python. The key thing with these languages is they don't give you sort of strings as just raw byte arrays. And they give us a simple object-oriented layer that keeps us away from the metal. The goal of C is to get close to the hardware, close to the metal. And so Java, JavaScript, C#, Python are all great languages, and they're great for what we use them for. They're just not well suited for writing an operating system kernel. The most likely language that is like C, like the next C, is probably Rust. The idea of Rust is that it stays close to the metal, but then gives us some simple and safe core data types. And recently, Linux is starting to accept some Rust in Linux. And so that means that Rust has to be mature. It means that Rust can't be like evolving rapidly. I've seen situations where operating systems like Mac OS decide to depend on Python. So there's parts of Mac OS that depend on Python 2, but then they can't really upgrade to Python 2 because of their operating system, blah, blah, blah. So for an operating system to depend on a programming language like Rust, it really has to be mature and, even more importantly, stable. You can't have clever innovations in the programming language causing regressions in an operating system, say like Linux. So I look for Rust. Now, C has been around a long time. Before C, we'll call C starting in 72, the book is published in 78. Before C, most of us would write assembly language or Fortran. Some people wrote PL1 that's not on here. Fortran is not really a general purpose programming language. You wouldn't write a command like cat in Fortran. Fortran was really for scientific computations, and the earliest of computers in the 50s, 60s were either sort of really specialized toward like payroll and HR systems, or they were really specialized to doing computations. And the ones that specialized were the science ones were used Fortran because it was just the right language for those computers that were aimed at doing scientific calculations. C as a language was kind of none of the above in that it was aimed at writing system code, a kernel, an operating system, and the utilities around it, including like other languages. And so C is kind of the mother tongue of all kinds of other derivative languages. And things like the Bash shell, Perl, Python, PHP, C++, JavaScript, Java, and C# and Objective-C just kind of were derivatives of this beginning of C. And that's why you see a lot of patterns in these other languages that are similar. And that's because JavaScript and Java both inherited their for loop syntax from C. So I've got a couple of videos in this section. This is Brian Kernighan and talking about the C programming language, and it's a short video. I didn't produce this video, but it's a great little video. Another video is from the creator of C++, Bjarne Stroustrup. This was an interview that I did with IEEE Computer Magazine. On top of this history of the C language, we can look at a brief history of computers. And I have a whole course called Internet History, Technology, and Security that really starts in the 1940s with a focus more on communication rather than computation, even though communication and computation were very much connected throughout the 40s through even today. In the early 1950s, computers were, you best think of them as like a multi-million-dollar strategic asset. Every single computer, and a lot of them were custom built. The first computer at Michigan State University, where I went to undergrad, was built by the electrical engineering students of that university, based on some designs that they'd borrowed, I think, from Iowa. And so things like the programming language, the operating system, you didn't have a lot of generalization. You didn't have a lot of sharing. You tended to write code and put it on a paper tape or later a magnetic tape and load it and run it. And so you were just pretty happy if the code worked. You didn't need an operating system. These weren't multiprocessing computers. And so the software environment was very minimalist. But in the late 50s and early 60s, you saw companies like IBM and Digital Equipment Corporation began selling general purpose computers. They just couldn't make them. And they started selling them. And they still were expensive, and they were only in, like, a business would have a couple of computers to help them do payroll, perhaps, or something like that. Something that was really, really important because the computers were expensive. But in the 60s, we really got to the point where the computer componentry, the chips, etc., were becoming commodities. You could just go to a place and buy chips, and then you could make a computer by buying a bunch of chips and putting those things together. And because you weren't building everything from scratch, the cost got a lot lower. The other thing that these less expensive computers were is they were a little slower. But by the end of the 1960s, there was a lot of computers. There were some, super expensive, weird, one-off, small production computers. There were computers that there was like the previous generation of mini computer where there were lots of them laying around old computer science departments or businesses that they weren't sure what they did with to do with them. They wanted to buy a new one. And then there were just innovative new low-cost computers coming out. And in the 70s, in this milieu of just lots of new and old computer hardware, the question was, is there a way we can do things with all of this old hardware? And is there sort of one solution? And that's where Unix and C came. And certainly after the 70s, we look at the 80s, and that's where microprocessors and personal computers. And so we went from computers that were sizes of refrigerators or desks to the size of a computer could be on a single chip. And in the beginning, those personal computers like the IBM PC or Commodore PET, they had really bad performance, but that performance, once you could get everything on a single chip, that performance could get faster very quickly. And because personal computers became a mass market item, a lot of money could be invested in personal computers. By the 1990s, personal computers continued to grow, right? And but the need to communicate and talk and exchange information became important. And so in the 1990s, we saw really an increasing focus on connecting computers with the internet and other kinds of networks. And the performance of these computers and the price kept going down, the performance kept going up. And then by the time we get to the 2000s, Amazon's AWS was founded in 2002, and it used personal computer microprocessors like from Intel and produced computing as a commodity. Right? And so you don't even buy computers anymore. You just go to Amazon and say, I'll rent a computer for $7 a month. And so we see in 1978, we see this moment where we are going from, the computers were becoming more common, they're going down in price, and there's getting to be more and more of them, and there was a diversity of computers. These days, there's actually less diversity. If we go back in history and you take a look at my internet history class, you can see I go to Bletchley Park and show you some of the earliest computations from the 1940s and World War II. We go to Computer History Museum in California and visit with Gordon Bell and talk about the PDP-1, and he talks a lot about buying the components and putting the components together and how sort of the mass availability of relatively low-cost components really allowed for a rapid innovation in computer architecture. A computer that I used in my computer science degree was the Control Data CDC 6500, and I have a video where we visit the Living Computer Museum in Seattle, Washington, and hear card readers work and card punches. And if we ever get to the point where everything opens back up again, it's a tremendous visit to go see all the technology that really through the years, except that in the Living Computer Museum, they like to have everything running. And then you can take a look at a more modern, smaller, the Raspberry Pi, which the Raspberry Pi is actually not an Intel-based system. The Raspberry Pi is based on ARM, the processor that really became popular as a result of the cell phone revolution. And so the Raspberry Pi is to take what the technology was advanced, both low power and high performance technology that was advanced because of mobile phone innovations. The Raspberry Pi came out and was a good single board computer. So let's take a look at the operating system. Unix is the operating system that is connected with C. In the 1960s, there was a multi-user operating system called Multics. And then in the 1970s, they wanted to come up with yet another operating system, and they eventually called it Unix. And the DEC PDP 1120, which was one of these new commodity part-based computers that was coming into the marketplace. And so in 1973, Unix was rewritten in C, but it only was there on the PDP-11, although they had laid the groundwork for portability from the beginning. They knew they wanted to have everything be portable. They just couldn't make it all portable. The first version, they just had to make it run on the PDP-11. And then by 1978, the second computer that Unix had run on was an Interdata 832. And that was quite a different computer. And so it was good. And so they really learned a lot about making Unix a portable bit of software. In the early 1970s, C was evolving in a way so that the Unix could be ported, right? So it's like, we got this problem between, let's just say, the PDP-11 and the Interdata. And how can we fix this? And we can both change how the operating system works, we can change the operating system code, and we can change the C compiler, and then we can rewrite the operating system code to get less and less assembly language and more C language. And so the idea was to get to the point where there was a very, very small amount of assembly language in Unix. And over the years, that's gotten lower and lower. Unix was rewritten. A number of versions came out in the 70s having to do with their portability. So by 1978, the Unix version 7 could also run on a whole new architecture from DEC called the VAX systems. The University of California, Berkeley had their own distribution of Unix called BSD, the Berkeley Software Distribution. And that was really cool because universities often pushed things like networking, TCP/IP, ARPANET. BSD Unix was the first place some of us saw TCP/IP. 1982, a company based solely on Unix called Sun Microsystems was found. Sun was some work at Stanford, some work at Berkeley, all based on Unix, and they created what in effect was the Unix workstation marketplace. At this point, you could imagine that the world was about to just adopt Unix. Unix was the greatest thing ever. Computer science departments were teaching Unix in their operating systems classes in the mid-80s. The problem became AT&T had never come up really with a business plan for what the purpose of Unix was, and so there was some fits and starts as to how they could monetize this extremely popular thing. And they didn't do a great job, and it took them a long time to figure out what was going to be successful. And by the time AT&T sort of figured things out, the market had moved on. And so Minix is an operating system that was developed in the Netherlands by Andrew Tannenbaum, and he built a completely free and open source operating system that was used for education. He built a textbook around it, and it was very popular. But he didn't want commercialization, at least not at that point in time. So he sort of held on to it too tightly. Again, kind of an intellectual property mistake. And in 1991, a program called Linus Torvalds decided he was going to build a fresh ground-up implementation of the Unix kernel that was 100% free. So he wasn't going to use Unix, he wasn't going to use Minix, he wanted to create another thing. And originally it was just like a hobby. I'm going to try to see how far I can go. By 1992, Linux started to work, and it adopted this license called the GPL, which is called the GNU Public Library License, which is a strongly open source license in the way that it's difficult to take Linux out of open source, which meant that people could then invest in Linux. And so Linux has become Unix, right? Linux in the modern world is the Unix-like system. And Unix tried to hold on for a while, but they really, really couldn't. And so the remaining Unix distributions are a tiny, tiny fraction of the marketplace, and Linux is the marketplace. So we can see some of this in some of the videos that I've got, like Andrew Tannenbaum will tell us the story of how Minix was created and how Minix kind of begat Linux, and so that there's some interesting stuff here, okay? So I'll lay on top of all this. Remember that 1978 is this moment in history where I claim like everything changed. Now, I've been a computer scientist for a very long time. I started in 1975. And in 1975, I learned things like Fortran on a computer, that CDC 6500 computer. It ran a special operating system called Scope Hustler. I knew how to do assembly. I knew to do Fortran and even Pascal. So Pascal in the 70s was one of these languages and I've got a video for Pascal as well, one of these languages that was sort of like saying, look, here's the future. Now, Pascal was really aimed at teaching, and so I used Pascal in an educational context. And as I became a professional programmer in the 1980s, I was using a bunch of stuff, assembly language, COBOL, a little bit of Unix and C here. It wasn't like by the early 80s, Unix was everywhere, at least not in the professional world, because the PC revolution was happening. So we had DOS, we had early Windows versions. I used things like DBase and Turbo Pascal. I taught classes of the IBM 360, and I taught assembly language. I used the DEC-VAX, and I used the VMS, not Unix operating system, and Fortran. And I also then taught in the mid-80s on an AT&T Western, I think it's called a GE AT&T 3B2. I taught Unix, I taught C, and I taught Fortran. And so even though we can trace back to like 1978 is the moment that everything changed, it's not like the market changed. The thing that happened in the 1990s, though, is that all these older computers, and the older computers vendors like Burroughs and Unisys and IBM and Cray and Control Data, as microprocessor speeds increased, all these little companies would create Unix workstations that were faster and faster and faster. And because they could build new hardware that was fast and then grab the Unix operating system, and make their operating system work on their new hardware, it allowed for some amazing innovation. So I was using Sun, Ardent, Stellar. These are all gone now. IBM RS6000, Convex C2400. I had a Next on my desk. I used C. But TCP/IP, Windows, HTTP, the web, and Windows and Mac OS were all kind of in the mix. But the innovation was really happening most rapidly in the Unix space. But by the 2000s, everything that I touched really had some aspect. I'm not a Windows person, so everything I touched had some aspect of Unix in it. Mac OS still has Unix in it, Linux, and my languages were sort of narrowing back down to Java, PHP, and JavaScript. And then in 2010s, right? Linux, Mac OS, Python, PHP, JavaScript. So things really have settled into a world, my own software development, where I'm pretty much using Unix-like systems all the time, and C-based or C-derived languages, because Python, Java, PHP, and JavaScript are all based on C. And that's why it's so important to understand C. I'm not writing C as a professional in any way, but I am using all my C knowledge every single day. And so that's a sort of a picture of me in my office. That's an IBM PS2 in my office. I was registering in 1989. I was registering with punch cards. When I first started, I was using a line printer and punch cards, and so there's my history. Now, I think it's important to acknowledge that, as I've shown you all these history documents and the videos and the oral histories that I've done, there is a preponderance of old white males in here. And I think that it is important to talk a bit about that and why that is, perhaps. And so I would encourage you to take a look at an article. It's an NPR article. It's actually you can listen to it, about what happened to computer science. The title of the article is When Women Stopped Coding. All the way up to 1980, computer science was just another field. And then it kept going up to sort of 1985, and then it went down. And so, all these other fields have a pretty good gender mix, and the computer science does not have a gender mix. And so I would encourage you to listen to this article. Another area that you can learn something about the diversity in computer science is this book by Jane Margolis called Unlocking the Clubhouse. The essence of the book is really talking about how social pressure, advertising pressure in the early 80s made it seem as though computing was a guy thing. And in particular, it made it so that young men, even in high school, would go fiddle around with computers as a hobby. And by the time they got to college, they were pretty skilled. And if you weren't skilled, the college classes were designed for people who already knew what programming was. And if you were a woman and you hadn't played with computers in 1980 when you were like 14 years old, you came to college at a distinct disadvantage. And this is what led to this fall off, where colleges tended to teach to programmers who already knew how to program. And that really meant that the hobbyists, people who are in their youth before they went to college and played with programming as a hobby, had a tremendous advantage. Now, Jane did her work in the 80s, late 80s and 90s. I myself am older than that, and I think that to some degree this notion of the social pressure that said that computing was really for young men and not young women, it's actually as much a symptom as it is the cause. Because I grew up in a time in the mid-70s where there were women everywhere. And this is a person who had a really large impact in my life. Her name is Helen Spence. She was a professor at Michigan State University, and I show you a URL to look at her oral history. She taught me operating systems. So in 1977 or 1978, I don't remember when, Helen was my operating systems teacher. The interesting thing about how Helen taught operating systems was she made it fun. It was really fun. I encountered my first autograder in Helen's class. She had made a piece of software that she called the HMS 5050, which itself is both Helen Spence and I think it's Her Majesty's ship at the same time. And what she did was she built a operating system simulator in Fortran, and our job as taking the class was to build functions and subroutines that would implement the tasks and the algorithms that operating systems need to do. So you'd run your program over and over and over again until you had written a successful operating system, and she wrote a autograder that would do things to your program and then measure whether or not you knew how to build an operating system. It was just a natural thing to have females as faculty members, and it was just there was a lot more fun in the field. And I have my own theories that I think complement Jane's theories as well, but I'll leave it here. That's a TED Talk for another day as to gender in computing. Right now I'm just acknowledging it and giving you some resources to read and reach your own conclusions. If you look at everything I've done since 2012 in the free online education in MOOC space, you'll notice that every course I've ever created has the words "for everybody." And that's not just a marketing thing. That's because it's my philosophy. If you've taken some of my classes like Python for everybody, or Django for everybody, web applications for everybody, Postgres for everybody, and now C programming for everybody, I try to build a course where I spend time thinking about how not to create the clubhouse that Jane talks about. And that is, I want you in the club. I want everybody in the club. I don't want it just to be a club for the super geniuses. And so part of why I'm building an entire curriculum is to perhaps just make a new club. And that is Programming for Everybody Club. And I think once you become a great programmer, I think that's a good time to study computer science. And so perhaps after we teach everybody programming, then we can teach everybody computer science. But again, that's a TED Talk for another day. So on to the course, C Programming for Everybody. I'll just say that C is the most important programming language you're going to ever learn. It should never be the first programming language taught to any students. You will likely never write a line of C in a professional context in your career. I'm not teaching you C so that you can go be a professional C programmer. I'm teaching you C so you can be a professional Java programmer, really. But if you learn C at the right time in your learning journey, it's a necessary step on the path to becoming a master programmer. But it's an important step, because I can't teach you Java if I hadn't already taught you C. I have to explain how Java works in terms of what you're going to learn in this class. So this class is not just like get a C certificate and go make lots of money, because I don't think that this certificate's going to make you a lot of money. But I do think this certificate is going to unlock the future of you as a programmer. So, please be patient with this material. Do not rush. It's an online class. I guarantee that you can search for solutions to every programming exercise that I create. I don't change them that much, so the solutions are out there. And if your goal is to game it and just search for solutions to programming, go ahead, finish the class. Congratulations. But you have just taken the opportunity to learn from yourself, right? You didn't trick me. I didn't lose anything by you searching for and just pasting in solutions to programs. Each exercise, from beginning to end, is trying to take you a little tiny step further down your understanding. And the easy exercises in the beginning, even if I have a bunch of them, they're there to prepare and strengthen you for something much more challenging in the course. If you start pasting in solutions in the beginning of the course, you have no chance in the end of the course. And you're just going to be pasting in solutions. And when you do that, you'll have only wasted your time. So, I look forward to you taking the rest of this course. I look forward to you telling me if I'm right in my instinct about how important this is for you, especially after you take a few more classes and then find your way to being a professional.
That Bell Labs, bunch of smart people. I call it 1,200 PhD level people in Murray Hill in basically one giant building. And so that's a lot of people rubbing up against each other. And they're all doing technical kinds of things. And the environment did not tell people what to do. It was go do your thing. And once a year, one side of one piece of paper, tell us what you did. And that will determine how much money you get next year. But it was a very long cycle. The one extra thing is that it was a problem-rich environment. And so there were things that you could work on, and there was this, I think, very gentle gravitational drift towards doing something that somebody else might care about. Now, lots of people, who cares what other people think? I'm going to do my stuff. But I think most people got some reward, psychic reward from, I do something, I give it to you, and you say, that was great. And then you say, and you tell me all the things that aren't yet great. But that kind of thing was very common at the labs because AT&T at that time basically supplied telephone service to most of the United States, 1 million people, all kinds of interesting problems in and around communications. And so no matter what you were interested in, there'd be some part of AT&T that could probably make use of that. So that was part of it. But then there was the external world as well. The research community, Bell Labs was just part of the academic research community. So they were both outlets, and the labs was perfectly happy to have people do either. And so all of that, I think, worked out really very well. And it helped to have stable funding, because basically at that point, if you made a long-distance phone call in the United States, remember the concept of long distance, right? If you made one of those calls, a tiny slice of the revenue of that financed Bell Labs with the charter of make the service better. And we won't worry about the details of how you do that. So at the time, there was a lot of interest in programming languages. This all came out of the Multics experience, right? Where people at Bell Labs and, of course, the folks at MIT had realized that writing things in a high-level language made sense. And then the question is, what's the high-level language? And they started with PL1, which in the abstract sounded like a good idea, and in reality was a horrible idea because it was a horrible language. And so Martin Richards from Cambridge, University of Cambridge, had this language called BCPL, and he had spent, if I understand it correctly, a sabbatical year at MIT, planted the language in some sense. And it was much simpler, much cleaner, much better suited to system programming kinds of things than any version of PL1 would have been. And so the people at Bell Labs, Ken Thompson, Dennis Ritchie, and so on, had gotten some experience with high-level languages as suitable for writing lots of different things. BCPL wasn't a suitable thing for modern machines because it was typeless. And newer machines clearly were coming on stream that would have types like bytes and integers and maybe bigger things. And so at some point, Ken did a lot of experimenting. It was Ken Thompson did a lot of experimenting with simpler versions even of BCPL, a particular one called B, which was an interpretive language, no compiler. And that was, again, expressive enough that people started to like it. And that's sort of where I started in on this. I mean, I had written bits of PL1. It was awful. I'd written Fortran, better. But the B was sort of nicer to use, but it was still typeless and an interpreter as well, so it wouldn't be terribly efficient. But with the PDP-11 in the offing, and I don't remember the exact timing here, it was clear that a version of something that felt sort of like B, but which had some mechanism to include types so that you could talk about characters or integers, was going to be the way to go. And that's where Dennis picked up and started developing the C language and the compiler to go with it and so on. Portability was very much on people's minds at that time because although the core Unix work was done on the PDP-11, there were other machines at the time that were, in the same equivalence class. Interdata had a couple of 732, 832, numbers like that. And I think there were probably HP machines as well, and et cetera. And the other thing that was in some ways harder was that there was the big mainframe kind of computers that were used by the local computer center. And these were fundamentally stripped down versions of the Multics machines. They were GE 635 kind of things. And so those were big, clunky, word-oriented machines. They were, in effect, IBM 7094s cleaned up a bit. And getting something that would compile sensibly for those machines that really didn't have characters in a language which had become what it was, so it could manipulate characters. I think there was a bit of a strain there. But that portability, how do you get the same language to work on different computers? And Dennis's original compiler really was targeted at the PDP-11. And Steve Johnson came along with the portable C compiler, which basically separated the front end. Okay, let's recognize the language, let's build some intermediate structure, and then let's generate code for different kinds of machines. I had written a tutorial on B because, I thought it was interesting. Maybe I can tell other people how to use it. And so when C started to be used, and I became somewhat better at using it, then I basically repurposed the B tutorial, brought it forward and made the C tutorial out of it. And so I used C for essentially all the software that I was writing at that time. And, kind of liked it. It was good. It was a nice match for the way people think about computing, I think, but also a very nice match for the actual hardware of the time. You could imagine what the compiler was doing. All of it was clear, so efficient and expressive, and nicely matched to everything around it. And then somewhere in probably 1977, early-ish, I coerced Dennis into writing a book about it. First edition came out in '78, and at that point the language was pretty reasonable. The book, I think, it was right on the cusp of whether structures were fully part of the language or not. A bit of overhang there, and I don't remember, but I think probably they were not quite, but awful close. And since Dennis was doing both compiler and book, it was at least a consistent viewpoint. The question is, can you pick up a structure as a unit and pass it around, or do you have to do something special? But that's a milestone. And then the next one is probably the 1988 book and the development of the ANSI C standard, the first standard, which is essentially, again, about the same time. And so I think those are the ways I measured. And at that point, call it 1988, give or take, just before you encountered it, C was probably just fine for anything you might reasonably want to do. And this is probably heresy or something, but I don't think that the changes in evolution since then have brought enough in some sense.
Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 0, Introduction. C is a general-purpose programming language. It has been closely associated with the Unix system since it was developed on that system, and since Unix and its software are written in C. The language, however, is not tied to any one operating system or machine, and although it has been called a system programming language because it is useful for writing operating systems, it has been used equally well to write major numerical, text processing, and database programs. C is a relatively low-level language. This characterization is not pejorative. It simply means that C deals with the same sort of objects that most computers do, namely characters, numbers, and addresses. These may be combined and moved about with the usual arithmetic and logical operators implemented by actual machines. C provides no operations to deal directly with composite objects such as character strings, sets, lists, or arrays considered as a whole. There is no analog, for example, of the PL1 operations which manipulate an entire array or string. The language does not define any storage allocation facility other than static definition and the stack discipline provided by the local variables of functions. There is no heap or garbage collection like that provided by Algol 68. Finally, C itself provides no input-output facilities. There are no read or write statements and no wired in-file access methods. All of these higher-level mechanisms must be provided by explicitly called functions. I would note that the lack of a heap or garbage collection feature in C is both one of the great strengths of the language and at the same time is likely the reason that the average programmer will never develop or maintain a major C application during their career. C provides a simple feature using malloc and free functions that allow a programmer to request a certain amount of memory be allocated dynamically, use the memory, and then return the memory to the C runtime library for reuse. For example, to convert a JPEG image to a PNG image, our application will read the JPEG data into memory, then convert the image into a PNG image in memory, and then write the PNG data out to a file. We don't know how large the images will be in advance, so we request whatever size we need from C and then give it back when we're done. The term heap refers to the memory that C manages on our behalf when we need to borrow a bit of memory and give it back later. There are a couple of issues with a simple heap implementation. First, if we forget to call free when we are done with the memory, we have created a memory leak, and our program will eventually run out of memory and abort. C places the onus of giving back any dynamically allocated memory on the programmer. Modern languages like Java, JavaScript, and Python keep track of when we stop using dynamic memory, using a dynamic memory layer that can automatically reclaim the memory. The more difficult problem is after a series of calls to malloc and free, the heap space becomes fragmented and some cleanup is needed. This cleanup is called garbage collection. Efficient memory allocation and garbage collection has been the subject of decades of computer science research. The Java language has built a number of increasingly effective garbage collection approaches over the years. Kernighan and Ritchie, in one simple paragraph, define most of the problem as out of scope for the C language, which makes it a bit challenging for us to make good use of dynamic memory allocation in C. But when we do it properly, it performs very well. If you are currently using a language like Java, Python, or PHP, every time you create a new string through concatenation without thinking about memory allocation, remember to appreciate the decades of work by computer scientists that made it easy for you. Kernighan and Ritchie knew that garbage collection was difficult, so they left it out of the C language and put it into a runtime library. Back to Chapter 0. Similarly, C offers only straightforward single-thread control flow constructions, tests, loops, grouping, and subprograms, but not multiprogramming, parallel operations, synchronization, or coroutines. Though the absence of some of these features may seem like a grave deficiency. You mean I have to call a function to compare two character strings? Keeping the language down to modest dimensions has brought real benefits. Since C is relatively small, it can be described in a small space and learned quickly. A compiler for C can be simple and compact. Compilers are also easily written using current technology. One can expect to prepare a compiler for a new machine in a couple of months, and to find that 80% of the code of a new compiler is common with existing ones. This provides a high degree of language mobility. Because the data types and control structures provided by C are supported directly by most existing computers, the runtime library required to implement self-contained programs is tiny. On the PDP-11, for example, it contains only the routines to do 32-bit multiplication and division and to perform subroutine entry and exit sequences. Of course, each implementation provides a comprehensive, compatible library of functions to carry out input-output, string handling, and storage allocation operations. But since they are only called explicitly, they can be avoided if required, and they can also be written portably in C itself. Again, because the language reflects the capabilities of current computers, C programs tend to be efficient enough that there is no compulsion to write assembly language. Instead, the most obvious example of this is the Unix operating system itself, which is written almost entirely in C. Of 13,000 lines of system code, only about 800 lines at the very lowest level are in assembler. In addition, essentially all of the Unix application software is written in C. The vast majority of Unix users, including one of the authors of this book, do not even know the PDP-11 assembly language. I would note that in this preface, the authors are carefully explaining the fact that many of the well-established programming languages of the 1960s and 1970s, like Fortran, COBOL, Pascal, ALGOL, and PL1, were solving many of the use cases that were needed by us programmers by adding syntax to the languages. The creators of C and Unix were advocating for a more minimal set of programming language constructs and more reliance on calling function in provided runtime libraries to meet programmer use cases. It may have seemed a strange approach for experienced programmers in the 1980s, but over time it has allowed C to expand to meet a very wide range of programmer needs without requiring major revisions to the core language or compiler. Back to Chapter 0. Although C matches the capabilities of many computers, it is independent of any particular machine architecture, and so with a little care, It is easy to write portable programs, that is, programs which can be run without change on a variety of hardware. It is now routine in our environment that software developed on Unix is transported to local Honeywell, IBM, and Interdata systems. In fact, the C compilers and runtime support on these 4 machines are much more compatible than the supposedly ANSI standard versions of Fortran. The Unix operating system itself now runs on both the PDP-11 and the Interdata 832. Outside of programs which are necessarily somewhat machine dependent, like the compiler, assembler, and debugger, software written in C is identical on both machines. Within the operating system itself, the 7,000 lines of code outside of the assembly language support and the I/O device handlers is about 95% identical. As a note, before Unix and C, if you were running the vendor operating system and writing in the best language for systems like the PDP-11 and Interdata 732, the user experience was completely different. Today we take for granted that we expect to be able to download the same application for Windows, Mac OS, or a Linux system. Even in the 1970s, those that were using Unix and C could write code once and move it between 2 hardware platforms and expect that it would work with no or relatively few changes. Back to Chapter 0. For programmers familiar with other languages, it may prove helpful to mention a few historical, technical, and philosophical aspects of C for contrast and comparison. Many of the most important ideas of C stem from the considerably older but still quite vital language BCPL, developed by Martin Richards. The influence of BCPL on C proceeded indirectly through the language B, which was written by Ken Thompson in 1970 for the first Unix system on the PDP-7. Although it shares several characteristic features with BCPL, C is in no sense a dialect of it. BCPL and B are typeless language. The only data type is the machine word, and access to other kinds of objects is by special operators or function calls. In C, the fundamental data objects are characters, integers of several sizes, and floating point numbers. In addition, there is a hierarchy of derived data types created with pointers, arrays, structures, unions, and functions. C provides the fundamental control constructions required for well-structured programs: statement grouping, decision-making with if, looping with termination test at the top using for and while, or at the bottom using do, and selecting one of a set of possible cases, switch. All of these were provided in BCPL as well, though with somewhat different syntax. That language anticipated the vogue for structured programming by several years. C provides pointers and the ability to do address arithmetic. The arguments to functions are passed by copying the value of an argument, and it is impossible for the called function to change the actual argument in the caller. When it is desired to achieve call by reference, a pointer may be passed explicitly, and the function may change the object to which the pointer points. Array names are passed as the location of the array origin, so array arguments are effectively call by reference. Any function can be called recursively, and its local variables are typically automatic, or created anew with each invocation. Function definitions may not be nested, but variables may be declared in a block-structured fashion. The functions of a C program may be compiled separately. Variables may be internal to a function, external, but known only within a single source file, or completely global. Internal variables may be automatic or static. Automatic variables may be placed in registers for increased efficiency, but the register declaration is only a hint to the compiler and does not refer to specific machine registers. C is not a strongly typed language in the sense of Pascal or Algo 68. It is relatively permissive about data conversion, although it will not automatically convert data types with the wild abandon of PL1. Existing compilers provide no runtime checking of array subscripts or argument types, etc. For those situations where strong type checking is desirable, a separate version of the compiler is used. This program is called lint, apparently because it picks up bits of fluff from one's program. Lint does not generate code, but instead applies a very strict check as to many aspects of the program as can be verified at compile and load time. It detects type mismatches, inconsistent argument use, unused or apparently uninitialized variables, potential portability difficulties, and the like. Programs which pass unscathed through lint enjoy, with few exceptions, freedom from type errors about as complete as do, for example, Algol 68 programs. We will mention other lint capabilities as the occasion arises. I would note that separately checking for things that might be wrong into the lint program keeps the C compiler simple and easy to port to a new computer. The lint program was naturally a very portable text processing application. While there's some overlap between a lint program and a compiler, over time there's quite distinct research and expertise in how to lint versus how to compile. Modern lint programs look at programs in far more detail than most compilers. Separating concerns of lint and the C compiler also allowed lint programs to use more memory and take more time to execute than compilers. Since the typical developer might use the compiler many times per day and run lint less often, it was nice for the compiler to run quickly and make light use of computer resources. We call this idea of building two smaller complementary programs that each specialize in one task separation of concerns, and it is an important principle in computer science. By keeping each component simple and focused, we can more easily build, test, and verify each component. Unix and C showed the benefits of taking many small components approach to solve an overall set of problems. Back to Chapter 0. Finally, C, like any other language, has its blemishes. Some of the operators have the wrong precedence. Some of the syntax could be better. There are several versions of the language extant, differing in minor ways. Nonetheless, C has proven to be an extremely effective and expressive language for a wide variety of programming applications. The rest of this book is organized as follows. Chapter 1 is a tutorial introduction to the central part of C. The purpose is to get the reader started as quickly as possible, since we believe strongly that the only way to learn a new language is to write programs in it. This tutorial does assume a working knowledge of the basic elements of programming. There is no explanation of computers, of compilation, nor the meaning of an expression like n equals n plus 1. Although we have tried where possible to show useful programming techniques, the book is not intended to be a reference work on data structures and algorithms. When forced to make a choice, we have concentrated on the language. Chapters 2 through 6 discuss the various aspects of C in more detail and rather more formally than does Chapter 1, although the emphasis is still on working examples of complete, useful programs rather than isolated fragments. Chapter 2 deals with basic data types, operators, and expressions, and Chapter 3 treats control flow, if-else, while, for, etc. Chapter 4 covers functions and program structure, external variables, scope rules, and so on. Chapter 5 discusses pointers and address arithmetic, and Chapter 6 contains the details of structures and unions. Chapter 7 describes the standard C I/O library, which provides a common interface to the operating system. This I/O library is supported on all machines that support C, so programs which use it for input, output, and other system functions can be moved from one system to another essentially without change. Chapter 8 describes the interface between C programs and the Unix operating system, concentrating on input-output, the file system, and portability. Although some of this chapter is Unix-specific, programmers who are not using a Unix system should still find useful material here, including some insight on how one version of the standard library is implemented and suggestions on achieving portable code. Appendix A contains the C reference manual. This is the official statement of the syntax and semantics of C, and, except for one owns compiler, the final arbiter of any ambiguities and omissions from earlier chapters. Since C is an evolving language that exists on a variety of systems, some of the material in this book may not correspond to the current state of developments for a particular system. We have tried to steer clear of such problems and warn of potential difficulties. When in doubt, however, we have chosen generally to describe the PDP-11 Unix system, since that is the environment of the majority of C programmers. Appendix A also describes implementation differences on the major C systems. This recording of Chapter 0 of the 1978 C programming book, written by Brian Kernighan and Dennis Ritchie, is part of my C Programming for Everybody course, where I teach C from a historical perspective. My name is Charles Severance, and I'm the teacher of the course. Hello, and welcome to C Programming for Everybody. I'm Charles Severance, and I'm your professor for this course. In this lecture, we are going to do a very rapid translation from Python to C. So as I've shown you in our earlier lectures, C is kind of like the mother tongue of advanced programming languages. Python itself was written and still is written in C. And Python is deeply influenced by C, even though the syntax looks very different, right? And if you've taken all my other classes, you will have seen PHP, you'll have seen JavaScript, and to some degree even CSS takes some of its inspiration from the syntax of C. And so I'm not intending for this to be your first programming class. I intend for you to be an expert in Python. Well, not expert, but certainly I'm not going to tell you what an if statement is. I'm not going to tell you what a variable is. I'm going to just tell you how to use variables in C, and I'm going to tell you how to use if statements in C. And so that's why a solid foundation of Python, not wizard, but solid foundation of Python is essential. And frankly, I would rather that you learned a bit of PHP, some JavaScript, and all this other stuff before you come. I think that C programming is not the first class that you should take, but instead it is your gateway to the advanced work that you're going to do. And so I think C is very, very important. I just don't think it's your first programming class. So you might think Python and C are not very different, although Python is written in C. Python has white space. That is part of its syntax. C, white space is ignored. I do like C better in that. Python is very object-oriented. If you read an article I wrote on Quora, you'll see I rank all my languages, and I put JavaScript and Python as the most object-oriented languages. Java is a little less object-oriented, and C is like the least un-object-oriented. C is not object-oriented at all. Python has wonderfully convenient data structures in the form of lists and dictionaries. PHP has arrays, and JavaScript has objects. All beautiful, beautiful stuff. They're very object-oriented structures. C does not. It's fast, it's efficient, it's powerful, it's got structs and pointers, and by golly, you will use them, and they're not convenient, but they are scorchingly fast. And by the time we're done with all this, we will see how to use structs and pointers to build lists and dictionaries. And that really is, we will follow down the path of building Python. So you'll see a common theme throughout this class of how Python achieves what it's trying to achieve by writing C. Python has automatic memory management to the point where if you've been a Python programmer, a PHP programmer, a Java programmer, or JavaScript programmer, you probably don't even know what memory management is. Well, you're going to by the end of this class. And by the end of this class, you're going to be able to see how Python automates memory management for you, right? Python is written in the 80s and C was written in the 70s. In many ways, I see Python as a convenience layer that was built on top of C. Just C programmers look at C, it's like, it's great, it's great, it's great. If we just had this layer of easiness on top of it, then things would be better. And so that's what Python is. Now, Python also introduced things like quite different syntax to make it indentation, required because they thought it was a good idea. So we could argue one way or the other. I mean, I'll tell you, when I'm writing a million lines of code, white space is not, to me, a good way to have syntax. So we're going to look at C through a Python lens, and we're going to learn by example. Now, most of the time, I tell you, don't copy and paste. Don't cheat. Don't look for solutions. This lecture is the exception to that rule. I've written this lecture as a Rosetta Stone. It's just a little tiny bit of connection to what you already know in Python to what you're going to do in C. And so I'm not intending at this point for you to build your own stuff based on reading a book. I actually just want you, and if I give you assignments to do these particular things, I really do want you to just watch this lecture, grab the PowerPoint, and feel free to cut and paste from my PowerPoint into my assignments. Because this is, I don't know if you've ever seen it, where the mama tiger is teaching a baby tiger how to hunt, and the mama tiger goes out and gets something or other and brings it back and puts it near the baby tiger and lets the baby tiger chase it. Well, that's kind of what I'm doing. I'm the mama tiger, and I'm giving you some C code, and I'm putting it right in front of you, and then I want you to take that C code, and I want you to run it and play with it and understand it. So I'm not expecting in this lecture that you're going to derive it, that you're going to sort of somehow read the textbook, look at a problem, and solve the problem. That's later. That's absolutely later. So this is the beginning. This is trying to make connections, conceptual connections to the complex knowledge you have about Python to little places where you can hook things onto in C. And so the idea is to go through it quickly. So I do assign some of these as programming exercises. It's intended for me, my intent is that you'll watch the lectures and just work on the code at the same time. I'm not trying to test what you learned. I really want you to watch and listen and type. That's how we learn, right? You could cut and paste it, or you could type it, and you could type it one piece at a time. And the mere act of you typing, even though you're just looking at a slide and typing it in, at this point in the course, that is the learning objective of this lecture. Now, that whole rule of just typing code in that you're looking at from someone else, don't do that forever. Later, I want you to do things like synthesize what you learn in the book, synthesize it, struggle through it, and figure things out and do the assignment yourself. So don't go searching if you want to gain maximum benefit. If you're just in the biggest hurry of all, just go ahead and search. But please, if you want benefit from this class, don't cheat yourself. There's a lot of similarities that I'm not going to cover. You can go read the textbook, like the plus, minus, asterisk, slash, and percent. Hey, probably when you were learning Python, you're like, whoa, what's this percent thing, and why did they choose percent? And the answer is, that's what C chose, and so modulo is just percent in all these other languages because they flipped a coin in C and decided percent was modulo. The comparison operators, the assignment operator is equal sign, which means that the equality operator's got to be double equals, exclamation equals, less than, greater than, less than or equal, all that stuff's the same. Variable naming rules, the same. You start with a letter, underscore, and then numbers, letters, and underscores, and case matters, both languages. While loops, the concept of break and continue, which, some people get all worried about. I love break and continue. If you've taken my other courses, and you'll see when we talk about it in C, I love break and continue in C too. Maybe because I learned C first, and I just love breaking. And okay, enough about that. I love breaking and continue. Okay, enough about that. Constants. About the only thing that's really different in constants is like strings and characters and booleans. And strings and characters are like the biggest thing in the beginning. Both have int and float and char and byte. Now, again, byte and string and char are not the same thing. C has no str class, which is the string class, list or dictionary. And Python has no concept of struct or double. And in a sense, you could think of Python's float is really C's double, right? And so by the time Python was written, the notion of shorter floating point numbers is less critical. There are some differences. A lot of this, I think, was in the design of Python, trying to be a little less obtuse and a little more convenient. For me, it's annoying. I write the C versions of the operators like and, double ampersand, not as exclamation point, we call that bang, or double vertical bar. And in Python, they're all convenient. We use the word AND, but okay, whatever. So there, in C, we have a for loop, but it's an indeterminate loop. If you remember the definition from Python for Everybody, indeterminate loop is one that you have to examine to see if it's got an infinite loop. Whereas in Python, if you say for X in some list, you're going to go through the whole list. It's a determinate loop. It only runs until that list is exhausted. C does not have such a thing, right? It just, every loop has got a condition to finish it. Now we write loops like for I equals 1 to 100 or 0 to 99. We write them and you can look at them and say, yeah, that's not an infinite loop. It's just technically you have to look at the loop to make sure that you haven't inadvertently made an infinite loop. There's no predefined true and false. I find this really like, wow, couldn't they got EOF, capital EOF for end of file in C. None and null are similar concepts, but quite different. None in Python is its own type. Null is the number 0. That's cast to be a pointer to nothing. And so none is like specially marked empty. Null is a 0. We'll get there. We'll get there. Strings and character arrays, for a while you can kind of pretend that character arrays in C are mostly like strings, like when you throw a constant and you pass it to a function. They kind of look the same. But like once we start working with them, you'll see they're very, very different. And that's kind of the first fun part of the first part of this class, is like strings are now your responsibility. There's no help, right? And C, of course, has no list or dictionary, and Python has no concept of like tightly packed data, which is what structs are, and doubles and floats. So here we go. Let's get started. Let's see if my pen is working here. Yeah. So what we're going to see is on one side, we're going to see some Python. On another side, we're going to see some C. And so this is just talking about output. This is Python 3, of course. And so we have a print function, and it takes any number of parameters. One of the things you'll notice about the print function is like hello space world. Well, that's part of this constant. But answer comma 42 puts a little space in between answer and 42 in the output. So if you want to suppress that kind of automatic addition of spacing, you have to maybe concatenate things together or some other trick. The print statement automatically knows if it's got a string or a float or an integer, and it just does things kind of all automatically. And so if you want to see something, usually you just print it. Okay? So let's take a look at the compare and contrast. So first off, you pretty much are going to have to start every one of your C programs with pound include standard io.h. Comments are different. Python comments are pound sign to the end of the line. C comments are /* across multiple lines to */. So everything in between there, that can be multiple lines. Later versions of C also add the what's called the C++ style of comments, and JavaScript uses those as comments, which is the /. So when you're writing, you probably can use // in the C that you're using, but I'm kind of being kind of strict, and so I'm pretending I'm in 1978, so I'm not using that C++ style comment. Again, that came from C++, it didn't come from JavaScript. Some of you have taken Python classes where there's this like __ main, and it calls this thing, and it makes a function and calls it and indents everything, one tab. And they're really imitating C in that respect. And I don't like that style. I think those people who do that in Python, I'm sure they have a good reason, but I think they're just like wishing it was C. Because the definition of C is code, a program starts, when it starts running, it searches for a function named main, and later we'll see that this function can actually have arguments, and it returns an integer as to the success or failure. So really, main is a function. And so that first line there, int main open paren, close paren, open curly brace, that is the definition of a function that happens to be named main. And then we have printf. Now, again, I don't know if you learned Python 2, but in Python 2 there was a print statement. In Python 3 there is a print function, and so here we're using a Python 3 print function, and C never did the statement. So C decided, as we'll talk about later, to not have any input-output, any reading or writing in the language itself, but instead put them in standard libraries. And that's what this pound includes stdio.h is saying. Okay, I'm going to do some I/O here, input-output here, and so include the C input-output library. Okay, and so printf takes as its first parameter a string. The other thing you see in C is you can't use single quotes for long strings. Later we'll see single quotes, but in C there's a major difference between single quotes and double quotes. Single quotes are single characters, and double quotes are a character array. Not a string, character array. The other thing is things like the end of line. So in Python, the new line is added implicitly. In C, you have to add it explicitly. And so that's basically saying print hello world and then go to the beginning of the next line. Now, this first parameter is actually not just a string. It's a string with embedded format codes that start with %. %D says there is a corresponding integer number, and I want you to convert that into a string and print it out. I guess I should probably just re-erase some of this. So it says answer and then a number. And so you can have more than one of these things, and then they match. So that says there's an integer as another parameter. So you can have one parameter, two parameters, etc. And so for beyond one parameter, like in this one, x %.1f, that corresponds to this first floating point number, and this %d corresponds to the integer one. Okay, so you have these % things. Now, we will learn that these % things have a language unto themselves in Chapter 8. And this is basically saying, please print me a floating point number with only one digit of precision, right? So %.1f says print a floating point number. And then if we want a string, it's %s, but this really, Sarah here, double quote Sarah, double quote, is a character array, and it's actually not 5 characters, but 6, because there is always a terminating 0 character at the end. And so %s says the parameter needs to be a character array and properly terminated by an end of string indicator, which is a 0 character. So that's this, right? It's pretty simple, but we got a lot of stuff to cover here. And this is the Rosetta Stone. It's more complex than C. You have more control. You're doing things that more explicitly, and it's not doing it for you automatically. So let's take a look at a simple number input. Now you'll see that some of these things come from my my Python for Everybody class. This is the famous US floor to European floor elevator converter. So we're going to print something out. Now one thing about C is that you've got to declare all your variables. Python is sort of a typeless language. It's increasingly getting more typey, but it's a typeless language. So we have to declare that we're going to have two variables, USF and EUF, and they're going to be integers. We print the statement. About the only difference there is we have to put the \n in, otherwise it won't automatically do that. And then we have this IO routine, again coming from stdio.h, called scanf. And its first parameter, much like printf, is actually a formatting string. And what this says is read for a little ways, find me a number, as long as it seems like a number, keep reading, and turn that into an integer and give it back to me. And so it actually has got some scanning built into it. And it reads until it finds a non-digit and then stops and says that's the number. So it turns out in C, the way you could type a lot of different things here. We won't go into that too much detail. We'll hold that until Chapter 8. But the idea is it doesn't work exactly the same. Although this input in Python reads a line. Now, again, I got this little note here. If you recall, in Python 2, there was an input and a raw input. And raw input was what read a line, which I tended to use when I was teaching Python 2. Input was a weird thing that had some kind of scanning thing going on, and it scanned and threw stuff away, and it grabbed something, and it might go to multiple lines, and it was totally inconsistent, and it was worse than scanf. So I was really glad when they just got rid of it in Python 3. And then they changed the name. What used to be Python 2's raw input became input in Python 3. So the old input from Python 2 is kind of like homage to scanf in C, but it's not exactly the same. And the reason it's not the same is the input in Python 2 was deriving the type of the data from what it encountered. So it might give you back a string, it might give you back a floating point, it might go like, oh, that's dangerous, right? And that's because the type of USF in Python here is determined. It's not pre-declared. So It's known because we're going to convert it to an integer. And by the way, both the input and the scanf, we can write stuff that confuses it badly and causes it to blow up. But we're not worrying too much about that right now. We're just kind of getting the basics done. So we read an integer, we subtract 1, we print it out, right? We read an integer. Oh, I forgot to say this ampersand. Call by reference and call by value. So in Python, this is coming back as a function return, so it's really easy to assign it into USF. Whereas in C, we put these parameters on a scanf call, and we have to say, oh, and by the way, I want you to change it, because ultimately, if we don't put ampersand on, it's what's called call by value, not call by reference. And ampersand USF is a way to tell C to actually give it the address of the USF variable rather than the value in the USF variable. And in that is a whole chapter that we will cover, like I think 4 and 5 will be all about the ampersand and call by reference. Now, we're way ahead because I don't think chapters 1 through 4 would, all they ever do is mention call by reference and then say, oh, that's in the future. So I'm going to just say, oh, that's in the future. I will tell you that ampersand is really important and the code doesn't work without it because it is the way that C does call by reference for simple variables like integers and floats. As you're going to see on the next slide, there's always an exception. String input. Okay, so here we're going to, this will help my hello Sarah thing, right? We say enter your name and then we say name input. Now the beauty is here in Python is input gives us the whole line, okay? And then we just print hello name and you'll notice that there's like this little space that comes out automatically. So switching over to C, we have our included the library, we have the int main, which is the, and then we have to pre-declare a character array. There is no like make it a string. If this were Python, we could say, hey, let's make a string, but you can't. And what's even more important is you got to tell it how long, which means that we could type too much stuff in here and blow our program up. And that's one of the difficulties of C is the fact that arrays, including character arrays, have fixed length and they don't auto-extend. There is no dot append in C. You can't like say, oh, name dot append. You can't do it. Python, it's an object. It's not an actual array. Python, it's an object. Name is a string object. Here, name is a character array with 100 elements, and if you put 20 in, you'll be fine. If you put 80 in, you'll be fine. If you put 101 in, it's going to blow up. Ah! Well, that's okay. That's why C is fast. We'll get to all that. So we print out a prompt and we say scanf and we say, in this case, %s, give me a string, and you can put a limit on it. So we're saying, look, only read up to 100 characters. And you'll notice there is no ampersand on name, and that is because name is an array. And so when you put name in with no square brackets, no index operator, then you're passing the address of the beginning of the array. And so that is, in a sense, an ampersand. That is the location of the beginning of a 100-character array. We're going to scan up to 100 characters into it, and so it really is roughly equivalent to the input. And then we just, again, say hello %s, and then name is the corresponding thing, and so it says hello, Sarah. Now, a lot of what we did in Python for Everybody is read whole lines of input, and we tended to use string parsing of those lines, like we would trim the stuff off the end and then we'd split it and do all these things. There's no good split in C, so we won't be doing too much of that, but it does help to understand how to read a whole line of input. So now we're going to read something that doesn't have it has lots of spaces. We're going to read the whole line, and we're just going to echo the whole line, right? Enter line, read the line, print the line. So now we're going to have, again, we have to declare how big of a string we're willing to take. Char line with 1,000 characters in it. The prompt by now should be pretty easy, and we have a really weird looking % square bracket caret \n close square bracket 1000s. Well, if you took Python for Everybody and you remember chapter 11, regular expressions, that should look familiar to you. Open bracket caret \n close bracket says match any character that's not a new line. So that says scan up to the end of a line, or until you hit 1,000 characters. That's what percent, open square bracket, caret, \n, close square bracket, 1000s means as the first parameter to scanf. Read a whole line, but stop at 1,000 characters. And then, of course, a line is just a parameter, and then we print that thing out. Okay, and so a lot of C programmers probably never written this particular line of code, but it gives you a sense that there's a lot of sort of programmability. And things like regular expressions that that Python had, well, those are kind of an old concept. Those are 1970s concepts. This C language had that concept in it in 1970. There's another way that's a little safer to do this, and these are the exact same thing where this command fgetS. So fgetS says put it into up to 1,000 characters, looking for a new line, and reading from what's called standard input. So in C there are 3 basic files. One is the standard input, which usually is read through up to EOF, standard output, which is where printf is going, and then there's a thing called standard error, which is where you send error messages that you don't just want to go to the output. So the input and the output, like if you're going to make a program to do uppercase, you would read your input, you would uppercase it, and then send it out. But if, for example, you encountered a character that you didn't want to copy and you wanted to send an error, says, I'm not going to copy, you wouldn't just send it to standard output, you actually send it to standard error. When you're running just on a terminal, like in your command line, standard input is your keyboard, standard output is your screen, and standard error is your screen. So you can see both the error messages and the output of the program. But if you're running sort of with redirecting input and output, you do tend to still see the error message on your screen, and it doesn't end up hidden in some standard output. But in this case, we're using fgetS, which is part of the standard library, and we are saying read this from standard input. Now, you'll see in a second when we read a file, fgetS can read a file, and that third parameter is the file handle, but there are 3 predefined file handles in C programs: standard in, standard out, and standard error. They're all named stdin. That's their name. They're predefined constants in the C standard stdio.h library. Okay, so now we're going to read a file. We do this a lot in Python. We go get a file handle, it reads it. This might fail, of course, if the file doesn't exist. Then we got a nice determinate loop. Remember we talked about indeterminate loops and this for in. It's so Python-y and it's so awesome and it's like so expressive. I love it. I miss it. Okay. And then line.strip, which takes the new line off. And so that's going to read, just reads the little file, writes it out. So we have to create a variable. We'll call it 1,000 characters. In Python, we could have any length of characters in our file and it would work. But in C, now we're going to have to actually say we can only handle up to 1,000 characters because we've declared the line that we're going to use, the line variable we're going to read this in, has 1,000. There is a equivalent to the handle. File is a type. It's defined in stdio.h, star hand, which means it's a pointer to a file object. And hand equals fopen, romeo.text r. So that's 2 character arrays, romeo.txt and r. And actually, the open in Python is inspired by the fopen in C. And that's because, again, when they were writing Python, they were writing it in C. Why don't we take an open? And all they did was made the open in Python be a little easier. So we don't have any kind of a IO for in, so we have to write our own while loop here. So we're going to call fgetS line, give me up to 1,000 characters from the file handle named hand. And fgetS returns null, which is a constant that's defined in stdio.h, if it reaches end of file. So this basically is a loop that says read everything up till end of file. Very similar to this for line in hand. And then we're printing it. Now, I don't have to strip it because fgetS actually takes the new line that is the end of each line. So in Python, you would get double spacing if you didn't strip the new line at the end of each one of these little things, right? Each line. Whereas the fgetS is nice enough not to give us the new line. So there we go. So a counted loop. Now, this honestly is not one of my favorite things in Python, but this range is a generator that's going to generate the numbers 0 through 4. For I in range, this is effectively kind of a dynamically generated set. And then we're going to print it. So we're going to 0, 1, 2, 3, 4. In C, we of course have to declare that I is going to be an int. And the for loop has 3 pieces separated by semicolons. There's the initialization piece. Now, PHP and JavaScript are the exact same thing, so if this looks familiar to you, that's because you took those classes. Congratulations. So for I equals 0 is the initialization. That says before the loop starts, set I to 0. Then there is the middle part is the test, whether or not the loop should run or continue to run. It's a top tested loop, and so I less than 5 must be true or the loop won't run at all. But given that I is 0 at the beginning, it's less than 5, so it's going to run at least once. And then each time through the loop at the bottom, after the loop is run, we're going to add 1 to I with a I++, a post-increment operator. And again, that line of code, PHP, JavaScript, Java, all look the same, except PHP has $signs for variable prefixes, which, bothers me, but it is what it is. And of course, we have a block, curly brace, open curly brace, and close curly brace denote the block, and then we simply print the variable out, and both bits of code produce the exact same output. So if we get a little bit trickier, we're going to do take an example from my Python for Everybody class and look at the max and min. And because we need to prime the loop, we're going to set our max val to none and the min val to none. And we're going to do a middle tested infinite loop. While true, we're going to read the input line, each line, like 5, 2, 9. We're going to strip it just because. We're going to check to see if it's the string done. If it is, we're going to break out of the loop, right? And then we're going to convert it to an integer. And we're going to check to see if max val is none or the value we read is greater than max val. We're going to remember it. And if min val is none or the value we just read is less than min val, we're going to remember it. And when the loop finally reads all the way through, we're going to print out the maximum and the minimum. So this is pretty much the same code, except we're using scanf with a %d format input format and scanning into the val integer variable and using ampersand to indicate that it's called by reference and to replace the current val. And then the rest of it's the same, right? If it's the first one or we've got a larger one, we keep it. If it's the first one or we got a smaller one, we keep that one as well. We loop through and it all goes. Now, one thing that if we're using scanf, as I mentioned before, scanf doesn't sort of stop at the end of lines. It keeps on going. And so if I have 5, 2, and 9, and again we have to use Control D or EOF here to finish this, or we have 5 space 2, 5 space 9, and then EOF, it does the same because scanf is just looking for an integer. It's algorithm. We'll see this in chapter 8, but the thing that it does, it's like, get me an integer, which means throw away stuff that's not an integer. So away you go. So that's a slightly more Cythonic version of this min-max using scanf. And it doesn't suffer from the problem of using getS and having to worry about the size of the arrays, character arrays. Here's a guessing game. That's one of my favorite applications. So we have an infinite loop, the ultimate non-determinate loop, a loop that you got to examine to know that it's going to finish. And in this particular one, we're just looping to EOF. You're using try and except. Why? Because line doesn't give you any return indication that it's hit into files. So we just have to have it blow up and then do an except and then jump out. Oh well. So we throw away the new line and then we convert the line to an integer. And we say, if guess is 42, nice work, and then break, which gets out of the loop. The break affects the loop, not the if. And then elif, guess less than 42, too low, else print too high. So this is a classic multi-way if, where you can have an if, you can have kind of as many elifs as you want, ... and then an else. We can do the same thing in C. We're going to use the scanf pattern, waiting till we see EOF. If the guess is 42, we print nice work and then break. Now we have to have curly braces here because that is a 2-statement block. And so if you're having more than one statement, you've got to do curly braces. And then else, this else matches up with that if. Else if guess less than 42, printf. Now, modern programmers would tend to put curly braces even though this is only one line, but this printf is the statement connected to the if. And it does not need curly braces because what comes after an if is a statement or block of statements with curly braces. And the same is true of this else. The printf is the single statement. So you'd not seeing curly braces here. And I would write this with curly braces, but because the authors of the book are really very succinct, they tend to not put curly braces in, so I'm calling your attention to that. Now, a really important thing to call your attention to is the difference between else space if and elif. Now, the high level is what we're doing in C is not really a multi-way if. What we're doing in Python is truly a multi-way if. This if and elif and else are really part of the same block of code. But this else if is two keywords. And so if you look at the first if, the first if has one block of code, which is the printf nice work and the break. And then the else clause of the first if is this entire block of code here, which is if guess less than 42, printf yada yada, and then another else. And so this is a block. So this is a block if, and in the else clause, there is another block if. And so if you look at this, really the indentation of this stuff ought to be in this, like the else if part in the else, that indentation should be further in. Now, by convention, we don't de-indent, we don't add that indentation, even though it's technically correct, because this is an else, and then there's one statement, and that statement is the if, okay? And so we use this idiomatically all the time. It looks like a multi-way if, else, but it's not. It's actually a further and further deeply nested else if, an else with an if inside the else, and then another else with an if inside the else. We just don't indent it. We indent it by convention as if it were a multi-way if. You don't need to know this precisely when you are writing code, but I just want to point that out in case, like in the back of your mind, you're like, why does Python call it elif, which is one reserved word, and why does C not have an elif, but instead has an else if? I think when Guido invented Python, he said, look, that's a cool convention. Let's make it actually part of the language rather than a idiomatic use of the language. Okay, enough of that. Okay, calling by value functions. This is pretty easy, right? There's no def keyword. You have the return value, the name of the function, and the parameters. And then, of course, before the curly braces, you have to have the type of the parameters. Those are not the type of the variables in the function. Those are the type of the parameters. In Python, you don't need to tell it what type they are. Python is kind of a flexible typeless language. The type of a variable goes right along with it. You could be inside MyMult and say, what kind of a thing is A? And then A could be an integer. It could be a float. It could be whatever. It could be a string, right? Because that's an object, and an object can have a type, whereas A is just a number, and you have to tell it in C, that number that's coming in, it is an integer. And if someone miscalls it in C, like put 6.0 here, it just blows up, doesn't work right. I mean, it might do something, it's just unexpected, right? So there's no cleverness. Now, there might be some checking. You might get a compiler warning that says, how come it's an integer here and it's a floating point here? That will be dangerous, but it won't fix it for you, and it doesn't automatically convert it. Whereas if you did this in Python, it would automatically convert. So you have a far greater responsibility to match your types up in C. Things like return statement pretty much functions the same. It was, the Python return statement is an imitation of the C return statement. You do have to declare your variable types that are going to be used temporarily inside the function. Scope-wise, right, this C is not outside. We will see later when we get to the functions chapter about external values and static values, etc. But the default scoping is that any variable that you declare inside of a function only lives inside the function. There's no A, B, or C in the main code. And that's the same as how Python works. Whew, that's a lot of Rosetta Stone. We talked about input-output, we talked about looping, we talked about reading a file, we've talked about strings, which are really character arrays. We've talked about float. And later, we're going to learn a lot. And chapters 5 and 6 are the crazy chapters, but we're going to play with how would we implement some of the things that Python strings, lists, and dictionaries handle. And before this course is over, we're going to come back and get inside the mind of what it would take to build Python using the C language. So we'll see how alloc, structures, pointers, etc., character arrays can be used to build string object, list object, and dict object. And that, to me, is the learning objective of this course, is not so much how to code C because it's your job, but what in C is necessary to make a higher level language like Python or JavaScript or Java or C# work. And we'll get to that before the end of the course. It is a long course, and again, this was a long lecture. This takes some time to absorb, and just zooming through this, you achieve nothing if you just do the homework without understanding it. So take your time. I put the lines in this lecture, the lines of code, are there very much on purpose. Every single one is trying to teach something. So I hope you'll take the time to learn all this material. Cheers. Hello, and welcome to Chapter 1 of Kernighan and Ritchie. My name is Charles Severance, and of course I'm your professor for this course that's about history. So, welcome to this course. It's really part of a learning path. I don't think that C should be your first programming language, and I don't think it should be your last programming language. I have a whole series of courses that are all free and available online, both just on the web, on places like freeCodeCamp and Coursera and edX. And the place that you're at in my learning path is that you're at right now is C programming. And we're not learning C programming to learn C programming. We're learning C programming to take a historical look at how computers work and lead into computer architecture. I'm not trying to teach you coding in C, but I am going to explain how computers work and things like how Java works using C as kind of like it just gives me a way to explain Java to you. So, the outline of the textbook is kind of pretty typical computer science textbook where it starts off easy and then, whoa, everything goes pretty crazy. So chapters 1 through 4, and we're on chapter 1 right now, is mostly syntax, and it's just another programming language, and especially if you know a little bit of Java or a little bit of PHP or a little bit of JavaScript, some of that syntax is going to be like, whoa, of course this is familiar. And the answer is, well, that's because all those languages came from C. So it kind of feels like just another programming language, except that arrays are not lists and character arrays are not strings, and character arrays kind of look like strings, but they don't work like strings, and you can get in all kinds of trouble. But other than that, once you sort of stop worrying about how long things are, pretend it's okay, which is dangerous, of course, when you write code. Chapters 1 through 4 feel a lot like you're just any other programming language, but then chapters 5 and 6 are the valuable chapters of this book, but they also become a lot more difficult. So don't give chapters 1 through 4 short shrift, because 5 and 6 are going to just go woo. And then 7 and 8 is just sort of filling in detail, and 7 and 8 are not so critical. It just kind of fills in all the gaps. So that's the outline of the book. Just expect that 1 through 4 is going to be smooth, and then 5 and 6 are going to be like, now we're really getting somewhere. Okay? So looking at chapter 1, again, sections 1 through 1.5 looks not that different than any other programming language that you've learned. It's chapter 1, section 1.6 is arrays. Static allocation. Arrays, you have to know how big they are when you declare them, and you can't resize them. until Chapter 5, at which point we'll start talking about dynamic memory and pointers and resizing. Chapter 1.7 and 1.8, functions and parameters, and it's all call by value in this early phase. Call by reference is in Chapter 5, because we need to know about pointers before we talked about Chapter 5, even though they use a little pointer syntax here and there in Chapter 1. And Section 1.9 is character arrays. Read this one closely, because there is no string object in C. There's no objects at all in C. And in Section 1.10, they talk about variable scoping between functions, and that feels kind of similar to other languages. And part of it is because other languages took their inspiration from C. So if we just take a quick look at C character arrays, we must understand that the size of the character array is at allocation time, and there is nothing auto-extended. And if you write a for loop that goes off the end of the loop, like I've got, where I have a character array that's 10 long and I write a loop that goes up to 1,000 storing data in it, eventually the program will blow up. And you can see, in Python you just add characters, whereas in C, if you add characters beyond what was allocated, the system blows up. And you probably heard me say more than once that the C language is probably responsible for 90% of the significant security holes in all of computing. And this kind of code where you allocate an array and then you wildly go beyond it ends up making it so that people can inject things into operating systems and routers and all kinds of things. So this is why we don't use C to write programs. Here we are in the first page. The example 1 of Chapter 1 is why we don't write C very often. Or if we do, we have to be really careful at reviewing it and making sure that it's right. It's really fast, but it's also dangerous. String constants and character constants. Strings and characters in most languages, Java's a little different, but PHP, Python, and JavaScript treat single and double quotes roughly the same, and they create string constants, and that's a multi-character thing that has a length. C doesn't have a multi-character thing that has a length. It has an array of characters that has a 0 character at the end of it. In C, single quotes are a single character, and double quotes are a character array. So a double quote with one character in it is actually 2 bytes because it's the character and the string ending. Whereas in Python, a string has a length. It doesn't really have an ending character. There's a special character that we use for an ending. In C, a character is a byte, which is a short integer, usually 8 bits in most computers. And so you got to be real careful. You got double quote things and single quote things, and single quote things in C are far more like integers and far less like strings. And so in Python, you just use them interchangeably, single quotes and double quotes. Character sets. The char in C is like a number. It's a tiny number. It's 8 bits long, so you can go from 0 to 255. And the character representations depend on the character set, but quite often they're ASCII. And so you can just go look up an ASCII chart and figure out what the numeric representation of the letter A is. And in Python, we can actually see the ordinal position of A by using the ord function. But that's the ord function of a single character string, which pulls the ord of the very first character. And we find that it's 65. And if you look up in the ASCII chart, it's 65. But in Python 3 are multi-byte characters that represent Unicode. And Unicode is much larger than 8 bits. I think Unicode is 32 bits. UTF-8 is a way to represent Unicode. And Unicode is a 32-bit character set. And so if you say, what is the integer equivalent of the character smiley face, you see that it's 128,522. And that's in a space of 32-bit. It's a 32-bit integer, and that's the character point within that 32-bit integer that represents smiley face. In C, there is no smiley face. You can't represent, unless you put a bunch of libraries into it, but the normal out-of-the-box C can't represent a smiley face. It can represent an uppercase A, and you can say, what is the A? And you'll notice we're printing it out with a %C and a %D, and it's the same thing. If you print a character out as a character, it's an A, and if you print it out as an integer, It's an A. We don't even need an ORD function because character constants are really integer constants in the ASCII character set. Okay? Just understand that. Every time you see single quote A, single quote, think of it as an integer, as a number that happens to be conveniently looked up for you by the C compiler. And you can take a look at the ASCII character set, and you can go look at uppercase A, and you see that its decimal equivalent is 65. You also see in this table that its hexadecimal is 41, and its octal is 101, and its binary, its actual bits are 1 bunch of zeros and a 1. Now the reason we like octal and hex as programmers is it's easier to convert directly one without having, converting from decimal requires like divisions and modulo and stuff like that. But converting from octal or hex to binary is direct on a digit by digit basis. So I can convert an octal digit to a binary set of binary digits just by looking at each digit in succession. So when we're printing out and we want to be able to understand what the raw bit pattern is of some data, we tend to print it out in hex or in octal so that we can quickly figure out what bits are set inside that value. Strings in C are not strings, they're arrays of characters. And there is no length. So you can ask Python what the length of a string is, and the string knows its length. But in C, you can ask what the length of a string is, but it turns into a for loop that scans until it finds the end of the string. And the end of the string is a special character, which is quote, \0 quote, which is 0. I mean, it's literally the integer 0. So you have characters that are non-zero, and then you have a 0 character. And the length is how many characters are in this array up to the end. Now, that is different than the allocation. So you can have, in this case, I have an example of a 6-character array, and I put 6 things in it. It's all full. I could have terminated it, like you notice I say x sub 3 equals 0. It's still got 6 characters in the array, but now the end of the string in that array, or the end of the character sequence in that array, has a 0 at position sub 3. And of course, arrays start at 0, so you see the first 3 characters. And the third one is an end, and that stops it to print out. And so you gotta A, allocate for the end of the character string, and you've got to have it there. Just because it goes up to 6, if you don't have the end of the string, it's going to go off and randomly go through memory until it blows up, probably, right? And so strings must be terminated. If you append something to a string, first you have to have enough space in that string. If you append something to a character array, you have to have enough space. And then if you overwrite the end of the string, you've got to add another little mark to say, now the end of the string has been moved. So terminating a string is a thing that you always got to think about, both when you're scanning through a string and when you're creating a new string. Like I said, the C string length is only computable by a loop that scans for a 0 character. So there's a strlen function in string.h that computes the string, but it's very, very different than the len function in Python. The len function in Python, x is an object and length is an attribute of that object. Whereas in C, there is an array and it has a length and it has a 0 position, but to ask how long is it, you've got to actually loop through all the characters looking for the 0 marker. So you kind of can find a length of a character, a length of a string, the length of a quote-unquote string in C, but you got to write a for loop to do it. You don't have to write a for loop because Python just knows the length. Later, we'll bring all these things together, much later. So, one of your assignments, exercise 117, is reversing a string in C without requiring any information, an extra string. You have a string, it's got a certain amount of space, and you've got to just flip. You got to swap the characters. You're going to probably have to draw a picture to do that. It is exercise 117, and I'm going to tell you, do not cheat. There are probably a million solutions out there on the internet. ChatGPT will tell you how to do it. Don't be tempted. As you do this, you will get there. I show you blurred out version of it. It's not all that much code. So don't shortcut this. Don't just, getting the solution to this assignment without actually doing it is the meanest thing you'll ever do to yourself. You have to do the reversal in place. It's a classic interview question. At the interview, you don't get to go to ChatGPT. You got to think about even length strings, odd length strings, empty strings, and single character strings. You're going to have to draw some pictures. Take your time. Enjoy this assignment. Seriously. It's not that big. And when you get it done, you can be very, very proud of yourself that you really thought through the low-level storage of what an array of characters with an ending marker is working with. And so that's why it's such a good interview question. So there we go. That's kind of my call-outs from Chapter 1. Give you an overall sense of the book, C character arrays, and encouraging you to actually do your homework, even though there's a million ways to get it done for you. Cheers. Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 1, a tutorial introduction. Let us begin with a quick introduction to C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details, formal rules, and exceptions. At this point, we are not trying to be complete or even precise. We want you to get as quickly as possible to the point where you can write useful programs. And to do that, we have to concentrate on the basics: variables and constants, arithmetic, control flow, functions, and the rudiments of input and output. We are quite intentionally leaving out of this chapter features of C which are of vital importance for writing bigger programs. These include pointers, structures, and most of C's rich set of operators, several control flow statements, and a myriad of details. This approach has its drawbacks, of course. Most notable is that the complete story on any particular language feature is not found in a single place. The tutorial, by being brief, may also mislead. And because they cannot use the full power of C, the examples are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned. Another drawback is that later chapters will necessarily repeat some of this chapter. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small, similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1. Getting started. The only way to learn a new programming language is by writing programs in it. The first program to write is the same for all languages. Print the words, "Hello, world." This is the basic hurdle. To leap over it, you have to be able to create the program text somewhere, compile it successfully, load it, run it, and find out where your output went. With these mechanical details mastered, everything else is comparatively easy. In traditional C, the program to print "Hello World" is main, open parenthesis, close parenthesis, open curly brace, printf, parenthesis, double quote, hello, comma, space world, \n, double quote, close parenthesis, semicolon, close curly brace. The modern minimal version of this program needs a bit more syntax. We add a single line at the beginning. #include space left angle brackets stdio.h right angle bracket pound include stdio.h. We have to add that line for the modern program. Back to the book. Just how to run this program depends on the system that you're using. As a specific example, on the Unix operating system, you must create the source program in a file whose name ends in .c, such as hello.c, and then you compile it with the command cc space hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. Running that by the command a.out will produce hello, world as its output. On other systems, the rules will be different. Check with a local expert. On modern systems, we use the GCC compiler with the -ANSI option to accept the legacy syntax of C. So we use GCC space -ANSI space hello.c. And to run the resulting a.out file, you need to prepend the local directory because most shell configurations do not include the current path in the paths to search for applications. So you need to write /a.out. Now for some explanations about the program itself. A C program, whatever its size, consists of one or more functions which specify the actual computing operations that are to be done. C functions are similar to functions and subroutines of a Fortran program or the procedures of PL1, Pascal, etc. In our example, main is such a function. Normally, you are at liberty to give functions whatever names you like, but main is a special name. Your program begins executing at the beginning of main. This means every program must have a main somewhere. Main will usually invoke other functions to perform its job, some coming from the same program and others from libraries of previously written functions. One method of communicating data between functions is by arguments. The parentheses following the function name surround the argument list. Here, main is a function of no arguments, indicated by open parenthesis, close parenthesis. The curly braces enclose the statements that make up the function. They're analogous to the do end of PL1 or the begin end of Algol or Pascal and so on. A function is invoked by naming it, followed by a parenthesized list of arguments. There is no call statement as there is in Fortran or PL1. The parentheses must be present even if there are no arguments. In the above text, the authors were making connections to the popular general-purpose programming languages of the time. When the book was written, it was not all assured that C and C-like languages would ever evolve past writing high-performance applications like operating system kernels and device drivers. By comparing C to these more general-purpose languages, the authors are trying to plant the seed that C could have value as a general-purpose language. Back to the text. The line that says printf parenthesis double quote hello comma space world \n double quote close parenthesis semicolon is a function call, which calls a function named printf with the argument hello world. Printf is a library function which prints the output to the terminal unless some other destination is specified. In this case, it prints the string of characters that make up its argument. Any sequence of any number of characters enclosed in double quotes is called a character string or string constant. For the moment, our only use of the character strings will be as arguments to printf and other functions. The sequence \n in the string is C notation for the new line character, which when printed advances the terminal to the left margin on the next line. If you leave out the \n, a worthwhile experiment by the way, you'll find that your output is not terminated by a line feed. The only way to get a new line character into the printf's argument is with \n. If you try to break it into two lines, like printf quote hello world, and then just hit the return, double quote, close parenthesis, semicolon on a new line, the C compiler will print out unfriendly diagnostics about missing quotes. Printf never supplies a new line automatically, so multiple calls can be used to build up an output line in stages. Our first program could have just as well been written as main open parenthesis, close parenthesis, open curly brace, printf quote hello quote semicolon, printf quote world quote semicolon, printf \n, semicolon, and then on a 6th line, close curly brace, and it would produce the identical output. Note that \n represents only a single character. An escape sequence like \n provides a general and extensible mechanism for representing hard-to-get or invisible characters. Among the others that C provides are \t for tab, \b for backspace, double quote for double quote, and \/ for the backslash itself. 1.2, page 8, Variables and Arithmetic. The next program prints the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. Using the formula, C equals parenthesis 5 divided by 9, close parenthesis, F minus 32. The table contains Fahrenheit of 0, Celsius of negative 17.8, Fahrenheit of 20, Celsius of negative 6.7, Fahrenheit of 40, Celsius of 4.4, and so forth. Here is the program itself. For reference, this program is on page 29 of the textbook. So it starts with #include stdio.h to include the standard library. Then it has a comment that says print the Fahrenheit Celsius table for F equals 0, 20, ... 300. Close comment. Main, open parenthesis, close parenthesis, open curly brace, int, lower, upper, step, semicolon, float, var, Celsius, lower equals 0, semicolon, followed by a comment, upper equals 300, semicolon, followed by a comment, step equals 20, semicolon, followed by a comment, var equals lower, and then while, open parenthesis, var less than or equal to upper, close parenthesis, open curly brace, Celsius equals parenthesis 5.0 / 9.0, close parenthesis, asterisk, open parenthesis, var minus 32.0, close parenthesis, semicolon. Then a printf statement, printf, open parenthesis, double quote, %4.0f space %6.1f \n, close quote, var, Celsius, close parenthesis, semicolon. Var equals var plus step, and then a closing curly brace to finish the while statement, and then a closing curly brace to finish the main statement. The first two lines, /* print Fahrenheit to Celsius table for F equals 0, 20, ... 300, / are a comment, which in this case explains briefly what the program does. Any characters between /* and */ are ignored by the compiler. They may be used to freely make the program easier to understand. Comments may appear anywhere a blank or new line can. In C, all variables must be declared before use, usually at the beginning of a function, before any executable statements. If you forget a declaration, you will get a diagnostic from the compiler. A declaration consists of a type and a list of variables that have that type, as in int, lower, upper, step, semicolon, float, var, Celsius, semicolon. The type int implies that the variables listed are integers. Float stands for floating point, i.e., numbers which may have a fractional part. The precision of both int and float depends on the particular machine that you are using. On the PDP-11, for instance, an int is a 16-bit signed number. That is, one that lies between negative 32,768 and positive 32,767. A float number is a 32-bit quantity which amounts to about 7 significant digits, with a magnitude of about 10 to the minus 38 and 10 to the plus 38. Chapter 2 lists the sizes for other machines. I would note that the 1970s was a time of transition in the amount of memory installed in computers. The C language int type was 16 bits in the older but more generally available computers like the PDP-11. C could be used to write programs like the Unix operating system that made efficient use of available memory. In particular, the 1978 version of C did not require that computers support 32-bit integers. But 32,768 is a pretty small number. The size of an integer affected the maximum size of arrays and strings. A lot of early C programs used the long type to get at least a 32-bit integer capable of representing numbers up to about 2 billion. In modern computers and databases, we tend to choose between 32-bit and 64-bit integers. Back to the text. C provides several other basic data types besides int and float. Char is a character, a single byte. Short is a short integer. Long is a long integer, and double is a double precision floating point. The size of these objects are also machine dependent, and details are in Chapter 2. There are also arrays, structures, and unions of these basic types, and pointers to them and functions that return them, all of which we will meet in due course. The actual computation in our temperature conversion program begins with the assignments lower equals 0, upper equals 300, step equals 20, far equals lower, all ending with semicolon. These set the variables to their starting values. Individual statements are terminated by semicolons. Each line of the table is computed in the same way, so we use a loop which repeats once per line. This is the purpose of the while statement. While, parenthesis, far less than or equal upper, close parenthesis, open curly brace, then the body of the loop, and then close curly brace. The condition in the parentheses is tested. If it is true, i.e. far is less than or equal to upper, the body of the loop, all of the statements included between the open curly brace and the closed curly brace are executed. Then the condition is retested. If true, the body is executed again. When the test becomes false, i.e. far exceeds upper, the loop ends and execution continues at the statement that follows the loop. There are no further statements in the program, so it terminates. The body of a while loop can be one or more statements enclosed in braces, as the temperature converter, or a single statement without braces, as in while, open parenthesis, I less than j, close parenthesis, I equals 2 times I, semicolon. In either case, the statements controlled by the while are indented by one tab stop, so you can see at a glance what statements are inside the loop. The indentation emphasizes the logical structure of the program. Although C is quite permissive about statement positioning, proper indentation and the use of white space are critical in making programs easy for people to read. We recommend writing only one statement per line and usually leaving blanks around operators. The position of the braces is less important. We have chosen one of the several popular styles. Pick a style that suits you and then use it consistently. I would add that with these words, the authors triggered a great debate about how to best indent code and use curly braces that continues to this day. The indentation style used in this book is often referred to as the K&R style. It tends to put open braces at the end of statements like if and while to keep code more compact in terms of the number of lines of code. The best advice is not to debate at all. When you modify someone else's code, just imitate the style that they used when they wrote their code. Back to the text. Most of the work gets done in the body of the loop. The Celsius temperature is computed and assigned to the Celsius variable by the statement Celsius equals, open parenthesis, 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, far minus 32.0, close parenthesis, semicolon. The reason for using 5.0 slash 9.0 instead of the simpler looking 5 slash 9 is that in C, as in many other languages, integer division truncates so that any fractional part is discarded. Thus, 5/9 is 0. And of course, so would then all the temperatures be 0. A decimal point in a constant indicates that it is floating point, so that 5.0 over 9.0 is 0.555 repeating, which is what we want. We also wrote 32.0 instead of 32, even though since far is a float, 32 would automatically be converted to float before the subtraction. But as a matter of style, it's wise to write floating point constants with explicit decimal points, even when they have integral values. It emphasizes their floating point nature for human readers and ensures the compiler will see things the way you do as well. I would note that for those of you familiar with Python, before Python 3, integer division truncated and returned an integer, just like C. In Python 3, one of the major improvements was that the division of two integers performs the division operation in floating point and returns a floating point result. C and Python 2 made the choice because of efficiency. Integer division with truncation, especially for 16-bit numbers, was quite fast in the 1970s computers compared to floating point division that kept the fractional part intact. Early PDP-11 computers did integer division in hardware, while all floating point was done with loops and functions, so it was far slower. If you wanted to write fast code in the 1970s, you avoided floating point numbers except for special situations. Modern computers usually do 64-bit floating point operations almost at the same speed as integer division, so we don't need to allow programmers to avoid using floating point computations in their code. The detailed rules for when integers are converted to floating point are in Chapter 2. For now, notice that the assignment far equals lower semicolon and the test while far less than or equals upper both work as expected. The int is converted to a float before the operation is done. This example also shows a bit more of how printf works. Printf is actually a general-purpose format conversion function, which we will describe completely in Chapter 7. Its first argument is a string of characters to be printed, with each % sign indicating where one of the other, second, third, etc. arguments is to be substituted and what form it is to be printed in. For instance, in the statement, printf parenthesis, double quote, %4.0f space %6.1f \n double quote, comma far, comma Celsius, the conversion specification %4.0f says that a floating point number is to be printed in a space at least 4 characters wide with no digits after the decimal point. %6.1f describes another number to occupy at least 6 spaces with 1 digit after the decimal point, analogous to the F6.1 of Fortran or the F parentheses 6, 1 of PL1. Parts of a specification may be omitted. %6f says that the number is to be at least 6 characters wide. %.2f requests 2 places after the decimal point, but the width is not constrained. And merely %f says to print the number itself as floating point. Printf also recognizes %d for decimal integers, %o for octal, %x for hexadecimal, and %c for characters, and %s for a character string, and % for the % itself. Each % construction in the first argument of printf is paired with its corresponding second, third, etc. argument. They must line up properly by number and type, or else you'll get meaningless answers. By the way, printf is not part of the C language. There is no input or output defined in C itself. There is nothing magic about printf. It's just a useful function, which is part of the standard library of routines that are normally accessible to C programs. In order to concentrate on C itself, we won't talk much about I/O until Chapter 7. In particular, we'll defer formatted input until then. If you have to input numbers, read the discussion of the function scanf in Chapter 7, Section 7.4. Scanf is much like printf, except that it reads input instead of writing output. The balance between building a feature into the language itself and providing it as a function in a library is something that computer language designers struggle with many years later. For example, in Python 2, print was a language element. In Python 3, one of the non-upwards compatible and somewhat unpopular changes was changing print to be a function. Many programmers feel that a print statement is a more elegant way to express printing, but from a compiler and language design perspective, a function call with a variable number of parameters is seen as technically more elegant and flexible. With Kernighan and Ritchie focused on keeping everything small and portable, they opted to keep all input-output functionality in libraries. The syntax is a little more complex, but given how computing has changed in the past 30 years, it is the right choice. Section 1.3, the for statement. As you might expect, there are plenty of different ways to write a program. Let's try a variation on the temperature converter. This is sample code is on page 11 of the textbook. # include less than stdio.h greater than. Main, open parenthesis, close parenthesis, open curly brace. Int var, that is FAHR, semicolon. For, open parenthesis, far equals 0, semicolon. Far less than or equal to 300, semicolon. Far equals far plus 20, close parenthesis. Printf, open parenthesis, double quote, %4d space %6.1f \n, close quote. Comma, far, comma, open parenthesis 5.0/9.0, close parenthesis, asterisk, open parenthesis, far minus 32, close parenthesis, semicolon. This code produces the same answers as the one before, but it certainly looks different. One major change is the elimination of most of the variables. Only far, F-A-H-R, remains as an int to show the %d conversion in printf. The lower and upper limits of the step size appear only as constants in the for statement itself. The for is a new construction, and the expression that computes the Celsius temperature now appears as the third argument of printf instead of in a separate assignment statement. This last change is an instance of a quite general rule in C. In any context where it is permissible to use the value of a variable of some type, you can use an expression of that type. Since the third argument of printf has to be a floating point value to match the %6.1f, any floating point expression can occur there. The for itself is a loop, a generalization of while. If you compare it to the earlier while, its operation should be clear. It contains three parts separated by semicolons. The first part, far equals 0, is done once before the loop proper is entered. The second part is the test or condition that controls the loop, far less than or equal to 300. This condition is evaluated. If it is true, the body of a loop, in this case a single printf, is executed, then the reinitialization step, far equals far plus 20, is done and the condition is reevaluated. The loop terminates when the condition becomes false. As with the while, the body of the loop can be a single statement or a group of statements enclosed in braces. The initialization and reinitialization parts can be any single expression. The choice between while and for is arbitrary and should be based on what seems clearer. The for is usually appropriate for loops in which the initialization and reinitialization are single statements and logically related, since it is more compact than while and keeps the loop control statements together in one place. I would note that the syntax of the for and while loop is a feature of C and derived C-like languages. In modern languages, we tend to have two kinds of loop structures, determinate and indeterminate. The for and the while loop structures in C are both indeterminate because you must read them closely to make sure they are properly constructed and, for example, are not unintentionally infinite loops. An example of a determinant loop is the for each loop in PHP or the for loop in Python. The semantics of both of these loops is to iterate all the elements in a collection. But since collections are never infinite, you can be assured that these determinant loops will not run forever. Section 1.4, Symbolic Constants. A final observation before we leave temperature conversion. It's a bad practice to bury magic numbers or magic constants like 320 or 320 in a program. They convey little information to someone who might read the program later, and they're hard to change in a systematic way. Fortunately, C provides a way to avoid such magic numbers. With the # define construction at the beginning of a program, we can define a symbolic name or symbolic constant to be a particular string of characters. Thereafter, the compiler will replace all unquoted occurrences of the name by the corresponding string. The replacement for the name can actually be any text at all. It's not related to numbers. So this is a sample code on page 13 of the text. # include less than stdio.h greater than. Next line. # define space lower space 0. Next line. # define space upper space 300. # define space step space 20. For these # statements, I would note that they have to start in the first column. The rest of this sample code is the code itself. Main open parenthesis close parenthesis, open curly brace, int far, F-A-H-R, for open parenthesis far equals uppercase lower, semicolon, far less than or equal to uppercase upper, semicolon, far equals far plus uppercase step. And then the same print statement. Printf, open parenthesis, double quote, %4d space %6.1f \n, quote, comma, far, comma, %5.0/9.0, close parenthesis, asterisk, open parenthesis, far -32, close parenthesis, semicolon, and then to end the program, close curly brace. The quantities, uppercase lower, uppercase upper, and uppercase step, are constants, so they do not appear in declarations. Symbolic names are commonly written in uppercase, so they can be readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a # define statement. Since the whole line after the defined name is substituted, there would be too many semicolons in the for. Section 1.5, a collection of useful programs. We are now going to consider a family of related programs for doing simple operations on character data. You will find that many programs are just expanded versions of the prototypes we discuss here. Character input and output. The standard library provides functions for reading and writing a character at a time. GetChar fetches the next input character each time it is called and returns the character as its value. That is, after C equals getChar open parenthesis close parenthesis, the variable C contains the next character of input. These characters normally come from the terminal or keyboard, but that need not concern us until chapter 7. The function putChar open parenthesis C close parenthesis is the complement of getChar. PutChar open parenthesis C close parenthesis prints the content of the variable C on some output medium, again usually the terminal or screen. Calls to putChar and printf may be interleaved. The output will appear in the order in which the calls are made. As with printf, there is nothing special about getChar and putChar. They are not part of the C language, but they are universally available. Once again, I would note that the authors are making the case that the syntax of the language should not include syntax for input-output operations, but instead call library functions. Keeping the compiler small and easy to port new systems was important to the creators of C. And even if something like putChar was part of the language syntax, it would be translated at runtime to call a function. Programming languages from the 1960s tended to have a small set of use cases. Read some input, run some calculation, and then write some output. so it seemed like a few language elements would be sufficient to describe all programs. But as programs started to make network connections, draw buttons on a screen, or respond to API calls over the network, it would have been difficult to keep expanding the core language syntax for each new use case. But it was extremely natural to add new libraries to languages like C with functions to call to accomplish these new use cases. File copying. Given getchar and putchar, you can write a surprising amount of useful code without knowing anything more about input-output. The simplest example is a program which copies its input to its output, one character at a time. In outline, here's what we do. Get a character. While the character is not the end-of-file signal, output the character we just read and then get a new character. Converting this into C gives us the sample code on page 14 of the textbook. Pound includes stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int C, semicolon. C equals getchar, open parenthesis, close parenthesis, semicolon. While C not equal EOF, uppercase EOF, close parenthesis, open curly brace, putchar C, C equals getchar, semicolon, close parenthesis, close curly brace. The relational operator, exclamation equals, means not equal to. The main problem is detecting the end of the input. By convention, getchar returns the value, which is not a valid character when it encounters the end of input. In this way, programs can detect when they did not get a character and they've actually simply run out of input. The only complication, which is a serious nuisance, is that there are two conventions in common use about what that end-of-file value really is. We have deferred this issue by using the symbolic name EOF, capital EOF, for the value, whatever it might be. In practice, EOF will be either -1 or 0, so the program must be preceded by the appropriate pound-define EOF -1 or pound-define EOF 0 to work properly. By using the symbolic constant EOF to represent the value that getchar returns when the end of file occurs, we are assured that only one thing in the program depends on the specific value, numeric value of EOF. I would note, most of that is incorrect. Modern C compilers actually define EOF in the stdio.h include file. So you never define EOF in your code. In modern C, the value of EOF is -1. You should just include stdio.h and use predefined EOF constant to check for end of file. The nuisance of different values for EOF was resolved shortly after 1978. Continuing with the text. We also declare C to be an int, not a char, so that it can hold the value which getchar returns. As we'll see in Chapter 2, the value is actually an int, because it must be capable of representing end of file in addition to all possible characters. So the program for copying could actually be written more concisely by experienced C programmers. In C, any assignment, such as C equals getchar, open parenthesis, close parenthesis, can be used in an expression. Its value is simply the residual value being assigned to the left-hand side. If the assignment of a character to the variable C is put inside the test part of a while statement, the file copy program can be written as shown in the example code on page 15 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, int space C semicolon. While, open parenthesis, C equals getchar, open parenthesis, close parenthesis, not equal EOF, close parenthesis, putchar C, parenthesis, C, close parenthesis, semicolon, close curly brace. The program gets a character, assigns it to C, and then tests whether the character was the end-of-file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of input is finally reached, the while terminates, and so does main. This version centralizes the input. There's now only one call to getchar and shrinks the program. Nesting an assignment is a test of one of the places where C permits a valuable conciseness. It is possible to get carried away and create impenetrable code, though that is a tendency we will try to curb. It's important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclamation equal, not equals, is higher than that of equals, the assignment operator, which means that in absence of parentheses, the relational test, exclamation equals, would be done before the assignment, equals. So the statement C equals get char parenthesis, open parenthesis, close parenthesis, not equal EOF is equivalent to C equals get char, is equivalent to C equals open parenthesis, get char, open parenthesis, close parenthesis, not equal EOF, close parenthesis. This has the undesired effect of setting. It is important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclamation equals is higher than that of equals, which means that in the absence of parentheses, the relational test not equals would be done before the assignment. So the statement C equals get char not equal EOF is equivalent to C equals open parenthesis get char not equal EOF, close parenthesis. This has the undesired effect of setting C to 0 or 1, depending on whether or not the call of getChar encountered the end of file. More on this in Chapter 2. The next program counts characters. It is a small elaboration of the copy program. This sample code is on page 16 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, long, NC semicolon, NC equals 0 semicolon, while open parenthesis get char open parenthesis close parenthesis exclamation equal EOF plus NC semicolon, printf double quote %LD \n double quote comma NC parenthesis semicolon close curly brace. The statement plus NC semicolon shows a new operator, plus, which means increment by 1. You could write NC equals NC plus 1, but plus NC is more concise and often more efficient. There is a corresponding operator, minus to decrement by 1. The operators plus and minus can either be prefix operators, plus NC, or postfix, NC++. These two forms have different values and expressions, as will be shown in Chapter 2. But +NC and NC++ both increment NC. For the moment, we'll stick to the prefix form. The character counting program accumulates its count in a long variable instead of an int. On a PDP-11, the maximum value of an int is 32,767, and it would take relatively little input to overflow that counter if it were declared as an int. In Honeywell and IBM C, long and int are synonymous and much larger. The conversion specification %LD signals to printf that the corresponding argument is a long integer. We again see another reference to the fact that the number of bits of the int type is in transition in 1978. The older PDP-11 used a 16-bit integer to save limited memory on a small, almost obsolete computer, while later computers from IBM and Honeywell have already switched to their int type to be 32 bits. This allowed code originally written for the PDP-11, like Unix or even the C compiler, to be recompiled on the IBM or Honeywell with very few changes. To cope with bigger numbers, you can use a double, which is a double-length float. We will also use a for statement instead of a while to illustrate an alternate way to write a while loop. This code is the second sample code on page 16 of the textbook. Pound include stdio.h, main open parenthesis, close parenthesis, open curly brace, double NC semicolon. For open parenthesis, NC equals 0 semicolon, getchar open parenthesis, close parenthesis, not equal EOF, semicolon, plus plus NC, close parenthesis, and then a semicolon. The semicolon in this case is an empty statement because there's nothing in the body of the for loop. And at the end we say printf, double quote, %.0f\n, double quote, comma, NC, close parenthesis, semicolon, close curly bracket. Printf uses %f for both float and double. %.0f suppresses printing of the non-existent fraction part. The body of the for loop here is empty because all the work is done in the test and reinitialization parts of the for loop. But the grammatical rules of C require that a for statement have a body. The isolated semicolon, technically a null statement, is there to satisfy that syntax requirement. We put it on a separate line to make it more visible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to getchar, so that the loop program produces 0, the right answer. This is an important observation. One of the nice things about while and for is they are tested at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done, even if that means never going through the loop body. Programs should act intelligently when handed input like no characters. The while and the for statements help ensure that they do reasonable things with boundary conditions. Line counting. The next program counts lines in its input. Input lines are assumed to be terminated by the new line character \n that has been carefully appended to every line written out. This is sample code on line 17 of the textbook. Pound includes stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int C, comma, NL, semicolon. NL equals 0, semicolon. While, open parenthesis, C equals getchar, open parenthesis, close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, C, double equals, single quote, \n, single quote, close parenthesis, plus plus, NL, semicolon. Printf, double quote, %d, \n, double quote, comma, NL, close parenthesis, semicolon, close curly brace. The body of the while loop now consists of an if, which in turn controls the increment plus plus NL. The if statement tests its parenthesized condition, and if true, does the statement or group of statements inside braces that follow. We have again indented to show what is controlled by what. The double equal sign is the C notation for is equal to, like fortrans.eq. This symbol is used to distinguish the equality test, the question being asked, from the single equal sign used for assignment. Since assignment is about twice as frequently used as equality testing in typical C programs, it's appropriate that the operator be half as long. A single character can be written between single quotes to produce a value equal to the numerical value of the character in the machine's character set. This is called a character constant. So for example, single quote A, single quote is a character constant. In the ASCII character set, its value is 65, the internal representation of the character A. Of course, single quote A, single quote is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. These escape sequences that are used in character strings are also legal and character constants. So in tests and arithmetic expressions, single quote \n, single quote, stands for the value of a new line character. You should note carefully that single quote \n is a single character, and in expressions is equivalent to a single integer. On the other hand, double quote \n double quote is a character string which happens to contain only one character. The topics of strings versus characters is discussed further in Chapter 2. The numeric values that are shown for characters are using the ASCII character set. The character sets in the 1970s were quite intricate. Most were 8 bits long to conserve computer memory and only support 100 or so Latin-like characters. This is why early programming languages use special characters like asterisk and curly brace in their syntax very carefully. They needed to choose characters that were commonly available on computer keyboards from different manufacturers. Modern programming languages like Python 3 and Ruby store internal string values using the Unicode character set, so they are all able to represent all the characters in all languages around the world. Modern languages tend to represent 8-bit values in the range from 0 to 256 using a byte or similar type. Python 2 strings were stored as 8-bit bytes, and Python 3 strings are stored as 32-bit Unicode characters. Moving to Unicode was a major effort in the Python 2 to Python 3 transition. Word counting. The fourth in our series of useful programs counts lines, words, and characters, with a loose definition that a word is any sequence of characters that does not contain a blank, a tab, or a new line. This is a very bare bones version of the Unix utility WC. This example is on page 18 in the textbook. Pound include stdio.h. Pound define yes, 1. Pound define no, 0. Main, open parenthesis, close parenthesis, open curly brace. Int c, nl, nw, nc, inword. Inword equals no. NL equals NW equals NC equals 0. While, open parenthesis, C equals getchar, not equal to EOF, open curly brace, plus plus NC. If, parenthesis, C double equals, quote, backslash N, quote, parenthesis, plus plus NL. If, open parenthesis, C double equals, single quote, space, single quote, double vertical bar, C double equals, single quote, backslash N, single quote, double vertical bar, C equals, single quote, backslash T, single quote, close parenthesis, inward equals no. Else if, open parenthesis, inward equal no, close parenthesis, open curly brace, inward equals yes, semicolon, plus plus NW, semicolon, close curly brace, printf, open parenthesis, double quote, %d, space, %d, space, %d, backslash n, double quote, comma, nl, comma, nw, comma, nc, close, curly brace. Every time the program encounters the first character of a word, it counts it. The variable inword records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value no. We prefer the symbolic constants yes and no to the literal values 1 and 0 because they make the program more readable. Of course, in a program as tiny as this, it makes little difference, but in larger programs, the increase of clarity is well worth the modest effort to write it this way, to make it more readable. You will also find that it's easier to make changes to programs where numbers appear only as symbolic constants. The line NL equals NW equals NC equals 0 sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment has a value and assignments associate right to left. It's really as if we had written NC equals open parenthesis NL equals open parenthesis NW equals 0, close parenthesis, semicolon. The operator double vertical bar means or. So the line if open parenthesis C double equals single quote space single quote vertical bar C double equals single quote backslash N single quote double vertical bar C double equals quote backslash T quote parenthesis says if C is a blank, or C is a new line, or C is a tab. The escape sequence \T is a visible representation of the tab character. There's a corresponding operator, which is $ampersand for AND. Expressions connected by $ampersand or double vertical bar are evaluated left to right, and it is guaranteed that the evaluation will stop as soon as the truth or falsehood for the overall expression is known. Thus, if C contains a blank, there is no need to test whether it contains a new line or tab. So these tests are not made. This isn't particularly important here, but is very significant in more complicated situations, as we will soon see. I would note that the double vertical bar and double ampersand are the norm for Boolean operators in C-like languages. When a new language was being designed, it was really easy to just adopt the C convention for logical operators because, while they may seem cryptic, millions of software developers were already familiar with the operators. In this way, the relationship between C and C-like languages is like the relationship between Latin and Romance languages, including English. Back to the text. The example also shows the C else statement, which specifies an alternative action to be done if the condition part of an if statement is false. The general form is if, open parenthesis, expression, close parenthesis, statement 1, else statement 2. One and only one of the two statements associated with an if-then-else is done. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can actually be, in fact, quite complicated. In the word count problem, the one after the else is an if that controls two statements in braces. Section 1.6, Arrays. Understanding the capabilities and limitations of C arrays is one of the most important topics in our historical look at the C programming language. Most importantly, the number of elements in an array declaration must be a constant at compile time, and the size of an array cannot be adjusted using an array declaration while the program's running. This inability to automatically resize C arrays as data is added leads to a class of security flaws that are generally referred to as buffer overflow, where a program reads more data in that can fit into an array and is tricked to overriding other data or code and compromising an application. Later in this book, we will create dynamic array-like structures in C using pointers and the standard library calloc function. Python has support for non-dynamic arrays, buffers. Python buffers are generally not used except for programmers writing library code that talks to low-level code written in a language other than Python, or talking to operating system things like Linux. The more commonly used Python list and dictionary structures can change their sizes automatically as elements are added and deleted at runtime. Java has support for non-dynamic arrays like C, which are given a length at the moment they are created, and the array length cannot be increased nor decreased without making a new array and copying all the elements from the first to the second array. Java does provide list and map structures that automatically adjust their length as data is added or removed. Java has a class called ArrayList, which can be dynamically extended but provides array-like linear access. It is a list internally, but it can be used like an array externally. The underlying technique that is used to implement language structures like Python's list is dynamic memory allocation and a linked list structure. Linked lists are one of the most important data structures in all of computer science. We will cover dynamic allocation and implementing data structures in C in Chapter 6. For now, we will merely examine the syntax of C arrays, but keep in mind that allocating an array in C is very different than creating a list in Python. Back to the text. Let us write a program to count the number of occurrences of each digit of white space characters, blank, tab, and new line, and all other characters. This is an artificial problem to solve, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input, so it is convenient to use an array to hold the number of occurrences of each digit rather than 10 individual variables. Actually 12 individual variables. Here is one version of the program on page 21 in the textbook. And I would note that as these programs get larger and larger, it is harder and harder for you to just listen to me read them, and you have to go look at them in the textbook. So I recommend that you go check out the textbook in page 20 and find this actual code. Pound include stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int c, comma I, comma n white, comma n other, semicolon. Int n digit, open square bracket 10, close square bracket, semicolon. N white equals n other equals 0, semicolon. 4, open parenthesis, I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis, n digit, open square bracket, I, close square bracket, equals 0, semicolon. Now we're going to have a loop to read all of our input, while double open parentheses, C equals getchar, open parenthesis, close parenthesis, and another close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, C greater than or equal to, single quote, 0, single quote, double ampersand, C less than or equal, single quote, 9, single quote, close parenthesis, plus plus, n digit, open square bracket, C minus single quote 0, single quote, close square bracket, semicolon. Else if, open parenthesis, C double equals space, quote, space, quote, or double vertical bar, C double equals single quote backslash n single quote, double vertical bar, C double equals single quote backslash T single quote, close parenthesis, plus plus n white, semicolon. Else plus plus n other. That if statement was a sort of a 3-branch if, checking to see if we were doing a digit, a white space character, or some other character. At the end of the while loop, or not the end of the while loop, and so we say printf, parenthesis, double quote, digits equals, double quote, close parenthesis, semicolon. Now we'll note in this that there is no new line. So we can have these printfs kind of concatenate outward without going to a separate line. 4, parenthesis, I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, space, %d, double quote, comma, n digit, open square bracket, I, close square bracket, close parenthesis, semicolon. Printf, open parenthesis, double quote, backslash n, white space equals, %d, comma, other equals, %d, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. Let's go through the code. The declaration, int, n digit, open square bracket, 10, close square bracket, semicolon, declares n digit to be an array of 10 integers. Array of subscripts always start as 0 in C rather than 1 as in Fortran or PL1, so the elements are n digit sub 0, n digit sub 1, dot dot dot, n digit sub 9. Square brackets are the sub. This is reflected in the for loops which initialize and print the array. A subscript can be any integer expression, which of course includes integer variables like I and integer constants. This particular program relies heavily on the properties of character representation of the digits. For example, if C greater than or equal to single quote 0, single quote, double ampersand, C less than or equal to single quote 9, single quote, close parenthesis, determines whether it's a digit. That is, if the numeric value of the digit and the numeric value of the digit is C minus double quote 0, double quote. This only works if double quote 0, double quote 1, etc. are positive and increasing order. And there's nothing but digits between 0 and 9. Fortunately, this is true for all conventional character sets. By definition, arithmetic involving chars and ints converts everything to int before proceeding. So char variables and constants are essentially identical to ints in arithmetic contexts. This is quite natural and convenient. For example, c minus single quote 0 single quote is an integer expression that gives us a value between 0 and 9, an integer value between 0 and 9, corresponding to the character quote 0 quote 2 quote 9 quote stored in C, and is thus a valid subscript for the 10-element array n digit. The decision as to whether the character is a digit, a white space, or something else is made by the sequence if open parenthesis C greater than or equal to quote 0 quote double ampersand C less than or equal quote 0 quote quote 9 quote close parenthesis plus plus n digit open square bracket C minus quote 0 quote close bracket semicolon. Else if C double equals single quote or C double equals single quote backslash n or C double equals single quote backslash t plus plus n white else plus plus n other. The pattern if in parentheses condition statement else if parentheses condition statement else statement occurs frequently in programs as a way to express a multi-way decision. The code is simply read from the top of the bot until the bottom until some condition is satisfied. At that point, the corresponding statement part is executed and the entire construction is finished. Of course, statement can be several statements enclosed in braces. If none of the conditions are satisfied, the statement after the final else is executed if present. If the final else and statement are omitted, as in the word count program, no action takes place. There can be an arbitrary number of else if condition statements, groups between the initial if and the final else. As a matter of style, it is advisable to format this construction, as we have shown, with proper indentation, so that long decisions do not march off the right side of the page. The switch statement, to be discussed in Chapter 3, provides another way to write multi-way branching that is particularly suitable when the condition being tested is simply whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in Chapter 3. Functions. In C, a function is equivalent to a subroutine or function in Fortran, or a procedure in PL1, Pascal, etc. A function provides a convenient way to encapsulate some computation in a black box, which can then be used without worrying about its innards. Functions are really the only way to cope with the potential complexity of large programs. With properly designed functions, it is possible to ignore how a job gets done. Knowing what is done is sufficient. C is designed to make the use of functions easy, convenient, and efficient. You will often see a function only a few lines long called only once, just because it clarifies some piece of code. So far, we have used functions like printf, getChar, and putChar that have been provided for us. Now it's time to write a few of our own. Since C has no exponentiation operator like the double asterisk of Fortran or PL1, let us illustrate the mechanics of function definition by writing a function, power, open parenthesis, m, comma, n, close parenthesis, to raise an integer into a positive power n. That is, the value of power, parenthesis 2, comma 5, is 32. This function certainly doesn't do the whole job of exponentiation since it only handles positive powers of small integers, but it is best to confuse only one issue at a time. Here is the function power and a main program to exercise it so you can see the whole structure at once. This sample code is on page 23 of the textbook. Pound include stdio.h. Main, open curly brace, int I, semicolon. For parenthesis I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, %d space, %d space, %d backslash n, double quote, comma. I, comma, power, open parenthesis 2, comma I, close parenthesis, comma, power, open parenthesis, -3, comma I, close parenthesis, semicolon, close curly brace, the end of the main. Now we begin the function. Power, open parenthesis, x comma n, close parenthesis. Int, x comma n, semicolon, open curly brace. Int, I comma p. P equals 1. For, open parenthesis, I equals 1 semicolon, I less than or equal to n semicolon, plus plus I. P equals p times x, semicolon. Return, open parenthesis, p, close parenthesis, semicolon, close curly brace. Each function has the same form. Function name, open parenthesis, argument list, if any, followed by argument declarations, if any, followed by the body of the function, which includes declarations and statements. The functions can appear in either order and in one source file or two. If, of course, the source file appears in two files, you will have to say more to compile and load it than if all appears in one. But that's an operating system matter, not a language attribute. For the moment, we'll just assume that both functions are in the same file, so whatever you learned about C programs, running them will not change. The function power is called twice in the line printf, open parenthesis, double quote, %d space %d space %d \n double quote, comma I, comma power, open parenthesis, 2 comma I, close parenthesis, comma power, open parenthesis, -3 comma I, close parenthesis, close parenthesis. Each call passes two arguments to the power function, which each time returns an integer to be formatted and printed. In the expression, power, open parenthesis, 2 comma I, is just an integer as 2 and I are. Not all functions produce an integer value, and we'll take this up in more detail in Chapter 4. In power, the arguments have to be declared appropriately so their types are known before the beginning of the body of the function. This is done by the line int x comma n semicolon that follows the function name. The argument declarations go between the argument list and the opening left brace. Each declaration is terminated by a semicolon. The names used for power and for its arguments are purely local to power and not accessible to any other functions. Other routines can use the same names for their variables without conflict. This is also true of the variables I and p within the function. The I in power is unrelated to the I in main. The value that power computes is returned to main by the return statement, which is just as in PL1. Any expression must occur within the parentheses. A function need not return a value. A return statement with no expression causes control but no useful value to be returned to the caller, as does falling off the end of a function by reaching the terminating right curly brace. Section 1.8, Arguments, Call by Value. One aspect of C function, which may be unfamiliar to programmers who are used to other languages, particularly Fortran and PL1, in C, all function arguments are passed by value. This means that the called function is given the values of its arguments in temporary variables, actually on a stack, rather than their addresses. This leads to some different properties than are seen with call by reference languages like Fortran and PL1, in which the called routine has handled the address of the argument, not its value. It may seem strange that the authors are calling so much attention to the fact that function arguments are passed call by value in the very first chapter. Most modern programming languages like Python, PHP, or Java pass single value arguments by value by default. And to pass in an argument by reference, you need to do something special, like adding the ampersand in the function declaration in PHP. Passing by reference was the norm before C, and passing by value was the norm after C. Since modern languages were deeply influenced by and often written in C, passing by value is the norm for modern languages. It's nice because it isolates the data in the calling code from the called code. So the called code can't easily mess with its arguments, either intentionally or by mistake, and create an unexpected side effect and possibly a bug or security flaw in the calling code. It was a bit of work to make pass-by value work in C. C implements a call stack where a bit of memory is automatically allocated at each function call, and C makes a copy of the values in the calling code to pass them into the called code in a way that the calling code can see the values and change their local copies without affecting the values in the calling code. The same call stack that made it possible for C function arguments to be passed by value also made it possible for a function to call itself recursively. Fortran functions could not be called recursively until the 1990 version of Fortran. If you know your Python, you know that simple variables like integers and strings are passed by value, while structured data like dictionaries and lists are passed by reference, i.e., the called function can modify its arguments. We will later see this in C as well. Talking about call stacks, recursive functions, and the fact that arrays and structured are called by reference is jumping ahead somewhat. So for now, let's just remember the author's point that normal values like integers and floats are passed by value in C. Back to the text. The main distinction is that in C, the called function cannot alter a variable in the calling function. It can only alter its private temporary copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables, because arguments can be treated as conveniently initialized local variables in the called routine. For example, here is a version of power which makes use of this fact. This code is on page 24 of the text. Power, open parenthesis, x, comma, n, close parenthesis. Int, x, comma, n, semicolon, open curly brace. Int, I, comma, p, semicolon. For, open parenthesis, p equals 1 semicolon, n greater than 0 semicolon, minus minus n, close parenthesis. P equals p times x, semicolon, return, open parenthesis, p, close parenthesis, semicolon, close curly brace. The argument n is used as a temporary variable and is counted down until it becomes 0. There is no longer a need for the variable I, as in the previous example. Whatever is done to n inside the power function has no effect on the argument that power was originally called with. When necessary, it is possible to arrange for a function to modify the variable in the calling routine. The caller must provide the address of their variable to be set, technically a pointer to the variable, and the called function must declare the argument to be a pointer and reference the actual variable indirectly through it. We will cover this in detail in Chapter 5. When the name of an array is used as an argument, the value passed to the function is actually the location or address of the beginning of the array. There is no copying of the elements in the array. By subscripting this value, the function can access and alter any element of the array in the calling code. This is the topic of the next section. Now, I would recommend that you're careful looking at the code samples in the rest of this chapter. Recall that in C, array sizes do not grow and shrink dynamically at all after they're allocated. The authors statically allocate character arrays capable of handling up to 1,000 characters long. Their code works, but it is somewhat brittle. So look at the next two sections as examples of C syntax with many important concepts about character strings stored as arrays and calling patterns when passing arrays to functions as parameters, but not exactly the best practice when handling dynamically sized data. Back to the text. Probably the most common type of array in C is an array of characters. To illustrate the use of character arrays and functions to manipulate them, let's write a program that reads a set of lines and prints the longest. The basic outline is simple enough. While there's another line, if it's longer than the previous longest, save it and its length, and then at the very end, print the longest line. The outline makes it clear that the program divides naturally into pieces. One piece gets a new line, another checks it, another saves it, and then the rest controls the process. Since things divide so nicely, it would be well to write them that way too. Accordingly, let's write first a separate function called getLine to fetch the next line of input. This is a generalization of getChar. To make the function useful in other contexts, we'll try to make it as flexible as possible. At the minimum, getLine has to return a signal about possible end of file. A more generally useful design would be to return the length of the line, or 0 if the end of file is encountered. 0 is never a valid line length since every line has at least one character. Even a line containing only a new line has length 1. I would note that here in Chapter 1, we have changed the book's original use of the function name getLine to get_line in the code examples because it conflicts with the stdio.h that defines getLine as a library function. In this chapter, the authors are providing examples around function naming and linking. In later chapters, code samples will simply use the built-in getLine without an underscore to read an input. When we find a line that is longer than the previous longest, it must be saved somewhere. This suggests a second function, copy, to copy the new line to a safe place. Finally, we need a main program to control getLine and copy. Here is the result. The sample code for this is on page 26. And it's a bit long, so you might want to take a look at the sample code in a browser. Pound include stdio.h. Pound define max line 1000. Main, open paren, close paren, open curly brace. Int len semicolon, which is the current line length. Int max semicolon, which is the maximum length we've seen so far. Char line, open square bracket, max line, close square bracket, semicolon. A character array that's the current input line. And then char save, open square bracket, max line, close square bracket, semicolon, which is a character array that has the longest line where we're going to save it. Onto the code. Max equals 0. While open parenthesis, len equals getLine, open parenthesis, line, comma, max line, close parenthesis, greater than 0. If len is greater than max, open curly brace, max equals len to save it, and then copy line, comma, save, close curly brace. If open parenthesis, max greater than 0, i.e. there was a line, printf, open parenthesis, double quote, %s, double quote, comma, save, close curly brace to end the main program. Now we're in the first function. GetLine, open parenthesis, s, comma, lim, close parenthesis. Char, s, open bracket, close bracket, semicolon. Since it's being passed in as an argument, we don't need to know the length of it. And the next argument is int lim semicolon. So getLine takes a character array of unknown length and a limit that tells us the length of the character array. Open curly brace, int c comma I semicolon. 4, open parenthesis, I equals 0 semicolon. I less than lim minus 1, double ampersand, parenthesis, c equals getChar, open parenthesis, close parenthesis, not equal EOF, and double ampersand, c not equal single quote backslash n single quote semicolon plus I. And in the body of the loop, it's s open square bracket I close square bracket equals c. From now on, I'll read that s sub I equals c. At the end of the loop, we say if open parenthesis, c double equals single quote backslash n single quote close parenthesis, open curly brace, s sub I equals c plus I close curly brace. S sub I equals quote backslash 0 quote semicolon return open parenthesis I close parenthesis semicolon close curly brace, and that's the end of the getLine function. And now we're on to the copy function. Copy, open parenthesis, S1, S2, close parenthesis. The purpose of this function is to copy S1 to S2, assume that S2 is big enough. The declaration is char S1, open square bracket, close square bracket, comma, S2, open square bracket, close square bracket. As a note, these arrays have a size. We just don't know what they are, and we hope that they're large enough. The body of the copy function starts with open curly brace, int I semicolon, I equals 0, while open parenthesis, S2 sub I equals S1 sub I, close parenthesis, not equal, single quote, backslash 0, single quote, plus plus I, close curly brace to end the copy function. Main and getLine communicate both through a pair of arguments and a returned value. In getLine, the arguments are declared by the lines char s open square bracket, close square bracket, semicolon, int lim semicolon, which specify that the first argument is an array of unknown length and the second is an integer. The length of the array s is not specified in getLine since it's determined in main. getLine uses return to send a value back to the caller, just as the function power did. Some functions return a useful value. Others, like copy, are only used for their effect and return no value. getLine puts the character \0, the null character whose integer value is 0, at the end of the array it's creating to mark the end of the string of characters. This convention is also used by the C compiler. When a string constant like double quote HELLO \n double quote is written in a C program, the compiler creates an array of characters containing the characters of the string and adds a \0 at the end to terminate it so that functions such as printf can detect the end. So that would lead to an array that has HELLO \n\0. So it's a 5-character array with a new line, which is a 6th character, and then \0, which is an actual character. Again, we don't know, the arrays don't know their length, and so you use the \0 as the indicator of the end of a string. The %s format specification in printf expects a string represented in exactly this form. If you examine copy, you will discover that it too relies on the fact that its input argument S1 is terminated by \0, and it copies this character, \0, into the argument, output argument S2. All of this implies that \0 is not part of normal text. It's merely a marker. It is worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? getLine works properly in that it stops collecting when the array is full, even if no new line has been seen. By testing the length in the last character returned, main can determine whether the line was too long, then cope with it as it wishes. In the interests of brevity, we have ignored this issue. There's also no way for a user of getLine function to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, a user of the copy function already knows or should be able to find out how big the strings are, so we have chosen not to add error checking to it. Section 1.10, Scope, External Variables. The variables in main, line, save, etc. are private or local to main. Because they are declared within main, no other function can have direct access to them. The same is true of the variables in the other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a routine comes into existence only when a function is called and disappears when the function is exited. It is for this reason that such variables are usually known as automatic variables. following terminology in other languages. We'll use the term automatic henceforth to refer to these dynamic local variables. Chapter 4 discusses the static storage class in which local variables do retain their values between function invocations. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables which are external to all functions, that is, global variables which can be accessed by name by any function that cares to. This function is rather like Fortran common or PL1 external. Because external variables are globally accessible, they can be used instead of arguments to communicate data between functions. Furthermore, because external variables remain in existence permanently rather than appearing and disappearing as functions are called and exited, they retain their values even after the functions that set them are done. An external variable has to be defined outside of any function. This allocates actual storage for it. The function also must be declared on each function that wants to access it. This may be done either by an explicit extern declaration or implicitly by context. To make the discussion concrete, let's rewrite the longest line program with line, save, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. This sample code is on page 29 of the textbook, and it's pretty long, but I'll read it for you. Pound include stdio.h. Pound define max line 1000. And we're still outside of main. Char line, open bracket max line, close bracket, semicolon. Char save, open bracket max line, semicolon. Int max semicolon. Those are our three global variables. Starting the main open paren, close paren, open curly brace. Int len, extern int max. So we're saying that this is an integer, but it's also not to be allocated inside of main. Extern char save, open square bracket, close square bracket. The length of the save array is defined above, so we don't need to define it here. Max equals 0, semicolon, while double parenthesis len, double left parenthesis len equals get line, parenthesis, greater than 0, parenthesis. If parenthesis len greater than max, open curly brace, max equals len, copy, open parenthesis, no parenthesis, semicolon, no parameters to copy, because it's going to simply talk to the global variables, close curly brace. After the loop finishes, we say if, open parenthesis, max greater than 0, then printf, open parenthesis, double quote, %s, double quote, comma, save, close parenthesis, semicolon, close curly brace, and that is the end of the main. So now we have the getLine function, which is specialized to deal with external variables. Okay. So we start getLine, open parenthesis, close parenthesis, no parameters, open curly brace, int, c, I, semicolon. These are local variables. Extern char line, open curly brace, close curly brace, semicolon. This is our reference inside of getLine to the global variable line. For open parenthesis, I equals 0, semicolon, I less than max line minus 1. Max line minus 1, max line is a predefined constant at compile time. For I less than max line minus 1, double ampersand, parenthesis, C equals get char, open parenthesis, close parenthesis, not equal EOF, double ampersand, i.e. and, C not equal single quote \n, single quote semicolon, plus I. Line sub I equals C. That's the for loop that in effect reads characters one at a time and puts them in line. But after the for loop, we say if, open parenthesis, C double equals single quote, \n, single quote, close parenthesis, open curly brace, line sub I equals C plus I, close curly brace. This ensures that we append the new line to the function. Line sub I equals single quote, \0, \, that's semicolon. That's the string termination character. Return I. Return open parenthesis I, close parenthesis. This is the length that getLine is returning. And then close curly brace to end the getLine function. And then we have the copy function. And again, it takes no parameters. Copy, open parenthesis, close parenthesis, curly brace, int I, extern, char, line, open bracket, close bracket, comma, save, open bracket, close bracket, semicolon. I equals 0, while, parenthesis, open parenthesis, save sub I equals line sub I, close parenthesis is not equal, quote, \0, quote, plus I. Close curly brace for copy. So the external variables in main, getLine, and copy are defined by the very first lines in the example above, outside of main, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like the declarations we used previously, but because they occur outside of any function, including outside the main function, the variables are external. Before a function can use or access an external variable, the name of the variable must be made known to the function. One way to do this is to write an extern declaration in the function. The declaration is the same as before except for the added keyword extern. In certain circumstances, the extern declaration can be omitted. If the external definition of the variable occurs in the same source file before it's used in a particular function, then there's no need for an extern declaration in the function. The extern declarations in main and getLine and copy are thus redundant. In fact, common practice is to place all definition of all external variables at the beginning of the source file and then omit all extern declarations. If the program is in several source files and a variable is defined in, say, file 1 and used in file 2, then an extern declaration is needed in file 2 to connect the two occurrences of the variables. This topic is discussed at length in Chapter 4. You should note that we are using the words declaration and definition very carefully when we refer to external variables in this section. Definition refers to the place where the variable is actually created or assigned storage. Declaration refers to places where the nature of the variable is stated but no storage is allocated. By the way, there is a tendency to make everything in sight an extern variable because it appears to simplify things. Argument lists are short and variables are always there when you want them, but external variables are always there also when you don't want them. The style of coding is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify when it becomes necessary. The second version of the longest line program is inferior to the first, partly because of these reasons, and partly because it destroys the generality of two quite useful functions by hardwiring them into the names of the variables they will manipulate. Section 1.11, Summary. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size. And it's probably a good idea if you paused long enough to do so. The exercises that follow are intended to give you suggestions for programs of somewhat greater complexity than the ones presented in this chapter. After you have this much C under control, it will be well worth your effort to read on, for the features covered in the next few chapters are where the power and expressiveness of the language begin to become apparent. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Welcome to Chapter 2, Types, Operators, and Expressions. So again, I'm not going to tell you everything. The book, I want you to read the book. The book does a great job. I'm just going to call your attention to some things that might seem a little bit weird if you're coming from a language like Python or JavaScript or even PHP, where things are objects and you don't even notice it. You've been using objects your whole career and you didn't even realize it. So we're going to talk about data types and storage allocation. One of the things that you just gotta, part of what I love about teaching this historical view on C is that we have to talk about storage allocation. Float and double worked out pretty well, partly because in the early days of C they did them all in software, so they just made them easy and they made them work well. They weren't expected to be fast. The things that they wanted to be super fast were like the integer and byte data, character data. Type conversion. And then there's a story that connects integer division in Python 2 and all that pain of Python 3 and how division changed and why it was the way it was and how that worked. And again, that has to do with performance and simple decisions that got made, sadly. Bitwise logical operations, we'll talk about them. You're probably not going to use them, but it's really important in a historical context to understand why they were so thorough. And it really had to do with the fact that because of word-oriented computers switching to character-oriented computers, all of us programmers were thinking in words, and if we didn't see shifting and masking and bitwise stuff, we'd be like, I can't program in this thing, because a lot of our work in those word-oriented computers was masking and shifting. And so it's like we had to have it. We didn't use it as much as we could have thought. So let's start with division. In the good old days, we were not worried too much about doing division. And if you were doing division and you cared about the division, you were probably doing it in floating point because you were doing scientific computing and you did that on supercomputers. You didn't do that on general purpose computers. Unix was really designed for general purpose computers. And in general purpose computers, you sort of thought to yourself, why is division that important? And I'm sure they made some decision somewhere. I do not know why. It probably had to do with one of the computers they were working with had truncating division in hardware and non-truncating division in software. I don't know, or rounding division or whatever. A lot of those computers didn't even have fast floating point, so some of the computers they were working on did all the floating point in software. And maybe they even did integer division in software with loops and stuff. But we don't know. I don't exactly know, but they made this decision to do integer division truncating. And this was one of the biggest things of going from Python 2 to Python 3 that was the most painful. So Python 2 was like over 25 years old, and it wasn't that long after C that Python 2 was written. Python 2 was written in C. And Python 2 to Python 3 transition was a big deal. It took a long time. It took 12 years to get there. But Python 2 was like the greatest thing ever, except for a few things. Because Python 2 was so related to C, the strings in Python 2 natively were ASCII, not Unicode, which meant it couldn't even do like Spanish characters, let alone Asian characters. The print was part of the language, and the programmers got a lot of help. Like they got an automated code converter and syntax checkers, and they did all kinds of things where they would take certain libraries like the print function, and they would put it in Python 3, then we backport it to Python 2, so you could like switch from using the print statement to the print function. And there were lots of things that made this transition as easy as possible. the one thing that they really never could crack, and we just had to bite the bullet and get used to it, was Python 2 returns integer and the division is truncated. So if you do 3 divided by 4 is 0 in Python 2. And in Python 3, it's integer 3 divided by integer 4 becomes a floating point 0.75 because that's what calculators do. And the Python 2 division truncated because it didn't seem like it mattered much back in the 80s, and C integer division truncated. So 3/4 in C was 0, and 3/4 integer 3/4 was 0 in C, and so it was in Python. And 20 plus years later, that was the one thing we couldn't auto-convert, and Python 3 does it the way Python does. So it's less of a problem in C because C is actually a strongly typed language, which means if I wanted to say 3/4, I knew whether it was integers or floats, and I could force that. And so, but in Python, you just, what's the variable? And so it imputes the variable type from the result of that expression. Whereas C has got to declare X as a float or a double or an int. So when a C programmer writes a division, they know already that they have to cast the values or use float constants to trigger type conversion in expressions. So as you're looking through the chapters, seeing these type conversions and casting, that's the kind of problem that was solved. But then Python simplified it and then made it really kind of yucky, and then they had to fix it. It's better in Python 3, and most of you have just learned Python 3, so consider yourselves lucky. So another thing they talk about a lot, and it has to do with as we start thinking about storage allocation on a bit-by-bit basis, we tend to need to know how to represent and print things out, not just in base 10. And it really has to do with the fact that base 8 and base 16 are better at printing out binary data, raw data. 10 is the number like where, how many pizzas do you want? I want 16 pizzas or 22 pizzas. It's our natural, the way we think, the way humans think. So to talk about bases, let's start by just reviewing what base 10 means. There is, the ones place and the tens place, and of course later there's hundreds and thousands, but the 4 in 42 represents 4 tens. So you can think of it as 4 times 10, which is 40, and then the ones place is 2 more. So 42 is 40 plus 2, which is kind of redundant. We do that instinctively. So now let's take a look at base 8. So 42 in base 10 is 52 in base 8. And what base 8 is really doing is it means that the digits in the two places mean something different. Meaning the 5 in 52 represents an 8. So there's 5 8s in this number that we're dealing with and 2 1s. And so 5 times 8 is 40 and 2 times 1 is 2. And so converting from 52 base 8 to 52 base 10, we get to 42. And we used base 8, and again, base 8 lines up perfectly with base 2 because 3 base 2 digits equals 1 base 8 digit. And I did a lot of base 8 in the early days, but base 16 is really the way we tend to do it now because it's a little more dense. The rightmost place is still the 1s, and the next place is the 16s. So the 2 in the 16's place represents 2 times 16, or 32. And then what's left over is 10, which we represent with an A, and 10 plus 32 is 42. Now the problem is we only have digits 0 through 9. So by convention, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. F is all the 1s. It's 4 1s. I know that. I just like 4 1s. So I can convert hex from hex to base 2 like very, very quickly. And if I need to look at a dump of some memory, I can dump it in hex, and then when I need to, I can convert it to base 2. So just converting back and forth between base 16 and base 2 is a bit of a trick. And I don't really care if you do much of this. You can grab this sample code and play with it. This is a conversion from base 10, a base number like 1, 2, 3, 4, to base 8 and then base 16. And the way this one does it is it converts the number in effect from the rightmost number up to the low digit up to the high digit. And so what you do is you use the modulo function. And so you take your number, 1, 2, 3, 4, and you take it modulo 8, and what's left over as a remainder is 2. So that's the far right number in the new one. And then you chop it off with integer division. You chop that off and see what's left, and that's 154. And you're accumulating the 2 in the converted number. And then you take the modulo of 154, modulo 8, and you get 2. And then you chop off the next 8 with integer divide by 4, and you get 19. So now your bottom 2 digits are 2, 2. And then you do 19 modulo 8, and you get 3. And that next digit from the right is a 3. Then you divide by 8, integer divide by 8 to get what's left over. And that's below 8, and so that the fourth digit from the right is a 2. So 1, 2, 3, 4 in base 8 is 2, 3, 2, 2. And you can do the exact same thing. The difference is you got to look up the digits because the base 16 needs the A, B, C, D, E, F, and so I make a little string. Now, we're talking Python here. And so we do repeatedly modulo 16, integer divide by 16, modulo 16, integer divide by 16, modulo 16, integer divide by 16. And so we take 1, 2, 3, 4, and when we convert it to base 16, it kind of comes up from the bottom as 2D4, which we read 4D2. So that's just an algorithm that converts these. You tend to use this modulo, and that's how we can convert from one base to another. Now, it's not critical in this class. We're not going to spend a lot of time converting bases, but we just need to be aware that because there was so much awareness of how bits were stored, we tended to print a lot of stuff out in hexadecimal or in base 8, and so I just want you to know what those things are. So if you look, for example, at the ASCII chart that we've already seen, you see that it shows us that the letter A is 65, and in hex it's 41, and in octal it's 101, and in base 2, or binary, it's 1 and a bunch of zeros and a 1. And so this is just something that's making, and in the old days you had to be just much more aware of the real bits inside the computer, and hex and base 8, hex and octal, were better ways to sort of know what the bits were. So there you go. Now, another thing that C really was one of the early innovative language was byte addressable computers, right? And so we don't think much. Everything's a string, and we can look at the characters in the string. But in the old days, before C and the generation of computers that kind of triggered C, we didn't have characters. You couldn't, in the hardware, load a character. You could only load a word, and then you had to find the character within the word. And the language that really was the immediate precursor to C was the B language. And the difference is the B language was a really cool, low-level, word-oriented language, and then the C language came from B and became a byte-oriented language. And so C sort of said, we're going to do byte addressing. So if I take a look at the way I had to do character support in a CDC 6500, which is the computer I was using in 1975, 1976, it was a scientific computer. It barely cared about printing characters. It didn't even have lowercase. It had 60-bit words and packed 6-bit uppercase characters into those words. And it used a series of zeros to fill it up. And so if I put the word hello world into the CDC 6500, it took 2 words, and hello space WORL was packed into the first word, and D was in the second one, and then we did what was called zero filling. The rest of those characters were all zeros, the integer zeros, 0, 0, 0, 0, 0, 0, 0. And if I wanted to know what the 5th character of this 2-word string was, like the O, for example, you would create a mask. And in that mask, you would have zeros where you wanted to get rid of stuff and ones where you wanted to copy stuff. So you would take hello world and you'd run it through this mask with the bits in the right position, and then you would get the O and all zeros in the rest of the word, and then you would have to shift it half the way down because there were 10 characters, so you had to shift it 5 characters to the right, and then you would have the letter O in the bottom 6 bits of that word, and then I could write an if statement. That's how I would say if the fifth character is the letter O, I had to extract the fifth character by hand. So you can imagine how happy I was when I began to see programming languages that allowed me to use more of an array syntax and say string sub 5, or even in this case 0, 1, 2, 3, 4, string sub 4, where I could treat characters as an array. The notion of a character array for me in 1977 was, what? Why would you, you couldn't do that, right? And so we, a whole generation of programmers go through their entire career without having to do any masking and shifting. So this chapter is going to talk to you about it. And you might say, well, if C was so good at doing it for you, why did they show it? And that is that people like me would not have had respect for this language if it weren't for the fact that they had good masking and shifting, because we were doing that all the time in these word-oriented computers and word-oriented languages. And just as C and Unix were making the world safe for characters, then we had this other problem. And I'm only going to talk a little bit about this. Just don't worry about it. The concept of endianness. So if you're loading words, do you load them with the least significant digits first or the most significant digits first? And most computers were big endian, and big endian to us software developers made the most sense because that's how we thought it would lay out. But it turns out that a few processors wanted to load, if they were going to do an add, they wanted to load the low end of the integer first so they could start the addition while they're bringing in the high end. And they could overlap the load and the add. And then Intel, which in those days wasn't all that popular, but they were so interested in the microprocessor performance that they became little endian so that their loading and addition were fast. And so we've been stuck with a lot of little endian microprocessors since then, and big endian and little endian. It's one of the harder things to solve, really. It really is. And so I'm going to show you some code. I really, all I want you to do is feel sorry for those of us who had to figure out little endian and big endian. And let me just give you an outline of what this code is doing. I'm not going to walk through it in detail. It just is kind of scary. So, and you're not even going to understand most of this code until chapter 5. It's just, let's just talk a little bit about the bits and how masking and shifting would have worked if we didn't have character arrays. So what I'm doing in this program is I'm creating a character array. The length of this character array is hello world plus 1 for the terminator, HELLO space WORLD. So 11 plus 1 should be 12 characters are allocated. And then what I'm doing in this next line that says int star SI is I'm actually saying I want to take this same storage and pretend it's an integer array. And so that's what that line is it takes the address of the beginning of the first character and convert it from a pointer to a character, which is char s is a pointer to a character, and have it be a pointer to an integer. And again, I'm sort of like jumping ahead in chapter 5. So I'm not expecting to understand all this. I'm just making you aware of it. So in those first two lines, I've got a character array and an integer array. Okay? And this is a 32-bit integer, and so that means that the characters are stuck into 32-bit integers in a little endian way. And so if you look, that means that if you just look at memory from left to right, that the lowest of the first 4, which is 32 bits, the first character that comes out is the L, right? And you can see the little endian, which in your mind thinks it should be shifted, but that's because this is running on a little endian computer. And different computers will give you different results. And this is a little endian example. And so you can see with masking and shifting where I'm going to try to get the E out, which would normally be the second character, but it's kind of the second from the bottom of the first integer. And so what I do is I make a mask, and I'm going to print this out. I take FF, which is 8 bits of ones, and then I shift it up 8 characters to the left, and you can see that in the printout. And then I mask out that character, which is the E, but then it's in the wrong position, and then I have to take that masked result and I have to shift it back down 8 so that it's in the bottom part. So now I can check to see what that letter is. This is how I would pull out the second character of a string so I could check to see if it's an E. Because I can't compare directly the second character of string, right? In Python, you're like, why are we doing this? And that's why you build a string class instead of use a character array for this. And I made it even worse by like starting with taking a character array and viewing it as an integer array and then playing with the integers. So, you don't have to understand this. Just be thankful that you use Python, and if you don't use Python, you use C, and whether it's a big endian or a little endian machine, you can treat an array of characters as an array of characters, and you can get the third one or the fifth one with a square bracket notation. Okay? Storage allocation, storage allocation, storage allocation. So a summary of this lecture is we talked about number-based conversion. We talked a little bit about division, why the Python 2 integer division happened. I don't really have a really good answer for that. Concept of integers and words and bytes and masking and shifting and characters, just because these topics are covered in this chapter and they will feel very foreign to you and unnatural. But just give them a shot, read through them, understand them, and they'll make sense later. Later we're going to learn about structures and pointers and addresses advancing and stuff like that. It'll all make a lot more sense coming up. Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 2. Types, Operators, and Expressions. Variables and constants are the basic data objects manipulated in a program. Declarations list the variables to be used and state what type they have and perhaps what their initial values are. Operators specify what is to be done to them. Expressions combine variables and constants to produce new values. These are the topics of this chapter. Section 2.1. Variable names. Although we didn't come out and say so, there are some restrictions on variable and symbolic constant names. Names are made up of letters and digits. The first character must be a letter. The underscore counts as a letter. It is useful for improving the readability of long variable names. Upper and lower case are different. Traditional C practice is to use lowercase for variable names and all uppercase for symbolic constants. Only the first 8 characters of an internal name are significant, although more may be used. For external names, such as function names and external variables, the number must be less than 8 because external names are used by various assemblers and loaders. Appendix A lists the details. Furthermore, keywords like if, else, int, float, etc. are reserved. You can't use them as variable names, and they must be in lowercase. I would note that in modern C languages, the limitation of the first 8 characters of a variable name being unique has been extended. In most C variants, at least 30 characters of a variable are treated as unique. The 8-character limitation was to reflect the typical limitation of identifier length in assembly language programming and runtime linkers of the time. Naturally, it's wise to choose variable names that mean something, that are related to the purpose of the variable, and are unlikely to get mixed up typographically. Section 2.2. Data types and sizes. There are only a few basic data types in C. Char, which is a single byte, capable of holding 1 character in the local character set. Int, an integer, typically reflecting the natural size of integers on the host machine. Float, a single precision floating point. And double is a double precision floating point. In addition, there are a number of qualifiers which can be applied to int: short, long, and unsigned. Short and long refer to different sizes of integers. Unsigned numbers obey the arithmetic of modulo 2 to the n, where n is the number of bits in an int. Unsigned numbers are always positive. The declarations for qualifiers look like short int x semicolon, long int y semicolon, unsigned int z semicolon. The word int can be omitted in such situations and typically is. The precision of these objects depends on the machine at hand. The table below shows some representative values. On a DEC PDP-11, a char is 8 bits. On int is 16, a short is 16, a char is 32, a float is 32, a double is 64. On a Honeywell 6000, which uses ASCII character set, a char is 9 bits, an int is 36 bits, a short is 36 bits, a char is 36 bits, and a float is 36 bits, and a double is 32 bits. On the IBM 370, which is EBCDIC in its character set, a char is 8 bits, an int is 32 bits, a short is 16 bits, a char is 32 bits, a float is 32 bits, and a double is 64 bits, and so on. The intent is that short and long should provide different lengths of integers where practical. Int will normally reflect the most natural size of a particular machine. As you can see, each compiler is free to interpret short and long as appropriate for their own hardware. About all you should count on is that short is no longer than long. In this table, we see that in the mid-1970s, C was designed to support a range of computer generations. The PDP-11 was a common previous generation computer that had less memory, so variable sizes were kept small. The more modern computers in the chart had a bit more memory and could afford to have slightly larger sizes. The idea of a natural size is the size that could be loaded, computed, and stored in usually a single machine language instruction. You knew as a programmer that when you used int, the machine code you would generate would not need to include extra instructions for a simple line of code like x equals x plus 1 semicolon. Modern int values in C are 32 bits long, and long values are 64 bits long. Even though modern computers can do 64-bit computations in a single instruction, using the shorter int type when appropriate can save on memory storage and memory bandwidth using int values. Interestingly, the length of a 32-bit int leads to a Unix and C problem with dates that is called the year 2038 problem. A common way to represent time in Unix C programs was as a 32-bit integer of the number of seconds since January 1st, 1970. It was quick and easy to compare or add or subtract these second counter dates in code and even in databases. But the number of seconds since January 1st, 1970 will overflow a 30-bit number on the 19th of January in 2038. By now, in order to avoid problems, most systems have converted to storing these number of second values in long or 64-bit values, which gives us almost 300 billion years until we need to worry about overflowing second timer counters again. Back when C was developed, we had 2 different character sets and 2 different character variable lengths. The world generally standardized on the ASCII character set for the core Western characters and the Unicode/UTF-8 to represent all characters in all languages worldwide. But that is a story for another time. For now, just think of the char type as also a byte type. It is 8 bits in length and can store ASCII. Modern languages like Python or Java have excellent support for wide character sets. In our historical look at C, we will not cover wide or multi-byte characters. Also, if you look at the float and double types, you will see different bit sizes. Even worse, each of these computers in the 1970s did floating point computation using slightly different hardware implementations, and the same code run on different computers would give slightly different results and have unpredictable behavior on overflow, underflow, and other extraordinary floating point operations. This was solved by the introduction of the IEEE 754 standard in 1985, which standardized floating point format. This standardized both the length of the float and the double, but also ensured that the same set of floating point calculations would produce the exact same result on different processors. 2.3 constants. Int and float constants have already been disposed of. except to note that the usual 123.456 E-7 or 0.12 E3 scientific notation for floats is also legal. Every floating point constant is taken to be double, so the E notation serves for both float and double. Long constants are written in the style 1, 2, 3, capital L. An ordinary integer constant that is too long to fit into an int is also assumed to be a long. There is a notation for octal and hexadecimal constants. A leading 0 on an int constant implies octal, and a leading 0x or 0x uppercase indicates hexadecimal. For example, the decimal 31 can be written as 037 in octal and 0x1f, or 0x1f, where f is capitalized, in hex. Hexadecimal and octal constants may also be followed by the letter L to make them long. A character constant is a single character written in single quotes, as in quote x quote. The value of the character constant is the numeric value of the character in the machine's character set. For example, the ASCII character set 0, or quote 0 quote, is 48, and an EBCDIC quote 0 quote is 240, both quite different from the numeric value 0. Writing quote 0 quote instead of a numeric value like 48 or 240 makes the program independent of the particular value. Character constants participate in numeric operations just like any other numbers, although they are most often used in comparisons with other characters. A later section treats conversion rules. Certain non-graphic characters can be represented in character constants by escape sequence, like \n for new line, \t for tab, \0 for null, \\/ for \/ itself, and \quote for single quote, etc. These look like two characters, but they're actually only one. In addition, an arbitrary byte-sized bit pattern can be generated by writing single quote, \, and then 3 digits, single quote, where the 3 digits is 1 to 3 octal digits, as in #define space form feed, single quote, \014, single quote, which is ASCII for a form feed. We mention form feed here because in the 1970s we sent much of our output to printers, physical printers. A form feed was the character we would send to the printer to advance to the top of a new page. The character constant, quote, \0 quote, represents the character with the value 0. Quote, \0 quote is often written instead of 0 to emphasize the character nature of some expression. A constant expression is an expression that only involves constants. Such expressions are evaluated at compile time rather than runtime, and accordingly may be used in any place a constant may be, as in #define max line 1000, char line open bracket max line +1 close bracket semicolon, or seconds equals 60 times 60 times hours. A string constant is a sequence of 0 or more characters surrounded by double quotes, as in double quote I space am space a space string double quote, or double quote, which is a way to show an empty string. The quotes are not part of the string, but only serve to delimit it. The same escape sequences used for character constants apply in strings. \double quote represents the double quote character. Technically, a string is an array whose elements are single characters. The compiler automatically places the null character, \0, at the end of each such string, so programs can conveniently find the end. This representation means that there is no real limit on how long a string can be, but programs have to scan 1 to completely determine its length. The physical storage required is one more location than the number of characters written between the quotes. The following function, strlen, taking the parameter s, returns the length of the character string s, excluding the terminal \0. Sterlin, open parenthesis, S, close parenthesis. Char, S, open bracket, close bracket, semicolon. Open curly brace. Int space I, semicolon. I equals 0, semicolon. While, parenthesis, S, sub I, exclamation equals, quote, \0, quote, close parenthesis, plus I, semicolon. Return, parenthesis, I, parenthesis, semicolon, close curly brace. Be careful to distinguish between the character constant and the string that it contains a single character. Single quote X, single quote, is not the same as double quote X, double quote. The former is a single character used to produce the numerical value of the letter X in the machine's character set. The latter is a character string that contains one character, the letter X, and a \0. Section 2.4. All variables must be declared before use, although certain declarations can be made implicitly by context. A declaration specifies a type and is followed by a list of one or more variables of that type, as in int lower, upper, step, semicolon. Char, C, line, open bracket 1000, close bracket, semicolon. Variables can be distributed among declaration in any fashion. The list above could be equally well written as int lower, semicolon, int upper, semicolon, int step, semicolon, char, C, semicolon, char, line, open bracket 1000, close bracket, semicolon. The latter form takes more room, but it is convenient for adding a comment to each declaration or for subsequent modifications. Variables may also be initialized in their declaration, although there are some restrictions. If the name is followed by an equal sign in a constant, that serves as an initializer, as in char equals single quote \\, single quote, semicolon. Int I equals 0, semicolon. Float EPS equals 1.0 E minus 5, semicolon. If the variable in question is external or static, the initialization is done once only, conceptually, before the program starts executing. Explicitly initialized automatic variables are initialized each time the function they are in is called. Automatic variables for which there is no explicit initializer have undefined, that is, garbage values. External and static variables are initialized 0 by default, but it is a good style to state the initialization anyway. We will discuss initialization further as new data types are introduced. Section 2.5. Arithmetic operators. The binary operators are plus, minus, asterisk, and slash, and the modulus operator %. There is a unary minus but no unary plus. Integer division truncates any fractional part. The expression x%y produces the remainder when x is divided by y, and is thus 0 when y divides x exactly. For example, a year is a leap year if it is divisible by 4 but not by 100, except that years divisible by 4 are leap years. Therefore, if year %4 equals 0, and year %100 not equal 0, or year %400 equals 0, it's a leap year, else it's not. The % operator cannot be applied to float or double. The plus and minus operators have the same precedence, which is lower than the identical precedence of asterisk, slash, and %, which are in turn lower than unary minus. Arithmetic operators group from left to right. A table at the end of this chapter summarizes precedence and associativity for all operators. The order of evaluation is not specified for associative and commutative operators like asterisk and plus. The compiler may rearrange a parenthesized computation involving these. Thus, a plus open parenthesis b plus c, close parenthesis, can be evaluated as open parenthesis a plus b, close parenthesis plus c. This rarely makes any difference, but if a particular order is required, explicit temporary variables might be used. The action on overflow or underflow depends on the machine at hand. I would note that the above paragraph allows the compiler allowing the compiler to reorder computations, even in the presence of parentheses, is known as the K&R C arrangement license. As the authors state, it almost never makes a difference unless an expression contains a value computed in a function call, or is there a pointer lookup to find a value for the computation that might fail. The rule was subtly adjusted in the ISO version of C, but ISO C still does not strictly force the order of otherwise commutative operations, even in the presence of parentheses. The good news is that as long as you keep your expression simple, you don't have to worry about this rule. Sometimes the real value of parentheses is to communicate your intentions to the human readers of your code. If you are writing code that depends on the order of overflow, function calls, and pointer dereferences in a single mathematical expression, perhaps you should break your expression into multiple statements. Section 2.6, Relational and Logical Operators. The relational operators are greater than or equal, less than or equal. They all have the same precedence. Just below them in precedence are the equality operators, double equals and exclamation equals, which have the same precedence. Relationals have lower precedence than arithmetic operators, so expressions like I less than lim minus 1 are taken as I less than open parenthesis lim minus 1 close parenthesis, as would be expected. More interesting are the logical connectives double ampersand and double vertical bar, and or. Expressions connected by double ampersand or double vertical bar are evaluated left to right, and the evaluation stops as soon as the truth or falsehood of the result is known. These properties are critical in writing programs that work. For example, here is a loop from the input function getLine, which we wrote in Chapter 1. For parenthesis I equals 0 semicolon, I less than lim minus 1 double ampersand, parenthesis C equals getchar open parenthesis, close parenthesis, not equal, single quote backslash n, single quote, double ampersand, C exclamation equal EOF semicolon, plus I, close parenthesis, S sub I equals C. Clearly, before reading a new character, it is necessary to check that there's room to store the array, so the test I less than lim minus 1 must be made first. Not only, but if this test fails, we must not go on and read another character. Similarly, it would be unfortunate if C were tested against EOF before getchar was called. The call must occur before the character C is checked against EOF. The precedence of double ampersand and is greater than that of double vertical bar or, and both are lower than the relational inequality operators. So expressions like I less than lim minus 1 double ampersand parenthesis C equals getchar open paren close paren not equal single quote backslash n single quote double ampersand C not equal EOF needs no extra parentheses. But since the parenthesis of not equals is higher than assignment, parentheses do need to be added in open paren C equals getchar open paren close paren not equal backslash n to achieve the desired result. Let's take a brief digression. One of the great debates of the 1970s was how to use structured programming to avoid any use of goto statements that lead to completely unreadable spaghetti code. Structured code was easier to read, debug, and validate. Structured code advocated for if-then-else, else-if, while-do loops, and do-while loops, where the loop exit test was at the top or the bottom of the loops, respectively. There was a move from flowcharts with lines, boxes, and arrows to structured programming techniques like Nashi-Schneiderman diagrams that used nested boxes to emphasize the structured nature of the code. The proponents of each approach tended to approach the problem based on the language they used. Algol and Pascal programmers were strong advocates of structured programming, and those languages had syntax that encouraged the approach. Fortran programs had decades of flowchart use and flowchart style thinking, and tended to avoid full adoption of structured programming. Kernighan and Ritchie chose a middle path and made it so that C could support both approaches to avoid angering either side of the structured programming debate. One area where the structured code movement kept hitting a snag was implementing a loop that reads a file and processes data until it reaches the end of file. The loop must be able to handle an empty file or no data at all. There are three ways to construct a read and process until EOF loop, and none of the approaches are ideal. The loop constructions that you can do are a top-tested loop with a priming read before the loop, a bottom-tested loop with a read as the first statement in the loop and an if-then-else as the rest of the body of the loop, a top-tested infinite loop with a priming read and a middle test and exit, and a top-tested loop with a side effect read in the test of the loop, which is the way that Kernighan and Ritchie chose to document in this chapter. All of this serves to explain the syntax, while open parenthesis, C equals getchar, open paren, close parenthesis, not equal EOF, close parenthesis, open curly brace, body of the loop, close curly brace. This construct is a top-tested loop, which most programmers prefer, and it folds the priming read and puts its value inside the variable C. But since getchar might also return EOF, we need to check if we actually receive no data at all and need to avoid executing the body of the loop or exit the loop. If EOF were defined as 0 instead of -1, the loop could have been written while open parenthesis C equals getchar, open paren, close parenthesis, open curly brace, body of the loop, close curly brace. Now, the getchar function returns a character or 0, and the test itself is looking at the side effect or residual value of the assignment statement to decide to start and or continue the loop body. The problem with using 0 as end of file, if you are reading a binary file like JPEG data, a 0 character might make perfect sense, and we would not want to incorrectly end the loop because of a 0 character in input data that is not end of file. So we get the double parentheses syntax. The side effect call to getchar and test the return value within the while test. I'm quite confident that this is far more detail that you wanted here in Chapter 2, but it is as good a time as any to understand how much thought goes into a programming language, how it is designed and documented. By the time we finish Chapter 3 and look at the break and continue statements, which are in languages like Python and Java, you will see that this 50-year-old structured programming debate is still unresolved in the minds of many software developers. Back to the book. The unary negation operator, logical negation operator, converts a non-zero or true operand into 0 and a 0 or false operand into 1. A common use of exclamation, which we often call bang, is in constructions like if, open parenthesis, exclamation point inward, close parenthesis, rather than if, open parenthesis, inward equal 0. It is hard to generalize about which of these two forms is better. Construction like exclamation inward read quite nicely as if not in word, but more complicated ones can be hard to understand. Section 2.7, Type Conversions. When operands of different types appear in expressions, they are converted to a common type according to a small number of rules. In general, the only conversions that happen automatically are those that make sense, such as converting an integer to a floating point in an expression like f plus I. Expressions that don't make sense, like using a float in a subscript, are disallowed. First, chars and ints may be freely intermixed in arithmetic expressions. Every char in an expression is automatically converted to an int. This permits considerable flexibility in certain kinds of character transformations. One is exemplified by the function a to I, which converts a string of digits into its numeric equivalent. A to I, open parenthesis, s, close parenthesis. Char, s, open bracket, close bracket, semicolon. Open curly brace. Int, I, comma, n, semicolon. N equals 0. for parenthesis I equals 0, semicolon, S sub I greater than or equal to, quote, 0, quote, double ampersand, S sub I less than or equal to, double, quote, 9, quote, semicolon, plus I, close parenthesis. N equals 10 asterisk N plus S sub I minus single quote 0, single quote, semicolon. Return open parenthesis N, close parenthesis, semicolon. Close curly brace to end the function. As we discussed in Chapter 1, the expression S sub I minus quote 0, quote gives the numeric value of the character stored in S sub I because the values 0, 1, etc. form a continuously increasing positive sequence. Another example of the char to int conversion is the function lower, which maps a single character to lowercase for the ASCII character set only. If the character is not an uppercase letter, lower is returned unchanged. Here's a function. Lower, open parenthesis, C, close parenthesis, int C semicolon, open curly brace. If, open parenthesis, C greater than or equal to, quote, capital A, quote, double ampersand, C less than or equal to, quote, Z, quote, uppercase Z, parenthesis, return, open parenthesis, C plus, quote, lowercase a, quote, minus, quote, uppercase A, quote, close parenthesis, semicolon, else return C. This works for ASCII because the corresponding upper and lowercase letters are a fixed distance apart as numeric values, and each alphabet is contiguous. There is nothing but letters between A and Z. This latter observation is not true of the EBCDIC character set on IBM 360-370 architectures, so this code fails on such systems. It converts more than letters. There is one subtle point about the conversion of characters to integer. The language does not specify whether the variables of type char are signed or unsigned quantities. When char is converted to an int, can it ever produce a negative number? Unfortunately, this varies from machine to machine, reflecting differences in architecture. On some machines, PDP-11 for instance, a char whose leftmost bit is 1 will be converted to negative integer using sign extension. On others, a char is promoted to an int by adding zeros at the left end and is thus always positive. The definition of C guarantees that any character in the machine standard character set will never appear to be negative, so these characters may be used freely in expressions as positive quantities, but arbitrary bit patterns stored in character variables may appear to be negative on some machines, yet positive on others. The most common occurrence of this situation is when the value -1 is used for EOF. Consider the code char C semicolon. C equals get char open paren close paren semicolon. If open paren C double equals EOF close paren ... On a machine which does not do sign extension, C is always positive because it returns a char. Yet EOF is negative. As a result, this test always fails. To avoid this, we have been careful to use int instead of char for any variable which holds a value returned by the function getChar. The real reason for using int instead of char is not related to any questions of possible sign extensions. It is simply that getChar must return all possible characters so that it can be used to read arbitrary input, and in addition, a distinct EOF value. Thus, its value cannot be represented as a char, but must instead be stored as an int. As an aside, since the book was written before the getChar function was standardized, the text is somewhat vague in this section. Shortly after the book was published, getChar was put into the stdio.h library and declared to return an integer so as to accommodate all possible characters and the integer -1 value to indicate the end file. The above code would be better written with C declared as an integer. Int C semicolon. C equals getChar, open paren, close paren, semicolon. If, open paren, C double equal EOF, close paren, ... While the conversion from char to int may or may not have sign extension, And yes, it still depends on the implementation 50 years later. The conversion from int to char is predictable, with the top bits being simply discarded. If you're using the library function getS to read a file line by line, we don't need to worry about this conversion. Since getS returns a pointer to a character array, i.e. a string, it indicates it has reached end of file by returning the null pointer, i.e. there is no more data to give. Back to the textbook. Another useful form of automatic type conversions is that relational expressions like I greater than j and logical expressions constructed by double ampersand and double vertical bar, and or respectively, are defined to have the value 1 if true and 0 if false. Thus, the assignment isDigit equals c greater than or equal to quote 0 quote double ampersand c less than or equal to quote 9 quote sets the variable isDigit to 1 if c is a digit and 0 if it's not. In the if test in a test part of an if, while, or for, true just means non-zero. Implicit arithmetic conversions work much as expected. In general, if an operator like C or asterisk for multiplication, which takes two operators, i.e. a binary operator, if it has operands of different types, the lower type is promoted to the higher type before the operation proceeds, and the result is the higher type. More precisely, for each arithmetic operator, the following sequence of conversion rules is applied. Char and short are converted to int, and float is converted to double. Then, if either operand is double, the other is converted to double, and the result is double. Otherwise, if either operand is long and the other is converted to long, the result is long. Otherwise, if either operand is unsigned, the other is converted to unsigned, and the result is unsigned. Otherwise, the operands must be int, and the result is int. Note that all float values in an expression are converted to double. All floating point arithmetic in C is done in double precision. Conversions take place across assignments. The value of the right side is converted to the type of the left, which is the type of the result. A character is converted to an integer either by sign extension or not, as described above. The reverse operation into char is well behaved. Excess high order bits are simply discarded. Thus in int I semicolon char c semicolon, I equals c, c equals I, the value of c is unchanged. And this is true whether or not sign extension is involved. If x is float and I is int, then x equals I and I equals x both cause conversions. Float to int causes truncation of any fractional part. Double is converted to float by rounding. Longer ints are converted to shorter ones or to chars by dropping excess high order bits. Since a function argument is an expression, type conversions also take place when arguments are passed to functions. In particular, char and short become int and float becomes double, and that is why we have declared function arguments to be int and double even when the function is called with char and float. Finally, explicit type conversions can be forced, also we call it coerced, in any expression with a construct called the cast. In the construction, open parenthesis type name, close parenthesis expression, the expression is converted to the named type by the conversion rules above. The precise meaning of cast is in fact as if the expression were assigned to a variable of the specified type, which is then used in place of the whole construction. For example, the library square root, sqrt, expects a double argument and will produce nonsense if inadvertently handed something else. So if n is an integer, sqrt, open parenthesis, double, close parenthesis, n, close parenthesis, converts n to double before passing it to sqrt. Note that the cast produces the value of n in the proper type. The actual content of n is not altered. The cast operator has the same precedence as other unary operations as is summarized in the table at the end of this chapter. Section 2.8, Increment and Decrement Operators. C provides two unusual operators for incrementing and decrementing variables. The increment operator, ++, adds 1 to its operand. The decrement operator, --- subtracts 1. We have frequently used plus plus to increment variables, as in if open parentheses c equals single quote backslash n single quote close parenthesis plus plus and l semicolon. The unusual aspect is that plus plus and minus minus may be used either as prefix operators, i.e. before the variable as in plus plus n, or postfix after the variable n plus plus. In both cases, the effect is to increment n, but the expression, the residual value of the expression plus plus n, increments n before using its value, while n plus plus increments n after its value has been used. This means that in a context where the value is used, not just the effect, plus plus n and n plus plus are different. If n is 5, then x equals n plus plus semicolon sets x to 5, the old value. But x equals plus plus n semicolon sets x to 6, the new value. In both cases, n becomes 6. The increment and decrement operators can only be applied to variables. An expression like x equals open parenthesis I plus j, close parenthesis plus plus is illegal. In a context where no value is wanted, just incrementing effect, as in if open parenthesis c double equals single quote backslash n single quote close parenthesis n l plus plus semicolon, choose prefix or postfix according to taste. But there are situations where one or the other is specifically called for. For example, consider the function squeeze, s, c, which removes all occurrences of the character c from the string s. Squeeze, open parenthesis, s, c, close parenthesis. Char, s, open bracket, close bracket, semicolon, int c, semicolon. Open curly brace, int I, j, semicolon. For parenthesis, I equals j equals 0, semicolon, s sub I not equal to single quote backslash 0 single quote semicolon I plus plus close parenthesis. If open parenthesis s sub I not equal to c close parenthesis, s sub j plus plus close parenthesis equals s sub I. And outside the for loop totally, s sub j equals backslash quote s sub j equals quote backslash 0 quote semicolon close curly brace. Each time a non-c, a character other than what's in the variable c, occurs, it is copied into the current j position, and only then is j incremented to be ready for the next character. This is exactly equivalent to if open parenthesis s sub I not equal to c close parenthesis open curly brace s sub j equals s sub I semicolon j plus plus semicolon close curly brace. Another example of a similar construction comes from the getLine function we wrote in chapter 1, where we can replace if open parenthesis c double equals quote backslash n quote close parenthesis open curly brace s sub I equals c semicolon plus plus I semicolon close parenthesis by the far more compact if parenthesis c double equals quote backslash n quote close parenthesis s sub I plus plus equals c semicolon. In a third example, the function stircat concatenates the string t to the end of the string s. Stircat does assume that there's enough space in s to hold the combination. Here's the code. Stircat, open parenthesis, s, t, close parenthesis. Char, s, open bracket, close bracket, comma, t, open bracket, close bracket, semicolon. Open curly brace. Int, I, j, semicolon. I equals j equals 0, semicolon. While, open paren, s sub I not equal, single quote backslash 0 single quote close paren I plus plus. In this we'd find the end of s. While open parenthesis s sub I plus plus equals t sub j plus plus close parenthesis not equal backslash 0 close parenthesis semicolon. That code copies the rest of t into s. Close curly brace. As each character is copied from T to S, the postfix ++ is applied to both I and J to make sure they are in position for the next pass through the loop. Section 2.9, Bitwise Logical Operators. C provides a number of operators for bit manipulation. These may not be applied to float or double. Ampersand is bitwise AND. Vertical bar is bitwise inclusive OR. Caret is bitwise exclusive OR. Less than is left shift, and greater than is right shift. And tilde is one complements, and it's a unary operator. The bitwise AND operator, ampersand, is often used to mask off some set of bits. For example, C equals N ampersand 0177 sets to 0 all but the lower 7 bits of N. The bitwise OR operator is used to turn bits on. X equals X vertical bar mask. Sets to 1 the X bits that are set to 1 in mask. You should carefully distinguish the bitwise operator ampersand and vertical bar from the logical connectives double ampersand and double vertical bar, which imply left to right evaluation of a truth value. For example, if X is 1 and Y is 2, then X single ampersand Y is 0, while X double ampersand Y is 1. Think about that for a moment. The shift operators less than and greater than perform left and right shifts respectively of their left operand by the number of bit positions given by the right operand. Thus, X less than 2 shifts X left by 2 positions, filling the vacated bits with 0. This is the equivalent to multiplication by 4. Right shifting an unsigned quantity fills the vacated bits with 0. Right shifting a signed quantity will fill the signed bits, or arithmetic shift, on some machines, such as PDP-11, and with 0 bits logical shift on other. The unary operator tilde yields the ones complement of an integer, that is, it converts each 1 bit into a 0 bit and vice versa. This operator typically finds use in expressions like X ampersand tilde 077, which masks the last 6 bits of X to 0. Note that X ampersand tilde 077 is independent of word length and is thus preferable to, for example, X ampersand 0177700, which assumes that X is a 16-bit quantity. The portable form involves no extra cost, since tilde 077 is a constant expression and thus evaluated at compile time. To illustrate the use of some of the bit operators, consider the function getBits, open parenthesis, x, p, n, which returns the right-adjusted n-bit field of x that begins at position p. We assume that bit position 0 is at the right end and that n and p are sensible positive values. For example, getBits, open paren x, 4, 3, close paren returns the 3 bits in bit positions 4, 3, and 2 right adjusted. Here we go with the code. GetBits, open paren x, p, n, unsigned x, p, n, semicolon, open curly brace. Return, open parenthesis, x, greater than, open parenthesis, p plus 1 minus n, close parenthesis, and ampersand, tilde, open parenthesis, tilde 0, less than, n, close parenthesis, semicolon, close curly brace. X, greater than, parenthesis, p plus 1 minus n, close parenthesis, moves the desired field to the right end of the word, declaring the argument to be x. Declaring the argument x to be unsigned ensures that when it is right shifted, vacated bits will be filled with zeros, not signed bits, regardless of the machine the program is run on. Tilde 0 is all 1 bits. Shifting it left n bit positions with tilde 0 tilde 0 less than n creates a mask with the zeros in the rightmost n bits and 1s everywhere else. Complementing that with tilde makes a mask with 1s in the rightmost bits. Bitwise operators may seem unnecessary for modern computers. But if you look at the internal structure of TCP/IP packets, the values are packed very tightly into the headers in order to save space. C made it possible to write portable TCP/IP implementations on a wide range of hardware architectures. Bitwise operators also play an important role in encryption, decryption, and checksum calculations. Modern languages like Java and Python support bitwise operators following the same patterns that we established in C, so that things like TCP/IP and encryption algorithms can also be implemented in these languages. By defining these operators, it kept software developers from needing to write non-portable assembly language to implement these low-level features in operating systems and libraries. Section 2.10, Assignment Operators and Expressions. Expressions such as I equals I plus 2, in which the left-hand side is repeated on the right, can be written in the compressed form I plus equals 2, using an assignment operator like plus equals. Most binary operators like plus that have a left and right operand, have a corresponding assignment operator, op equals, where op is one of plus, minus, asterisk for multiplication, slash for division, percent for modulo, less than, left shift, greater than, right shift, ampersand, bitwise and, caret, exclusive or, vertical bar, bitwise or. If E1 and E2 are expressions, then E1 operand equals E2 is equivalent to E1 equals E1 operand E2, except that E1 is only computed once. Note the parentheses around E2. X star equals Y plus 1 is actually X equals X times parenthesis Y plus 1 close parenthesis, rather than X times Y plus 1. As an example, the function bit count counts the number of 1 bits in its integer argument. Here's the code. Bit count, open parenthesis, n, close parenthesis, unsigned, n, semicolon. Open curly brace, int b. For, open parenthesis, b equals 0, semicolon, n, exclamation equals 0, semicolon, n, greater than equal 1, close parenthesis. If, open parenthesis, n ampersand 0, 1, close parenthesis, b plus plus semicolon, return, open paren, b, close paren, semicolon, curly brace. Quite apart from its conciseness, assignment operators have the advantage in that they correspond better to the way people think. We say add 2 to I, or increment I by 2, not take I, add 2, and put the result back in I. Thus, I plus equal 2. In addition, for a complicated expression like yyval, open bracket, yypv, open bracket, p3 plus p4, close bracket, plus yypv, open bracket, p1 plus p2, close bracket, plus equals 2, the assignment operator makes it code easier to understand, since the reader doesn't have to check painstakingly that 2 long expressions are indeed the same or wonder why they're not. An assignment operator may even help the compiler to produce more efficient code. We have already used the fact that the assignment statement has a side effect value and can occur in expressions. The most common example is while, open parenthesis, C equals getchar, open parenthesis, close parenthesis, exclamation equal EOF, close parenthesis, and then the rest of the loop. Assignments using other assignment operators, plus equal, minus equal, can also occur in expressions, although it's a less frequent occurrence. The type of an assignment expression is the type of its left operand. Section 2.11, Conditional Expressions. The statements, if parenthesis, A greater than B, close parenthesis, Z equals A, semicolon, else Z equals B, semicolon, of course, compute Z in the maximum of A and B. The conditional expression, written with a ternary operator, which is question mark and colon, provides an alternate way to write this and similar constructions. In the expression E1 question mark E2 colon E3, the expression E1 is evaluated first. If it is non-zero, true, then the expression E2 is evaluated, and that is the value of the conditional expression. Otherwise, E3 is evaluated, and that is the value. Only one of E2 and E3 are evaluated. Thus, to set Z to the maximum of A and B, we say Z equals parenthesis A greater than B, close parenthesis, question mark, A colon B. And this implements Z equals max of A and B. It should be noted that the conditional expression is indeed an expression and can be used just as any other expression. If E1 and if E2 and E3 are different types, the type of the result is determined by the conversion rules described earlier in this chapter. For example, if f is a float and n is an int, then the expression parenthesis n greater than 0, close parenthesis, question mark f colon n is of type double, regardless of whether n is positive or not. Parentheses are not necessary around the first expression of a conditional expression since the precedence of question mark colon is very low, just above assignment. They are advisable anyway, however, since they make the condition part of the expression easier to see. The conditional expression often leads to succinct code. For example, this loop prints n elements of an array, 10 per line, with each column separated by one blank, and with each line, including the last, terminated by exactly one new line. Here's the code. For parenthesis I equals 0, semicolon, I less than n, semicolon, I plus plus, close parenthesis. Printf, open parenthesis, double quote, %6d, %c, double quote, comma, a sub I, comma, open parenthesis, I %10, double equal 9, or double vertical bar, I double equal n minus 1, close parenthesis, question mark, single quote, backslash n, single quote, colon, single quote, space, single quote, close parenthesis, semicolon. A new line is printed after every 10th element and after the nth, and all elements are followed by one blank. Although this might look tricky, it's instructive to try to write it without the conditional expression. Section 2.12, Precedence and Order of Evaluation. The table below summarizes the rules for precedence and associativity of all operators, including those which we have not yet discussed. Operators on the same line have the same precedence. Rows are in order of decreasing precedence. So, for example, asterisk, slash, and percent all have the same precedence, which is higher than that of plus and minus. Parentheses, square brackets, the arrow operator, and the dot operator are first with the left to right associativity. Next precedence is exclamation, tilde, plus plus, minus minus, single minus, the cast, multiplication, bitwise and, size of, with right to left associativity. Then multiplication, division, and modulo with left to right associativity. Then plus and minus with left to right associativity. Then left shift, which is less than, and right shift, which is right greater than, with left to right associativity. Then logical operators, less than or equal to, greater than or equal to, with left to right associativity. Then comparison, double equals, not equal, exclamation equal, left to right. Then we have some bitwise operators, the bitwise and with left to right associativity. Then the bitwise exclusive or with left-right associativity, which is a caret. Then the single vertical bar, which is bitwise or with left to right associativity. Then we have ampersand, ampersand, which is and, the logical and, left to right associativity. Then double vertical bar, which is the logical or with left to right associativity. Then the ternary operator, which is question mark and colon with right to left associativity. Then the assignments, equals, plus equals, minus equals, etc., with right to left associativity. And then the comma, which we'll cover in the next chapter, with left to right associativity. The operators dash, greater than, and dot are used to access members of structures. They'll be covered in Chapter 6, along with size of, and then in Chapter 5, we'll discuss asterisk, indirection, and ampersand, address of. Note that the precedence of the bitwise logical operators ampersand, caret, and vertical bar falls below double equals and exclamation equals. This implies that bit testing expressions like if, parenthesis, x, ampersand, mass, close parenthesis, equal 0, close parenthesis, must be fully parenthesized to get proper results. As mentioned before, expressions involving one or more of the associative and commutative operators like multiply, plus, bitwise and, bitwise or, and bitwise exclusive or can be rearranged even when parenthesized. In most cases, this makes no difference whatsoever. In situations where it might, explicit temporary variables can use to force a particular order of evaluation. C, like most languages, does not specify in what order operands of an operator are evaluated. For example, in a statement like x equals f open parenthesis close parenthesis plus g open parenthesis close parenthesis semicolon, f may be evaluated before g or vice versa. Thus, if f or g alters an external variable that the other depends on, x can depend on the order value of evaluation. Again, intermediate results can be stored in temporary variables to ensure a particular sequence. Similarly, the order which function arguments are evaluated is not specified. So, the statement printf open parenthesis double quote %d space %d \n double quote comma plus n comma power open parenthesis 2 comma n close parenthesis is wrong. It can and often does produce different results on different machines, depending on whether or not n is incremented before power is called. The solution, of course, is to write +n semicolon printf open parenthesis double quote %d space %d \n double quote comma n comma power open parenthesis 2 comma n close parenthesis. Function calls, nested assignment statements, and increment and decrement operators cause side effects. Some variable is changed as a byproduct of the evaluation of an expression. In any expression involving side effects, there can be subtle dependencies on the order in which variables taking part in the expression are stored. One unhappy situation is typified by the statement, a sub I equals I plus plus. The question is whether or not the subscript is the old value of I or the new value. The compiler can do this in different ways and generate different answers depending on its interpretation. When side effects, i.e. assignment to actual variables, takes place, is left to the discretion of the compiler since the best order strongly depends on machine architecture. The moral of this discussion is writing code which depends on the order of evaluation is a bad programming practice in any language. Naturally, it is necessary to know what things to avoid, but if you don't know how they are done on various machines, that innocence may help to protect you. The C verifier lint will detect most dependencies on order of evaluation. I would add that the real moral of the story is to use side effect operators very carefully. They are generally only used in idiomatic situations and then written using simple code. The authors are happy to tell you everything that you can do in C in great detail. And they are also suggesting that just because you can do something does not mean that you should do something. Remember that a key aspect of writing programs is to communicate with future human readers of your code, including you reading your own code in the future. With modern-day compilers and optimizers, you gain little performance by writing dense or obtuse code. Write the code, describe what you want done, and let the compiler find the best way to do it. One of the reasons that a common senior project in many computer science degrees was to write a compiler is to make sure that all computer scientists understand that they can trust the compiler to generate great code. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications. Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 3, Control Flow. The control flow statements of a language specify the order in which the computations are done. We have already met the most common control flow constructions of C in earlier examples. Here we will complete the set and be more precise about the ones discussed above. 3.1 Statements and Blocks. An expression such as x equals 0 or I++ or printf open paren ... close paren becomes a statement when it is followed by a semicolon, as in x equals 0 semicolon, I++ semicolon, printf open parentheses something, close parenthesis, semicolon. In C, the semicolon is a statement terminator rather than a separator as it is in ALGOL-like languages. The braces, the curly braces, open curly brace and close curly brace, are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that actually surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for are another. Variables can actually be declared inside any block. We will talk about this in Chapter 4. There is never a semicolon after the right curly brace that ends a block. Ah, C, how do I love thee? Let me count the ways. Quote by Dr. Chuck with homage to Elizabeth Barrett Browning. The humble semicolon is why spacing and line ends do not matter in C and C-like languages. It means that we, as programmers, can focus all of our white space and line ends on communicating our intent to humans. This freedom is not an excuse to write obtuse code or dense code. For example, see the obfuscated Perl contest, but instead, freedom to describe what we mean or use spacing to help us understand or maintain our code. We can take a quick look at how a few other C-like languages that came after C treat the semicolon. Java is just like C in that the semicolon terminates statements. Python treats the semicolon as a separator, like ALGOL, allowing more than one statement on a single line. But since Python treats the end of a line as a statement separator, you generally never use semicolon in Python. But for people like me who automatically add a semicolon when typing code too fast, at least Python ignores the few semicolons I mistakenly add to my code out of habit. JavaScript treats the semicolon as a separator, but since JavaScript ignores the end of the line, it's treated as white space. Semicolons are required when a block of code consists of more than one statement. When I write JavaScript, I meticulously include semicolons at the end of all statements because any good programmer can write C in any language. Back to the text. 3.2. If-else. The if-else statement is used to make decisions. Formally, the syntax is if, parentheses, expression, parentheses, statement 1, else, statement 2, where the else part is optional. The expression in parentheses is evaluated. If it evaluates to true, that is, the expression has a non-zero value, Statement 1 is done. If it is false, the expression is 0. And there's an else part, statement 2 is executed instead. Since an if simply tests the numeric value of the expression, certain coding shortcuts are possible. The most obvious is writing if, open parenthesis, expression, instead of if, open parenthesis, expression, not equal 0, close parenthesis. Sometimes this is natural and clear, other times it's cryptic. Because the else part of an if-else is optional, there is an ambiguity when an else is omitted from a nested if sequence. This is resolved the usual way. The else is associated with the closest previous elseless if. For example, if open parenthesis n greater than 0 close parenthesis, if open parenthesis a greater than b close parenthesis, z equals a semicolon, else z equals b. The else with the z equals b goes with the inner if, as we have shown by the indentation in the above example. If that's not what you want, braces must be used to force the proper association. If n greater than 0, open curly brace, if a greater than b, z equals a semicolon, close curly brace, else z equals b. This ambiguity is especially pernicious in situations like if open parenthesis n greater than 0, for open parenthesis I equals 0 semicolon, I less than n semicolon, I plus plus close parenthesis, if open parenthesis s sub I greater than 0 close parenthesis, open curly brace, printf, string, ... close parenthesis, semicolon, return, open parenthesis I, close parenthesis, semicolon, close curly brace, else, and this is where it's wrong, printf, open parenthesis, error, n is 0, close parenthesis, semicolon. The indentation in the above example shows unequivocally what you want, but the compiler does not get the message and associates the else with the inner if. This bug can be very hard to find. By the way, notice that there is a semicolon after z equals a in if, open parenthesis, a greater than b, close parenthesis, z equals a semicolon, else z equals b semicolon. That is because grammatically a statement follows the if, and an expression like z equals a is always terminated by a semicolon. Section 3.3, else if. The construction if, open parenthesis, expression, close parenthesis, statement, else, blank, if, open parenthesis, expression, close parenthesis, statement, else, if, open parenthesis, expression, close parenthesis, statement, else statement occurs so often that it's worth a brief separate discussion. The sequence of ifs is the most general way of writing a multi-way decision. The expressions are evaluated in order. If any expression is true, the statement associated with it is executed, and this terminates the whole chain. The code for each statement is either a single statement or a group of statements in braces. The last else handles the none of the above or default case where none of the other conditions was satisfied. Sometimes there is no explicit action for the default. In that case, the trailing else statement can be omitted, or it may be used for error checking to catch an impossible condition. To illustrate three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array v. The elements of v must be in increasing order. The function returns the position, a number between 0 and n minus 1 if x occurs in v, n minus 1 if not. This sample code is on page 54. It is the first example on page 54 in the book. Binary, open parenthesis, x, comma, v, comma, n, close parenthesis. Int x, comma, v, open square bracket, close square bracket, comma, n, semicolon, open curly brace. Int low, comma, high, comma, mid, semicolon. Low equals 0, semicolon. High equals n minus 1, semicolon.
while, open parenthesis, low less than or equal to high, close parenthesis, open curly brace, mid equals open parenthesis, low plus high, close parenthesis, /2 semicolon. If, open parenthesis, x less than v sub mid, close parenthesis, high equals mid minus 1 semicolon. Else, if, open parenthesis, x greater than v sub mid, close parenthesis, low equals mid plus 1. Else, return, open parenthesis, mid, close parenthesis, semicolon, close curly brace, closing the while, and then return, open parenthesis, minus 1, close parenthesis, semicolon, close curly brace to end the function. The fundamental decision in this code is whether x is less than, greater than, or equal to the middle element v sub mid at each step. This is a natural for else if. I would note that in the above examples, the else and the if in C are two language constructs that are just being used idiomatically to construct a multi-way branch or else if pattern with indentation that captures the idiom. If we are pedantic about the indentation of the above sequence, we would be separating the else and if and indenting each succeeding block further as follows, with brackets or added for clarity. If, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, and now we're quite indented at this point, if, open parenthesis, expression, close parenthesis, open curly brace, statement, close curly brace, else, open curly brace, statement, close curly brace, close curly brace, close curly brace. Java and JavaScript keep the else and if as separate language elements and document their idiomatic usage and indentation just like C. But in Python, elif is a single keyword and a new language construct that achieves the same idiom as shown below. If, open parenthesis, expression, close parenthesis, colon, block. elif, open parenthesis, expression, close parenthesis, colon, block. elif, if elif, parenthesis, expression, parenthesis, colon, block, else, colon, block. The C, Java, JavaScript, and Python idioms thankfully look the same when the idiomatic indentation is used. Even Fortran 77 supports the else-if construct to implement multi-way logic. Section 3.4, switch. The switch statement is a special multi-way decision maker that tests whether an expression matches one of a number of constant values and branches accordingly. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters using a sequence of if-else, if-else. Here's the same program with a switch. This is the first example program on page 55. Pound include less than stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int c, comma I, comma n white, comma n other, comma n digit, open square bracket, 10, close square bracket, a 10-element array. N white equals n other equals 0. For I equals 0, I less than 10, I plus plus, n digit sub I equals 0. While parenthesis, parenthesis, c equals getchar, open paren, close paren, not equal EOF, close paren, switch, open parenthesis, c, close parenthesis, open curly brace. Case, quote 0, quote, colon, case, quote 1, quote, colon, case, quote 2, quote, colon, case, quote 3, quote, colon, case, quote 4, quote, colon, case, quote 5, quote, colon, case, quote 6, quote, colon, case, quote 7, quote, colon, case, quote 8, quote, colon, case, quote 9, quote, colon, n digit sub c minus quote 0 quote, close bracket, plus plus, break. Now that bit of code right there was to take all of 0 through 9 and guide it to the line of code that incremented the particular element of the n-digit array by 1. Continuing after the break, semicolon. Case quote space quote colon, case quote backslash n quote colon, case quote backslash t quote colon, n white plus plus semicolon, break. Default colon, n other plus plus colon, break semicolon, close curly brace. Print f, open parenthesis, double quote, digits equals double quote, close parenthesis, semicolon. 4, open parent I equals 0, I less than 10, I semicolon I plus plus, close parenthesis. Print f, open parenthesis, percent, space, percent d, close double quote, comma, n digit sub I, close parenthesis, semicolon. Print f, quote, backslash n, white space equals, percent d, comma, other equals percent d, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. The switch statement evaluates the integer expression in parentheses, in this case the character c, and compares its value simultaneously to all the cases. Each case must be labeled by an integer or character constant or constant expression. If a case matches the expression value, execution starts at that case. The case labeled default is executed if none of the other cases is satisfied. Default is optional. If it isn't there and none of the cases matches, no action at all takes place. Cases in default can occur in any order. Cases must all be different. The break statement causes an immediate exit from the switch. Because the cases serve as labels, after the code for one case is done, execution falls through to the next unless you take explicit action to escape. Break and return are the most common ways to leave a switch. A break statement can be used to force an immediate exit from a while, for, and do loops, as well as will be discussed later in this chapter. Falling through the cases is a mixed blessing. On the positive side, it allows multiple cases for a single action, as with blank tab or new line in this example. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust, being prone to disintegration when the program is modified. With the exception of multiple labels for a single computation, fall-throughs should be used sparingly. As a matter of good form, put a break after the last case, in this case default, although it's logically unnecessary. Someday, when another case gets added at the end, this bit of defensive programming will save you. The switch statement. What is there to say? I think that the switch statement was added to C to compete with the earlier Fortran computed goto statement, or just to keep low-level assembly language programmers from switching into assembly language to implement the concept of a branch table. The authors spend most of the previous section apologizing for the switch statement, so you should perhaps take this as a hint and never use it. There are very few situations where a branch table outperforms a series of this if-then-else checks, and those are likely deep in a library or operating system code. Programmers should only use switch if they understand what a branch table is and why a branch table is more efficient for the particular bit of a program they're writing. Otherwise, just use else if and do the readers of your code a favor. 3.5 loops, while and for. We have already encountered the while and for loops. In while open parenthesis expression close parenthesis statement, the expression is evaluated. If it is non-zero, the statement is executed and the expression is reevaluated. This cycle continues until the expression becomes a zero, at which point execution resumes after the statement. The for statement, for, open parenthesis, expression 1, semicolon, expression 2, semicolon, expression 3, close parenthesis, statement is equivalent to expression 1, semicolon, while, open parenthesis, expression 2, close parenthesis, open curly brace, statement, expression 3, semicolon, close curly brace. Grammatically, the three components of the for are expressions. Most commonly, expression 1 and expression 3 are assignments or function calls, and expression 2 is a relational expression. Any of the three parts can be omitted, although the semicolons must remain. If expression 1 or expression 3 is left out, it is simply dropped from the expansion. If the test expression 2 is not present, it is taken as permanently true. So, the code for, open parenthesis, semicolon, semicolon, close parenthesis, open curly brace, dot, 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 close curly brace, is an infinite loop, presumably to be broken by some other means, such as a break or a return. Whether to use while or for is largely a matter of taste. For example, in the code, while, open parenthesis, C equals get char, open paren, close parenthesis, equal, quote, space, quote, or C quote, backslash n, quote, or C quote, backslash T, quote, close parenthesis, semicolon, skipping white characters, there is no initialization or reinitialization, so a while seems more natural. The for is clearly superior when there is simple initialization and reinitialization, since it keeps the loop control statements close together and visible at the top of the loop. This is the most obvious in for, open paren, I equals 0, semicolon, I less than n, semicolon, I plus plus, close paren, which is the C idiom for processing the first n elements of an array, the analog of a Fortran or PL1 do loop. The analogy is not perfect, however, since the limits of a for loop can be altered within the loop and the controlling variable I retains its value when the loop terminates for any reason. Because the components of the for are arbitrary expressions, for loops are not restricted to arithmetic progressions. Nonetheless, it is bad style to force unrelated computations into a for. It is best reserved for loop control operations. As a larger example, here is another version of the a to I function for converting a string to its numeric equivalent. This one is more general. It copes with optional leading white space and an optional plus or minus sign. Chapter 4 shows A to F, which does the same conversion for floating point numbers. The basic structure of the program reflects the form of the input. Skip white space if any, get the sign if any, get the integer part, and convert it. Each step does its part and leaves a clean slate for the next. The whole process terminates on the first character that would not be part of a number. This is the first example on page 58 of the textbook. A to I, open paren, S, close paren, which is going to convert S to an integer. Char, S, open square bracket, close square bracket, semicolon. Open curly brace, int, I, comma, n, comma, sign, semicolon. For, I equals 0, S sub I equal, quote, space, quote, or S sub I equals, quote, backslash n, quote, or S sub I equals, backslash, quote, backslash T, quote, semicolon, I plus plus, semicolon. Skip white space. This is a for loop with an empty loop body. Sign equals 1, semicolon. If S sub I equal plus, or S sub I equal, quote, minus quote, close parenthesis, sign equals, and here we use a ternary operator, open parenthesis, S sub I plus plus, equal, quote, plus quote, close parenthesis, question mark, 1, colon, minus 1, semicolon. For, open parenthesis, n equals 0, semicolon, S sub I greater than or equal to, quote, 0, quote, and S sub I less than or equal to, quote, 9, quote, I plus plus, close parenthesis. n equals 10 times n plus s sub I minus quote 0 quote semicolon. Return, open parenthesis, sine times n, close parenthesis, semicolon. Close curly brace to end the function. The advantages of keeping loop control centralized are even more obvious when there are several nested loops. The following function is a shell sort for sorting an array of integers. The basic idea of the shell sort is that in early stages, far apart elements are compared rather than adjacent ones, as in simple interchange sorts. This tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between the compared elements is gradually decreased to 1, at which point the sort becomes effectively an adjacent interchange method. This sample code is the second example in page 58 of the textbook. Shell open parenthesis v comma n close parenthesis int v open square bracket close square bracket comma n semicolon. Open curly brace int gap comma I comma j comma temp. For open paren gap equals n divided by 2 semicolon gap greater than 0 semicolon gap slash equals 2 close parenthesis. For open parenthesis I equals gap semicolon I less than n I plus close parenthesis. For, and now we're 3 deep nested in the for loops. For open parenthesis j equals I minus gap semicolon j greater than or equal to 0 and v sub j greater than v sub j plus gap semicolon j minus equals gap close parenthesis open curly brace temp equals v sub j. V sub j equals v sub j plus gap semicolon v sub j plus gap equals temp semicolon. Just a swap of v and v sub j plus gap, v sub j and v sub j plus gap. Close curly brace, and that close the innermost for loop, and then the next close curly brace closes the function. There are 3 nested loops. The outermost loop controls the gap between the compared elements, shrinking it from n over 2 by a factor of 2 each pass until it becomes 0. The middle loop compares each pair of elements that is separated by gap. The innermost loop reverses any elements that are out of order. Since gap is eventually reduced to 1, all elements are eventually ordered correctly. Note that the generality of the for makes the outer loop fit the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, which most often finds use in the for statement. A pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in a for statement, it is possible to place multiple expressions in the various parts. For example, to process 2 parallel indices. This is illustrated in the function reverse, which reverses the function string in place. This code is from page 59 of the textbook, and it is the first example on page 59. Pound include less than string.h greater than. Reverse open paren s close paren. Char s open square bracket close square bracket semicolon. Open curly brace. Int c comma I comma j. For open parenthesis I equals 0 comma j equals strlen sub s minus 1 semicolon. I less than j semicolon. I plus plus comma j minus minus close parenthesis open curly brace. C equals s sub I equals s sub j semicolon, s sub j equals c semicolon, close curly brace to end the function. The commas that separate the function arguments, variables, declarations, etc., are not comma operators and do not guarantee left to right evaluation. Section 3.6, loops, do while. The while and for loops share the desirable attribute of testing the termination condition at the top rather than at the bottom, as we discussed in Chapter 1. The third loop in C, the do while, tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax is as follows. Do statement while open parenthesis expression close parenthesis semicolon. The statement is executed, then the expression is evaluated. If it is true, statement is evaluated again, and so on. If the expression becomes false, the loop terminates. As might be expected, do while is much less used than while and for, accounting perhaps 5% of all loops. Nonetheless, it is from time to time valuable as in the following function I to A, which converts a number to a character string, the inverse of A to I. The job is slightly more complicated than it might be thought at first, because the easy methods of generating the digits generate them in the wrong order. We have chosen to generate the string backwards and then reverse it. This is the first sample code on page 60 of the textbook. I to A, open parenthesis, n comma s, close parenthesis. Char, s, open square bracket, close square bracket, semicolon. Int, n, semicolon. Open curly brace. Int, I, comma, sign, semicolon. If, open parenthesis, sign equals n, close parenthesis, less than 0, close parenthesis, n equals minus n semicolon. That's a bit of a complex if, I would say there. It has an assignment statement that both copies n into sign and then evaluates as to whether or not it's less than 0. The n or sign is less than 0 because it's a side effect assignment statement with a residual value. But the net result is sign contains n, and then it's negated, then n is made positive. So, continuing, I equals 0, semicolon. Do, open curly brace, s sub I plus plus equals n modulo 10 plus, quote, 0, quote, semicolon. Close curly brace, while, parenthesis, n slash equals 10, close parenthesis, greater than 0, close parenthesis, semicolon. If, open parenthesis, sign less than 0, close parenthesis, s sub I plus plus equals, quote, dash, quote, or minus sign, semicolon. S sub I equals, quote, slash 0, quote, semicolon, in a sense to terminate the string. And then we call the function reverse, open parenthesis, s, close parenthesis, semicolon, close curly brace. The do while is necessary, or at least convenient, since at least one character must be installed in the array s regardless of the value of n. We have also used braces around the single statement that makes up the body of the do while, even though they are unnecessary, so the hasty reader will not mistake the while part for the beginning of a while loop. I would note that it's important for any language to provide top-tested loops and bottom-tested loops. But don't feel bad if you write code for years and never feel like a bottom-tested loop is the right way to solve a problem you're facing. It is usually rare to write a loop that you insist will run once, regardless of its input data. Section 3.7, break. It is sometimes convenient to be able to control loop exits other than by testing at the top or the bottom. The break statement provides an early exit from a for, while, or do, just as it does from the switch statement. A break statement causes the innermost enclosing loop or switch to be exited immediately. The following program removes trailing blanks and tabs from the end of each line of input using a break to exit from a loop when the rightmost character is non-blank, non-tab is found. This example code is on page 61 of the textbook, and it is the first example on that page. Pound include less than stdio.h, pound define max line 1000, main open parenthesis, close parenthesis, open curly brace, int n semicolon, char line open bracket, max line, close bracket, semicolon. While, open paren, n equals get line, open paren, line, comma, max line, close paren, greater than 0, close paren, open curly brace. While, open parenthesis, minus minus n greater than or equal to 0, close parenthesis. If, open parenthesis, line sub n not equal quote space quote, and line sub n not equal quote backslash t quote, and line sub n not equal quote backslash n quote, close parenthesis, break. Line sub n plus 1 equals quote backslash 0 quote semicolon, printf double quote %s backslash n double quote comma line close parenthesis semicolon, close curly brace to end the while, and then close curly brace to end the main. GetLine returns the length of the line. The inner while loop starts at the last character of line. Recall that minus minus n decrements n before using the value and scans backward looking for the first character that is not a blank tab or new line. The loop is broken when 1 is found, or when n becomes negative, that is, when the entire line has been scanned. You should verify that this is the correct behavior, even when the line contains only whitespace characters. An alternative to break is to put the testing in the loop itself. While, open parenthesis, n equals getLine, open parenthesis, line comma max line, close parenthesis, greater than 0, close parenthesis, open curly brace. While, open paren, minus minus n greater than or equal to 0, and open paren, line sub n equal quote space quote, or line sub n equals quote backslash t quote, or line sub n equals quote backslash n quote close paren semicolon dot 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 close curly brace. This is inferior to the previous version because the test is harder to understand. Tests which require a mixture of and, or, not, and parentheses should generally be avoided. 3.8 Continue. The continue statement is related to break, but less often used. It causes the next iteration of the enclosing loop, for, while, or do, to begin. In the while and do, this means that the test part is executed immediately. In the for, control passes to the reinitialization step. By the way, continue applies only to loops, not to switch. A continue inside a switch statement inside of a loop causes the next loop iteration. As an example, this fragment processes only positive elements in the array A. Negative values are skipped. For, open paren, I equals 0, semicolon, I less than n, semicolon, I plus plus, close paren, open curly brace. If, open paren, A sub I less than 0, close paren, continue. This line skips the negative elements, and then the rest of the body of the loop, dot, 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 will run only for the positive elements of the loop, and the loop finishes with a closed curly brace. The continue statement is often used when part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. It's time for a bit of an aside. Now that we have seen the break and continue language structures in C that also have made it into C-like languages and learned about middle-tested loops, it is time to revisit the structured programming debate and the need for priming operations when a program must process all data until it finishes and still handle the there is no data at all situation. In the previous chapter, the authors somewhat skirted the issue by using a top-tested while loop and a side effect statement with residual value that was compared to EOF to decide when to exit the loop. Int C colon while open parenthesis C equals getchar open paren close parenthesis not equal EOF close parenthesis open curly brace process your data close curly brace. And just for fun, now that we do know about the for loop, let's rewrite this loop as a for loop to make sure we really understand how for loops work. Int C semicolon for open paren C equals getchar open paren close paren semicolon C not equal EOF semicolon C equals getchar open paren close paren curly brace process your data close curly brace for the for loop. Now you will almost never see a read all characters until EOF written this way because it is not the way K&R told us. K&R told us to use a while loop for this. But the for loop formulation is probably clearer to many than the while formulation, especially to a reader who is not familiar with the assignment side effect idiom commonly used in C. In particular, the for formulation does not require that the assignment statement has a residual value of the value that was assigned. The first part of the for is a priming read. The second part of the for is a top text tested exit criteria that works both for no data and after all data has been read and processed. And the third part of the for is done at the bottom of the loop to advance to the next character or encounter EOF before going back to the top and doing the loop test. The call to get char is done twice in the for formulation of the read all available data loop. And while we don't like to repeat ourselves in code, if it is a small and obvious bit of code, perhaps this code is more clear with a bit of repetition. So, with all this as background, you can take this page of the document and sit down with a friend at a coffee shop and debate as long as you like about which is the better formulation for the read all available data. But if at that coffee shop you ask Dr. Chuck's opinion, neither of these is ideal because in the real world, we build data-oriented loops that usually do a lot more than get one character from standard input. My formulation of a data loop will upset the structured programming purists and probably upset Kernighan and Ritchie as well. But I write code in the real world, so here is my version. Int C semicolon. While open paren 1 close paren open curly brace C equals get char. If open paren C double equals EOF close paren break. Process your data. And then close curly brace to end the loop. And if I wanted to skip blanks and new lines, I could use both break and continue, further angering the structured programming purists. Int C semicolon. While open parenthesis 1 close parenthesis open curly brace C equals get char open parenthesis close parenthesis semicolon. If open parenthesis C equal EOF close parenthesis break. If open parenthesis C equal quote space quote or C equal quote backslash end quote close parenthesis continue. Then process your data. Close parenthesis. I use this middle tested approach because usually the data I am processing is coming from a more complex source than the keyboard, and I don't want a function with 2 to 3 parameters stuck inside of a side effect statement in a while test. And also sometimes you want an exit loop not just based on the return value from the function, but instead based on the complex structure that came back from the function itself. As these data processing loops get more complex, the middle tested loop is a tried and true pattern. Even Kernighan and Ritchie point out its benefits above. And with that, I have now triggered endless coffee shop conversations about the best way to write a data handling loop. Section 3.9, Go-Tos and Labels. C provides the infinitely abusable go-to statement and labels to branch to. Formally, the go-to is never necessary, and in practice, it is almost always easy to write code without it. We have not used go-to in this book. Nevertheless, we will suggest a few situations where go-tos might find a place. The most common use is to abandon processing in some deeply nested structure, such as breaking out of 2 loops at once. The break statement cannot be used directly since it leaves only the most innermost loop. Thus, for open parenthesis, close parenthesis, for open parenthesis, close parenthesis, open curly brace, do some stuff. If open parenthesis, disaster, close parenthesis, go to error, semicolon, close curly brace, and then error, colon, and then clean up the mess. This organization is handy if the error handling code is non-trivial and if errors can occur in several places. A label has the same form as a variable name and is followed by a colon. It can be attached to any statement in the same function as the go-to. Another example, consider the possibility of finding the first negative element in a 2-dimensional array. Multi-dimensional arrays are discussed in Chapter 5. One possibility is for open parenthesis I equals 0 semicolon I less than n semicolon I plus plus close parenthesis For, open parenthesis, j equals 0, semicolon, j less than m, semicolon, j plus plus, close parenthesis. If, open parenthesis, v sub I sub j less than 0, close parenthesis, go to found. Otherwise, and then you handle, and you keep going. And then found colon include is where it comes to, jumps to. Code involving a goto can always be written without one, but though perhaps at the price of somewhat repeated tests or an extra variable. For example, the array search becomes found equals 0. For, open parenthesis, I equals 0, semicolon, I less than n, ampersand, ampersand, exclamation, found, semicolon, I plus plus. For, open parenthesis, j equals 0, semicolon, j less than m, ampersand, ampersand, exclamation, found, semicolon, j plus plus. Found equals v sub I sub j less than 0. If found, continue, else not found. Although we are not dogmatic about the matter, it does seem that go-to statements should be used sparingly, if at all. I would add, before we leave control flow, I need to say that I agree with structured programming experts as well as Kernighan and Ritchie in that the go-to is universally a bad idea. There are a lot of little details that make them a real problem. Things like how the stack works in function calls, and how code blocks happen, and patching the stack up correctly when a go-to happens in the middle of a deeply nested mess. You might be tempted to use a go-to when you want to exit multiple nested loops in a single statement. Break and continue only exit the innermost loop. The authors use this example above, but are quite lukewarm when describing it as the use of go-to. Usually, if your problem is that complex, putting things in a function and using return or adding a few if statements is a better choice. The Dr. Chuck middle-tested loop data processing solves this because the loop is always the innermost loop. Also, as new languages were built, the concept of exceptions became part of language design and was by far more elegant solution to a path of some deeply nested code that just needs to get out. So most of the time, you think that go-to might be a good idea, you should lean towards a throw-catch pattern to make your intention clear. It is one of the reasons why we prefer languages like Java or Python over C when writing general-purpose code. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.
Hello, and welcome to Chapter 3. I'm Charles Severance, and I'm your instructor. So here in Chapter 3, again, I want you to read the book. I'm just going to call your attention to a few of the unique things that might help you make more sense of the book. So we're going to talk about semicolon use, how it's started in C and is used across multiple languages, how else if is a little different across languages, the switch statement, a bit of motivation, why the switch statement is even in C, the comma, operator, separator, and then sort of this tendency towards excessive succinctness or brevity that is pretty common in C programming, right? It's like there's such a value in making things really, really short, and that makes it kind of different. So I love semicolon-based languages, and we have a whole bunch of semicolon-based languages that that we've learned and are going to learn. Certainly 1978, the C programming language with its non-syntactically important spacing. The key to C is that C, the semicolon, is a terminator, and every statement must be terminated by a semicolon. So we say x equals x plus 1 semicolon and x equals x divided by 2 semicolon, right? And that's the idea. The printf ends in a semicolon. So you may or may not know in Python you're allowed to have semicolons. They're pretty much optional. Like on the print open paren x close paren, that semicolon does not need to be there. But it is a separator, not a terminator. So you can think of the print open paren x close paren semicolon as one statement followed by a separator followed by an empty statement, which does nothing. But the interesting thing is you can put more than one line on one line. You can put more than one line of code by using a separator. So there I say x equals x plus 1 semicolon x equals x over 2 semicolon. I don't have to indent that. It's two lines in the same block of code, and that's legal. Most of the time people choose not to use semicolon. The other thing about that is that shell scripting, which is sort of the Linux automation, treats it as a separator. And so that sort of looks a bit like shell scripting to have multiple statements on the same line separated by semicolons. In Java, it tends to follow the C pattern where it's a terminator. I tend to like it as a terminator. I don't like the idea that you can leave it off the way JavaScript does. And so you see it's on 2 assignment statements and the system out println in Java. In PHP, PHP follows C very closely, and so it is a terminator there as well, and so I think that's natural. And the good news, if it's a separator, like in JavaScript in the next example, where it's separating it, and so in this case the x equals x divided by 2 does not need to be terminated because the closed curly brace is going to terminate that. And like even the console.log open paren close paren semicolon, that semicolon is optional. When I tend to write JavaScript, I tend to put semicolons everywhere. When I tend to write Python, I put semicolons nowhere. And then in PHP, C, and Java, I tend to, put semicolons everywhere. Even though sometimes there are things you can leave out. Another thing that is very, very subtle is the notion of else-if. So C predates Python, and C in this book shows else-if as 2 separate words, and there's an else keyword and an if keyword. And so you say else space if, and then you have the expression and another statement, else space if expression and another statement, and then else for the one where none of those expressions are true. And if you look at Python, it looks almost identical. It says if expression, then elif expression, elif expression, and else. The key is that elif is a separate language construct in Python. And I think it's actually really beautiful and elegant. And the key is that this else if, while it is, I can think of it in C as like indented incorrectly. So you can look at it as the very first if has an if and an else, and everything from the second if on down is really part of that else. And so if you look to the right, you see the curly braces with the indentation that's explicit. It's exactly the same thing, but what you're going to see is you can see that if you were going to truly correctly indent an if, else in C, you would indent it the way it's shown on the right side. And it's neither here nor there. It is very rare that you would see any C programmer, do all the indentation the technically right way. But I just want to call your attention to it, that it's different than elif. Elif is its own language element that is not a deeper and deeper nesting. If you were to nest it, you see on the right-hand side, you see I've got 3 closed curly braces, curly brace, curly brace, curly brace, and it's just, ugh. So the elif, I think, is a really elegant addition that Python has added. The switch statement. I think that the reason that the authors put the switch statement into C is there was a time where we would write code in assembly language using what we call a jump table, where we take sort of the take a number, maybe mask it so it's only from 0 through 16, and then look up a series of addresses and jump through a jump table. And the computed goto was the way in Fortran of expressing a jump table. But in Fortran, it was just a mess. You got these labels and columns 1 through 6, and the continue statement doesn't work like the continue in C and C-like languages. And you had to have these gotos to get out of the switch statement. If you think about it from an assembly language perspective, it's not that hard to build the computed goto with a little tiny jump table. And so I think to some degree, whether or not we have to use a jump table in modern C it's really, really rare where you have to use a jump table. We just would do a few repeating else ifs, and it's just fine. Back then, a few extra statements might have bothered something if you were going to do it a million times a minute or something. The switch statement is much prettier. You do have to put the break statements in there. You can kind of nest you have the stacked cases, and then there's a default case. So if at least I compare the C switch statement with the Fortran computed goto, I want to say that the C switch statement was pretty much a lot more elegant, a lot easier to use, a lot easier to understand. And because assembly language programmers of the time did think in terms of jump tables, if a high-level language didn't have a way to express a jump table in that language, then we would kind of think of it as missing. But frankly, in your programming, I'm not sure I've written a switch statement because Java has a switch statement too. I probably haven't written a switch statement in over 20 years and maybe more. So I like the fact that it improved on Fortran, but that doesn't mean that you should use it. The comma operator or comma separator, I like to think of it as like a light version of the semicolon. And most people almost never use it, and the only place we use it is when it is sort of idiomatic, where in a for statement, because we're already using semicolon to separate the start before the loop test, and then the loop increment per iteration, we're using semicolon for that. So if we want to do like 2 statements, we are going to I equals 0, j equals sterlen, s minus 1, with a comma in between to say do these 2 things before the loop starts. And then at the end you say I plus plus comma j minus minus. That says do these 2 things at the end of each loop. So I only see it in idiomatic situations. Just think of it as like we couldn't use a semicolon here. It functions exactly like a semicolon, although the syntax already has a semicolon in it. So I think it's actually a pretty clever way to say, I want to put 2 statements in here. Maybe you could put curly braces in there or something, but I thought the comma was a pretty cool thing. Another problem is that there was just this notion that we as assembly language programmers, we could do things like be smart and leave some value in a register and then check the register a couple of different ways, and that would lead to really succinct, fast code, hand-tuned code where you might have to look at it to figure out what it's doing, but then you realize, well, I did that in 6 statements rather than 12 statements. 12 statements might have made more sense, but the 6 statements were really fast. And in the early days, in the early 70s, they were changing their compilers so fast and changing their hardware so fast that they really didn't build super great optimizing compilers. So they would look at the source code that came out of the compiler and like, I could do better than that. So there was a lot of a kind of comparison of the source code between what the C compiler would generate and whatever. And so they found over time that if they would kind of use these tricks that like told the compiler to like take this C equals get char and leave the C in a register and compare it to a space, and then compare it again to a new line and compare it again to a tab, we would think, oh, I can see how that would run in assembly language, and I can hope that the compiler would generate the assembly language that would make me happy. And then another pattern you see in this is the number 4 thing, where all the work's been done in the loop test. This is a while loop. That whole big expression is just the test to know when it's done, but it's actually reading the data, comparing it 3 times, storing it in a variable, and when that's all done, there's nothing to do in the loop, and so that's why you say close paren, semicolon. And you'll see a lot of those things, especially when you're doing string stuff where you're sort of zooming through an array and you did it all in the for loop and you don't really have anything to do in the for loop. And again, we're thinking in the early days of how this is going to translate into assembly language, and so you're trying to make that loop really, really small. And again, it's amazing how often they looked at the resulting assembly language in a non-optimizing compiler situation and then wondered if the compiler could have done better. So that gets us going in this chapter. We talked about the semicolon, we talked about the switch statement, the else-if subtle syntax difference between Python and C, the comma, and just get used to the notion that it's obtuse code. Please don't write obtuse code. These days the optimizers are so great. And so don't write obtuse code, but don't be too upset as you read the textbook and see obtuse code.
Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective.
Chapter 4, Functions in Program Structure. Functions break large computing tasks into smaller ones and enable people to build on what others have done instead of starting over from scratch. Appropriate functions can often hide details of operation from parts of the program that don't need to know about them, thus clarifying the whole and easing the pain of making changes. C has been designed to make functions efficient and easy to use. C programs generally consist of numerous small functions rather than a few big ones. A program may reside on one or more source files in any convenient way. The source files may be compiled separately and loaded together, along with previously compiled functions from libraries. We will not go into that process here, since the details vary according to the local system. Most programmers are familiar with library functions for input and output like getChar and putChar, and numerical computations like sine, cosine, and square root. In this chapter, we will show more about writing new functions. 4.1 Basics. To begin, let us design and write a program to print each line of input that contains a particular pattern or string of characters. This is a special function of the Unix utility program grep. For example, searching for the pattern the in the set of lines, now is the time for all good men to come to the aid of their party, will produce the output, now is the time men to come to the aid of their party. The basic structure of the task falls neatly into three pieces. While there's another line, if that line contains a pattern, print it. Although it's certainly possible to put the code for all of this in one main routine, a better way is to use the natural structure to advantage by making each part a separate function. Three small pieces are easier to deal with than the one big one, because irrelevant details can be buried in the functions, and the chance of unwanted interactions minimized. And the pieces might even be useful later in their own right. While there is another line is getLine, a function we wrote in Chapter 1. And printit is printf, which someone has already provided for us. This means that we need to only write a routine which decides if the line contains an occurrence of the pattern. We can solve that problem by stealing a design from PL1. The function index s, t returns the position or index in the string s where the string t begins, or -1 if s doesn't contain t. We use 0 rather than 1 as the starting position in S because C arrays always begin at position 0. When we later need more sophisticated pattern matching, we only have to replace index. The rest of the code can remain the same. Recall that because the modern stdout.h defines a getLine function, whenever the book writes this function to teach a feature of functions, we rename it to get_line. Given this much design, filling in the details of the program is straightforward. Here's the whole thing, so you can see how the pieces fit together. For now, the pattern to be searched for is a literal string in the argument of index, which is not the most general of mechanisms. We will return shortly to a discussion of how to initialize character arrays, and in Chapter 5, we will show how to make the pattern a parameter that is set when the program is run. This is also a new version of getLine. You might find it instructive to compare it to the one in Chapter 1. Pound include stdio.h. Pound define max line 1000. Main, open parenthesis, close parenthesis, open curly brace. Char line, open square bracket, max line, close square bracket, semicolon. While, parenthesis, get line, open parenthesis, line, comma, max line, close parenthesis, greater than 0, close parenthesis. If, open parenthesis, index, open parenthesis, line, comma, double quote, the, double quote, close parenthesis, greater than or equal to 0, close parenthesis, printf, open parenthesis, double quote, %s, double quote, comma, line, close parenthesis, semicolon, and a closed curly brace to finish the main function. Next function is getLine. GetLine, open parenthesis, s, comma, lim, close parenthesis. Char s, open square bracket, close square bracket, semicolon. Int, lim, semicolon. Open curly brace. Int, c, comma, I, semicolon. For I equals 0, semicolon, I less than lim minus 1, and paren c equals get char, open paren, close paren, not equal EOF, double ampersand, c not equal, double quote, backslash n, double quote, semicolon, plus I, close parenthesis, s sub I equals c. That loop basically read until it found a new line or end of file. If, open parenthesis, c double equals, quote, backslash n, quote, close parenthesis, open curly brace, s sub I equals c, plus I, semicolon, close curly brace, closing the if. S sub I equals, quote, backslash 0, quote, semicolon, to terminate the string properly. Return, open paren, I, close paren, semicolon, to return the length of the line, and then close curly brace to finish the getLine function. And now the new code. Index, open parenthesis, s, comma, t, close parenthesis. Char, s, open square bracket, close square bracket, comma, t, open square bracket, close square bracket, semicolon. I would note that when we are declaring a character array and we don't give the length of the array, that means that we're inside of a function. The length of the array exists, but it was from the calling code. So char s, open square bracket, close square bracket, t, open square bracket, close square bracket, semicolon means parameters s and t are strings of some length, and we will use backslash 0 to know when that length is done. Beginning the code in index with an open curly brace. Int I, comma, j, comma, k, semicolon. And then we have two nested for loops. For open paren I equals 0, s sub I not equal to, quote, backslash 0, quote, semicolon, I plus plus. Open curly brace. For j equals I, comma, k equals 0, semicolon, t sub k not equal to backslash 0, and, double ampersand, s sub j double equals t sub k, semicolon, j plus plus, k plus plus, semicolon. If, open paren, t sub k double equals, quote, backslash 0, quote, close paren, return, open paren, I, close paren, semicolon, close curly brace, return, open paren minus 1, close paren, semicolon, curly brace. Each function has the form, name, argument list, if any, in parentheses, argument declarations, if any, open curly brace, declarations and statements, if any, close curly brace. As suggested, various parts may be absent. A minimal function is dummy, open paren, close paren, open curly brace, close curly brace, which does nothing. A do-nothing function is sometimes useful as a placeholder during program development. The function name may also be preceded by a type if the function returns something other than an integer value. This is the topic of the next section.
A program is just a set of individual function definitions. Communication between the functions is, in this case, by arguments and values returned by the functions. It can also be via external variables. The functions can occur in any order in the source file, and the source program can be split into multiple files, so long as no function is split. The return statement is the mechanism for returning a residual value from the called function to its caller. Any expression can follow return. Return, open parenthesis, expression, close parenthesis. The calling function is free to ignore the return value if it wishes. Furthermore, there is no need to have an expression after the return. In that case, no value is returned to the caller. Control also returns to the caller with no value when execution falls off the end of the function by reaching the right closing brace. It is not illegal, but probably a sign of trouble if a function returns a value from one place and no value from another place. In any case, the residual value of a function which does not return one is certain to be garbage. The C verifier lint checks for such errors. The mechanics of how to compile and load a C program which resides on multiple source files vary from one system to the next. On the Unix system, for example, the cc command mentioned in Chapter 1 does the job. Suppose that three functions are in three files called main.c, getLine.c, and index.c. Then the command cc main.c, getLine.c, index.c compiles the three files and places the resulting relocatable object code in files main.o, getLine.o, and index.o, and loads them all into an executable file named a.out. If there is an error, say in main.c, that file can be recompiled by itself and the result loaded with the previous object files with the command cc main.c, getLine.o, index.o. The cc command uses the .c suffix versus the .o suffix naming convention to distinguish source files from object files. I would note that this cc example, exactly as the authors wrote it, does not quite work as described in modern C compilers. If you want to compile your source code and leave the compiled object code around after the compile, you add the -c option to the compiler call. Modern C compilers generally do accept multiple files with either .c or .o suffixes and combine them into a runnable application. Section 4.2, Functions returning non-integers. So far, none of our programs has contained any declaration of the type of a function. This is because, by default, a function is implicitly declared by its appearance in an expression or statement, such as while, open paren, get line, open paren, line, comma, max line, close paren, greater than 0, close paren. If a name which has not been previously declared occurs in an expression and is followed by a left parentheses, it is declared by context to be a function name. Furthermore, by default, the function is assumed to return an int. Since char promotes to int in expressions, there is no need to declare functions that return char. These assumptions cover the majority of classes, including all of our examples so far. I would add, that's not quite true anymore. In modern C languages, you are required to provide a type for each function. If you leave off the type for a function declaration, at a minimum, you will get a stern warning message. But sometimes functions do not intend to return anything at all, and so the void type was invented to indicate that a function returns nothing. The rule of requiring a type on a modern function definition in C, even if it's void, allows the compiler to check to make sure all of your return values in a function match the expected return type. Back to the text. But what happens if a function must return some other type? Many numerical functions like square root, sine, and cosine return double. Other specialized functions return other types. To illustrate how to deal with this, let us write and use the function a to f, which converts its argument string s to its double precision floating point equivalent. A to f is an extension of a to I, which we wrote versions of in chapters 2 and 3. It handles an optional sign and decimal point and the presence or absence of either the integer or fractional part. We would note that this is not a high-quality input conversion routine. Doing everything takes a bit more space than we care to use here in this book. First,
A to F must declare the type of the value it returns since it's not int. Because float is converted to double in expressions, there is no point in saying that A to F returns float. We might as well make use of the extra precision and thus declare it to return double. The type name precedes the function name, like this. Double, A to F, open parenthesis, S, close parenthesis. Char, S, open square bracket, close square bracket, open curly brace. Double, val, comma, power, int, I, comma, sign, semicolon. For, I equals 0, semicolon, S sub I, double equals, quote, space, quote, or S sub I, double equals, quote, backslash n, quote, or S sub I, double equals, quote, backslash t, quote, semicolon, I plus plus, semicolon. That skips the white space. Sign equals 1. If S sub I double equals quote plus quote, or S sub I double equals quote minus quote, sign equals, and now we're going to use a ternary operator here, paren S sub I plus plus, close bracket, double equals quote plus quote, close paren, question mark, 1, colon, minus 1, semicolon. And that basically tells us it makes sign be 1 or negative 1 based on the presence or absence of a plus or minus. For val equals 0, semicolon, S sub I greater than or equal to quote 0, quote, double ampersand, S sub I less than or equal to double quote 9, quote, I plus plus, close paren. Val equals 10 times val plus S sub I minus quote 0, quote, semicolon. What this is doing is multiplying the current value by 10, in effect shifting it left, and then adding in that new lower empty spot the digit that we're encountering, which is somewhere between the character 0 and the character 9. Continuing, if parenthesis S sub I double equals quote dot quote, close parenthesis, I plus plus. For open parenthesis power equals 1, semicolon, S sub I greater than or equal to quote 0, quote, double ampersand, S sub I less than or equal to quote 9, quote, semicolon, I plus plus, open curly brace, val equals 10 times val plus S sub I minus quote 0, quote. Again, shifting the number to the left as we encounter characters. Power star equals 10, semicolon, close curly brace. Return, open parenthesis, sign times val over power, close parenthesis, semicolon, close curly brace. Second, and just as important, the calling routine must state that A to F returns a non-int value. The declaration is shown in the following primitive desk calculator, barely adequate for checkbook balancing, which reads one number per line, optionally preceded by sign, and adds them all up, printing the sum after each input. This example is from page 70 of the textbook. Pound include stdio.h. Pound define max line 100. Main, open parenthesis, close parenthesis. Open curly brace. Double, sum, comma, A to F, open parenthesis, close parenthesis, semicolon. Char, line, open square bracket, max line, close square bracket, semicolon. Sum equals 0. While, open parenthesis, get line, open parenthesis, line, comma, max line, close parenthesis, greater than 0, close parenthesis, print f, quote, backslash t, percent dot to f backslash n, comma, sum plus equals A to F, open parenthesis, line, close parenthesis, semicolon, close curly brace. That code used the plus equals side effect operator and merged the call to A to F right into the parameter of the second parameter of printf. The declaration double sum A to F open parenthesis close parenthesis says that sum is a double variable and that A to F is a function that returns a double value. As a mnemonic, it suggests that sum and A to F parenthesis dot 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 are both double precision floating point values. Unless A to F is explicitly declared in both places, C assumes it returns an integer and you will get nonsense answers. If A to F itself and the call to it in main aren't typed inconsistently in the same source file, it will be detected by the compiler. But if, as is more likely, A to F were compiled separately, the mismatch would not be detected, and A to F would return a double, which main would treat as an int, and meaningless answers would result. lint catches this error. Given A to F, we could, in principle, write A to I to convert a string to an integer in terms of it. Int A to I, open parenthesis, S, close parenthesis, char, S, open square bracket, close square bracket, semicolon, open curly brace, double, A to F, open parenthesis, close parenthesis, semicolon. Return, open parenthesis, A to F, close parenthesis, S, close parenthesis, semicolon, close curly brace. Note the structure of the declarations in the return statement. The value in the expression in return expression is always converted to the type of the function before the return is taken. Therefore, the value of A to F, a double, is converted automatically to int when it appears in a return, since the function A to I returns an int. The conversion of a floating point value to int truncates any fractional part, as we discussed in Chapter 2. More on function arguments. In Chapter 1, we discussed the fact that function arguments are passed by value. That is, the called function receives a private, temporary copy of each argument, not its address. This means that the function cannot affect the original argument in the calling function. Within a function, each argument is in effect a local variable initialized to the value with which the function was called. When an array name appears as an argument to a function, the location of the beginning of the array is passed. Elements are not copied. The function can alter elements of the array by subscripting from this location. The effect is that arrays are always passed by reference. In Chapter 5, we will discuss the use of pointers to permit functions to affect non-arrays in calling functions. A bit of a digression. Since including array as an argument passes the location or memory address of the array into the function can change the items in the array using array subscripts. In particular, the array contents are not copied when an array is passed into a C function. When we get to structs in a future chapter, we will find that the content of structs also are passed using the address of the entire struct, so structs are passed by reference as well. When thinking about pass by reference or pass by value, remember that a char variable is a single item similar to int and passed by value, i.e. it is copied. In C, strings are arrays of characters, so they are passed by reference. Python follows this design for the same efficiency reason as C. Normal single variables like int or float are copied before being passed into a function and therefore passed by value. Collections like list or dict are passed into functions by reference, so the contents can be changed within a function. Python strings are not technically copied when being passed into a function, but the way assignments happen in Python make it seem like strings are passed by value, since they can never be modified. You can learn more with a bit of web research, but the easy way is to imagine in Python that strings are passed by value with a clever trick to avoid requiring a copy for every function call. PHP follows the same pattern of passing numbers and strings by value and passing arrays as reference. PHP passes strings by value without requiring a copy, again using clever runtime code. Because in Java, JavaScript, and PHP, strings are objects, of course, which we haven't discussed much yet. Those languages can make sure that strings act as if they were passed by value and not passed by reference the way they are always passed in C. C made decisions on its runtime based on getting the maximum performance out of the hardware of the 1970s at the expense of making it too easy to write code that overwrites memory and leads to corrupted programs that have dangerous and undefined behavior. Languages like PHP, Java, and JavaScript add a small amount of runtime overhead to do things like store the length of an array and make sure we programmers don't over-reference the array and overwrite random bits of our program's code or data. The creators of C placed more priority on speed and efficient use of memory than safety. It is like driving an automobile in the rain without ABS, automatic braking system. It is fast but dangerous and should be reserved by highly skilled and very careful programmers and drivers, and those drivers should probably be on a race course. By the way, back to the text. By the way, there is no entirely satisfactory way to write a portable function that accepts a variable number of arguments, because there is no portable way for the called function to determine how many arguments were actually passed in a given call. Thus, you can't write a truly portable function that will compute the maximum of an arbitrary number of arguments, as will the max functions that are built into Fortran and PL1. It is generally safe to deal with a variable number of arguments if the called function doesn't use an argument that was not actually supplied, and if the types are consistent. Printf, the most common C function with a variable number of arguments, uses information from the first argument, which is the formatting string, to determine how many other arguments are present and what their types are. It fails badly if the caller does not supply enough arguments or if types are not what the first argument says. It is also non-portable and therefore must be modified for different programming environments. Alternatively, if arguments are of known types, it is possible to mark the end of the argument list in some agreed-upon way, such as a special argument value, often 0, that stands for the end of the arguments. Interestingly, modern languages like Python, PHP, and Java go to great lengths to make variable length argument lists work predictably and portably. The syntax for variable length argument lists in these languages can be a bit obtuse at times, but at least it's allowed, documented, reliable, and portable. Section 4. External variables. A C program consists of a set of external objects which are either variables or functions. The adjective external is used primarily in contrast to internal, which describes arguments and automatic variables defined inside functions. External variables are defined outside any function and are thus potentially available to many functions. Functions themselves are always external, because C does not allow functions to be defined inside other functions. By default, external variables are also global, so that all references to such a variable by the same name, even from functions that are compiled separately, are references to the same thing. In this sense, external variables are analogous to Fortran Common or PL1 external. We will later see how to define external variables in functions that are not globally available, but instead only visible within a single source file. Because external variables are globally accessible, they provide an alternative to function arguments and return values for communicating data between functions. Any function may access an external variable by referring it to by name, if the name has been declared somehow. If a large number of variables must be shared among functions, external variables are more convenient and efficient than long argument lists. As pointed out in Chapter 1, however, this reasoning should be applied with some caution, for it can have a bad effect on program structure and lead to programs with many data connections between functions. A second reason for using external variables concerns initialization. In particular, external arrays may be initialized, but automatic, i.e. internal arrays, may not. We will treat initialization near the end of this chapter. The third reason for using external variables is their scope and lifetime. Automatic variables are internal to a function. They come into existence when the routine is entered and disappear when it's left. External variables, on the other hand, are permanent. They do not come and go, so they retain values from one function invocation to the next. Thus, if two functions must share some data, yet neither calls the other, it is often most convenient if the shared data is kept in external variables rather than passed in and out via arguments. Let's examine this issue further with a larger example. The problem is to write another calculator program better than the previous one. This one permits plus, minus, asterisk, and slash, and equals. Equals will print our answer. Because it is somewhat easier to implement, the calculator will use reverse Polish notation instead of infix notation. Reverse Polish notation is the scheme used by, for example, Hewlett-Packard Pocket calculators. In reverse Polish notation, each operator follows its operands. An infix expression like open parenthesis 1 minus 2, close parenthesis C star, open parenthesis 4 plus 5, close parenthesis equals, is entered as 1, 2 minus 4, 5 plus star equals. Parentheses are not needed in reverse Polish notation. The implementation is quite simple. Each operand is pushed onto a stack. When an operator arrives, the proper number of operands, 2 for binary operators, are popped, the operator applied to them, and the result is pushed back onto the stack. In the example above, 1 and 2 are pushed, then replaced by their difference, -1. Next, 4 and 5 are pushed, then replaced by their sum, 9. And then the product of -1 and 9, which is -9, replaces them on the stack, and then the equal sign operator prints the top element without removing it. So intermediate steps in a calculation can be checked. The operations of pushing and popping a stack are trivial, but by the time error detection and recovery are added, they're long enough so it's better to put each in a separate function than to repeat the code throughout the whole program. And there should be a separate function for fetching the next input operator or operand. Thus, the overall structure of the program is while next operator or operand is not end of file. If it's a number, push it. Else, if it's an operator, pop operands, do the operation, and push the result. Else, error. The main design decision that has not yet been discussed is where the stack is. That is, what routines access it directly. One possibility is to keep it in main and pass the stack and current stack position to the routines that push and pop it. But main doesn't need to know about the variables that control the stack. It should only think about pushing and popping. So we have decided to make the stack and its associated information external variables accessible to push and pop, but not to main. Translating this outline to code is easy enough. The main program is primarily a big switch on the type of operator or operand. This is a more typical use of switch than the one shown in Chapter 3. This sample code is from page 74 of the textbook. Pound include stdio.h. Pound define maxop 20. Pound define number, quote 0, quote. This is going to be a signal we found a number. And pound define too big, quote 9, quote. A signal that the string is too big. Main, open parenthesis, close parenthesis, open curly brace. Int, type, semicolon. Char, s, open square bracket, maxop, close square bracket, semicolon. Double, op2, a to f, open parenthesis, close parenthesis, comma, pop, open parenthesis, close parenthesis, comma, push, open parenthesis, close parenthesis, semicolon. While, open parenthesis, type equals getUp, open parenthesis, s, comma, maxop, close parenthesis, not equal EOF, close parenthesis. Switch, open parenthesis, type, close parenthesis, open curly brace. Case, number, colon. Note that number is a predefined constant above. Push, open parenthesis, A to F, open parenthesis, S, close parenthesis, semicolon, break. Case, quote plus quote, colon, push, open parenthesis, pop, open paren, close paren, plus pop, open paren, close paren, semicolon, break, semicolon. Case, quote, asterisk, quote, colon, push, open paren, pop, open paren, close paren, asterisk, pop, open paren, close paren, semicolon, break, semicolon. That was the multiplication. Case, quote, minus quote, colon. Op2 equals pop, open paren, close paren, push, open paren, pop, minus op2, close paren, semicolon, break, semicolon. That was subtraction. Case, open paren slash close paren, colon, op2 equals pop, open paren, semicolon. If op2 not equals 0.0, push, open paren, pop, open paren, close paren, slash op2, close paren, semicolon. Else, printf, double quote, 0 divisor popped, \n, double quote, close paren, semicolon, break. Case, quote, equal, quote, colon, printf, open paren, double quote, \t, %f, \n, double quote, comma, push, open paren, pop, open paren, close paren, semicolon. So to print it, we pop it and push it, and then print the residual value of the push function. The next line is break, semicolon. Case, quote, C, quote, colon, clear, open paren, close paren, semicolon, break, semicolon. Case, too big, colon, printf, double quote, %.20s, space, is too long, \n, double quote, comma, s, close paren, semicolon, break, semicolon. Default, colon, printf, open paren, double quote, unknown command, %c, \n, double quote, comma, type, open paren, close paren, semicolon, break, semicolon, close curly brace to finish the switch statement, and then close curly brace to finish the main. So now we're going to have a separate file that has some of these functions defined. This file is on page 75 of the textbook. This file will be compiled separately, but then later linked all together with the main program. But we're going to define push, pop, and clear in this file. Pound include stdio.h. Pound define maxval 100. Maximum value, that would be the maximum value of our stack, the maximum size of our stack, maximum depth of our stack. Now we are declaring variables outside of any function. These are the external variables. Int sp equals 0, double val, open square bracket, max val, close square bracket, semicolon. And so those variables are external variables, and they're outside of all of the functions, but we can use them in any function, and there's just one copy no matter what function we're using it. So now we define our functions. Double push, open paren f, close paren, double f, semicolon, open curly brace. If, open paren, sp, less than max val, close paren, return, open paren, val, open square bracket, sp++, close square bracket, equals f, close paren, semicolon. Else, open curly brace, printf, double quote, air, colon, stack, full, \n, double quote, close paren, semicolon. Clear, open paren, close paren, semicolon. Return, open paren, 0, close paren, semicolon. Close curly brace to finish the else, and then close curly brace to finish the double function, the push function. And now we define the pop. Double pop, open paren, close paren, open curly brace. If, open paren, sp greater than 0, close paren, return, open paren, val, open square bracket, minus sp, close square bracket, close curly brace, semicolon. Else, open curly brace, printf, open paren, double quote, air, colon, stack, empty, \n, close quote, close double quote, close paren, semicolon. Clear, open paren, close paren, semicolon. Return, open paren, 0, close paren, semicolon. Close curly brace to finish the else, and then close curly brace to finish the double. And the last function we're going to define is the clear function, which is quite simple. Clear, open paren, close paren, open curly brace, sp equals 0, semicolon, close paren. I would note that just read this one carefully. They're very good at using side effect operators and side effect assignments, and to keep this code very simple and succinct. And you really have to understand a lot of the other stuff that you've covered in the book up to this point. Back to the text. The command C clears the stack with the function clear, which can also be used by push and pop in case of error. We'll return to getOp in a moment. As discussed in Chapter 1, a variable is external if it is defined outside the body of any function. Thus, the stack and stack pointer, which must be shared by push, pop, and clear, are defined outside the three functions. But if main itself does not refer to the stack or stack pointer,
their representation is carefully hidden. Thus, the code for the equal operator must use push, open paren, pop, parenthesis, close parenthesis, semicolon, to examine the top of the stack without disturbing it. Notice also that because plus and multiplication are commutative operators, the order in which the popped operands are combined is irrelevant, but for the minus and slash operators, the left and right operands must be distinguished. This example code above shows why it's important to remember the K&R C rearrangement license as it applies to operators that are associative and commutative. If the code for the minus operator were written push, open paren, pop, open paren, close paren, minus pop, open paren, close paren, semicolon, there is no guarantee that the left pop will run before the right pop. And since these functions access global variables and have side effects, it is important to force the compiler not to rearrange the order of the function calls. To force the evaluation order, the code is broken into two statements. Op2 equals pop, open paren, close paren, semicolon. Push, open paren, pop, open paren, close paren, minus op2, close paren, semicolon. Now you might think that the lesson here is that the K&R C arrangement license, which was done to allow optimization and performance, is a bad idea. But the more important lesson is that writing low-level utility functions like push and pop that use global variables and have side effects is a dangerous pattern in any programming language. Section 4.5, Scope Rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. The two questions of interest are, how are declarations written so that variables are properly declared during compilation, and how are declarations set up so that all the pieces will be properly linked or connected when the program is loaded? The scope of a name is the part of the program over which the name is defined. For an automatic variable declared at the beginning of a function, the scope is the function in which the name is declared, and variables of the same name in different functions are unrelated. The same is true of the arguments of the function. The scope of an external variable lasts from the point at which it is declared in a source file to the end of that file. For example, if val, sp, push, pop, and clear are defined in one file in the order shown above, that is, int sp equals 0, double val, open square bracket, max val, close square bracket, semicolon, double push, open paren, f, close paren, open curly brace, close curly brace, double pop, open paren, close paren, open curly brace, close curly brace, clear, open paren, open curly brace, close curly brace. Then the variables val and sp may be used in push, pop, and clear simply by naming them, and no further declarations are needed. On the other hand, if an external variable is to be referenced before it is defined, or it is defined in a different source file from the one in which it's being used, then an extern declaration is mandatory. It is very important to distinguish between the declaration of an external variable and its definition. A declaration announces the property of the variable, its type, its size, etc. A definition also causes storage to be allocated. If the lines int sp semicolon, double val, open square bracket, max val, close square bracket, semicolon, appear outside any function, they define the external variables sp and val and cause the storage to be allocated, and also serve as the declaration for the rest of that source file. On the other hand, the lines extern int sp, extern double val, open square bracket, close square bracket, semicolon, declare for the rest of the source file that sp is an int and val is a double array, whose size is determined and allocated elsewhere, but they do not create variables or allocate storage for them. There must be only one definition of an external variable among all the files that make up the source program. Other files may contain extern declarations to access it. There may also be an extern declaration in the file containing the definition. Any initialization of an external variable goes only with the definition.
Array sizes must be specified with the definition, but are optional with the extern declaration. Although it is not a likely organization for this program, val and sp could be defined and initialized in one file, and the functions push, pop, and clear defined in another. Then these definitions and declarations would be necessary to tie them together. In file 1, we would see int sp equals 0 semicolon, double val, open square bracket, max val, close square bracket, semicolon, and then in file 2, extern int sp semicolon, extern double val, open square bracket, close square bracket, semicolon, double push, open paren, f, close paren, open curly brace, dot, 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 close curly brace, double pop, open paren, close paren, open curly brace, dot, 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 close curly brace, clear, open paren, close paren, open curly brace, dot, 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 close curly brace. Because the extern declarations in file 2 lie ahead and outside the three functions, they apply to all. One set of declarations suffices for all of file 2. For larger programs, the #include file inclusion facility discussed later in this chapter allows one to keep only a single copy of the extern declarations for the program and have that inserted in each source file as it's being compiled. Let us now turn to the implementation of getup, the function that fetches the next operator or operand. The basic task is easy. Skip blanks, tabs, and new lines. If the character is not a digit or a decimal point, return it. Otherwise, collect a string of digits that might include a decimal point and return number, a single signal that a number has been collected. The routine is substantially complicated by an attempt to handle the situation properly when the input number is too long. Getup reads digits, perhaps with an intervening decimal point, until it doesn't see anymore, but only stores the ones that fit. If there was no overflow, it returns number in the string of digits. If the number was too long, however, getup discards the rest of the input line, so the user can simply retype the line from the point of error. It returns too big as the overflow signal. This example code is from page 78 of the textbook, and you can view it at www.cc4e.com/code, page 78. Getup, open paren s comma lim, close paren, char s open square bracket, close square bracket, semicolon, int lim semicolon, open curly brace, int I comma c semicolon, while open paren c equals get ch, open paren, close paren, double equals quote space quote, or c double equals quote backslash t quote, or c double equals quote backslash n quote, close paren, semicolon. Skip all the blanks. If c is not equal quote dot quote and open paren c less than quote 0 quote, vertical bar, c greater than quote 9 quote, close paren, return open paren c, close paren. S sub 0 equals c. For paren I equals 1 semicolon, open paren c equals get chart, open paren, close paren, greater than or equal to quote 0 quote, and c less than or equal to quote 9 quote, semicolon, I plus plus, inside the for loop. If I less than lim, s sub I equals c. If open paren c double equals quote dot quote, close paren, open curly brace, we begin to collect the fraction. If open paren I less than lim, close paren, s sub I equals c. For open paren I plus plus, c equals get char, open paren, close paren, greater than or equal to quote 0 quote, ampersand, c less than or equal to quote 9 quote, semicolon, I plus plus, close paren. If open paren I less than lim, close paren, s sub I equals c. Close curly brace to close the if statement where we're collecting the fraction. If, open paren, I less than lim, close paren, open curly brace, this means the number is good. Unget ch, open paren c, close paren, semicolon. S sub I equals quote backslash 0 quote, semicolon. Return, open paren number, close paren. And recall that number is a predefined constant. Close curly brace, else open curly brace. If it's too big, we're going to skip to the end of the line. While open paren c not equal quote backslash n quote and c not equal EOF, open paren c equals get char, open paren close paren semicolon, s sub lim minus 1 equals quote backslash 0 quote semicolon. Return too big, semicolon. Close curly brace to finish the if, and then close curly brace to finish the function. Recall that too big is a constant that indicates that we've read too much. Back to the text. What are get ch and unget ch? Well, it is often the case that a programming reading input cannot determine that it is read enough until it is read too much. One instance is collecting characters that make up a number. Until the first non-digit is seen, the number is not complete. But then the program has read one character too far, and that is a character it is not prepared for. The problem would be solved if it were possible to unread the unwanted character. Then every time the program reads one character too many, it could push it back on the input so that the rest of the code would behave as if it never been read. Fortunately, it is easy to simulate ungetting a character by writing a pair of cooperating functions. Get.ch delivers the next input character to be considered. Unget.ch puts the character back on the input, so the next call to get.ch will return it again. How they work together is simple. Unget.ch puts the pushed back characters into a shared buffer, a character array. Get.ch reads from the buffer as there's anything there, and then it calls get.char if the buffer is empty. There must be an index variable which records the position of the current character in the buffer. Since the buffer and index are shared by get.ch and unget.ch and must retain their values between calls, they must be external to both routines. Thus, we can write get.ch and unget.ch and their shared variables as follows. This is on page 79 of the textbook. You can see the code at www.cc4e.com/code and go to page 79. Pound include stdio.h. Pound define buff size 100. Char buff open square bracket buff size close square bracket semicolon. Int buff p equals 0 semicolon. Those are the external variables outside any function. Here's the first function. Get.ch open paren close paren open curly brace return open parenthesis buff p greater than 0 close parenthesis question mark buff open square bracket minus buff p close square bracket colon get char open paren close paren semicolon. Close curly brace to finish the get.ch function. The unget.ch function pushes a character back on input. Unget.ch open paren c close paren int c semicolon open curly brace. If open paren buff p greater than buff size printf open paren double quote unget.ch colon too many characters backslash n double quote close paren semicolon. Else buff open square bracket buff p plus plus close square bracket equals c semicolon, and then close curly brace to finish the unget.ch function. We have used an array for pushback rather than a single character, since the generality may come in handy later. Section 4.6, Static Variables. Static variables are a third class of storage, in addition to the extern and automatic that we've already met. Static variables may either be internal or external. Internal static variables are local to a particular function, just like automatic variables are, but unlike automatics, they remain in existence rather than coming and going each time the function is activated. This means that internal static variables provide private, permanent storage in a function. Character strings that appear within a function, such as the arguments of printf, are internal static. An external static variable is known within the remainder of the source file in which it's declared, but not in any other file. External static thus provides a way to hide names like buff and buff-p in the getch, ungetch combination, which must be external so they can be shared, yet which should not be visible to users of getch and ungetch, so there's no possibility of conflict. If the two routines are compiled in one file, as in static char buff, open square bracket buff size, close square bracket semicolon, static int buff p equals 0 semicolon, getch open paren close paren, open curly brace dot 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 close curly brace, ungetch open paren c close paren, open curly brace dot 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 close curly brace, then no other routine will be able to access buff and buff p. In fact, they will not conflict with the same names in other files of the same program. Static storage, whether internal or external, is specified by prefixing the normal declaration with the word static. The variable is external if it's defined outside of any function, and internal if defined inside a function. Normally, functions are external objects. Their names are known globally. It is possible for a function, however, to be declared static. This makes its name unknown outside the file in which it's declared. In C, static connotates not only permanence, but also a degree of what might be called privacy. Internal static objects are known only inside one function. External static objects, variables, or function are known only within the source file in which they appear. Their names do not interfere with variables or functions of the same name in other files. External static variables and functions provide a way to conceal data objects and any internal routines that manipulate them so that other routines and data cannot conflict, even inadvertently. For example, getch and ungetch form a module for character input and pushback. Buff and buff-p should be static, so they are inaccessible from the outside. In the same way, push, pop, and clear form a module for stack manipulations. Val and SP should also be external static. 4.7, Register Variables. The fourth and final storage class is called Register. A register declaration advises the compiler that the variable in question will be heavily used. When possible, register variables are placed in machine registers, which may result in smaller and faster programs. The register declaration looks like register int x semicolon, register char c semicolon, and so on. The int part may be omitted. Register can only be applied to automatic variables and the formal parameters of a function. In this latter case, the function declaration looks like f open paren c comma n close paren, register int c comma n semicolon, open curly brace, register int I semicolon, and then dot 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 close curly brace. In practice, there are some restrictions on register variables, reflecting the realities of the underlying hardware. Only a few variables in each function may be kept in registers, and only certain types are allowed. The word register is ignored for excess or disallowed declarations, and it is not possible to take the address of a register variable, a topic that will be covered in Chapter 5. The specific restrictions vary from machine to machine. As an example, on the PDP-11, only the first 3 register declarations in a function are effective, and the types must be int, char, or pointer. As a quick aside, the description of the details of the implementation of the register modifier on the PDP-11 is a delightful peek into how the C compiler generated runtime code on that particular system in the 1970s. As compilers have become more sophisticated, the compiler could decide which variables to keep in registers far better than the programmer could. And since how variables would be allocated to registers might be different on different hardware architectures, the register indication is generally ignored by modern C compilers, so you should probably never use it in your code. As a matter of fact, I wrote the following sample C program and compiled it with the -S option so I could see the generated assembly language with and without the register declaration. With optimization, there was no difference between the code generated with or without the register declaration. The reason the generated assembly code was identical once you take a look at it was, regardless of the use of the register keyboard, was that the C optimizer on my ARM-based computer in 2022 realized the best way to implement the code was to keep both of the variables in registers, because the loop code was so simple and the CPU in my computer has plenty of registers and optimized any loading and storing of the data for these variables right out of the program. In 1978, the authors likely included the register function as a feature to convince experienced assembly language programmers that they should write all but the lowest level code in C. So write a little tiny bit in C and then, write a little tiny bit in assembly language and write everything else in C. So here's an example that's not in the textbook. It's on page 81. If it were in the textbook, you can see this code at www.cc4e.com/code, page 81. And this is code that I wrote to play with the register keyword to mostly convince myself it was pointless to use it. But here we go. Pound include stdio.h, int main, open paren, close paren, open curly brace, int compute, semicolon, register int iter, semicolon, scanf, open paren, double quote, %d, close quote, comma, ampersand, compute, close parenthesis, semicolon. Printf, open parenthesis, double quote, compute space %d \n, double quote, comma, compute, close parenthesis, semicolon. 4, open paren, iter equals 0, semicolon, iter less than 1000, semicolon, iter plus plus, close parenthesis, open curly brace, compute equals open parenthesis, compute times 22, close parenthesis, times 7. If compute greater than 1000, compute equals compute modulo 1000. Close curly brace. Printf, open paren, double quote, compute space %d \n, close quote, comma, compute, semicolon, close curly brace. Now, some of these, I wrote this code in a way that tries to convince the optimizer that I'm actually going to use these values. That's why I read the value from input as compared to a constant. It would actually the optimizer so smart that it would just eliminate all the constant calculations. So, but that's my sample playing with register. Section 4.8, block structure. C is not a block-structured language in the sense of PL1 or ALGOL, in that functions may not be defined within other functions. On the other hand, variables can be defined in a block-structured fashion. Declarations of variables, including initializations, may follow the left brace that introduces any compound statement, not just the one that begins a function. Variables declared this way supersede any identically named variables in outer blocks and remain in existence until the matching right brace. For example, if open parenthesis n greater than 0, close parenthesis, open curly brace, int I semicolon, declare a new I, for open parenthesis I equals 0 semicolon, I less than n semicolon, I plus plus, close parenthesis, and the rest of the for loop, and then a close curly brace for the if. The scope of the variable I is in the true branch of the if. This I is unrelated to any other I in the program. Block structure also applies to external variables. Given the declarations int x semicolon, f open parenthesis, close parenthesis, open curly brace, double x semicolon, close parenthesis. Then within the function f, occurrences of x refer to the internal double variable. Outside of f, they refer to the external integer. Same is true of the names of formal parameters. For example, int z semicolon outside of any function, f open parenthesis z close parenthesis, double z semicolon, open curly brace, close curly brace. Within function f, z refers to the formal parameter, not the external variable. Section 4.9, initialization. Initialization has been mentioned in passing many times so far, but always peripherally to some other topic. This section summarizes some of the rules now that we have discussed the various storage classes. In absence of explicit initialization, external and static variables are guaranteed to be initialized to 0. Automatic and register variables have undefined or garbage values. Simple variables, not arrays or structures, may be initialized when they are declared by following the name with an equal sign and a constant expression. Int x equals 1, semicolon. Char s quote equals single quote backslash single quote, semicolon, a constant of a single character that is a single quote itself. Long day equals 60 times 24, semicolon, which is the minutes in a day. For external and static variables, the initialization is done once conceptually at compile time. For automatic and register variables, it is done each time the function or block is entered. For automatic and register variables, the initializer is not restricted to being a constant. It may in fact be any valid expression involving previously defined values, even function calls. For example, the initializations of the binary search program that we wrote in Chapter 3 could be written as binary, open parenthesis, x, comma, v, comma, n, close parenthesis, int, x, comma, v, open square bracket, close square bracket, comma, n, semicolon. Open curly brace, int low equals 0, semicolon, int high equals n minus 1, semicolon, and int mid, followed by the rest of the function, and then close curly brace, instead of initializing these as the first executable statements. And we would do this with binary, open paren, x, comma, v, comma, n, close paren, int x, comma, v, open square bracket, close square bracket, comma, n, semicolon, open curly brace, int low, comma, mid, comma, high, semicolon. Low equals 0, semicolon, high equals n minus 1, semicolon, and so forth. In effect, initializations of automatic variables are just shorthand for assignment statements. Which form to prefer is largely a matter of taste. We have generally used explicit assignments because initializers and declarations are harder to see. Automatic arrays may not be initialized. External and static arrays may be initialized by following the declaration with a list of initializers enclosed in braces and separated by commas. For example, the character counting program of Chapter 1, which originally was main, open parenthesis, close parenthesis, open curly brace, int c, comma I, comma n white, comma n other, int n digit, open square bracket 10, close square bracket, semicolon, n white equals n other equals 0, for open parenthesis I equals 0, semicolon, I less than 10, semicolon, I plus plus, close parenthesis, n digit sub I equals 0, and then the rest of the code, followed by a close curly brace finishing main. This could be written instead using initializers as follows. Int n white equals 0, semicolon, int n other equals 0, semicolon, int n digit, open square bracket 10, close square bracket equals open curly brace 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, close curly brace. 10 zeros in a row, and separated by commas and in braces. And then the main code is simply main, open paren, close paren, open curly brace, int, comma c, comma I, and then the rest of the main code, close curly brace. The idea is that with the initializers, as with the external variables outside of the main function, you do not need to initialize them, even with a for loop in the beginning of the main program. These initializations are actually all unnecessary since they're all 0 anyways, but it's a good form to make them explicit anyway. If there are fewer initializers than the specialized size, the others will be 0. It is an error to have too many initializers. Regrettably, there is no way to specify the repetition of an initializer, nor to initialize an element in the middle of the array without supplying all the intervening values as well. Character arrays are a special case of initialization. A string may be used instead of the braces and commas notation, as in char pattern open square bracket close square bracket equals double quote the double quote semicolon. This is a shorthand for the longer but equivalent char pattern, open square bracket, close square bracket, equals, open curly brace, single quote T, single quote, comma, single quote H, single quote, comma, single quote E, single quote, comma, single quote, backslash 0, single quote, close curly brace, semicolon. When the size of an array of any type is omitted, the compiler will compute the length of the array by counting the initializers. In this specific case, the size of pattern is 4, 3 actual characters plus the terminating backslash 0. I would note that the primary difference between C and C-influenced like languages like Java, PHP, and JavaScript, the key is that C strings are character arrays, while in the other languages, strings are objects. These string objects do have inside themselves an array of bytes or characters, but they also keep track of things like the length of the string and provide functionality like extract a substring in the methods in these objects. In C, there is a set of library functions that perform string operations like compare two strings, while string comparison is built into the string objects in each of the other languages. Strings as character arrays allow programmers to build very fast, low-level code in libraries and operating systems. But to write the code well, you need to understand what is really going on at the low level. Section 4.10, Recursion. C functions may be used recursively. That is, a function may call itself either directly or indirectly. One traditional example involves printing of a number as a character string. As we mentioned before, the digits are generated in the wrong order. Low-order digits are available for high-order digits, but they have to be printed in the other way around. There are two solutions to this problem. One is to store the digits in an array as they are generated and then print them in reverse order, as we did in Chapter 3 with I to A. The first version of printd follows this pattern. This is sample code on page 85 of the textbook. You can view the sample code at www.cc4e.com/code, page 85, example 1. Pound include stdio.h, printd, open paren, n, close paren, int n, open curly brace, char, s, open square bracket, 10, close square bracket, semicolon, int I, semicolon. If, parenthesis, n less than 0, parenthesis, open curly brace, put char, open paren, single quote, dash, single quote, close paren, semicolon. N equals minus n, semicolon, close curly brace. I equals 0, semicolon. Do, open curly brace, s sub I++ equals n modulo 10 plus, quote, 0, quote, which gets the next character, while, parenthesis, parenthesis, n slash equal 10, close parenthesis, greater than 0, close parenthesis, semicolon. Then we reverse the string, while, open paren, minus minus I greater than or equal to 0, close paren, put char, open paren, s sub I, close paren, semicolon, close curly brace to end the printd function. The alternative is a recursive solution in which each call of printd first calls itself to cope with any leading digits, then prints the trailing digit after that call returns. This is an example on page 85 of the textbook and its example 2. Pound include stdio.h, printd, open paren, n, close paren, int n, semicolon, open curly brace, int I, semicolon. If, open paren, n less than 0, close paren, open curly brace, put char, open paren, single quote, dash, single quote, close paren, semicolon, n equals minus n, semicolon, close curly brace to finish the if. If, open paren, I equals n over 10, close paren, not equals 0, close paren, printd, open paren, I, close paren, semicolon. That's the recursive call. And after the recursive call comes back, we do put char, open paren, n modulo 10 plus single quote, 0, single quote, close paren, semicolon, close curly brace to end the print D function. When a function calls itself recursively, each invocation gets a fresh set of all the automatic variables quite independent of the previous set. Thus, in print D 123, the first print D has n equals 123. It passes 12 to a second print D, then prints 3 when that one returns. In the same way, the second print D passes 1 to a third, which prints it, and then prints 2. Recursion generally provides no saving in storage, since somewhere a stack of values is being processed or has to be maintained, nor will it be faster. But recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. As an aside, recursion. Recursion is a beloved concept in computer science. It is often taught early in most programming courses because it is just so cool. Most examples are sadly like computing factorial, or the example above, converting an integer to a string, and they're not good uses of recursion actually. But when you do finally find yourself in need of traversing a tree-based structure like an XML document, or parsing a mathematical expression with parentheses, recursion is the ideal solution. So the problem, in a sense, is not recursion, but when it is taught and what examples are used. Interestingly, Kernighan and Ritchie include the correct warning about using recursion when it is not the best solution in the above text, and it bears another read. Back to the book. Recursion generally provides no saving in storage, since somewhere a stack of values is being processed or has to be maintained, nor will it be faster. But recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. I couldn't have said it better. Section 4.11, the C preprocessor. C provides certain language extensions by means of a simple macro preprocessor. The #define capability, which we have used, is the most common of these extensions. Another is the ability to include the entire contents of other files during compilation. File inclusion. To facilitate handling of #defines and declarations, among other things, C provides a file inclusion feature. Any line that looks like #include space double quote file name double quote is replaced by the contents of the file name. The quotes are indeed mandatory. Often a line or two of this form appears at the very beginning of each source file to include common #define statements and extern declarations for global variables. #includes may be nested. #include is the preferred way to tie declarations together for a large problem and in a large program. It guarantees that all the source files will be supplied with the same definitions and variable declarations, thus eliminating a particularly nasty kind of bug. Of course, when an include file is changed, all the files that depend on it must be recompiled. Macro substitution. A definition of the form #define yes 1 calls for a macro substitution of the simplest kind, replacing a logical name by a string of characters. Names in the #define have the same forms as the C identifiers. The replacement text is arbitrary. Normally, the replacement text is the rest of the line. A long definition may be continued by pasting a backslash at the end of the line to be continued. The scope of the name defined with #define is from its point of definition to the end of the source file. Names may be redefined, and a definition may use previous definitions. Substitutions do not take place within quoted strings. So, for example, if yes is a defined name, there would be no substitution in printf, open paren, double quote, yes, double quote, close paren. Since implementation of #define is a macro pre-pass, not part of the compiler proper, there are very few grammatical restrictions on what can be defined. For example, Algol fans can say #define then, and then nothing, define begin, open curly brace, define end, semicolon, close curly brace. And then write, approximate algol, if paren I greater than 0, close paren, then begin A equals 1, semicolon, B equals 2, end. It is also possible to define macros with arguments. So the replacement text depends on the way the macro is called. As an example, define a macro called max, like this. Define max, open paren A, comma B. Open paren A, close paren, greater than, open paren B, close paren, question mark, open paren A, close paren, colon, open paren B, close paren. Now, the line x equals max, open paren P plus Q, comma, R plus S, close paren, semicolon, will be replaced in the preprocessor by the line x equals open paren P plus Q, close paren, greater than, open paren R plus S, close paren, question mark, open paren P plus Q, close paren, colon, open paren R plus S, close paren, semicolon. This provides a maximum function that expands into inline code rather than a function call. So long as the arguments are treated consistently, this macro will serve for any data type. There is no need for different kinds of max for different data types, as there would be with functions. Of course, if you examine the expansion of max above, you will notice some pitfalls. The expressions are evaluated twice. It is bad if they involve side effects like function calls, increment operators, or perhaps push and pop like we've used before. Some care has to be taken with parentheses to make sure the order of evaluation is preserved. Consider the macro define square, open paren x, close paren, equals x times x. When it is invoked as square, open paren z plus 1, close paren. There are even some purely lexical problems. There can be no space between the macro name and the left parentheses that introduces the argument list. Nevertheless, macros are quite valuable. One practical example is the standard I/O library to be described in Chapter 7, in which getchar and putchar are defined as macros. Obviously, putchar needs an argument, thus avoiding the overhead of a function call per character process. Other capabilities of the macro processor are described in Appendix A. As a bit of a long aside, in this section we are talking about the preprocessor. It's probably a good time to talk a bit about why we use this terminology. For those of you with a computer science degree from back in the day, many of you wrote a compiler as a senior project, just like I did. Building a compiler was a great project because part of the goal of computer science is to understand the technologies that make programming possible, from the language syntax down to the hardware. The compiler that translates our source code into machine code is an essential part of the technology stack that we use. Early compilers for languages like the early Fortran variants tended to be translators. They just translated code one line at a time from a high-level language to assembly language. You could think of early Fortran programs in the 1950s and the 1960s as just more convenient ways to write assembly language for programmers that knew assembly language. You always needed to be aware of assembly language and the translation that it was going to write fast Fortran. Programs were small and optimization was done at the Fortran level, often leading to some hard-to-understand code. By the mid-1970s, programming languages were based on parsing theory, and we used what is called a grammar to define the language. Kernighan and Ritchie kept I/O statements out of the C language to keep its formal definition, i.e. its grammar, as simple as possible. As these new languages emerged, they allowed for a more theoretical and powerful approach to converting source code to machine language. The theoretical advances in compiler and language design meant that parts of the compiler might be reusable across multiple programming languages. Each language could have its own syntax and grammar rules, and they could be plugged into the compiler and poof, you would have a new programming language. It got to the point where Unix systems had a tool called YAC, which stood for Yet Another Compiler. You would give it a grammar for your new language and it would make a compiler for you. As a matter of fact, the JavaScript language that was created in 10 days back in 1995 was possible because Brendan Eich had a lot of experience with compiler generators. He defined a grammar for JavaScript and generated his first compiler. Part of what made a compiler generator possible is the idea of a multi-step compiler, or the tasks of a compiler were broken down into a series of simpler and more well-defined steps. Here are the steps of a typical C compiler in the 1970s. First, a preprocessor step that takes C code with syntax like pound define and pound include as its input and produces raw C code output with those instructions processed and or expanded. The preprocessor was a C to C transformation. Next, a parser step that took the raw C code, applied the grammar to the language, and created what is called a parse tree. Think of the tree as a hierarchy of statements grouped into blocks, grouped into functions, etc. Things like a loop or just one node in a parse tree. After that, a code generation would turn the parse tree into some kind of simplistic, portable internal code that expanded things like loops and if-then-else statements into code. After that, a code optimization that looked at the internal code and moved things around, eliminating any redundant computations. Say, don't compute the same things twice. This step is why the authors make such a big fuss about how there are times where C might do things in a slightly different order in an expression, even in the presence of parentheses. Remember the K&R C arrangement license back in Chapter 2? That rule removes constraints on the compiler's optimization step so it can generate the most efficient code. I would note that all the steps up to this point did not depend in any way on the actual machine language of the system that they were running on. This meant a preprocessor, parser, code generator, and code optimizer could literally be written in C and used on any architecture. The final step is a code generator that takes the optimized intermediate code and generates the actual assembly and machine language for the processor. For fun, you can add the -S parameter to your C compiler and see the resulting assembly language output for your system. If you look at the machine language generated on an Intel or AMD processor and compare it to the machine language on an ARM processor, it will look very different. Because all but the final compiler steps did not depend on the computer where the program is being run, you could actually create a C compiler on a new computer architecture by writing a code generator on the new computer, then running all but the last step of the compiler on one computer, then copying the internal code generated by the compiler to the new compiler and running the code generation step on the new computer. Then you actually have a working C compiler on the new computer. And the first step is usually to recompile the C compiler itself from source code to produce a fully native C compiler on the new computer that can compile all the rest of the C code you have, including possibly the mostly portable elements of the Unix operating system on the new compiler. Yes, describing how to cross-compile and bootstrap a C compiler onto a new computer hardware architecture can give you a headache if you think about it too much. But this notion of bootstrapping a C compiler onto a new architecture was an important technique to move C and then Unix to a wide range of very different computer architectures. We see this in action as the Unix-like Mac OS operating system over the past 20 years was delivered initially on a Motorola 68000 family processors, then on PowerPC processors, and then on Intel processors, and most recently on ARM-based processors built by Apple. Using the software portability patterns that come from C and Unix and described by Kernighan and Ritchie in this book, Apple now makes their own hardware that can be tuned and evolved over time as their operating system and their applications requirements dictate. The use of a grammar, by the way, is to define a programming language is one of the reasons that syntax errors are so obtuse. The compiler is not looking at your code like a human. It is following a very set of simple rules to parse your code, and it's stuck with something illogical and gives you a message like unexpected statement, block, or constant on line 17, and the error is nowhere near line 17. Modern compilers are more sophisticated, of course, than the steps above, but these steps give you a sense that the compiler does many things to make it so your code can actually run very efficiently. And given that Kernighan and Ritchie were building a programming language C, mostly portable operating system written in C, Unix, and a mostly portable C compiler written in C. Some of their innovative work and research into compiler design finds its way into this book, so we have a section in this chapter called the C Preprocessor. So here we are at the end of chapter 4, and it's a good time to talk about the word address. Up to this point in the book, if you count them, the word address has been used 10 times without a precise definition beyond the notion that data is stored in memory and the address of the data is where the data is stored in memory. In the next chapter, this notion of the address where the data is stored becomes very real and tangible as we explore pointers as well as the ampersand and asterisk operators. Up to now, an experienced JavaScript, PHP, or Java programmer can view C as just another set of similar syntax rules with a few quirky runtime bits. But in the next chapter, we will deeply explore the concept of data allocation and location. It turns out that every programming language pays a lot of attention to data allocation and location, but the runtime environments of modern languages work very hard not to expose you to those details. Just because modern languages hide the difficult bits from us, it does not mean that those languages solve the problem using magic. Eventually, the problem needs to be solved. And that is why the compiler and low-level runtime elements of language like PHP, JavaScript, and Java are usually written in C. So the builders of those languages can solve the difficult data storage and allocation problems for you. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.
Welcome to Chapter 4, Functions and Program Structure. In this chapter, we're going to start digging a little deeper. Part of the goal of this course is to get you to the point where we can talk about how things really work. Eventually, in the next course, we'll even go down to hardware and architecture and gates. And so it's time to start opening things up and looking at how things work. And so this is a good time to do so. And the big thing we're going to learn, among other things, is the concept of a stack. How pass by reference works, how pass by value and pass by reference work, a little bit about recursion. Recursion's a thing that I worry about a lot. Well, we'll get there. And a preprocessor. So these are all things where we're really starting. It's not so much about just how functions work, but how functions are implemented and how that affects how they work. So the first thing I want to talk to you about is a really nifty computer science concept called a stack. A stack is a data structure that we use, and it has a couple of attributes. The idea of a stack is we start with an empty stack and we put things on the stack and then we take things off. When we take them off, the last thing we put on is the first thing we get off, and they go up and they go down. You can push things onto them and take things off of them. We can approximate this with a Python list. So we start with an empty list, we append the string 1 to it, and the stack has a 1 on it. It's kind of growing up from the bottom, and it's going to shrink from the top. And then we append a 2 to it, and then our stack is now 1 and 2. So the bottom thing in the stack is 1, and the top one is 2. And then we append a 3 to it, and we have 1, 2, 3 on the stack. At that point, we pop. Pop says, give me the most recent pushed thing and then take it off. So we pop off 3 and the stack remains with 1 and 2. Again, this is also known as a last in, first out, or LIFO queue. A queue is like a line of things. And so the last thing in is the first thing you got out. So that's a stack. And we're going to use stacks in function calls. So historically, when we talk about call by value and call by reference, we basically say that call by value means that somehow this value, like in the main program MA with a variable with a value 42, ends up being copied into the function, and the parameter OP is got a copy of the 42. It's not the original MA, it's the copy of 42. So 42 gets passed in the function 1, and OP is a copy of 42. So then inside the function we can subtract 10 from it, and then we can see that, but then when we get back in the main function, we see that MA has been unchanged. And it's like, oh, we build a little wall around the function and nothing inside the function happens. The outside world is unaffected by it. And that's a great oversimplification of call by value. Of course, call by reference means the stuff you do in this function can affect outside the function. But let's talk a little bit about how a stack is used to accomplish this. So just to use some terminology, C calls these variables that are allocated inside the function before the function starts as the automatic variables. And frankly, int MA equals 42 in main is an automatic variable inside the main, because main is a function inside a C program that happens to be the one that starts everything out. So if we get to the point where it says int MA equals 42 and then it prints MA being 42, at that point on the stack, the C runtime has allocated one integer and we've assigned 42 to it. So that's what the stack looks like at that first print statement in main. Then we call the function 1 and pass MA in. And this is where the C runtime library, kind of before everything starts out in the function 1, it allocates what's called a stack frame. And a stack frame includes the parameters, OP, and the automatic variables that are inside of that function. And so in this case, we're going to get two variables. We're going to get OP as an integer and TN as an integer. And before the program starts up, the value 42 is copied from MA into OP. And so the stack frame is the context in which that function operates. So when it first starts, you see that OP has 42. You also see we have two copies of the number 42. And we have a parameter, OP, and then we have the automatic variable, the TN. Then the next line runs, okay? And at that point, OP is changed. OP equals OP minus TN. And so OP becomes 32. But you'll notice that on the stack, out beyond the stack frame is our current execution of the function 1. Beyond the stack frame, the 42 is still there. We can't see it. We're in the function right now, and we're only seeing the top part of the stack. We're not seeing the part of the stack that belongs to the main program. So that's where it prints out 32. So 32 in the function says OP is 32, and that's fine. And then we return, and that's when the C runtime removes the stack frame, pops those things off the stack. It remembers how much it put on, and it pops all the stuff off the stack that it put on, and then it basically comes back into MA, and the stack frame for the main program has one variable in it, and it's MA, and it has 42. And that's because 1 operated in its stack frame, and now the main program is back to operating in the same stack frame. You can almost think of this as like 1 never happened, right? From main's perspective, it had some variables. 1 ran and a stack frame was created. Some of the main data was copied into the 1 stack frame. 1 operated in its stack frame, and then the stack frame went away right before 1, or right at the moment that 1 returned, and the return value ends up in the stack frame too. I just haven't shown you that, and these don't send return value. So the return value comes back from the stack frame. But you can see how main started with a stack with one variable on it, and then 1 ran and all that stuff happened, and then it kind of was undone, and that's where the changed variable just kind of went away. And so the stack, it's as if nothing ever happened except it went up and then it went back down. Now, one thing we notice, and in Python we see this too, where you say everything is call by value, which implies a copy, except for things like certain objects and calling methods and objects. But if you look at, say, this function zap, and we pass in x, and x starts out as original, and then it calls the zap function, and it passes in, and it's got the original, then it gets changed inside the zap function, and that change prints out. But then when it comes back, it is back to the original. So x is back to the original in the main code. And you might say, oh, that looks right. And that's actually quite intuitive, in that Python has made it so a call by value inside of this, call by value to the zap function, it happened, meaning that nothing changed outside of the zap function, and it was a call by value, not a call by reference. Now, I'm not going to go into it, at least not right now, talking about why that really worked, and it's less about call by value and call by reference, and more about the fact that y is really a pointer to an object, and when y equals changed executes inside of zap, the object pointer, it points to a different object, but x never changed. And so Python has a slightly different runtime, but it leads to this notion that seems like a string variable in Python is call by value. Now, if we look at the similar but quite different code inside of C, we see the main has a character array x of unknown length, which is original, and that just unknown length means that it's looks like 8 characters plus a \0, which is 9 characters, and it prints out kind of like a string. It's a character array with a terminator, and then we call zap, pass x in, and then inside of zap takes a character array as its parameter, and it can print out the word original when it starts, and then it copies changed into it, and then it says at the end, the y is at the end is changed, but then we come back, and back in the main program it got changed. So does that mean it was called by reference or what? And the answer is sort of, and this is where it kind of helps. So it turns out that when you are passing an array into a function in C, you're not actually passing the contents of the array. So most of the time we think of that 42 being copied if it's an integer. If it's just like a scalar thing like a float or an int or a char or something, that's being copied. But when you have an array, that could be gigantic. So it doesn't actually copy in the whole array. So when x is being passed into zap and being received as y, we're not actually passing the string, because that could be 1,000,000 characters for all we know. So it's not like it makes an extra copy of 1,000,000 characters. What it's doing is it's passing in the address of the start of the string, not on the stack, but somewhere else. It actually could be on the stack somewhere, but it's not in the stack frame, and the word original is not copied into the stack frame. The stack frame only includes a pointer, or the address. X is the address of the letter O, and then Y is also the address of the letter O, which means when we're calling strcopy, we are overwriting those characters. Oh, and by the way, I carefully made sure that the string changed was shorter than the string original, or my program could have blown up, because this is C, and arrays don't get bigger. Python strings get bigger, but arrays don't. In a couple more lectures, we will build a data structure where it's like a Python string, and we can add to it, and you'll see that the code is very complex. A character array is very simple, okay? And so it's not exactly a pass by reference. It is a pass by location. And if you happen to misuse that location, meaning you write to that location, you write to location. Now this might have been in like read-only memory something. Your program might have blown up. So you better be sure what you're doing when you start messing inside of a function with an array that's been passed to you. Now sometimes you're supposed to. Sometimes we tell you to write that. Another thing that you're going to see in this is the reference to register variables. This is another rather historical notion, and in my opinion it really had to do with convincing really skilled assembly language programmers that they could get the same performance out of C that they were used to getting inside assembly language. And so What are registers? Well, when you have a central processing unit and you have memory, the data lives in the memory and the registers live in the central processing unit. And depending on the speed of things, a register might be, 40 times faster than regular memory. And so if you could keep a variable like I in a loop, you could keep that in a register that's faster. And so what we can do with saying register int x is say, hey, by the way, next few lines, x is a really important variable and I expect to use it a lot. So if you can possibly not store this in memory, please do so. And that's why the only kind of weird thing about the register is you can't get the memory address of a register variable. Now, in modern compilers, we have runtime optimizers that are miraculous. I mean, they border on miraculous. Even the simplest of runtime optimizers that speed the code up at runtime are miraculous, and saying this is a register or that's a register might actually confuse things. So all the register does is, hey, I am never going to ask you the address of this variable, so don't bother putting it in memory if you don't feel like it. Okay, and so it's probably, but I also think it's kind of fascinating and fun to think about this. Think about how early C developers were so deeply connected to their assembly language that is at the runtime. Recursion. When a function calls itself, it's called recursion. It's a powerful, it's a beautiful concept. There is places when, if you're given a tree-like structure, like you parse some XML or something and you're reading through the XML, recursion is such a pretty way to write code. I'm about to show you a very simple recursion example that are two things. First, they're really inefficient and silly uses of recursion, and they mislead you as to why you should use recursion. And they misleadingly kind of tell you that, like, recursion is great, let's use it for something it is not well used for. So really in this section, I'm not trying to show you what recursion is used for well. I'm more interested in giving you a really artificial, synthetic example to show how the call stack works and how recursion works with the call stack. So here we have, some tortured code. It is not pretty code. This is I'm writing code that, if given a number like 3, adds up 1 plus 2 plus 3. Okay, and gives me 6. There are so many ways to do this. There's even a closed form solution that doesn't even require a loop. That's called algebra. But we're going to use recursion. So if you look at the int main, I'm going to say sum up 3. That means sum up things 1, 2, 3. So sum up is being called from main, and then I've got the return value, and I say sup. And you'll notice in the printout that sup is the very last thing that comes out. And so if you walk through sum up, you see that there is a parameter called above that's coming. I call that above because it's coming from whoever's calling us. There's a parameter below, which is we're going to compute a value and send it down to the next copy of ourselves down. And then sum is the sum of the above value and the sum of the below values. And then retval sum is just coming back from the call to ourselves. And then retval is adding those two things together. And I do this in exceedingly slow motion with print statements everywhere that just makes this look ugly, because really the only thing that matters is where it says sum equals sum up below, and what we're doing is we're calling the same function again. So if you look in main and you see the sum up call, that is going to create a stack frame. And in that stack frame, it's going to have whatever the 3 number is. We're going to make an above variable, copy 3 into the above variable, and allocate a below sum and retval. So our stack frame is going to have 4 integers on it. And then the function starts working. And the way the recursion works is there's always got to be a time at which it stops. This is kind of like going down, 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 and then has to work its way back up. If it goes down forever, that's called a stack overflow, and then your computer runs out of memory and your application blows up. So you have to have a time at which the stack algorithm stops. So what we're saying is, if we're being told to sum up 1 or less, well, we define the sum of that as 1. So we just return the sum of everything up to 1 as 1, and that's our way of stopping the recursion at the bottom. And then what we do is we take below and we subtract 1 from it. So if we're being called with 3, below becomes 2. And so you see that over in the lower stack frame. Below is 2. right? Below is 2, and we're about to go down deeper into the call tree. And so we're going to call sum equals sum up below. So what happens now is we're passing 2 in to another stack frame. And so there's not really another copy of the code, but there's another stack frame. And so now we're calling sum up with 2 as the parameter. That's our below. But then we see the stack frame. And now this is the stack frame that's kind of on the left-hand side there. Above in this stack frame is 2. And then execution begins, and we subtract 1 from below. Well, above is not less than 1, so we subtract 1, and below becomes 1 because it's 2 minus 1, and we're going to go down. So it says down 1, which means it's going to, again, say sum equals sum up below, and below in this case is 1. And so it makes another stack frame. So we're actually, there is a maximum of like 3 calls here, and then it's going to work its way out. So then it calls another stack frame that's not shown on the right-hand side, and then it runs with 1 as above, and then above is less than or equal to 1, so it returns 1, and that's why it says in 1, and it doesn't say anything because then it's returned, and it returned the value 1. So now the third stack frame comes off, and now we're in the other stack frame, and sum is what the return value of the sum up call was, so it says back 1, and then it says above. Now we're in the stack frame that's on the right-hand side. So sum is 1, below is 1, above is 2, and so we compute retval, which is 1 plus 2, and that's 3, and we print that out, and that's kind of where we're indicating, and then we return the 3, right? And then it returns retval, and then it runs some more. It gets 3 back, then it adds the 3 to it, and returns one more time, and the stack all pops up, and eventually you get 6. And this is you can look at this as long as you like. This code is like a foolish way to make this calculation, like most artificial recursion examples. The key thing here is just think about the stack frame, right? Every time you call in, another stack frame happens. Call in, stack frame happens, and then when the return value happens, it goes back to that stack frame. So the stack frame is a way of pausing execution at the moment, create a new stack frame, execute in that stack frame, and if you need to, have yet another stack frame. And so this idea of creating stack frame with the parameters and automatic variables each time you call a function, copying the parameters into that stack frame, and then executing the function in that stack frame. We're not making extra copies of the function. We are just creating a new stack frame. That's what the essence of recursion is the fact that you have a stack, and each call makes a stack frame, and if you recursively call again, you just make another stack frame. And so it's almost easier in my mind to think through how stack frames work than it is to think through how recursive code works. Now I want to talk a little bit about the C preprocessor. It's the last thing of this chapter, and it's in some ways orthogonal to functions and program structure. I mean, it is part of program structure. And so I've talked a lot about how wonderfully the C compiler and eventually Unix solves so many problems of software source code portability. And things like endianness and character arrays and masking and shifting not being necessary, those were awesome. But the problem is that C has always operated in an environment. The language has changed. In the early days, it wasn't standardized. By '84, it got standardized. ANSI C came out. A lot of people used it outside its original creation, and so a lot of things got fixed in the first decade of C's use. The language evolved a lot. The language kept evolving, and a lot of the things that would make it evolve are things like integers went from 32 bits in some situations to 64 bits, and then you have to say, well, what is a long? Is long 64 or long 32? Because in some it started with int being 16 bits and long being 32, and then long was 64. Well, for a while then ints were 32 and longs were 32, and then ints were 32 and longs were 64. And what would happen if ints were 64? And it had to do with computer architecture, 64 bits, right? And so sometimes you would have a bit of code and it just, you knew you wanted a 32-bit thing and you weren't sure if an int or a long or a short was going to give you 32. And so you had to say, I really need different source code. Like if I'm working on a PDP-11, I want one thing, and if I'm working at Interdata 732, I want another thing, because really I want a 32-bit integer. And now there's actually int32 in some of these things, because you do need to know sometimes you're using 32-bit integer. Then libraries changed. There's calling sequences that changed because, again, as computers got bigger and bigger, and memory got bigger, and disk drives got bigger, you would be in a certain version of an operating system, and the calls to reading files might be slightly different. And so it's not really that the source code was portable, it's the calling sequences to libraries started to change. Hardware evolved, operating systems evolved, C started running on non-Unix because C originally started on Unix, but then it quickly went to other operating systems because it was such a powerful concept. But sometimes in these other operating systems, just things were kind of different because they weren't working on Unix. And so the preprocessor really was in effect a way to patch your source code so that you could say, look, I wrote this source code 10 years ago and it worked on a PDP-11, and now I'm going to run this on an IBM 360 architecture, and I don't want to change that. There's a few changes I need to make that have nothing to do with sort of what a for loop looks like, but it has to do with like what library I'm calling or what the return type for that library might be. So the preprocessor allowed us to put variations in the source code. And the preprocessor, it really feels weird because its syntax is very different, because the preprocessor is kind of a line-oriented processor, and it has these pound things, right? These like pound if-def, pound define, pound else, pound end-if, and pound include. That's even a preprocessor. So what the preprocessor is not a compiler at all. It is a source code to source code translator. It expands the include files, and then it makes changes. So in the top example where you see pound include stdio.h, you can actually run GCC minus capital E, and it says just run the preprocessor and shows me what comes out. You take 10, 12 lines of code on the left, and it puts out hundreds and hundreds of lines of code on the right. I'm only showing you a subset of it. But the biggest part is the fact that include stdio.h is literally expanded. And then that is C code without the pound include. Okay, so that's the preprocessor. But then another example here is I'm creating this use_long. This is not really a variable. This is a compiled time variable. So I'm going to create a new string called int_32. And if useLong has been defined, I'm going to make int32 be a long. Else, I'm going to make int_32 be an int. And again, this could be a thing where I'm compiling for different architectures, and I want this variable IP address to be a 32-bit integer, and I need it to work on different operating systems. So in this case, because useLong is not defined, int32 as a string substitution, like a macro string substitution before the compiler even does anything, turns int32 into int. And so that's what the 5 lines of pound if def and all that stuff do, is it says change this int32 string in my source code into int. And so what we see on the right is really C code. What we see on the left is kind of C preprocessor plus C code. And so the preprocessor transforms source code to source code. So I was looking around at some old code that I happened to have grabbed and put into GitHub, which was some code from 1994 from Xmosaic 1.2. And for those of you who took my Internet History, Technology, and Security, you know that Xmosaic was the first web browser that was portable across multiple operating systems. And then eventually Mosaic ended up on Unix systems with X Windows. That's why it's called Xmosaic. And it went to the Mac and went to the PC. And so it was really many Unixes, Mac, and PC. And what we're seeing here on the right-hand side is actual source code from that which was written in like 1993, 1994. And what you see is a bunch of if-defs, if-end-defs, and some comments, and like there's a if-def Solaris 9 broken. And it has to do with like, where do we find the error messages on this across all these weird operating systems? Because the way they'd put error messages, sometimes they would use extern, which are global variables defined inside the runtime, and we would just look at those variables. We would make a function call, and it would write into these global variables. But then that global variable might be different. So this is actually from some code that was HTTP P in C. That was some early network connections. Now these days, we just do this stuff in like the pound import requests in Python. But in those days, the C libraries for network connections were really different, meaning that they were just, here comes the network, here's this language C, it's been around by, 89, 90, 91. The network was there, and so we were building libraries, but then how each library worked in each operating system was a little wonky, and so they had to write different C code to compensate for the different operating systems that this C program, a web browser, would be running on. And so all these if-defs mean that one source code with a few predefined constants, compile time constants, could then work on a wide range of operating systems. And so yes, the C language itself is portable, but we also want to be portable over time. And so sometimes libraries change, operating systems change, and we want to be able to compensate for that. And so this is an important part of C. These days it's less important because a lot of the libraries have stabilized and they don't change quite so much. And so this code here would probably just be a bit of socket code, and the errors would come back the same way no matter what version. Like VMS is an operating system that doesn't exist anymore. ThinkC doesn't exist anymore. Next doesn't exist anymore. Solaris doesn't exist anymore. So these are all operating systems that don't even exist anymore. But this code was portable across all those things. And actually, I compiled all this, and you can kind of take a look at it. I made a video where I resurrected this code. It's got to be 8 or 9 years ago on a Macintosh, which is evolved from Next. I don't know if I could get it to work again, but back then I got it to work on a Macintosh, and I defined it as Next. And so I compiled this C code, and there is an X Windows on Macintosh, so I got the X Windows library, I got all this stuff working, and I told it, you're a Next, and then I recompiled the C code, and eventually something came up. And I made a video about it, and so because I knew that it'd be very difficult to keep this thing working over time. But to go from 1994 to 2014 and recompile something in 20 years later, that's still pretty impressive that Next code would still work. Things like the VMS code, there's no VMS computers that I know of these days. So it just shows that the idea of portability is some of it is simple and elegant and was laid down in 1978, but then there are things outside the programming language that were evolving and still are evolving to this day. And if you are doing C coding today or C++ coding today, you may be using things that start with #, which are compiler directives rather than C code. So with that, dive into Chapter 4 and learn about functions. Hello, and welcome to our lecture on Kernighan and Ritchie, Chapter 5, putting some context around it. Chapter 5 is Functions and Program Structure. So, the first thing I want to call your attention to is Section 5.1. I actually think that Section 5.1 is the most poignant and beautiful section in the book. Everything you've learned up till now, everything I've talked about, size of data, etc., has led to the point where you can read 5.1 and understand every word of it. You should enjoy reading it. I think of it as like a love letter from the creators of C to future computer scientists. So 5.1 is important. We'll talk a little bit about pointer arithmetic. 5.6 we'll look at the duality between pointers and integers. Then we'll hit call by reference and call by value that are enabled in C by pointers. And then look at the biggest security hole that C has caused over the past 40 plus years, buffer overflow. Now, the chapter gets a little dense in some of the sections, and so I'll just have you skim some of those sections. This is the essential example of pointers. We have two variables, int x and y. we have a variable px, which is of type pointer. It points to an integer. That's what int star means. We store 42 in x, and we store the address of x into px using the ampersand operator. And then we use the address of x, which is in px, and then we use a lookup operator or a dereference operator, star px. It says, go to the memory location pointed to by px and load me an integer and put that into y. And so we can see when we print out x is 42 and y is 42, and px is a long hexadecimal number that is some memory location inside the actual computer. And so ampersand and asterisk and int star, the star is a sort of a modifier for a type, are the important things. One of the things that you've probably never seen in Python is the ID function. We've used functions like type and dir, and there are ways for us to inquire about variables and constants. ID is a way to ask for the ID of something. Now in CPython, and just to be clear, there are multiple versions of Python. CPython is the classic one. It's the implementation of Python that happens to be written in C. There are other implementations of Python. And so what I'm telling you with this ID function is something that will work for the moment in CPython, but not necessarily every other one. If you print it out and you say what is x and what is the ID of x, it's kind of like the address. And if you look at the documentation, it says, don't think this is the address, right? And it says the Python ID function is not intended to be dereferenceable, meaning we're not supposed to look up memory from that. The fact that it's based on the memory address is a CPython implementation detail that other Python implementations do not follow. Now, if you download the source code, kr0501.py, I actually have a completely unauthorized implementation of a lookup, a dereference. And it has to know the type of the thing that it's dereferencing, y equals deref of px, and it can then give me back that integer pointed to by the address. But this is not guaranteed to work. It's not supposed to be how it works. It just is, things have addresses, and in CPython, at least for this particular version of Python that I'm using, you can use them. Pointers gives us the ability to do call by reference. And so, if you've done Python, you see that I had a slide in an early version of my Python class that said, sorry, Python doesn't do call by reference. It only does call by value. And that means that within a function, you change the parameters and nothing happens. But some languages do have call by reference, which means the parameters that come into a function are somehow handles that allow us to actually change the values in the main programmer or where we've been calling from. So the language Pascal and C and C++, PHP, and C# have this formal notion of call by reference. And languages that don't have it are like Python and Java and JavaScript. Now there is a notion, the fact that I said this is for simple types like integers, objects are passed in, but then if you call methods in objects, you can actually change the data that the object has. But it's not like you're changing the object, you're changing the object's data. So let's take a look at a bit of code. Now the first example is actually Pascal. Now Pascal's a programming language that was written by Nicholas Wirth and in Switzerland in 1970, and it had a call by reference. And it had this notion of var, and so you're creating a function named func, takes two parameters. One is a call by value, which is a, and then the other one's call by reference, which is a b. And we set a and b to two new numbers. And then in the main program, we set x equals 42 and y equals 43, and then we call the function, and you'll notice there's no extra syntax in the function. And then we come back, and you will see that the y variable is changed and the x variable is not. And then the C version of this, we have x equals 42, y equals 43, and then when we call func, we say we're going to pass in x and then ampersand y, which is the address of y. And if you go back to the very first example in section 5.1, we're passing in a number, which we're actually passing in by value, but the value is the address. And then inside the function, we take a and then a pointer to b, pb, and we say that a is just an integer and pb is an address of an integer by adding the little asterisk there. So the address, where it's at, has been passed by value, But using that value, we can dereference it and get to the thing. So we say A equals 1, and then we say star PB equals 2. That says store 2 as an integer into the location pointed to by PB. And then when you come back, the second parameter will have been changed, Y will have been changed, and X will not be changed. If we take a look at a few other languages, so here we have the C code again. Python, 1989, doesn't have the notion of pass by reference. And so one of the things that I think is an excellent compromise that is the case in Python is the notion of returning a tuple. Not just a single value, but a tuple return. And so that way we could, if we really wanted to get back a value, more than one value, we could return a tuple, and then in the main program we assign the tuple. So if we really wanted X and Y to change from inside the function, we could do so by just explicitly saying the function is going to return two values and we're going to change them both. And if we look at PHP, which is 1994, we see a very elegant, I think. Now, whenever you look at PHP, you got to realize the $ is just part of the variable name. That's just the first character of all variables in PHP. So what we do inside a function is we say ampersand $b, which is the second parameter is b, $b, and we're expecting to change it. And you'll note that we don't change the syntax inside the function, $b equals 2, $a equals 1. The syntax doesn't change. And when we make the call, func $x, $y, we don't change that either, and yet call by reference works. So if you look at all these examples, other than the weird $ convention, I would say that the simplest and most elegant is probably the PHP implementation, right? Because we don't have to do anything inside the function except I'm planning on changing this. Now, C#, which is much later, 2000, has this notion of ref, which is somewhat a throwback to Pascal, but also, it's the ampersand thing. And but the one thing I like about it is inside the call to func, you have to kind of agree. The calling code by saying ref x is in a sense agreeing that it is aware that x is likely to be changed by that function. And so that's call by reference. Now, we're in a C class, and so ampersand and asterisk are how we do it. So again, that's just, it's really quite straightforward inside a C code, as long as you are very good at understanding what the asterisk and ampersand do in C. Another important thing that's easily understood with a very simple bit of code is pointer arithmetic. The key to pointer arithmetic is that a pointer to an integer is different than a pointer to a character. Now, both these pointers are the same size because they are an address, and addresses are all the same size. But if you add 1 to a character pointer, that actually adds 1 to the address. And if you add 1 to an integer pointer, then it adds 4. And that's because each integer takes 4 characters. And so when you're doing increments and subtracts, etc., when they're pointers, it increments based on the type of the thing that's pointed to. So a pointer is not just a pointer, it's a pointer to a thing with a type. And when you're incrementing and decrementing, the type that's being pointed to is more important than the fact that it's a pointer. It goes up and goes down, but it doesn't always just go up and down by 1. Pointers are not integers. So if you go back to chapter 2, there was from the book a table of the sizes of things. And so if you look in the PDP 11, integers are 16 bits. In the Honeywell 6000, they're 36 bits. In IBM 370, they are 32 bits. In Interdata 832, there's 32 bits. Now I've added a line to this that tells the number of bits in addresses in these systems. And you can see if you compare the int numbers to the address numbers that in all the cases except the PDP 11, the integer is larger than the address, which means that there is extra space in the address, and we can almost treat addresses as unsigned integers. Now, the PDP 11 is a little weird in that 16 to 32 is a range of delivered computers over the years, and not all computers had full memory, and not all applications use the entire memory of the entire computer. So most of the time, you can conveniently put an address into an integer and then get that address back out and not have truncated that address or messed it up. So treating pointers as integers almost works. And the longer ago in history it was, the more likely it did work. Addresses are generally positive numbers that often start from 0. Sometimes heap numbers come down and sometimes stack numbers go up or whatever. But most computers did not come with a maximum memory installed. And if you're a multi-user computer, you didn't give all the system's memory to every application. And we tended to use very little memory in applications. We were very careful about it. So we just never ran into the problem of our memory addresses not fitting into integers. So in the early 70s, applications could get away with having a function that returned an address, return it as an integer, and then copy it into a pointer without conversion. And so by like the early 80s, the notion of a void pointer gave us a way to have a generic address, that is, a pointer to something we don't know what type it is. Because all addresses are addresses, but what they point to is different. And so if you take a look at the alloc function, which we'll play a lot more in the next chapter, the alloc says, oh, give me 42 bytes and give it back to me as a pointer. Give me a pointer to 42 new bytes that you just allocated. So if you go in the early 70s, alloc returned an int, but then we would cast it to whatever type we wanted. So we would say alloc 42, it would give us an address, that'd be an integer, but then we'd cast it to an integer star, which is a no loss cast, and then we would store it. By the time in the 1978 CNR book, we tended to call it a char star, because the 42 is how many characters we're going to allocate. And then you would take the pointer to a character and cast it to a pointer to an integer. And so alloc of 42 would give us 14 integers, actually, I think, if I got my multiplication right. But in modern C, we have this pointer, a void pointer, which basically says, look, alloc is going to return an address, and you have to cast it to something. So alloc 42 returns a void star, which is casted to an int star, which is a lossless cast, and not something that's going to confuse the compiler. And then we store it in our int star variable. And so void, everything you'll ever touch will be using void. But I just wanted to give you a little bit of the history of it and why void's kind of not mentioned in this 1978 book. Every time in the class, I'm like, hey, it's time to learn about security. And everybody kind of groans like, oh, no. Back when I taught HTML injection and SQL injection and cross-site scripting in all my previous classes. And here's the classic XKCD where the mom has named their child with a bit of SQL and some single quotes and some comments. And that's all fun. It's important that we as software developers are aware of how the things that we build could be corrupted by those with evil intent, right? So it has come time to talk about that for C. Probably the single worst security hole in all of computing history. From 1950 to today, even before C was a thing, is what's called buffer overflow. And it has to do with the fact that there is no sense that a string of characters has a length. It has an allocated length, but it doesn't have a runtime length. And so when we put more data into a string than can hold the string, it just keeps on storing beyond the end of the string. It doesn't like make a little more space. And so this is from the Wikipedia page where you have an 8-character string followed by a 2-character integer or something. And we copy the string excessive, which is a 9-character, which includes 9 characters and the /0, the 0. And that completely overwrites, by just trying to write into the A string, it overwrites the B variable as well. And so that's buffer overflow. It's sort of like somehow we're going to push too much into this variable so that it extends where it's been allocated and that never is detected, and then it keeps going on. And it means that you can do all kinds of things with buffer overflow. You can change variables, you can like turn on super user permission. Who knows? You got to look at the source code, you got to carefully construct a sort of nasty attack, but the attack vector is the fact that string arrays bounds are not checked when we're copying stuff in. And if you write bad code, or if the system writes bad code, it's just going to go wiping out memory. So it turns out that probably the worst offender of this is the getS function. And this was part of standard C for a long time. And so here what I'm doing is I'm creating a 15 character string array, character array, which is 15 elements. And I'm calling getS. And the problem with getS is like somebody's going to give us that data and it's not us. And then I print it out. So the first thing you see is when I compile a bit of code that has getS, the compiler is upset. I have greatly simplified the errors. It comes out with 3 errors, and this is a subset of one of the errors. The compiler is telling you don't use getS. If you didn't hear what I said the first time, don't use getS. And so the compiler is not happy. But it's like, people write that, so we're going to run it, okay? A.out, which starts the code, as soon as that line getS runs, the runtime of the C standard SDIO.H says, before it prompts us for the data, it actually adds a print statement. It's not our print statement, it's the library saying, you really, really should not be using getS. And if you think this program is trustworthy, you're probably wrong. So I type hello world, which is 11 characters. Hello space world. Yeah, it's 11 characters. Hello world's 11 characters. I type 11 characters in. That includes the 12th character, which is the \0, and that fits into S15, a 15 element string character array in the variable S. So the program works just fine. Then I type A.out again, and it once again tells me, please don't use getS. You're going to be in so much trouble. And now I type instead a bunch of a hello and a bunch of spaces and then world, and it prints out hello, bunch of spaces and world, but it has overwritten all kinds of unknown data after the S15. So that's like 30 or 25 or 30 characters. And the first 15 are in S, but then the next 15 are somewhere else. And S is on the stack because it's an automatic variable in main, and it goes wiping out the rest of the stack. Now it turns out that the C runtime puts things on the stack to kind of mark or to catch this overflow. And so what happens is, as soon as that code finishes, it says abort trap 6, which is basically the C runtime saying, you know what, I'm not going to let this program proceed any further because there has been an array that got messed up. And it's not that it caught the array messing up. It didn't know how long it was. It just put characters in. But what it did is it put something after the array, and then it checked for it later, and that got wiped out. And it's like, okay, you wiped out my magic little secret, and so I'm going to not let you continue. And so we don't want you to use getS, and this is a buffer overflow. And I can give you, eventually maybe we will look at some much more complex examples of this, where we try to use something like getS to manipulate what the program does rather than just blow the program up. But this is a very simple example of buffer overflow. So in summary, pointers are the most beautiful part of C. They're complex, but basically pointers make it so that a high-level language can function like a low-level language. If we don't have pointers, and I mean not even kind of crappy Python ones, I mean pointers that we can look up and then dereference officially and formally and not have it be a sneaky way that we're doing it, that means that you can do the things that operating systems need to do, the kinds of things that we used to write assembly language for, meaning here's a buffer of memory, we're going to copy this buffer, we're going to do another thing, and there's another buffer, and there's a linked list of all the different buffers, So understanding pointers leads you to the path of assembly language, machine language, and then ultimately hardware. So you should not rush through this material. Pointers are really, really important. Everything we're going to do from now on, pointer is I'm just going to say pointer, pointer, pointer. Just like I say object-oriented all the time, I'm going to say pointer all the time. Sections 5.7 and 5.10 through 5.12 are a little dense. So what I really want you to do is understand the stuff I just talked about and the corresponding sections. And chapter 6 will be more fun because we'll be doing much more with the pointers rather than just what is a pointer.
Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective.
Chapter 5, Pointers and Arrays. Before we start Chapter 5, a quick note from your narrator. From time to time, I have been adding some of my interpretation to this book, but I won't be adding anything to this chapter. I think that sections 5.1 through 5.6 contain some of the most elegantly written text in the book. The concepts are clearly stated, and the example code is short, direct, and easy to understand. Pointers are the essential difference between C and any other modern programming language. So pay close attention to this chapter and make sure that you understand it before continuing. This chapter is as strong now as it was in 1978, and so without further ado, we read and listen as Kernighan and Ritchie teach us about pointers and arrays. A pointer is a variable that contains the address of another variable. Pointers are very much used in C, partly because they are sometimes the only way to express a computation, and partly because they usually lead to more compact and efficient code than can be obtained in other ways. Pointers have been lumped with a go-to statement as a marvelous way to create impossible-to-understand programs. This is certainly true when they are used carelessly, and it is easy to create pointers that point somewhere unexpected. With discipline, however, pointers can also be used to achieve clarity and simplicity. This is the aspect that we will try to illustrate. Section 5.1, Pointers and Addresses. Since a pointer contains the address of an object, it is possible to access the object indirectly through the pointer. Suppose that x is a variable, say int, and that px is a pointer, created in some as yet unspecified way. The unary operator ampersand gives the address of an object, so the statement px equals ampersand x semicolon assigns the address of x to the variable px. Px is now said to point to x. The ampersand operator can be applied only to variables and array elements. Construct like ampersand open paren x plus 1 close paren and ampersand 3 are illegal. It is also illegal to take the address of a register variable. The unary operator asterisk treats its operand as the address of the ultimate target and accesses that address to fetch the contents. Thus, if y is also an int, y equals star px semicolon assigns to y the contents of whatever px points to. So the sequence px equals ampersand x semicolon y equals star px semicolon assigns the same value to y as does y equals x. It is also necessary to declare the variables that participate in all of this. Int x comma y semicolon int star px semicolon. The declaration of x and y is what we have seen all along. The declaration of the pointer px is new. Int star px semicolon is intended as a mnemonic. It says that the combination star px is an int. That is, if px occurs in the context star px, it is equivalent to a variable of type int. In effect, the syntax of the declaration for a variable mimics the syntax of expressions in which the variable might appear. This reasoning is useful in all cases involving complicated declarations. For example, double a to f open parenthesis close parenthesis comma star dp semicolon says that in a particular expression a to f open paren close paren and star dp have values of type double. You should also note the implication in the declaration that a pointer is constrained to point to a particular kind of objects. Pointers can occur in expressions. For example, if px points to the integer x, then star px can occur in any context where x could. Y equals star px plus 1 sets y to 1 more than x. Print f, open parenthesis, double quote, %d, \n, double quote, comma, star px, close paren, prints the current value of x. And d equals square root, open paren, double, close paren, star px, close paren, produces in d the square root of x, which is coerced into a double before being passed to square root. In expressions like y equals star px plus 1, the unary operators star and ampersand bind more tightly than arithmetic operators. So this expression takes whatever px points at, adds 1, and assigns it to y. We will return shortly to what y equals star open paren px plus 1 close paren might mean. Pointer references can also occur on the left side of assignments. If px points to x, then star px equals 0 sets x to 0, and star px plus equals 1 increments it, as does open paren star px close paren plus plus. The parentheses are necessary in this last example. Without them, the expression would increment px instead of what it points to, because unary operators like star and plus plus are evaluated right to left. Finally, since pointers are variables, they can be manipulated as other variables can. If py is another pointer to int, then py equals px copies the contents of px into py, thus making py point to whatever px points to. Section 5.2, Pointers and Function Arguments. Since C passes arguments to functions by call by value, there is no direct way for the called function to alter the variable in the calling function. What do you do if you really have to change an ordinary argument? For example, a sorting routine might exchange two out-of-order elements with a function called swap. It's not enough to write swap open parenthesis a comma b close parenthesis semicolon, where the swap function is defined as, and this is sample source code on page 91 of the textbook, and you can see it at www.cc4e.com/code. This is a wrong swap, by the way. This is showing you the code that you're not supposed to do. Swap open paren x comma y close paren int x comma y semicolon open curly brace int temp semicolon temp equals x, x equals y semicolon y equals temp semicolon close curly brace. Because of call by value, swap can't affect the arguments a and b in the routine that called it. Fortunately, there is a way to obtain the desired effect. The calling point program passes pointers to the values to be changed. The call is swap open parenthesis ampersand a comma ampersand b close parenthesis semicolon. Since the operator ampersand gives the address of a variable, ampersand a is a pointer to a. In swap itself, the arguments are declared to be pointers, and the actual operands are accessed through them. So the correct code is on page 92. Swap open paren px comma py close paren int star px comma star py semicolon open curly brace int temp semicolon. Temp equals star px semicolon. Star px equals star py semicolon. Star py equals temp semicolon and close curly brace. One common use of pointer arguments is in functions that must return more than a single value. You might say that swap actually returns two values, the new values of its arguments. As an example, consider a function getInt, which performs a free format input conversion by breaking a stream of characters into integer values, one integer per call. GetInt has to return the value that it found or an end-of-file signal when there is no more input. These values have to be returned as separate objects, for no matter what value is used for EOF, that could also be a value of the integer. One solution, which is based on the input function scanf that we will describe in Chapter 7, is to have getInt return EOF as its function value it finds end of file, and any other return value signals a normal integer. The numeric value of the integer it found is returned through an argument, which then must be a pointer to an integer. This organization separates the end of file status from the returned numeric value. The following loop fills an array with integers by calls to getInt. Int, n, array, open paren size, close paren, semicolon. For n equals 0, n less than size, double ampersand, getInt, open paren, ampersand v, close paren, not equal EOF, semicolon, n plus plus, close parenthesis, array sub n equals v. Each call sets v to the next integer found in the input. Notice that it is essential to write ampersand v instead of v as the argument to getInt. Using plain v is likely to cause an addressing error since getInt believes that it's been handed a valid pointer. GetInt is an obvious modification to a to I, which we wrote earlier. The sample code is on page 93 of the textbook, and you can see this sample code at www.cc4e.com/code. Pound include stdio.h. GetInt, open paren, pn, close paren, int, star pn, semicolon. Open curly brace, int c comma sign. While open paren, c equals get ch, open paren, close paren, double equals, quote, space, quote, or c double equals, quote, backslash n, quote, or c double equals backslash t, quote, close paren, semicolon. This loop we've done before, and it skips the white space. Sign equals 1, semicolon. If open paren c double equals quote plus quote, or c double equals quote minus quote, close paren, open curly brace, sign equals open paren c double equals quote plus quote, close paren, question mark 1 colon minus 1 semicolon. C equals get ch to advance the character, semicolon, and then close curly brace. Those 4 lines record the sign. Now, for star pn equals 0, c greater than or equal to quote 0 quote, and c less than or equal to quote 9 quote, colon, semicolon, c equals get ch, open paren, close curly brace. Star pn equals 10 times star pn plus c minus quote 0 quote. Star pn star equals sign. If open paren c not equal to EOF, close paren, unget ch, open paren c, close paren, semicolon, return c. Throughout getInt, star pn is used as an ordinary int variable. We have also used getch and ungetch as described in Chapter 4, so the one extra character that must be read can be pushed back onto the input. Section 5.3, Pointers and Arrays. In C, there is a strong relationship between pointers and arrays, strong enough that pointers and arrays should really be treated simultaneously. Any operation which can be achieved by array subscripting can also be done with pointers. The pointer version will in general be faster, but at least to the uninitiated, somewhat harder to grasp immediately. The declaration, int a sub 10, defines an array A of size 10 that is a block of 10 consecutive objects named a sub 0, a sub 1, ... a sub 9. The notation a sub I means the element of the array I positions from the beginning. If PA is a pointer to an integer declared as int star PA, then the assignment PA equals ampersand A sub 0 sets PA to point to the 0th element of A. That is, PA contains the address of A sub 0. Now, the assignment x equals star PA will copy the contents of A sub 0 into x. If PA points to a particular element of array A, then by definition, PA points to the next element. No. If PA points to a particular element of an array A, then by definition, PA plus 1 points to the next element. And in general, PA minus I points to I elements before PA, and PA plus I points to I elements after. Thus, if PA points to A sub 0, star, parenthesis, PA plus 1, close parenthesis, refers to the contents of A sub 1. PA plus I is the address of A sub I, and star open paren PA plus I is the contents of A sub I. These remarks are true regardless of the type of the variables in the array A. The definition of adding 1 to a pointer, and by extension all pointer arithmetic, is that the increment is scaled by the size of the storage of the object that is pointed to. Thus, in PA plus I is multiplied by the size of the objects that PA points to before being added to PA. The correspondence between indexing and pointer arithmetic is evidently very close. In fact, a reference to an array is converted by the compiler to a pointer to the beginning of the array. The effect is that the array name is a pointer expression. This has quite a few useful implications. Since the name of an array is a synonym for the location of the 0th element, the assignment PA equals ampersand A sub 0 can also be written as PA equals A. Rather more surprising, at least at first sight, is the fact that a reference to A sub I can also be written as star open paren A plus I close paren. In evaluating A sub I, C converts it to star open paren A plus I close paren immediately. The two forms are completely equivalent. Applying the operator ampersand to both parts of this equivalence, it follows that ampersand A sub I and A plus I are also identical. A plus I is the address of the ith element beyond A. As on the other side of this coin, if PA is a pointer, expressions may use it with a subscript. PA sub I is identical to star open paren PA plus I close paren. In short, any array and index expression can be rewritten as a pointer and an offset, and vice versa, even in the same statement. There is one difference between an array name and a pointer that must be kept in mind. A pointer is a variable, so PA equals A and PA plus plus are sensible operations. But an array name is a constant, not a variable. Constructions like A equals PA or A plus plus or P equals ampersand A are illegal. When an array name is passed to a function, what is passed is the location of the beginning of the array. Within the called function, this argument is a variable, just like any other variable. And so an array name argument is truly a pointer, that is, a variable containing an address. We can use this fact to write a new version of strlen, which computes the length of the string. This sample code is on page 95 of the book, and you can see it in www.cc4e.com/code, page 95. Int sterlen, open paren, s, close paren, char, star s, semicolon, open curly brace, int n semicolon. 4, open parenthesis, n equals 0, semicolon, star s, not equal, quote, backslash 0, quote, semicolon, s plus plus, close paren, n plus plus. Return, open paren, n, close paren, semicolon, close curly brace. Incrementing s is perfectly legal since it's a pointer variable. S++ has no effect on the character string in the function that called sterlen, but merely increments the sterlen's private copy of the address. As the formal parameters in a function definition, char, s, open square bracket, close square bracket, semicolon, and char star s, semicolon, are exactly equivalent. Which one should be written is determined largely by how expressions will be written in the function. When an array name is passed to a function, the function can, at its convenience, believe that it has been handed either an array or a pointer and manipulate it accordingly. It can even use both kinds of operations if it seems appropriate and clear. It is possible to pass part of an array to a function by passing a pointer to the beginning of the subarray. For example, if A is an array, f, open paren, ampersand, a sub 2, close paren, and f, open paren, a plus 2, close paren, both pass to the function f the address of the element a sub 2, because ampersand a sub 2 and a plus 2 are both pointer expressions that refer to the third element of A. Within f, the argument declaration can read f, open paren, array, close paren, int array, open bracket, close bracket, semicolon, ... or f, open paren, array, close paren, int star array, semicolon, ... So far as f is concerned, the fact that the argument really refers to part of a larger array is really of no consequence. Section 5.4, Address Arithmetic. If p is a pointer, then p++ increments p to point to the next element of whatever kind of object p points to. And p plus equals I increments p to the point I elements beyond where it currently does. These and similar constructions are the simplest and most common forms of pointer or address arithmetic. C is consistent and regular in its approach to address arithmetic. Its integration of pointers, arrays, and address arithmetic is one of the major strengths of the language. Let us illustrate some of the properties by writing a rudimentary storage allocator, but useful in spite of its simplicity. There are two routines. Alloc, open paren, n, close paren, returns a pointer p to n consecutive character positions, which can be used by the caller of alloc for storing characters. Free, open paren, p, close paren, releases the storage thus acquired so it can later be reused. These routines are rudimentary because the calls to free must be made in the opposite order to the calls on alloc. That is, storage managed by alloc and free is a stack, or last in, first out. The standard C library provides analogous functions which have no such restrictions, and in Chapter 8 we'll show how improved versions as well. In the meantime, however, many applications really only need a trivial alloc to dispense little pieces of storage of unpredictable sizes at unpredictable times. The simplest implementation is to have alloc hand out pieces of a large character array, which we will call alloc buff. This array is private to alloc and free. Since they deal in pointers and not array indices, no other routine need know the name of the array, which can be declared as external static, that is, local to the source file containing alloc and free and invisible outside it. In practical implementations, the array may well not even have a name. It might be obtained by asking the operating system for a pointer to some unnamed block of storage. The other information needed is how much alloc buff has been used. We use a pointer to the next free element called alloc CP. When alloc is asked for n characters, it checks to see if there is enough room left in alloc buff. If so, alloc returns the current value of alloc p, i.e. the beginning of the free block, and then increments it by n to point to the next free area. Free p merely sets alloc p to p if p is inside alloc buff. This next code example is on page 97 of the textbook. You can see the code at www.cc4e.com/code. Pound include stdio.h. Pound define null 0. It's a pointer value for in the error report. Pound define alloc size 1000, the size of the available space. Static char alloc buff open square bracket alloc size close square bracket semicolon. Static char star alloc p equals alloc buff next free position initialized to the start of the array. Char star alloc open paren n close paren return a pointer to n characters. Int n semicolon open curly brace. If alloc cp plus n less than or equal to alloc buff plus alloc size close paren open curly brace, meaning we have space, alloc cp plus equals n, return alloc cp minus n, close parenthesis, semicolon. Close curly brace. Else, if there's not enough room, return open paren null, close paren, semicolon, close curly brace. Free open paren p close paren. This function will free the storage pointed to by p. Char star p open curly brace. If open paren p greater than or equal to alloc buff and p less than alloc buff plus alloc size, alloc cp equals p, close curly brace. Some explanations. In general, a pointer can be initialized just as any other variable can, though normally only meaningful values are null, discussed below, or an expression involving the address of a previously defined data of the appropriate type. The declaration static char star alloc cp equals alloc buff defines alloc cp to be a character pointer and initializes it to point to alloc buff, which is the next free position when the program starts. This could also have been written static char star alloc cp equals ampersand alloc buff sub 0 semicolon, since the array name is the address of the 0th element, whichever is more natural. The test, if open paren alloc p plus n less than or equal to alloc buff plus alloc size, checks if there's enough room to satisfy a request for n characters. If there is, the new value of alloc p would be at most 1 beyond the end of alloc buff. If the request can be satisfied, alloc returns a normal pointer. Notice the declaration of the function itself. If not, alloc must return some kind of signal that there's no space left. C guarantees that no pointer that validly points to data will ever contain a 0, so a return value of 0 can be used to signal an abnormal event, in this case, no space. We write null instead of 0, however, to indicate more clearly that this is a special value for a pointer. In general, integers cannot be meaningfully assigned to pointers, but 0 is a special case. Tests like if open paren alloc p plus n less than or equal to alloc buff plus alloc size, and if open paren p greater than or equal to alloc buff and p less than alloc buff plus alloc size, shows several important facets of pointer arithmetic. First, pointers may be compared on certain circumstances. If p and q point to members of the same array, then relations like less than, greater than, equal, etc. work properly. P greater than q is true, for example, if p points to an earlier member of the array than q. The relations double equals and not equals exclamation equals also work. Any pointer can be meaningfully compared for equality or inequality with null. But all bets are off if you do arithmetic or comparisons with pointers that point to different arrays. If you're lucky, you get obvious nonsense on all machines. If you're unlucky, your code will work on one machine but collapse mysteriously on another. Second, we've already observed that a pointer and an integer can be added or subtracted. The construction p plus n means the nth object beyond the one p currently points to. This is true regardless of the kind of object p is declared to point at. The compiler scales n according to the size of the objects p points to, which is determined by the declaration of p. For example, on the PDP-11, the factors are 1 for char, 2 for int and short, and 4 for long float and float, and 8 for double. Pointer subtraction is also valid. If p and q point to members of the same array, p minus q is the number of elements between p and q. This fact can be used to write yet another version of strlen. Strlen, open paren s, close paren, char star s, semicolon, open curly brace. Char star p equals s, semicolon, while star p not equal backslash single quote, backslash 0 single quote, close paren, p plus plus, semicolon. Return, open paren, p minus s, close paren, semicolon, close curly brace. In its declaration, p is initialized to s, that is, to point to the first character. In the while loop, each character in turn is examined until backslash 0 at the end is seen. Since backslash 0 is 0, and since while tests only whether the expression is 0, it is possible to omit the explicit test, and such loops are often written as while, open paren, star p, close paren, p plus plus, semicolon. Because p points to characters, p plus plus advances p up to the next character each time, and p minus s gives the number of characters advanced over, that is, the string length. Pointer arithmetic is consistent. If we'd been dealing with floats, which occupy more storage than chars, and if p were a pointer to a float, p plus plus would advance to the next float. Thus, we could write another version of alloc which maintains, say, floats instead of chars, merely by changing char to float throughout alloc and free. All the pointer manipulations automatically take into the account the size of the object pointed to, so nothing else has to be altered. Other than the operations mentioned here, adding or subtracting a pointer in an integer, subtracting or comparing two pointers, all other pointer arithmetic is illegal. It is not permitted to add two pointers, or to multiply, or divide, or shift, or mask them, or add float or double to them. Section 5.5, Character Pointers and Functions. A string constant, written as double quote, I am a string, double quote, is an array of characters. In the internal representation, the compiler terminates the array with the character backslash 0, so programs can find the end. The length in storage is thus one more than the number of characters between the double quotes. Perhaps the most common occurrence of a string constant is arguments to functions, as in printf, open paren, double quote, hello, comma, world, backslash n, double quote. When a character string appears like this in a program, access to it is through a character pointer. What printf receives is a pointer to the character array. Character arrays, of course, need not be function arguments. If message is declared as char star message, then the statement message equals double quote now is the time double quote semicolon assigns message to a pointer to the actual characters. This is not a string copy. Only pointers are involved. C does not provide any operators for processing an entire string of characters as a unit in the language. We will illustrate more aspects of pointers and arrays by studying two useful functions from the standard I/O library to be discussed in Chapter 7. The first function is strcopy, open paren s, t, which copies the string t to the string s. The arguments are written in this order by analogy to assignment, where one would say s equals t to assign t to s. The array version is first. Strcopy, open paren s, t, close paren, char s, open square bracket, close square bracket, comma, t, open square bracket, close square bracket, semicolon, open curly brace, int I, semicolon. I equals 0, semicolon. While, open paren, S sub I equals T sub I, close paren, not equal, quote, \0, quote, close parenthesis, I++, semicolon, close curly brace. You'll note in that while statement that there is a copying of the actual characters as an assignment, and then the side effect of the result of that assignment is compared to the new line, to the end of string, which terminates the while loop. For contrast, here is a version of strcpy with pointers, and this is on page 100 of the textbook, and you can see all the code in the textbook at www.cc4e.com/code. And again, this is example number 2 on page 100. Strcpy, open paren s comma t, close paren, char star s comma star t, semicolon, open curly brace, while, open paren, star s equals star t, close paren, not equal, single quote, \0, single quote, close paren, open curly brace, s plus plus, comma, semicolon, t plus plus, semicolon, close curly brace to end the function. Because the arguments are passed by value, strcpy can use s and t in any way it pleases. Here they are, conveniently initialized pointers, which are marched along the arrays, a character at a time, until the backslash terminates. Then t has been copied to s. In practice, strcpy would not be written as we showed above. A second possibility might be, and this is the third example on page 100 of the textbook. Strcpy, open paren s comma t, close paren, char star s comma star t, semicolon, open curly brace, while paren star s plus plus equals star t plus plus, close paren, not equal, quote, \0, quote, close paren, semicolon, curly brace. This moves the increment in s and t into the test part. The value of star t plus plus is the character that t pointed to before t was incremented. The postfix plus plus doesn't change t until after this character has been fetched. In the same way, the character is stored in the old position of s before s is incremented. The character is also the value that is compared against \0 to control the loop. The net effect is that the characters are copied from t to s up to and including the terminating \0. As the final abbreviation of this solving this problem, we can observe that the comparison against \0 is redundant, so the function is often written as, and now this is the first sample code on page 101 of the textbook. Strcpy, open paren s comma t, close paren, char star s comma star t, semicolon, open curly brace, while, open paren, star s plus plus equals star t plus plus, close paren, semicolon, curly brace. Although this may seem cryptic at first, the notational convenience is considerable, and the idiom should be mastered if for no other reason than you will see it frequently in C programs. The second routine is strcomp, open paren s comma t, which compares the character strings s and t and returns negative, 0, or positive according to as s is lexicographically less than, equal to, or greater than t. The value returned is obtained by subtracting the characters at the first position where s and t disagree. This is the second example on page 101 of the textbook, which you can see at www.cc4e.com/code. Strcomp, open paren s comma t, close paren, char s open square bracket, close square bracket, comma t open square bracket, close square bracket, semicolon, open curly brace, int I semicolon, I equals 0 semicolon, while s sub I double equals t sub I, close paren, open paren, s sub I plus plus double equals single quote \0 single quote close paren, return 0. Return, open paren, s sub I minus t sub I, close paren, semicolon, close curly brace. The pointer version of strcomp is the first example on page 102 of the textbook. Strcomp, open paren s, t, close paren, char star s, star t, open curly brace. For, open paren, semicolon, star s, double equals star t, semicolon, s plus plus, comma, t plus plus, close paren. If, open paren, star s, equal, single quote, backslash 0, single quote, close paren, return, open paren 0, close paren, return, open paren, star s minus star t, close paren, semicolon, close curly brace. Since plus plus and minus minus are either prefix or postfix operators, the combination of star and plus plus and minus minus occur, although less frequently. For example, star plus plus p increments p before fetching the character that p points to. Star minus minus p decrements p first. Section 5.6. Pointers are not integers. You may notice in older C programs a rather cavalier attitude towards copying pointers. It has generally been true that on most machines a pointer may be assigned to an integer and back again without changing it. No scaling or conversion takes place and no bits are lost. Regrettably, this has led to the taking of liberties with routines that return pointers which are then merely passed to other routines. The requisite pointer declarations are often left out. For example, consider the function stir-save, open paren, s, close paren, which copies the string s into a safe place, obtained by a call to alloc, and returns a pointer to it. Properly, this should be written as, this is the first example on page 103 of the textbook. You can see the sample code at www.cc4e.com/code. Pound include stdlib.h. Char star stir save open paren s close paren, save a string somewhere. Char star s semicolon, open curly brace. Char star p star alloc open paren close paren semicolon. If open paren p equals alloc open paren stirlen open paren s close paren plus 1 close paren not equal null close paren stir copy open paren p comma s close paren semicolon, return open paren p close paren semicolon, curly brace. In practice, there would be a strong tendency, mistaken tendency that is, to omit declarations. This is the example 2 on page 103. Pound include stdlib.h, stir save open paren s close paren, open curly brace, char star p semicolon. If parenthesis p equals alloc open paren stirlen open paren s close paren plus 1 close paren not equal null close paren stir copy open paren p comma s close paren semicolon, return open paren p close paren semicolon. This will work on many machines since the default type for functions and arguments is int. An int and pointer can usually be safely assigned back and forth. Nonetheless, this kind of code is inherently risky, for it depends on the details of the implementation and machine architecture, which may not hold for the particular compiler you use. It is wiser to be complete in all declarations. The program lint will warn of such constructions in case they creep in inadvertently.
Section 5.7, Multidimensional Arrays. In general, rectangular multidimensional arrays are used in computational programs like a weather simulation and were a way, back in the day, to write C code that could accept Fortran multidimensional arrays as parameters so that computational or statistical libraries could be written in C. Arrays of pointers are a better mapping to the typical operating system and string manipulation use cases that are more the core of C applications. We also call these ragged arrays because each row can be a different length. This also works well as data is dynamically allocated in C as compared to the more static allocation approach that's typical in Fortran's multidimensional arrays. Now to the textbook. C provides for rectangular multidimensional arrays, although in practice, they tend to be much less used than the arrays of pointers. In this section, we will show some of their properties. Consider the problem of date conversion, from the day of the month to the day of the year and vice versa. For example, March 1st is the 60th day of a non-leap year and 61st day of a leap year. Let us define two functions to do the conversions. Day of year converts month and day to the day of the year, and month day converts the day of the year into the month and the day. Since this latter function returns two values, the month and day arguments will be pointers. Month day, open parenthesis, 1977, comma 60, ampersand m, comma ampersand d, close parenthesis. Sets m to 3 and d to 1, which is March 1st. These functions both need the same information, a table of the number of days in each month, 30 days, half September, etc. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array, rather than try to keep track of what happens in February during computation. The array and the functions performing the transformations are as follows. This is example number 1 on page 104 of the textbook, and you can see the code at www.cc4e.com/code. Static int day tab, open paren 2, close paren, open paren 13, close paren, equals open curly brace, 0, comma 31, and then a number of numbers, close curly brace, comma, open curly brace, 0, comma 31, 29, and then a bunch of numbers, close curly brace, semicolon. Day of the year, open paren year, comma month, comma day, int year, comma month, comma day, semicolon, open curly brace, int I, comma leap, semicolon. Leap equals 0, year modulo 4, double equals 0, and year modulo 100 not equals 0, or year modulo 400 equals 0, semicolon. For open paren I equals 1, I less than month, I plus plus, close paren, day plus equals day tab, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon. Return open paren day, close paren, semicolon, close curly brace. Then the month day function. Month day, open paren year, comma year day, comma p month, comma p day, close paren. Int year, comma year day, star p month, comma star p day, semicolon. Open curly brace. Int I, comma leap, semicolon. Leap equals year percent 4, double equals 0, and year percent 100 not equals 0, or year percent 1400 double equals 0. For I equals 1, year day greater than day tab, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon, I plus plus, close parenthesis. Year day minus equal day tab, open square parenthesis, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon. Star p month equals I, star p day equals year day, semicolon, close paren. The array day tab has to be external to both day of year and month day, so they can both use it. Day tab is the first two-dimensional array we've dealt with. In C, by definition, a two-dimensional array is really a one-dimensional array, each of which elements is also an array. Hence, subscripts are written as day tab, open square bracket I, close square bracket, open square bracket J, close square bracket, rather than day tab, open square bracket I, comma J, close square bracket, as in most languages. Other than this, a two-dimensional array can be treated much the same in the same way as other languages. Elements are stored by rows, that is, the rightmost subscript varies fastest as elements are accessed in storage order. An array is initialized by a list of initializers and braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We started the array datetab with a column of 0 so that month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not a premium here, this is easier than adjusting indices. If a two-dimensional array is to be passed to a function, the argument declaration in the function must include the column dimension. The row dimension is irrelevant since what is passed in, as before, it is a pointer. In this particular case, it's a pointer to objects which are arrays of 13 ints. Thus, the array datetab, if it's to be passed to a function, f, the declaration would be f open paren datetab close paren int datetab open square bracket 2 close square bracket open square bracket 13 close square bracket semicolon open curly brace close curly brace. The argument declaration in f could also be int datetab open square bracket close square bracket open square bracket 13 close square bracket semicolon. Since the number of rows is actually irrelevant, it could also be seen as int open paren star datetab close paren open bracket 13 close bracket semicolon, which says that the argument is a pointer to an array of 13 integers. The parentheses are necessary since the brackets have higher precedence than asterisk. Without parentheses, the declaration int star datetab sub 13 close square bracket semicolon is an array of 13 pointers to integers, as we shall see in the next section. Section 5.8, Pointer Arrays, Pointers to Pointers. Since pointers are variables themselves, you might expect that there would be uses for arrays of pointers. This is indeed the case. Let us illustrate by writing a program that will sort a set of text lines into alphabetic order, then a stripped down version of the Unix utility sort. In Chapter 3, we presented a shell sort function that would sort an array of integers. This same algorithm will work, except that now we have to deal with lines of text which are of different lengths and which, unlike integers, can't be compared or moved in a single operation. We will need a data representation, data structure, that will cope efficiently and conveniently with variable length text lines. This is where an array of pointers enters. If the lines to be sorted are stored end-to-end in one long character array, maintained by ALEC perhaps, then each line can be accessed by a pointer to its first character. The pointers themselves can be stored in an array. Two lines can be compared by passing their pointers to strcomp. When two out-of-order lines have to be swapped or exchanged, the pointers in the pointer array are exchanged, not the text lines themselves. This eliminates the twin problems of complex storage management and high overhead that would go with moving the text of the actual lines. The sorting process involves 3 steps. Read all the lines of input, sort them, and then print them in order. As usual, it's best to divide the program into functions that match this natural division, with the main routine controlling things. Let us defer the sorting step for a moment and concentrate on the data structures and the input and output. The input routine has to collect and save the characters in each line and build an array of pointers to the lines. It will also have to count the number of input lines, since that information is also needed for sorting and printing. Since the input function can only cope with a finite number of input lines, it can return some illegal line count like -1 if too much input is presented. The output routine only has to print the lines in the order in which they appear in the array of pointers. This next code segment is actually a combination of 3 successive sample code segments starting on page 106 of the textbook, and it's pretty complex, so it might be best for you to see them on www.cc4e.com/code, line 106, example 1. Okay. Pound include stdio.h, pound include string.h, pound define lines 100, the maximum lines that's supported, to be sorted. Main, open paren, close paren. Char, line ptr, open square bracket lines, close square bracket, semicolon. Int n lines, which is the number of lines read. If open paren n lines equals read lines, open paren line ptr, comma, lines, close paren greater than or equal to 0,
close paren, open curly brace, sort, open paren, line PTR, comma, end lines, close paren, right lines, open paren, line PTR, comma, end lines, close paren, semicolon, close curly brace, else, printf, open paren, double quote, input too big to sort, \n, close double quote, close paren, semicolon, and close curly brace to end the main program. This next routine is actually from page 107 of the textbook, but we combined them into one. Pound define maxlen 1000. Read lines, open paren, line PTR, comma, max lines, close paren. Char, star, line PTR, open square bracket, close square bracket, semicolon. This is an array of pointers to characters. An array of pointers, pointers being, long, like 4 bytes, characters being generally 1 byte. Int, max line, semicolon, open curly brace. Int, len, comma, end lines, semicolon, char, star p, star, alloc, open paren, close paren, comma, line, open square bracket, max len, close square bracket, semicolon. So just to recall, alloc is a function we did earlier that allows us to allocate some text of a varying length, and then lines of max len is a place that we're going to read each line into. Beginning the code of read lines. End lines equals 0. While open paren, len equals get line, open paren, line, comma, max len, close paren, greater than or equal to 0, close paren. If open paren, end lines greater than or equal to max lines, close paren, return open paren -1, close paren, semicolon. Else if open paren, p equals alloc, open paren, len, close paren, double equals null, close paren, return -1. So those two tests basically make sure that we don't get too many lines and that we have enough space in our dynamic data area that alloc is managing for us. So continuing with the if, we're at the else, open curly brace, line sub len -1 equals quote \0 quote semicolon. Stir copy p comma line close paren semicolon. Line PTR sub n lines plus equals p semicolon. Close curly brace that finishes the else segment. Return n lines semicolon and close curly brace to finish the read lines function. Now, at a high level, we're reading a line into a allocated automatic variable line, and then we are calling alloc to get another place to copy that line. Then we're making a copy of that line, and then we are remembering the pointer to the beginning of that line in line PTR, and that's the essence of it. Okay. Right lines, open paren, line PTR, comma, end lines, close paren, char, star, line PTR, open square bracket, close square bracket, semicolon. Again, an array of pointer characters, int end lines, semicolon, which is the number of character pointers in line PTR. Open curly brace, int I, semicolon. For paren I equals 0, semicolon, I less than n lines, semicolon, I plus, close paren, printf, open paren, double quote, %s \n, double quote, comma, line PTR sub I, close paren, semicolon, close curly brace. A simple loop that goes through the array of character pointers and then prints each one out using printf. The main new thing is the declaration for line PTR, char, star line PTR sub, open square bracket, lines, close square bracket, semicolon. It says that line PTR is an array of lines elements, each element of which is a pointer to a char. That is, line PTR sub I is a character pointer, and star line PTR sub I accesses a character. Since line PTR itself is an array that was passed to right lines, it can be treated as a pointer exactly in the same manner as our earlier examples, and the function can be written instead as right lines, open paren, line PTR, comma, n lines, close paren, char, star line PTR, open square bracket, close square bracket, semicolon, int n line, semicolon, open curly brace, while, open paren, minus minus n lines greater than or equal to 0, close paren, printf, open paren, double quote, %s backslash n, double quote, comma, star, line PTR plus plus, close paren, semicolon. That code, by the way, was on page 108, example 1 of the textbook. Star line PTR points initially to the first line, but each increment of line PTR advances it to the next line while n lines is counted down. With input and output under control, we can proceed to sorting. The shell sort from chapter 3 needs minor changes. The declarations have to be modified, and the comparison operation must be moved into a function. But the basic algorithm remains the same, which gives us some confidence that it will still work. And this is the second example on page 108 of the textbook, and you can see this example at www.cc4e.com/code. Sort, open paren, v, comma, n, close paren. Char, star v, open square bracket, close square bracket, semicolon, int n, semicolon, open curly brace. So we're getting an array of pointers to the beginnings of lines, and how many of those pointers matter. And the rest of it is shell sort, with the strcomp being used to do the string comparison. So it's a 3-nested for loop with a simple if test in it. So here we go. Open curly brace for the sort function. Int gap, comma, I, comma, j, semicolon, char, star, temp, semicolon. And that's a pointer to a character. For open paren gap equals n over 2 semicolon, gap greater than 0, semicolon, gap slash equals 2, close parenthesis. For I equals gap, semicolon, I less than n, semicolon, I plus plus, close parenthesis. For open paren j equals I minus gap, semicolon, j greater than or equal to 0, semicolon, j minus equals gap, close paren, open curly brace. So that's sort of the shell part of the shell sort. And now we have to do our comparison. If open paren strcomp, open paren v sub j, comma, v sub j plus gap, close paren, less than or equal to 0, close paren, break. And note that that's only breaking the third deep for loop, which it just goes and then runs the next iteration of the second for loop. Now we do the swapping. Temp equals v sub j, semicolon, v sub j equals a v sub j plus gap, semicolon, v sub j plus gap equals temp. Now that's just swapping pointer values. So the strings that are pointed to by these two pointers, v sub j and v sub j plus gap, if they're out of order, we're going to swap the pointers in the array and move them so that if you then go through like we did in write lines earlier, then they come out in order. But we literally read the data once, we copy it once into its final destination using alloc and strcopy, but once we sort it, which is the most complex part of the calculation, we're only moving the pointers back and forth. So this sort is very efficient and requires no extra memory than what we had before the sort. So that's really nice, and it sorts in place. So back to the text. Since any individual element of v, which is an alias to line pointer, PTR, is a character pointer, temp should also be one, so one can be copied to the other. We wrote the program about as straightforwardly as possible so as to get it working quickly. It might be faster, for instance, to copy the incoming lines directly into an array made by readlines rather than copying them into line and then to a hidden place maintained by alloc. But it's wiser to make the first draft of something easy to understand and worry about efficiency later. The way to make this program significantly faster is probably not by avoiding an unnecessary copy of the input lines, just instead replacing the shell sort by something quicker and better, like quicksort, is much more likely to make a real difference that matters. In Chapter 1, we pointed out that because while and for loops test the termination condition before executing the loop body even once, they help to ensure that the programs will work at their boundaries, in particular with no input. It's illuminating to walk through the functions of the sorting program, checking what happens if there is no input text at all. Section 5.9, Initialization of Pointer Arrays. Consider the problem of writing a function month name, open paren and close paren, which returns a pointer to a character string containing the name of the nth month. This is an ideal application for an internal static array. Month name contains a private array of character strings and returns a pointer to the proper one when called. The topic of this section is how that array of names is initialized. The syntax is quite similar to the previous initializations. This is sample code from page 109 of the textbook, which you can see at www.cc4e.com/code. char star month name open paren close paren. So the return value for this function is a character pointer. Int n semicolon open curly brace. Static char star name open square bracket close square bracket equals open curly brace. Quote illegal month quote comma double quote January double quote comma double quote February double quote comma and so forth down to double quote December double quote close curly brace semicolon. The body of the function is one line. Return open paren n less than 1 or n greater than 12 close paren question mark name sub 0 colon name sub n close paren semicolon close curly brace. The declaration of name, which is an array of character pointers, is the same as line PTR in the sorting example. The initializer is simply a list of character strings, each assigned to the corresponding position in the array. More precisely, the characters of the ith string are placed somewhere else, and a pointer to them is stored in name sub I. Since the size of the array name is not specified, the compiler itself counts the initializers and fills in the correct number. Section 5.10, Pointers versus Multidimensional Arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as name in the example above. Given the declarations int a open square bracket 10 close square bracket open square bracket 10 close square bracket semicolon and int star b open square bracket 10 close square bracket semicolon, the usage of a and b may be similar in that a sub 55 and b sub 55 are both legal references to a single integer. But a is a true array. All 100 storage cells have been allocated, and the conventional rectangular subscript calculation is done to find any given element. For b, however, the declaration only allocates 10 pointers. Each must be set to point to an array of integers. Assuming that each does point to a 10-element array, then there will be 100 storage cells set aside, plus the 10 cells for the pointers. Thus, the array of pointers uses slightly more space and may require an explicit initialization step. But it has two advantages. Accessing an element is done by indirection through a pointer rather than by a multiplication and an addition, and the rows of the array may be of different lengths. That is, each element of B need not point to a 10-element vector. Some may point to 2 elements, others may point to 20, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is like that shown in month name, to store character strings of diverse lengths. Section 5.11, Command Line Arguments. In environments that support C, there is a way to pass command line arguments or parameters to a program when it begins executing. When main is called to begin execution, it is called with 2 arguments. The first, conventionally called argc, is the number of command line arguments the program was invoked with. The second, argv, is a pointer to an array of character strings that contain the arguments, 1 per string. Manipulating these character strings is a common use of multiple levels of pointers.
I would note that back in 1978, the two largest bodies of C code were likely the AT&T Unix kernel itself and Unix utilities like grep, ls, or the login shell. So writing an operating system was fresh on the mind of the authors while writing this book. These topics find their way into the text of this book. In a sense, a likely second-order goal of the book was to train programmers that might learn C and then might help build and maintain Unix. The 1978 edition of this textbook fits nicely into a series of AT&T Bell Labs technical reports like The Portability of C Programs in the Unix System, written by Stephen C. Johnson and Dennis M. Ritchie, published in the Bell System Technical Journal, Volume 57, Number 6, Part 2, July through August 1978, pages 2021 through 2048. You can see this one online if you search for it. Back to the textbook. The simplest illustration of the necessary declarations and use is in the program echo, which simply echoes its command line arguments in a single line separated by blanks. That is, if the command echo hello, world is given, the output is hello, world. By convention, argv sub 0 is the name by which the program was invoked, so argc is at least 1. In the above example, argc is 3, and argv sub 0, argv sub 1, and argv sub 2 are echo, hello, and world, respectively. The first real argument is argv sub 1, and the last is argv sub argc minus 1. And if argc is 1, there are no command line arguments after the program name. This is shown in the source code to echo. And this source code is on page 111 of the textbook, and you can see this source code at www.cc4e.com/code. Pound include stdio.h. Pound include string.h. Main open paren argc, argv, close paren. Int argc semicolon. Char star argv, open square bracket, close square bracket, semicolon. Open curly brace. Int I semicolon. For open paren I equals 1 semicolon I less than argc semicolon I plus plus close paren. Printf open paren double quote %s %c double quote comma argv sub I comma open paren I less than argc minus 1 close paren question mark single quote space single quote colon single quotes \n single quote close parenthesis semicolon close curly brace to end it. Since argv is a pointer to an array of pointers, there are several ways to write this program that involve manipulating the pointer rather than indexing an array. Let us show two variations, and this is the example number 2 on page 111 of the textbook. Pound include stdio.h, pound include string.h, main open paren argc, argv, close paren, int argc semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace. While open paren minus minus argc greater than 0, close paren, printf open paren double quote %s %c double quote comma star plus plus argv comma open paren argc greater than 1 close paren question mark single quote space single quote colon single quote \n single quote close paren semicolon close curly brace. Since argv is a pointer to the beginning of an array of argument strings, incrementing it by 1 plus plus argv makes it point to at the original array argv sub 1 instead of argv sub 0. Each successive increment moves it along to the next argument. Star argv is then the pointer to that argument. At the same time, argc is decremented, and when it becomes 0, there are no arguments left to print. Another version, the third version on page 111 of the textbook. Pound include stdio.h, pound include string.h, main open paren argc, argv, close paren, int argc semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace. While
open paren, minus minus argc greater than 0, close paren. Printf, open paren, argc greater than 1, close paren, question mark, double quote, %s blank, double quote, colon, double quote, %s backslash n, double quote, comma, star plus plus, argv, close paren, semicolon, close curly brace. This version shows that the format argument of printf can be an expression just like any of the others. This usage is not very frequent, but worth remembering. As a second example, let's make some enhancements to the pattern finding program from Chapter 4. If you recall, we wired the search pattern deep into the program, and this is an obviously unsatisfactory arrangement for flexible code. Following the lead of the Unix utility grep, which stands for the Generalized Regular Expression Parser, let us change the program so that the pattern to be matched is specified by the first argument on the command line. This is example 1 on page 112 of the book, which you can see at www.cc4e.com/code. Pound include stdio.h, pound include string.h, pound define max line 1000, main, open paren, argc, comma, argv, close paren, int argc, semicolon, char star argv, open square bracket, close square bracket, semicolon, open curly brace. Char line, open square bracket, max line, close square bracket, semicolon. If, open paren, argc, not equal to, close paren, printf, double quote, usage, colon, find pattern, backslash n, double quote, close paren, semicolon. Else, while, open paren, get line, open paren, line, comma, max line, close paren, greater than 0, close paren, if index, open paren, line, comma, argv, sub 1, close paren, greater than or equal to 0, close paren, printf, open paren, double quote, %s, double quote, comma, line, close paren, semicolon, close curly brace. The basic model can now be elaborated to illustrate further pointer constructions. Suppose we want to allow 2 optional arguments. One says print all the lines except those that match the pattern. The second says precede each printed line with its line number. A common convention for C programs is that an argument beginning with a minus sign introduces an optional flag or parameter. If we choose -x for except to signal the inversion and -n number to request line numbering, then the command find space -x space -n the with the input now is the time for all good men to come to the aid of their party should produce 2, for all good men. Optional arguments should be permitted in any order, and the rest of the program should be insensitive to the number of arguments which were actually present. In particular, the call to index should not refer to argv sub 2, where a single flag argument, and to argv sub 1, when there was no single flag. Furthermore, it's convenient for users if option arguments can be concatenated and, as in find space -nx space the. Here is the program. And this program is on page 113 of the textbook. And it is complex enough that I suggest that you take a look at it at www.cc4e.com/code. It's about 35 lines long. The commentary on the program, hopefully now you're looking at it. argv is incremented before each optional argument, and argc is decremented. If there are no errors at the end of the loop, argc should be 1, and star argv should point to the pattern. Note that star plus plus argv is a pointer to an argument string. Open paren, star plus plus argv, close paren, open square bracket, 0 square bracket, is its first character. The parentheses are necessary, for without them, the expression would be star plus plus, open paren, argv sub 0, close paren, which is quite different and wrong. An alternate valid form would be star star plus plus argv. Section 5.12, pointers to functions. In C, a function itself is not a variable, but it is possible to define a pointer to a function. which can be manipulated, passed to functions, placed in arrays, and so on. We will illustrate this by modifying the sorting procedure written earlier in this chapter so that if the optional argument -n is given, it will sort the input lines numerically instead of lexigraphically. A sort often consists of three parts: a comparison, which determines the ordering of any pair of objects, an exchange, which reverses their order, and a sorting algorithm, which makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations. So by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. This approach is taken in our new sort. The lexicographic comparison of the two lines is done by strcomp and swapping by swap as before. We'll also need a routine numcomp, which compares two lines on the basis of numeric value and returns the same kind of condition indication as strcomp does. These three functions are declared in main, and pointers to them are passed to sort. Sort, in turn, calls the functions via pointers. We have skimped on error processing for arguments so as to concentrate on the main issues. This sample code is from page 115 of the textbook, which you can view at www.cc4e.com/code. Pound include stdio.h, pound include string.h, pound define lines 100. Main, open paren, argc, argv, close paren. Int, argc, semicolon. Char, star, argv, open square bracket, close square bracket, semicolon. Open curly brace. Char, star, line, ptr, open bracket, lines, close square bracket, semicolon. This is the pointers to the text lines. So we're going to be reading in the lines, saving them, and keeping an array of the pointer, and then we're going to sort that way. Int, nlines, semicolon. Int, strcomp, open paren, close paren, comma numcomp, open paren, close paren, which are comparison functions. Int swap, open paren, close paren, semicolon. Int numeric equals 0, and this is going to be 1 if it's a numeric sort. First, we parse the arguments. If open paren argc greater than 1, ampersand, ampersand, argv sub 1 sub 0 equal, quote minus quote, and argv open bracket 1 close bracket, open bracket 1 close bracket, double equals quote and quote, close paren, numeric equals 1. If open paren, nlines equals read lines, open paren, line ptr, comma lines, close paren, greater than or equal to 0, close paren, open curly brace. If open paren, numeric, close paren, sort, open paren, line ptr, nlines, numcomp, comma swap, close paren, semicolon. Else, sort, open paren, line ptr, comma nlines, comma strcomp, comma swap, close paren. Right lines, line ptr, comma nlines, close paren. Close curly brace. Else, printf, open paren, double quote, input too big to sort, \n, double quote, close paren, semicolon. Strcomp, numcomp, and swap are addresses of functions. Since they're known to be functions, the ampersand operator is not necessary, in the same way that it is not needed before an array name. The compiler arranges for the address of the function to be passed. The second step is to modify our sort function, and this is the first example on page 116 of the textbook. Sort, open paren, v, comma n, comma comp, comma exch, exchange, close paren. Char, star v, open square bracket, close square bracket, semicolon. That's our pointer array of pointers. Int, n, semicolon. Int, open paren, star comp, close paren, open paren, close paren, comma, open paren, star exchange, close paren, open paren, close paren, semicolon. That declared the type and the fact that these are pointers to functions. It's a little more complex here in the call to code. Open curly brace. Int gap, comma I, comma j, semicolon. And now we're going to do the 3 nested for loops for the shell sort. And then the only really change is in the code, checking to see if the pair of items are out of order, and then what we do. So for open paren gap equals n over 2, semicolon, gap greater than 0, semicolon, gap slash equals 2, close paren. For open paren I equals gap, semicolon, I less than n, semicolon, I plus plus, close paren. For open paren j equals I minus gap, semicolon, j greater than or equal to 0, semicolon, j minus equals gap, close paren, open curly brace. And now here starts the different code. If open paren star comp, close paren, open paren v sub j, comma, v sub j plus gap, close paren less than or equal to 0, close paren, break. Open paren star ex exchange, close paren, open paren ampersand v sub j, comma, ampersand v sub j plus gap, close paren, semicolon, close curly brace for the for loop, and then close curly brace for the sort function. And so really all we're doing is we're checking the order of the two items, v sub j and v sub j plus gap, and if they're out of order, i.e. less than or equal to 0, greater than or equal to greater than 0, then we just exchange them with the provided exchange function. And so the key thing here is it looks exactly like the previous time we wrote this code, except we're calling the pointer to the comparison function and the pointer to the exchange function, which makes this flexible so it can handle different kinds of data. Back to the textbook. The declaration should be studied with some care. Int open paren star comp close paren open paren close paren says that comp is a pointer to a function that returns an int. The first set of parentheses are necessary. Without them, int star comp open paren close paren would say that comp is a function returning a pointer to an int, which is a quite different thing. The use of comp in the line if open paren star comp close paren open paren v sub j, comma, v sub j plus gap, close paren, less than or equal to 0, close paren, is consistent with the declaration. Comp is a pointer to the function, and star comp is the function. And open paren star comp close paren open paren v sub j, comma, v sub j plus gap, close paren, is the call to it. The parentheses are needed so the components are correctly associated. We've already shown strcomp, which compares two strings. Here is numcomp, which compares two strings on a leading numeric value. This is sample code from page 117 of the textbook, which you can see at www.cc4e.com/code. Numcomp, open paren s1, comma, s2, close paren, char star s1, comma, star s2, semicolon, open curly brace, double, a to f, open paren, close paren, comma, v1, comma, v2. v1 equals a to f, open paren, s1, close paren, semicolon. v2 equals a to f, open paren, s2, close paren, semicolon. If open paren v1 less than v2, close paren, return open paren minus 1. Else if open paren v1 greater than v2, close paren, return open paren 1, close paren, semicolon. Else return open paren 0, close paren, semicolon, close curly brace. The final step is to add the function swap, which exchanges the two pointers. This is adapted directly from what we presented earlier in the chapter. Swap open paren px, comma, py, close paren, char star px, open square bracket, close square bracket, comma, star py, open square bracket, close square bracket, semicolon. Open curly brace, char star temp, semicolon. Temp equals star px, semicolon, star px equals star py, semicolon, star py equals temp, semicolon, close curly brace. There are a variety of other options that can be added to the sorting program. Some make challenging exercises.
This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T. but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.
So hello, welcome to Chapter 6. In this chapter we talk about structures, but so much more. There is a mid-chapter surprise in this book, and I'm sure that it's so surprising that it's caused a few too many people to drop out of computer science, first computer science course. And that's because in sections 6.1 through 6.4, we're learning the C language. And we're learning just what a structure is. It's a simple, beautiful, elegant concept. It's a sort of a wrapper for a whole bunch of types. It groups them together so that you can create a new type. And it really, at this point, is the last foundational component of the core C language. And then in section 6.5, the authors pivot to talking about data structures, and that is the applications of C structures. And it's the foundational notion in computer science. It's the kind of thing where how do you build a Python dictionary in C? And so this is a pattern we call the knee of the curve, where things are going along just fine up to 6.4. Like, oh, here's a for loop, and here's a string, and here's an array. And here's even a pointer. That's not that hard. And structures are not that hard. But then when we start talking about applications of structures, what we call data structures. And structures was named because data structures was a concept. But how we use structures is quite a next level thing. We're kind of leveling up. So I want you, starting from here, Chapter 6 is the last real chapter that I'm going to cover. But it is expanding, because Chapter 6 is the beginning of a whole additional course, a course on data structures. So I want you, if you're rushing, I want you to slow down. I want you to take your time and understand, because if you understand this, you have a doorway into a lot of computer science. We'll talk about recursion even by the end. And so just don't rush. Work on mastery. These are complex concepts. They are not natural to understand. And so before we start, I want to do something different. I want to read you a poem. One of my favorite poems from Robert Frost. I was fortunate enough to be a good friend of Bob Frost, who was a grandson of Robert Frost. Bob Frost had a connection to the University of Michigan. Robert Frost has a Michigan and University of Michigan connection. And I loved this poem that I'm about to read you long before I met Bob Frost, the grandson of Robert Frost. So, the poem that I talk a lot about, and really it's one line: miles to go before I sleep. This is the poem called Stopping by the Woods on a Snowy Evening. And to me, it speaks of the notion that journeys are not short nor easy, and it's okay. Accept that. So here we go. Dr. Chuck in poetry. Whose woods these are, I think I know. His house is in the village, though. He will not see me stopping here to watch his woods fill up with snow. My little horse must think it queer to stop without a farmhouse near, between the woods and frozen lake, the darkest evening of the year. He gives his harness bells a shake to ask if there is some mistake. The only other sounds the sweep of easy wind and downy flake. The woods are lovely, dark and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. So the essence of this is that you have come a long way to get to 6.4 in this book, and it may feel like you've gone long enough and you should just pat yourself on the back. But after 6.4, there are miles to go before I sleep. But the good news is, when you're done, you can relax. So what I want you to do is take your time. Things get much more complex really fast going forward, and I don't want to lose you. Structures. Structures is one of the most beautiful parts of C, like pointers. It's a user-defined type that contains sort of one or more types within it. We call things like X and Y, in this case, members of the structure. X is a member of the struct point, and Y is a member of the struct point. The dot operator allows us to take a variable that is a structure variable that has all these members within it, and then access the members of the structure. So an example, kr0601.c, we have struct point, open curly brace, double x semicolon, double y semicolon, close curly brace semicolon. And this defines a new type. It doesn't allocate any data. And then we say struct point p1 comma p2 semicolon, and that actually allocates 2 points, which is 4 doubles, named p1 and 2 of each point is p1 and p2. Then I say p1.x equals 3.0, and I say p1.y equals 4.0, and then I say p2 equals p1, which copies all the fields into the corresponding locations in p2, and then I print them out, and I get 3 and 4. And so that's basic structures. Simple, clean, elegant. Understand every line of this, memorize it. When you do a, in a sense, call by value with a structure, the entire structure is placed on the stack. And so you don't want to make structures too gigantically big. You know, if they're like 10 to 40 bytes of characters, they're not all that bad. But when we make struct point PM and set x and y to 3 and 4, and then we call func with func open paren PM close paren, PM is a structure that is in the scope of the main program, and then we're calling func and passing it in, and then we're accepting it as a structure inside of func. And the key thing there is, at this point, it's a sort of copy of a call by value where the entire structure is allocated on the stack and then passed into func. So if we change it inside func, pf.x equals 9.0 and pf.y equals 8.0, it changes locally, and we can print it out, and then when it returns, the PM that's in the main program is unchanged. And that's because the entire structure, PM, is duplicated into the stack frame for function func. Operating inside function func, we're only messing with the copy that's in our stack frame. And then when we sort of undo that, it restores PM back to the way it was. So those are just plain structures, but pointers to structures are where we get a lot more powerful. So here we have a same struct with a double x and a double y. And now we say struct point PT, which is a regular old variable, and then star PP, which is a pointer to a structure, an address of a structure. And you can take the address of a structure just like you can take the address of an integer. A structure is a very fundamental type. So PP equals ampersand PT copies the address of the actual structure PT into the variable PP. PT.x equals 3.0, or open paren star pp close paren dot y equals 4.0. So if we have a pointer to a structure, we have to use the asterisk to sort of look up the actual structure, and then we can do structure things with it, like set the .y value. There's a shortcut: take an address, dereference it with the asterisk, and then use the dot. They're combined into kind of what we call the arrow operator, which is pp dash greater than y, which is the same as open paren star pp close paren dot x. And so this, we call it the arrow operator, and so it's kind of a shorthand, and it's used all the time. And you'll see when we look later at things like PHP, they adopted this arrow operator. Most other object-oriented languages tend to use the dot operator, but others use the arrow operator. So if we're going to pass a structure by reference, you use the ampersand in the call and the asterisk inside the function. So we create struct point PM, set x and y within that to 3 and 4 respectively. Then we print it out, and then we call func, but now we call it with ampersand PM, which says pass in the address of PM. And then in the function, we take in pp, and we declare its type as struct point star pp, which means we're getting as a parameter an address, not the value. And then we use the arrow operator, pp arrow x equals 9, pp arrow y equals 8. We print that in the function, but because pp just points to PM, it's also changed in the copy that's in the main. So PM is being changed at the moment that pp is being changed. And so when it comes back, you see that the value is 9 and 8 outside of the function. So this is simply passing by reference. It almost would be better to call it pass by address. So if you take a look at the stack frame, what you see is when we're calling func open paren ampersand PM close paren, we are making a copy of the address and putting that into the stack frame, and then passing that stack frame into func. And so now func has an address of something. It happens to not be in its domain, meaning that PM is still in main, but we can work with the arrow operator and actually make changes in the underlying object. And so the key there is that you could change pp, but pp arrow x, you're actually changing the single copy that is in PM at that point. Storage allocation. Now, pretty soon we're going to be dynamically allocating things. We've always said that, oh, you create a char array of char with open bracket 10. There's 10 things in that. What if we want more? And we've said you can't reallocate this stuff. But now we have this thing we're going to start allocating. So it turns out when you're allocating things, you have to know how big they are. Okay, and so there's this size of operator. So size of, so if we take struct point pt and star pp, which means we have a structure with 2 doubles in it, and then a pointer to a structure with 2 doubles of it, and we simply say, what is the size of the structure? And it's 16, because each double is 8. And then what is the size of a pointer to a structure? And that is 8, because 8 is how big addresses are. The fact that doubles and addresses happen to both be the same thing is not relevant here. Addresses are, on most C systems, 8 characters. You can also, because it's an operator, not just give it a variable, but also give it a type. So we can say size of open paren struct point close paren, and that also will be 16, because the size of a struct, if we were going to allocate it, is 16 characters. So size of returns the size of something in characters. And so we have this function called malloc. And malloc, you have to include stdlib.h to do it. And so now what we're going to do is create the structure point again, and we're going to create a pointer. And we're going to not actually allocate it, so that struct point star pp allocates an 8-character address, not the actual double 2 doubles. Now what we do is we say pp equals, first, and we're casting this, we're casting the returned address from malloc, paren struct point star paren, close paren, that is casting it to a pointer to a struct, a pointer to a point, and then we say malloc open paren size of struct point close paren, and so that says malloc 16, because a struct point is 16 characters. So malloc goes and finds some free memory for us in its pool of free memory and gives us back an address, which we then convert to a pointer to a point, and then we store that in pp. And at that point we have data. We have a working structure, and we can set the X and the Y value just as the normal way. Whether we use the arrow operator or the star and dot operators, we can access that information. The next thing we're going to talk about is combining all these things, dynamic memory and structures, to create lists. And this is a simple Python program. Lines equals list, hand equals open paren romeo.txt, then loop through and then append each line after stripping the new lines, and then printing them out. So lines is a list object. Now underneath it, there is a data structure, which by the end of this course you're going to get to know really well. But this will print out the 4 lines from romeo.txt, and this is kr0607.py. Now we're going to build this list structure, and then we can store some data in it. The entries of the list are going to be stored in dynamically allocated memory, and each list contains some data and then links to other members. And so we're going to create a thing called struct lnode, open paren char star text, which is a pointer to a list, an array of characters of unknown length, struct lnode star next semicolon, close curly brace semicolon. And so if you construct a real live linked list, you need also to have 2 variables, struct lnode star head and struct lnode star tail. And if we end up with a linked list of 3 things, head points to the first item in the list, and then within that there is the text. The text points to some string, in this case it's the letter C, and then the next is an address of the second thing in the list. In that second thing, text points to is, and next points to the third thing in the list. And then next and the third thing in the list points to a value called null, which is our indication that it's an address to nowhere. Null and 0 are pretty much the same thing. All addresses are non-zero, so we look for an address of 0, and that tells us that we've got to the end. And then in order to append to this list, we have another value, which is a pointer called tail, which points to the last element in the list. When we start the list, head and tail both point to null. And so ultimately what we've done is we've created a dynamically allocable structure where we can put sort of any number of lines in it. And so it's kind of like a Python list. So the first line of this, the while statement, reads a value into line, a string value into line, the next line from the file, right? And so we have a pointer to a character that we pre-allocated above this, and that points to the variable fun, 3 characters plus an end of string. And then the next thing we're going to do is allocate a new string that is the same length plus 1. So we're going to allocate 4 characters using malloc. Sterlen line plus 1, which is going to give us 4. Then we're going to get that address back, and we're going to cast that to a char star, and then we are going to assign that to save. So that's the place we're going to save this new item. The next thing we're going to do is allocate a brand new L node, a brand new node in our list, and we're going to malloc size of struct L node, and then we're going to cast it to a struct L node star, and then we're going to assign that into a struct L node star variable named new. We saved our string, and we've got a pointer to that saved string and a pointer to a empty at this point L node. Then what we do is we connect with if tail is not equal to null, tail next equals new. So we take the about to be second to last item, and we connect it to the last item. And then what we do is we take the text pointer inside of our newly allocated list node and point it at the saved copy of our string in dynamic memory. And then we point the next to be null, and then we simply advance tail so that next time we do this, tail is pointing to the new end of the string. Now we've got one more thing that we've got to do, and that is if head is null, we have to set head to new. That's only going to happen on the very first one. And so at this point, our list has 3 entries. It went from 2 entries to 3 entries. And so we can go back up and read the next line, and this sequence of statements will figure it out. So I would just say, take your time on this. One thing that we learn when we're working on linked data structures inside of C is you got to draw a picture. I literally can't do this from memory. I just draw the picture and then it's really easy to do. So sometimes you want to walk through a linked list. So we tend to call this, we make a variable called current, which is a struct L node star, a pointer to an L node. And so this is the same as looping through a Python list. We set current to head because that's where we're going to start going through the list. And then we print out current text, which prints C out. And then we go to the bottom of the loop and then we advance current to current next. It's kind of like adding +1, but we just went from the first item in the list to the second item in the list. And then we do it again, and we are printing out the third item of the list, and then current equals current next gets to null. And so then the list is over, and we have printed all of them out. So in addition to creating linked lists, we're going to do many different things with linked lists. We're going to delete things, we're going to sort things, we're going to find things, we're going to look things up, we're going to change things. So one of the things that will save you a lot of craziness when working with linked lists is always draw pictures and arrows. It's just necessary. And frankly, those programming exams, all they ever tell you is to draw these pictures sometimes. Draw a picture of a hash map as a good example. So I'm just going to show you some pictures rather than showing you a bunch of code, and then I think you can produce the code later. So I want to show you how you delete an item from a singly linked list. So first you got to find it. You got to do the walking of the linked list, which I just showed you. You got to walk through and you got to find the item that you want to delete. Now if you walk through and you don't find it, there's nothing to delete. So our goal is to delete the line is. And so, but you got to handle three cases. There's the easy one, which is where the thing you found is in the middle of the list, or if the thing that you found is at the start of the list, or if the thing you found is the last item in the list. And again, you got to draw pictures, and you may have to draw them separately because we're going to be adjusting head and tail in addition to the next values. Now it turns out when you're going to do a delete, you want to not only track the current item in the list, you want to track the previous item in the list. So as you're walking down the list, current moves ahead and prev moves right behind it. So prev trails current by one item. You can see that current, the is line, is the one we're going to delete. And it's pretty simple. The only real thing that you've got to change is you take prev next and you point it at cur next, right? So you can see on the right hand side that the little link from the C to the fun has just bypassed the is. Now you do have to deallocate the struct L node and the string, but that's pretty much all you need to do. And so the middle is really easy. You find it, you keep track of prev, you have current, and then you just kind of bypass it by moving next. So that's the easy one. The next thing that you got to do is what if it's the first node? And in this case, prev will point at null because we have not really seen more than one. Prev only goes non-null when we've passed the first one. So current is pointing at head. Let's say we want to delete the line that says C. And so we notice that prev is null. And so what we do is we actually just move the head to cur next. Right? You can see on the right hand, the head just points. Now the head is now bypassed that first line. And that's all we've got to do except clean up the memory of the first entry, both the string and the struct L node. So that's pretty easy. You detect that by noticing that prev is null because you're catching it in the first time through the loop, and prev trails current by one, and if you have not seen the second one, prev is still null. So that's a pretty easy one. But you got to check it. You got to check all. So this one is if prev is null, you're sitting at the front, so you mess with head, and that's all you've got to do other than get rid of the data and free it up. The last node is perhaps a little bit trickier. And so if you look, and how you know you're on the last node is cur next is null, right? Because if you're pointing at the very last node in the list, then the next is null. So if cur next is null, then what you're doing is you know you're deleting the last one. And so you first set prev next to be null, because that's the new last one, and then you have to update tail to point to prev. So tail was pointing at cur, at the current, and then tail at the end points to prev, and then you got to clean up your data of that formerly last item in the list. So now we're going to talk about doubly linked lists. And the main purpose to have doubly linked lists is to be able to reverse a list. Python is easy. There's a method in the list object called reverse. What we're about to see is exactly how reverse works. So you just read the lines in and you say lines.reverse, and then you print them out and they come out in backwards order. Now, somebody, probably Guido van Rossum, who wrote this in the first place in 1991, he's writing a doubly linked list to make reverse easy. So if you remember how we did the deleting where we kept track of prev, well, in a doubly linked list, we actually just have prev in the L node. And so in addition to the text we're going to store, we're going to have a prev pointer and a next pointer. And at the beginning of the list, the prev will be null, and at the end of the list, next will be null. It's called a doubly linked list because it has both reverse and forward chains of pointers, and we keep them working all the time. So it turns out that making a doubly linked list in terms of code is not that different. We have another thing in the L node. We now have three things, struct L node star prev. And as we're linking a new thing onto the end of the list, we basically take new prev, the new item we're adding, and we copy tail into that because tail points to the last one. We're adding a new one to the last one, and the previous one is tail. And then we do that before we set tail to new. So we add a new one, and then we set tail to new. So it's not that hard. So this is an example of the 3-item list with all of the previous and nexts properly shown. And so it just links together. Once you draw these things in a picture and you get the understanding of what they're talking about, they're not too hard. And section 6.5.1 in the book, which I added actually, walks through this doubly linked list in some detail. So I won't replicate that here. Now, let's just say that you have a doubly linked list and you want to now reverse it. Well, it's pretty simple. You set current to tail, same as long as current stays not null, and then say current equals current prev. So you're sort of popping back up one at a time. So the second time through the loop, current has followed the prev from the last item, and now it's on the second to last item. And then it does it again, and then it goes to the top, and then the last time it goes up to the prev of the top one and finds null, and then the loop finishes because current has become null, and you printed out the 3 lines, cool is C, backwards. So this is just an example in KR0609.C, and I won't walk through it in this lecture. I'll let you take a look at that. It's quite common to encode all this stuff in some functions rather than just in straight line code. It's not all that hard. You don't want to pass in the list structure and the line. List is passed in by reference, and so you have to say ampersand my list on this list add function, and inside the function you have the list be a pointer to that structure, and then you have to use the arrow syntax inside of the function. The next thing I want to talk about is unions. A union is like a structure, but it reallocates the same memory over and over, whereas a structure allocates more memory. This says, I'm going to take this same piece of memory and I'm going to view it different ways. And so it's the same area and you can assign multiple types to it. This is useful in like network protocols and pulling bits out of memory, etc. And so in my current sample, I've got my union sample open curly brace int I semicolon char ca bracket 4 bracket semicolon float f semicolon close curly brace semicolon. What I have done here is allocated in a sense 4 bytes. Integers in this case are 32 bits. CA4 is 4 bytes, which is 4 times 8 is 32, and floats are 32-bit floating point numbers. So that's the same amount of memory. So instead of being 4 times 3 or 12 bytes, this is actually 4 bytes that I can see it. I can view it either as an integer or as a character array of 4 characters or float. And I've carefully lined them up so that they're the same width. I allocate union sample u, and then I set the integer version of that 4 bytes to 42, and then I print it out, and you can see the hex, floating point, that's a complete failure. 0.000 is like, it's not a very good big floating point number. And then as a character, string, it is an asterisk. And then I take u.ca, which is viewing that same area of memory as a character array, and I copy quote capital A, B, C into it, and you'll see that it prints out as a string as ABC. The floating point number is still zeros. It's still kind of a bad floating point number. But then I see the hex as 00636241. Now, this is a little endian computer that I'm running on it. So the A is the 41, the B is the 62, and the C is the 63. And the 0 is the end of string indicator. And so that's why I picked very carefully only copying a 3-character string into a 4-character array. So I could copy that end of string indicator. Then I take u.f, which is taking that exact same memory and perceiving it as a floating point, and I put 1/3 into it. So now when I print that out, it's 0.33. Lovely. When I print it out as a string, it is pretty bad. And so it turns out that the first 3 characters are the string, but there's no 0 at the end of the string, so that greater than isn't there, and it just keeps on going. It goes into memory, and that all that stuff that's greater than $HK, that's just random garbage on the stack somewhere, that because the %s is wandering randomly through memory at this point. And then if I print that out as hex, and if we wanted to, we could learn something about the IEEE floating point format, but 3E AA is 1/3. And that is a base 2 repeating 1/3 with an exponent, and floating point internal formats are not the subject for this course. I've accomplished everything I wanted you to know about C. And so the next topic is going to be object-oriented programming. But not just how to use object-oriented programming in Python or whatever. C doesn't have it. What I want to do is look at if we were writing Python itself in C, which is what CPython is, how would we have to build things like a list structure, a list object, a string object, and a dictionary object? How would we build them? And we'll take a look at other programming languages that have object-oriented features like C++ and Java and etc. And so really the next bit is going to be about the implementation details for object-oriented programming.
Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective.
Chapter 6, Structures. A structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient handling. While we talk about data structures and how to use them in every language, this section is about understanding how software developers carefully control the low-level shape of their data items to solve their problems. When you first learn about the C struct keyword, you might think it's equivalent to a Python dict, a dynamic key value store like a PHP array, Java, MyApp, or JavaScript object. But nothing is further from the truth. These other languages provide us with easy-to-use data structures where all of the challenging problems are solved. This chapter tells, or told, the creators of Python, PHP, Java, and JavaScript how to solve the complex problems and build convenient and flexible data structures, which we now all use in those object-oriented languages. One way to look at this code in this chapter is to think of it as a lesson on how one might build Python's list and dict data structures. If the code in the chapter takes you a little while to figure out, mentally make a note of thanks for all the hard work that modern languages invest to make their high-level data structures flexible and easy to use. Back to the textbook. The traditional example of a structure is a payroll record. An employee is described as a set of attributes such as name, address, social security number, salary, etc. Some of these in turn could be structures. A name has several components, as does an address and even a salary. Structures help organize complicated data, particularly in large programs, because in many situations they permit a group of related variables to be treated as a unit instead of separate entities. In this chapter, we'll try to illustrate how structures are used. The programs that we will use are bigger than many others in the book, but are still of modest size. Section 6.1 Basics. Let us revisit the date conversion routines of Chapter 5. A date consists of several parts, such as the day, month, and year, and perhaps the day of the year and the month name. These 5 variables can all be placed in a single structure, like this. Struct, date, open curly brace, int day semicolon, int month semicolon, int year semicolon, int year day semicolon, char, mun name, open square bracket 4, close square bracket semicolon, curly brace, semicolon. The keyword struct introduces a structure declaration, which is a list of declarations enclosed in braces. An optional name called the structure tag may follow the word struct, as with date here. The tag names this kind of a structure and can subsequently be used as shorthand for the detailed declaration. The elements or variables mentioned in a structure are called its members. A structure, member, or tag and ordinary, i.e. non-member variable, can have the same name without conflict, since they are always distinguished by context. Of course, as a matter of style, one would normally use the same names only for closely related objects. The right brace that terminates the list of members may be followed by a list of variables, just as for any basic type. That is, struct, open curly brace, ... close curly brace, x, y, z, semicolon, is syntactically analogous to int x, y, z, semicolon, in the sense that each statement declares x, y, and z to be variables of the named type and causes space to be allocated for them. A structured declaration that is not followed by a list of variables allocates no storage. It merely describes a template or the shape of the structure. If the declaration is tagged, however, the tag can be used in later definitions of the actual instances of the structure. For example, given the declaration of date above, struct date d defines a variable d which is a structure of type date. An external or static structure can be initialized by following its definition with a list of initializers for the components. Struct date d equals open curly brace 14, 7, 1776, 186, double quote JUL, double quote, close curly brace, semicolon. A member of a particular structure is referred to in an expression by a construction of the form structure name dot member. The structure member operator dot connects the structure name and the member name. To set leap from the date in structure D, for example, leap equals d dot year modulo 4 double equals 0 and d dot year modulo 100 not equal to 0 or d dot year modulo 400 double equals 0 semicolon. Or to check the month name, if open paren strcomp open paren d dot mon name comma double quote aug double quote close paren double equals 0 close paren dot dot dot. Or, to convert the first character of the month name to lowercase, d.munname sub 0 equals lower open paren d.munname sub 0 close paren semicolon. Structures may be nested. A payroll record might actually look like struct person open curly brace, char name open square bracket name size close square bracket semicolon, char address open square bracket address size close square bracket semicolon, long zip code semicolon, long SS number semicolon, double salary, struct date birth date semicolon, struct date hire date semicolon, close curly brace semicolon. The person structure contains 2 dates. If we declare emp as struct person emp semicolon, then emp.birthdate.month refers to the month of birth. The structure member operator dot associates left to right. Section 6.2, Structures and Functions. There are a number of restrictions on C structures. The essential rules are that only operations you can perform on a structure are to take its address with ampersand and access one of its members. This implies that structures may not be assigned or copied to as a unit, and that they cannot be passed or returned from functions. These restrictions will be removed in forthcoming versions. Pointers to structures do not suffer these limitations, however, so structures and functions do work together comfortably. Finally, automatic structures, like automatic arrays, cannot be initialized. Only external or static structures can. This prediction was indeed accurate. Modern C compilers do support the copying of a structure with a single assignment statement. Given that a C structure is just a fixed length block of memory, it's easy to generate machine code to copy it. A key bit to remember that when the C structure is copied, it is done as a shallow copy. A shallow copy copies the values of the variables and the pointers in the structure, but does not make copies of any data which the pointers point to. A structure that contains other structures, i.e. not pointers to structures, then those structures are shallow copied as well. Back to the text. Let us investigate some of these points by rewriting the date conversion functions in the last chapter to use structures. Since the rules prohibit passing of a structure to a function directly, we must either pass the components separately or pass a pointer to the whole thing. The first alternative uses of day of year, which as we wrote in chapter 5. d.yearday equals day of year, open paren, d.year, comma, d.month, comma, d.day, close paren, semicolon. The other way is to pass a pointer. If we've declared higher date as struct date, higher date, semicolon, and rewritten day of year, we could then say higher date.year day equals day of year, open paren, ampersand, higher date, close paren, semicolon. To pass a pointer to higher date to day of year, the function has to be modified because its argument is now a pointer rather than a list of variables. This example code is on page 122 of the textbook, and you can see it at www.cc4e.com/code. Struct date, open curly brace, int day, semicolon, int month, semicolon, int year, semicolon, int year day, semicolon, int mon name, open square bracket 4, close square bracket, semicolon, close curly brace, semicolon. Static int day tab, open square bracket 2, close square bracket, open square bracket 13, close square bracket, equals open curly brace, 0, 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31, close curly brace, comma, and then another list just as long as that with a close curly brace and a semicolon. That just initialized the lookup table for the days in each month. Now on to the function. Day of year, open paren, PD, close paren, struct date star PD, semicolon, open curly brace, int I, comma, day, comma, leap, semicolon. Day equals PD minus greater than day, semicolon. Leap equals PD minus greater than year, %4, double equals 0, and PD minus greater than year, %100, not equal to 0, or PD minus greater than year, %400, double equals 0, semicolon. For, open paren, I equals 1, semicolon, I less than PD minus greater than month, semicolon, I plus plus, close paren, day plus equals day tab, open square bracket leap, close square bracket, open square bracket I, close square bracket, semicolon. Return, open paren, day, close paren, semicolon, close curly brace. The declaration struct date star PD says that PD is a pointer to a structure of type date. The notion exemplified by PD minus greater than year. I think I'll call that at this point PD right arrow, because that's really what it is. It's the minus greater than looks like an arrow to the right. So I'm going to call it right arrow, but it's really 2 characters. PD right arrow year is new. If P is a pointer to a structure, then PD right arrow member of structure refers to the particular member. The operator right arrow is a minus sign followed by a greater than.
Since PD points to the structure, the year member could also be referenced as open paren star PD close paren dot year. But pointers to structures are so frequently used that the right arrow notation is provided both as a convenient shorthand. The parentheses are necessary in open paren star PD close paren dot year because the precedence of the structure member operator dot is higher than the pointer lookup operator asterisk. Both right arrow and dot associate from left to right. So P, right arrow, Q, right arrow mem, and emp.birthdate.month are open paren P, right arrow, Q, close paren, right arrow mem, and open paren emp.birthdate, close paren.month. For completeness, here is the other function, month day, rewritten to use the structure. This is the first example on page 123 of the text, which you can look at the source code at www.cc4e.com/code. I won't read the struct and the struct date definition and the struct int static int day tab definition. We'll just go month day. Month day, open paren, PD, close paren, struct date, star PD, semicolon, open curly brace, int I, comma, leap, semicolon. Leap equals PD right arrow year, %4 double equals 0, and PD right arrow year, %100 not equal to 0, or PD right arrow year, %400 double equals 0, semicolon. PD right arrow day equals PD right arrow year day. 4, open paren I equals 1, semicolon, PD right arrow day greater than day tab sub leap sub I, semicolon, I++, close paren. PD right arrow day minus equals day tab sub leap sub I, semicolon, PD right arrow month equals I, semicolon, close curly brace. The structure operators right arrow and dot, together with parentheses for argument lists and square brackets for subscripts, are the top of the precedence hierarchy and then thus bind very tightly. For example, given the declaration struct open curly brace int x int star y semicolon close curly brace star p semicolon, then plus p right arrow x increments x, not p, because the implied parenthesization is plus open paren p right arrow x close paren. Parentheses can be used after the binding. Open paren plus p right arrow x increments p before accessing x, and open paren p plus close paren right arrow x increments p afterward. The last set of parentheses is unnecessary. In the same way, star p right arrow y fetches whatever y points to. Star p right arrow y plus increments y after accessing whatever it points to, just like star s plus. Open paren star p right arrow y close paren plus increments whatever y points to, and star p plus right arrow y increments p after accessing whatever y points to. Section 6.3, Arrays of Structures. Structures are especially suitable for managing arrays of related variables. For instance, consider a program to count the occurrences of each C keyword. We need an array of character strings to hold the names and an array of integers to hold the counts. One possibility is to use two parallel arrays, keyword and key count, as in char star keyword, open square bracket, n keys, close square bracket, semicolon, int key count, open square bracket, n keys, close square bracket, semicolon. But the very fact that the arrays are parallel indicates a different organization is possible. Each keyword entry is really a pair. Char star keyword, semicolon, int key count, semicolon. And there's an array of the pairs. The structure declaration, struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, key tab, open square bracket, n keys, close square bracket, semicolon, defines an array key tab of structures of this type and allocates storage to them. Each element of the array is a structure. This could also be written struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, semicolon, struct key, key tab, open square bracket, n keys, close square bracket, semicolon. Since the structure key tab actually contains a constant set of names, it's easiest to initialize it once and for all when it's defined. The structure initialization is quite analogous to the earlier ones. The definition is followed by a list of initializers enclosed in braces. Struct key, open curly brace, char star keyword, semicolon, int key count, semicolon, close curly brace, key tab, open square bracket, close square bracket, equals, open curly brace, double quote, break, comma, 0, comma, double quote, case, comma, 0, comma, double quote, char, comma, 0, comma, and so forth, down to double quote, unsigned, double quote, comma, 0, comma, double quote, while, double quote, comma, 0, close curly brace, semicolon. These initializers are listed in pairs corresponding to the structure members. It would be more precise to enclose initializers for each row or structure in the braces, as in open curly brace, double quote, break, double quote, comma, 0, close curly brace, comma, open curly brace, double quote, case, double quote, comma, 0, close curly brace, comma, and so forth. But the inner braces are not necessarily when the initializers are simple variables or character strings, and when all are present. As usual, the compiler will compute the number of entries in the array key tab if the initializers are present and the open square bracket, close square bracket is left empty. The keyword counting program, which begins with a definition of key tab. The main routine reads the input repeatedly by calling a function getWord that fetches input one word at a time. Each word is looked up in key tab with a version of the binary search function we wrote in Chapter 3. Of course, the list of keywords has to be given in increasing order for this to work. Here's the first example on page 125 of the textbook. You can see this at www.cc4e.com/code. Pound include stdio.h. Pound define max word 20. Pound define letter, quote, a quote. Main, open paren, close paren, open curly brace. Int n comma t, semicolon. Char, word, open square bracket, max word, close square bracket, semicolon. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t double equal letter, close paren, if, double open paren, n equals binary, open paren, word, comma, key tab, comma, n keys, close paren, greater than or equal to 0, close paren, key tab, sub n, dot, key count, plus, plus. For, open paren, n equals 0, semicolon, n less than n keys, semicolon, n plus, plus. If, open paren, key tab, sub n dot key count, greater than 0, close paren, printf, double quote, %4d, space, %s, backslash n, double quote, comma, key tab sub n dot key count, comma, key tab sub n dot keyword, close paren, semicolon, and then a close curly brace to finish main. Binary, to find the word in the table. Binary, open paren, word, comma, tab, comma, n, close paren. Char star word, semicolon. Struct key tab, open square bracket, close square bracket, semicolon, int n, open curly brace, int low, comma, high, comma, mid, comma, cond, low equals 0, semicolon, high equals n minus 1, semicolon, while, open paren, low less than or equal to high, close paren, open curly brace, mid equals paren, low plus high, close paren, over 2, semicolon. If, open paren, cond equals strcomp, open paren, word, comma, tab, comma, open square bracket, mid, close square bracket, dot keyword, close paren, less than 0, close paren, high, equals mid minus 1, semicolon, else if, open paren, cond,
greater than 0, close paren, low equals mid plus 1, semicolon, else, return, open paren, mid, close paren, semicolon, close curly brace to finish the while, and then return, open paren, -1, close paren, semicolon, close curly brace. And that's really a rewrite of the binary function from the earlier part where we were just taking the keyword and the count and looking up in the array, but then using the dot keyword to find the actual keyword. Back to the text. We'll show function getWord in a moment. For now, it suffices to say it returns letter each time it finds a word and copies the word into its first argument. The quantity n keys is the number of keywords in key tab. Although we could count this by hand, it's a lot easier and safer to do it by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a null pointer, and then the loop along key tab just runs until the end is found. But this is more than is needed, since the size of the array is completely determined at compile time. The number of entries is just the size of key tab divided by the size of the struct key. C provides a compile time unary operator called sizeOf, which can be used to compute the size of any object. The expression sizeOf open paren object close paren yields an integer equal to the size of the specified object. The size is given in unspecified units called bytes, which are the same size as a char, close paren. The object can be an actual variable or an array or structure, or the name of a basic type like int or double, or the name of a derived type like a structure. In our case, the number of keywords is the array size divided by the size of one array element, and this computation is used in a pound define statement to set the value of n keys. Pound define n keys, open paren sizeOf open paren key tab close paren divided by sizeOf open paren struct key close paren close paren. Now for the function getWord. We have actually written a more general getWord than is necessary for this program, but it is not really much more complicated. GetWord returns the next word from the input, where a word is either a string of letters or digits beginning with a letter or a single character. The type of the object that is the returned function as a function value. It is the letter if the token is a word, EOF for end of file, or the character itself if it's non-alphabetic. This sample code is on page 127 of the textbook, which you can see at www.cc4e.com/code. Pound define letter, quote, a quote. Pound define digit, quote, 0 quote. GetWord, open paren, w, comma, lim, close paren. Char, star w, colon, semicolon. Int, lim, semicolon, open curly brace. Int, c, comma, t, semicolon. If open paren type open paren c equals star w plus plus equals get ch open paren close paren not equal letter close paren open curly brace star w equals quote \0 quote semicolon return open paren c close paren semicolon close curly brace. That if statement has got some stuff going on in it. You might want to look at it very closely. While, open paren, minus lim, greater than 0, close paren, open curly brace, t equals type, open paren, c equals star w plus plus equals get ch, open paren, close paren, semicolon. If open paren, t not equal letter, and t not equal digit, close paren, open curly brace, unget ch, open paren, c, close paren, semicolon, break, semicolon, close curly brace, star, open paren, w minus 1, close paren, equals, quote, \0, quote, semicolon, return, open paren, letter, close paren, semicolon, close curly brace, close curly brace. That example code has a lot of stuff about pointers and incrementing pointers and dereferencing pointers, etc. So take a good look at that code. Back to the text. GetWord uses the routines getch and ungetch, which we wrote in Chapter 4. When the collection of an alphabetic token stops, GetWord has gone one character too far. The call to ungetch pushes that character back on the input for the next call. GetWord calls another function called type to determine the type of each individual character for input. Here is a version that's only for ASCII. This code is the second example on page 127 of the textbook at www.cc4e.com/code. Type open paren C close paren, int C semicolon. Open curly brace. If open paren C greater than or equal to quote A quote and C less than or equal to quote Z quote, or C greater than or equal to quote uppercase A quote and C less than or equal to quote uppercase Z quote close paren, return letter semicolon. Else if open paren C greater than or equal to quote 0 quote and C less than or equal to quote 9 quote close paren, return open paren digit close paren semicolon. Else return open paren C close paren semicolon. Close curly brace. The symbolic constants, letter, and digits can have any values that do not conflict with non-alphanumeric values and EOF. The obvious choices are quote A quote and quote 0 quote. GetWord can be faster if calls to the function type are replaced by references to the appropriate array type. The standard C library provides macros like isAlpha and isDigit, which operate in this manner. Section 6.4, Pointers to Structures. To illustrate some of the considerations involved with pointers and arrays of structures, let us write a keyword counting program again, this time using pointers instead of array indices. As an aside, I would note that it's a classic early assignment in any programming language to do a word frequency program. Here is a Python program from my Python for Everybody course to count words from an input stream. Handle equals open parenthesis, single quote, Romeo.txt, close, single quote, comma, quote, R, quote, close parenthesis. Words equals handle.read, open paren, close paren, dot split, open paren, close paren. Counts equals dict, open paren, close paren. For word in words, colon. Counts subword equals counts.get, open paren, word, comma, 0, close paren, plus 1. Print, open paren, counts, close paren. This section in this book implements a less general word counting program in C. The code depends on several functions from earlier in the book, and the code below is pretty complex, where the programmer only has access to low-level language without powerful and easy-to-use data types, like Python's list or dict. It is likely that Guido van Rossum read this book, took a long look at this code, and designed the dict data structure in Python so the rest of us could write a data parsing and word frequency program in the above 6 lines of code without worrying about dynamic memory allocation, pointer management, string length, and a myriad of other details that must be solved when you're solving this program in C. Since Python is open source, you can actually look at the C code that implements the dict object in a file called dictobject.c. It is almost 6,000 lines of code and includes other files or utility code. Thankfully, we only have to write one line of Python to use it. Counts equals dict, open paren, close paren. We will leave the complex bits to the C programmers that build and maintain. This section is not showing us how to use the Python dict object. Rather, it is showing how one would build a dict-like structure using C. So, continuing with section 6.4, pointers to structures. The external definition of key tab do not need to change, but main and binary do need modification. This is example on page 129 of the textbook, and that is available at www.cc4e.com/code. Pointer version of counting C keywords. Main, open paren, close paren, open curly brace, int t semicolon. Char, word, open square bracket, max word, close square bracket, semicolon. Struct key, star, binary, open paren, close paren, comma, star p, semicolon. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t equal letter, close paren. If, open paren, b equals binary, open paren, word, comma, key tab, comma, n keys, close paren, not equal null, close paren, P right arrow key count plus plus. For P equals key tab, P less than key tab plus N keys, semicolon, P plus plus, close parenthesis. If, open paren, P right arrow key count greater than 0, close paren, printf, open paren, double quote, %4d space %s, \n, double quote, comma, P right arrow key count, comma, P right arrow keyword. And now we'll look at the binary search. Struct key star binary, open paren word, comma, tab, comma, n, close paren, char star word, struct key tab, open square bracket, close square bracket, semicolon, int n, open curly brace, int cond, semicolon, struct key star low equals ampersand tab sub 0, semicolon, struct key star high equals ampersand tab sub n minus 1, semicolon, struct key equals mid. While, open paren, low less than or equal to high, close paren, open curly brace. Mid equals low plus high minus low divided by 2. If, open paren, cond equals strcomp, word, comma, mid, right arrow keyword, close paren, less than 0, close paren, high equals mid minus 1, semicolon. Else if, close paren, cond greater than 0, close paren, low equals mid plus 1, semicolon. Else return, open paren, mid, close paren, semicolon, close curly brace to finish the while, and then return, open paren, null, close paren, close curly brace. There are several things worthy of note here. First, the declaration of binary must indicate that it returns a pointer to the structure type key instead of an integer. This is declared both in main and in binary. If binary finds the word, it returns a pointer to it. If it fails, it returns null. Second, all the accessing elements of keydab is done by pointers. This causes one very significant change in binary. The computation of the middle element can no longer be simply mid equals paren low plus high, close paren, divided by 2, because the addition of 2 pointers will not produce any kind of useful answer, even when divided by 2, and is fact illegal. This must be changed to mid equals low plus open paren high minus low, close paren, divided by 2, which sets mid to the point to the element halfway between low and high. You should also study the initializers for low and high. It is possible to initialize a pointer to the address of a previously defined object, and that is precisely what we have done here. In main, we wrote for open paren p equals keytab semicolon, p less than keytab plus n keys semicolon, p plus plus close paren. If p is a pointer to a structure, any arithmetic on p takes into the account the actual size of the structure. So p plus plus increments p by the correct amount to get to the next element in the array of structures. But don't assume that the size of a structure is the sum of the sizes of its members, because alignment requirements for different objects potentially may cause holes in the structure. Finally, an aside on program format. When a function returns a complicated type, as in struct, key, star, binary, open paren, word, comma, tab, comma, n, close paren, the function name can kind of be hard to see and or find with a text editor. Alternately, another style is sometimes used. On 2 lines now, struct key star on the first line, and binary, open paren, word, comma, tab, comma, n, close paren. The spacing is mostly a matter of personal taste. Pick the form you like and hold to it. Section 6.5, Self-Referential Structures. Before we start this section, a slightly longer aside from your narrator. Up to now, I've resisted the temptation to augment the book with my own bits of code. But we have reached the single point in the book where I feel that there is too big of a conceptual leap between 2 sections, so I'm going to add some of my own narrative between section 6.4 and 6.5. The rest of this chapter talks very nicely about binary trees and hash tables, both essential low-level data structures in computer science and both excellent ways to understand pointers,
and how C can be used to build data structures like the Python dictionary. However, the author skipped separately describing the structure of a dynamically constructed linked list, which is the first and foundational collection data structure in computer science and should be understood before moving to tree and hash map structures. Linked lists form the foundation of the Python list object, Java array object, PHP numeric key arrays, and JavaScript arrays. The linked list can be dynamically extended, and items can be added in the middle efficiently as well as being pushed or popped on or off the front or back of the list. Linked lists are used also to implement queues as well as other aspects of operating system. I will attempt to mimic the author's writing style in this new section of the book. I'll write some sample code using a more modern dialect of C so it's easier to run on a modern compiler. Section 6.5.1, Linked Lists, Bonus Content. Suppose we want to read a file and print the file in reverse order. We don't know how many lines will be in the file before we read the file, so we can't simply use an array of pointers to strings and character arrays, like lines. In a sense, we need a dynamic array that grows as we encounter new lines. When we reach the end of the file, we then just loop through our stored lines from the end to the beginning so we can print them out in reverse order. One solution is to make a data structure called a doubly linked list of character strings. In addition to each line of data, we will store a pointer to the previous line and the next line as well as a pointer to the first item, the add to the list, and then we'll call this the head of the list, and then the most recent item we've added to the list, which we'll call the tail of the list. We will see a singly linked list as part of the hash map data structure in a following section. A single linked list can only be traversed in a forward direction. A doubly linked list can be traversed either forwards or backwards. Given that our linked list of strings will keep expanding as we get new lines, we avoid hard-coding array sizes like #define maxlen 1000 in the previous chapter. We were building a program to sort a file. Going back to the description of a line in our doubly linked list, it is clearly a structure with three components: struct lnode open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace. This recursive definition of lnode might look chancy, but it's actually quite correct. It is illegal for a structure to contain an instance of itself, but struct lnode star prev declares prev to be a pointer to an lnode, not an lnode itself. We'll write this code in a more modern C dialect using modern memory allocation and I/O routines provided by the standard C library. This code is on page 130 of the textbook, available at www.cc4e.com/code. #include stdio.h, #include stdlib.h, #include string.h, #define maxline 1000. This is the length of the line, not the number of lines. Struct lnode open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace semicolon. Now we have our main program to print the lines in reverse. And we will use int main open paren close paren because we're coding in a modern dialect of C. Open curly brace. Struct lnode star head equals null semicolon. Struct lnode star tail equals null semicolon. Char line, submax line, semicolon. While open paren fgetS open paren line, comma max line, comma stdin, close paren not equal null, close paren open curly brace. Char star save equals open paren char star, close paren malloc, open paren stirlen, open paren line, close paren +1, close paren semicolon. Stir copy, save comma line. Struct lnode star new equals open paren struct lnode star close paren malloc open paren size of struct lnode close paren semicolon. New right arrow text equals save, new right arrow next equals null, new right arrow prev equals tail, and tail equals new. If head equals null,
close paren, head equals new, semicolon. Close curly brace to finish the while. Now we'll print it all out. For, open paren, struct, lnode, star current equals tail, semicolon, current not equal to null, semicolon, current equals current, right arrow, prev, close parenthesis, open curly brace, printf, open paren, double quote, s, close, double quote, comma, current, right arrow, text, close paren, semicolon, close curly brace to finish the for, and then close curly brace to finish the main. Interestingly, if we wanted to print the list in forward order, or if we did have only a singly linked list, our loop would look as follows. For, open paren, struct, lnode, star current equals head, semicolon, current not equal to null, semicolon, current equals current, right arrow, next, close paren, open curly brace. Printf, open paren, double quote, %s, double quote, comma, current, right arrow, text, close paren, semicolon, close curly brace. In general, we use the variable names head, tail, and current, as well as next and prev, or similar names when writing code that builds or uses a linked list, so other programmers will quickly understand what we are talking about. After a while, reading a for loop to traverse a linked list becomes as natural as reading a for loop that progresses through a sequence of numbers. Section 6.5.2, Binary Trees. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can't conveniently sort it and use a binary search. Yet we can't do a linear search for each word that has arrived to see if it's already been seen. The program would take forever. More precisely, what is the expected running time? And it would grow quadratically with the number of input words. How can we organize the data to cope efficiently with a list of arbitrary words? Our solution is to keep the set of words seen so far sorted at all times by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting the words in a linear array, though. That takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains a pointer to the text of the word, a count of the number of occurrences of the word, a pointer to the left child node, and a pointer to the right child of node. No node may have more than two children. It might have only 0 or 1. The nodes are maintained so that any node in the left tree contains only words that are less than the words at the node, and the right tree only contains words that are greater. To find out whether a new word is already in the tree, one starts at the root and compares the new word to the word starting at that node. If they match, we found it. If the new word is less than the tree word, the search continues down the left. Otherwise, the right child is searched. If there is no child in the required direction, then the word is not in the tree. And in fact, the proper place for it to be is the missing child. This search process is inherently recursive, since the search from any node uses a search from one of its children. Accordingly, recursive routines for inserting and printing will be the most natural. Going back to the description of a node, it is clearly a structure with 4 components. Struct tnode, open curly brace. Char star word, int count, semicolon. Struct tnode star left, semicolon. Struct tnode star right, semicolon, close curly brace. This recursive declaration of a node might look chancy, but actually it's quite correct. It's illegal for a structure to contain an instance of itself, but struct tnode star left, semicolon declares left to be a pointer to a node, not a node itself. The code for the whole program is surprisingly small, given the handful of supporting routines that we've already written. These are getWord to fetch input and alloc to provide space for squirreling the words away. The main routine simply reads words with getWord, installs them in the tree with tree. This is the first example on page 131 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h. Pound define max word 20. Pound define letter, single quote A, single quote. Main, open paren, close paren, open curly brace. Struct tnode, star root, comma, star tree, open paren, close paren, semicolon. Char, word, open square bracket, max word, close square bracket, semicolon. Int t, semicolon. Root equals null. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t double equal letter, close paren, root equals tree, open paren, root, comma, word, close paren, semicolon. Tree print, open paren, root, close paren, semicolon, close curly brace. Tree itself is straightforward. A word is presented by main to the top level root of the tree. At each stage, that word is compared to the word already stored at the node and is percolated down either to the left or right subtree by a recursive call to tree. Eventually, the word either matches something already in the tree, in which case the count simply is incremented, or a null pointer is encountered, indicating the node must be created and added to the tree. If a new node is created, tree returns a pointer to it, which is installed in the parent node. This is the example on page 132 of the textbook at www.cc4e.com/code. Pound includes string.h. Struct, tnode, open curly brace, char, star word, semicolon, int, count, semicolon, struct, tnode, star left, semicolon, struct, tnode, star right, semicolon, close curly brace, semicolon. Struct, tnode, star tree, open paren, p, comma, w, close paren. We're going to install w at or below p. Struct, tnode, star p, semicolon, char, star w, open curly brace. Struct, tnode, star t alloc, open paren, close paren, semicolon, char, star, stir save, open paren, close paren, semicolon, int, cond, semicolon. If, open paren, p double equal null, close paren, open curly brace. We've got a new word. P equals t alloc, open paren, close paren, to make a new node. P right arrow word equals stir save, open paren, w, close paren, semicolon. P right arrow count equals 1. P right arrow left equals P right arrow right equals null. Close curly brace. Else if open paren, cond equals stir comp, w, comma, p, right arrow word, close paren, double equals 0, close paren, p, right arrow count, plus, plus. Indicate that we've seen the word one more time. Else if, open paren, cond, less than 0, close paren, lower will go into the left part of the tree. P right arrow left equals tree P right arrow left, comma, W, close paren, semicolon. Else, P right arrow right equals tree, open paren, P right arrow right, comma, W, close paren, semicolon. Return, open paren, P, close paren, semicolon, close curly brace. And that's a bit of code. It's not much, and it's beautiful. Recursion is happening. The return P at the very end is really, really important because we're kind of always overriding it, but we're okay. So the overriding works its way back up to the recursion because it's recursive, it's using pointers, away we go. Back to the text. Storage for the new node is fetched by a routine called talloc, which is an adaptation of the alloc we wrote earlier. It returns a pointer to a free space suitable for holding a tree node. We'll discuss this more in a moment. The new word is copied to a hidden place by stir save. The count is initialized and the two children are made null. This part of the code is executed only at the edge of the tree when a new node is being added. We have, unwisely for a production program, omitted error checking on the values returned by stir save and talloc. Tree print prints the tree in left subtree order. At each node, it prints its left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about recursion, draw yourself a tree and print it with tree print. It's one of the cleanest recursive routines you can find. This example code is on page 133 of the textbook, which you can see at www.cc4e.com/code. I won't read the struct tnode code, just tree print. Tree print, open paren, p, close paren. Struct tnode star p semicolon, open curly brace, if open paren p not equal to null, close paren, curly brace, open curly brace. Tree print, open paren p right arrow left, close paren, semicolon, printf, %4d space %s \n double quote, comma, p right arrow count, comma, p right arrow word, close parenthesis, semicolon. Tree print, open paren, p right arrow right, close paren, semicolon. Close curly brace for the if, and then close curly brace for the tree print function. Again, I agree with the authors, and that is one of the cleanest and most beautiful and most applicable uses of recursion that you will probably ever see in all your career. I'm not a fan of recursion in all cases, but you really can't do this any other way well. Back to the text. As a practical note, if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too fast. As a worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree, notably 2-3 trees, AVL trees, and I would add balanced binary trees, which do not suffer from this worst case behavior, but we will not describe them here. Before we leave this example, it's also worth a brief digression on a problem related to storage allocators. Clearly, it's desirable that there only be one storage allocator in a program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct tnodes, two questions arise. First, does it meet the requirement of most real machines that objects of a certain types must satisfy alignment restrictions? For example, integers must often be located on even addresses. Second, what declarations can cope with the fact that alloc necessarily returns different kinds of pointers? Alignment requirements can generally be satisfied easily at the cost of some wasted space merely by ensuring the allocator always returns a pointer that meets all alignment restrictions. For an example, on the PDP-11, it is sufficient that alloc always returns an even pointer since any type of object may be stored at an even address. The only cost is a wasted character on the odd length requests. Similar actions are taken on other machines. Thus, the implementation of alloc may not be portable, but its usage is. The alloc of Chapter 5 does not guarantee any particular alignment. In Chapter 8, we'll show how to do the job right. As an aside, by now you know that when the authors mention the PDP-11, they are sharing some aspects of the challenge of making C work on previous generation computers with short memory words and small amounts of memory, and at the same time making them work well on the incoming generation of computers with larger words and more memory. The research, thought, and care that went into making sure the C code was portable across multiple generations of computer hardware is on display in the previous paragraph. The question of the type declaration for alloc is a vexing one for any language that takes its type checking seriously. In C, the best procedure is to declare that alloc returns a pointer to char and then explicitly coerce the pointer into the desired type with a cast. Therefore, if P is declared as char star P semicolon, then open paren struct tnode star close paren P converts it into a tnode pointer expression. Thus, talloc is written as struct tnode star talloc open paren close paren, open curly brace, char star alloc, return open paren struct tnode star close paren, alloc open paren size of open paren struct tnode close paren close paren close paren. This is more than is needed for current compilers, but represents the safest course for the future. I would add that these concerns that the authors mention in this section are also nicely resolved in modern C compilers. In the NC version of C, they introduced the notion of the void type. The void type indicates the lack of a type. much like null is used to indicate not a valid pointer or not a flying toy. In 1978, because the char type was generally the most native type on any system, it was often used as the generic pointer needed to return memory from an allocation function. In modern C, we use pointers to void and then cast the returning pointer to be a pointer to whatever struct or other data we just allocated. If we were writing alloc, the alloc routine in this book using modern C, it would return a pointer to void. The 1978 version is char star alloc open paren close paren, and the modern version is void star alloc open paren close paren. We've left the book alone. We haven't used void throughout the book, but it is a testament to the foresight of the authors that all the pointer casting code in this book still works today the same, regardless of whether the memory allocation functions return char or void pointers to the allocated data. Section 6.6, Table Lookup. As an aside, in this section, we finish our quick tour of the implementations of the 3 core data structures in computer science. 1, the linked list, 2, the tree, and 3, the hash map, as described in this section. A singly linked list is also part of a hash map implementation, so you can compare it to the doubly linked list code introduced in the earlier bonus section 6.5.1. This section is worth understanding well because not only is it an excellent review of pointers and structures, but also because one of the most common questions on a face-to-face programming interview is, draw a hash map on the whiteboard and explain how it works. This is an easy question if you study and understand this section of the book, and almost impossible if you have not. In some ways, this section is the most intricate data structure that's described in the book. It is why it is so popular in coding interviews. Chapters 7 and 8 talk about lots of practical things like input-output of the Unix operating system. Elegant data structures and their use are core concepts in computer science. Understanding them highlights the difference between a good programmer and a computer scientist. In a sense, understanding how a hash map is the secret handshake of computer science. And it is the secret handshake because of this book and this section of this book, written back in 1978 and used in a course that the person interviewing you may have took when they were in college. Hash maps were difficult for them to understand back then, and so if you understand the concept, then you must be solid. So I hope you pay close attention to this section and remember the handshake. Back to the text. In this section, we will write the innards of a table lookup package as an illustration of more aspects of structures. This code is typical of what might be found in the symbol table management routines of a macro processor or a compiler. For example, consider the C #define statement. When a line like #define yes 1 is encountered, the name yes and the replacement text 1 are stored in a table. Later, when the name yes appears in a statement like in-word equals yes, it must be replaced by 1. There are 2 major routines that manipulate the names and replacement text. Install open paren s, t, close paren, records the name s and the replacement t in the table. S and t are just character strings. Lookup open paren s, close paren, searches for s in the table and returns a pointer to the place where it was found, or null if it wasn't there. The algorithm used is a hash search. The incoming name is converted to a small positive integer, which is then used to index into an array of pointers. An array element points to the beginning of a chain of blocks describing the names that have the hash value, and if it is null, then no names have hashed to that value. A block in the chain is a structure containing pointers to the name, the replacement text, and the next block in the chain. A null next pointer marks the end of the chain. Struct enlist open paren, char star name semicolon, char star def semicolon, struct enlist star next semicolon, close curly brace semicolon. The pointer array is just #define hash size 100. Static struct enlist star hash tab, open square bracket, hash size, close square bracket, semicolon. The hashing function, which is used by both lookup and install, simply adds up the character values in the string and forms the remainder modulo the array size. This is not the best possible algorithm, but it has the merit of extreme simplicity. Hash open paren s close paren, char star s semicolon, open curly brace, int hash val. For open curly brace, hash val equals 0, star s not equal, quote, single quote, backslash 0, single quote, semicolon, close paren. Hash val plus equals star s plus plus, semicolon, return, open paren, hash val modulo, percent, hash size, close paren, semicolon, close curly brace. As an aside, hashing functions are one of the foundational notions in computer science. Hashing functions are used for everything from high-performance in-memory structures, organizing databases, data, digital signing, network packet checksums, security algorithms, and much more. The above text is a really great example of a really simple hashing function. You should understand this simple presentation well so that when you encounter a more complex implementation or use of hashing, you can fall back on this text to understand that at its core, hashing is a very simple concept. So much of this chapter is a succinct example of some of the most powerful concepts in computer science. Please don't look at the 8 lines of code above and think, I got that, and just jump to the next bit. This chapter is showing you the way of the master programmer. Wax on, wax off. Be patient, slow down, and enjoy your time here. Back to the text. The hashing process produces a starting index in the array hash tab. If the string is to be found anywhere, it will be in the chain of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it just returns a pointer to it. If not, it returns null. Here's the code. Struct enlist star lookup open paren s close paren char star s semicolon open curly brace struct enlist star np semicolon. For open paren np equals hash tab sub hash open paren s close paren close square bracket semicolon np not equal null semicolon np equals np right arrow next close parenthesis. If strcomp open paren s comma np right arrow name close paren double equals 0 return open paren np close paren semicolon return open paren null close paren semicolon close curly brace. Install uses lookup to determine whether the name installed is already present. If so, the new definition must supersede the old one. Otherwise, a completely new entry is created. Install returns null if for any reason there's no room for a new entry. Struct enlist star install open paren name comma def close paren char star name comma star def semicolon open curly brace struct enlist star np comma star lookup open paren close paren semicolon char stir save comma star alloc open paren close paren semicolon int hash val semicolon. If open paren np equals lookup open paren name close paren double equal null close paren open curly brace, i.e. it's not found, np equals open paren struct enlist star close paren alloc open paren size of open paren star np close paren semicolon. If np equals null, return null. That means the allocation failed. If open paren np right arrow name equals stir save open paren name close paren double equals null close paren return open paren null close paren semicolon. Hash val equals hash, open paren, np, right arrow, name, close paren, semicolon. np next equals hash tab, open square bracket, hash val, close square bracket, second, semicolon. Hash tab, open square bracket, hash val, close square bracket equals np, semicolon. We're actually pushing these new ones to the head of this singly linked list. And so those last two statements push the most recent top of the list forward and then replace with the new one at the top of the list. The list does not stay in any order. So we have a close curly brace to end all that if for the not found code, close curly brace, else, this is the already there code, free, open paren, np, right arrow, def, close paren, semicolon, free the previous definition. That's the string part of the pound define. If open paren, np, right arrow, def, equal stir save, open paren, def, close paren equals null, close paren, return open paren, null, close paren, semicolon, return open paren, np, close paren, semicolon, close curly brace. So that last bit there was to, if you have a pound define with the same keyword and a different, later you have a different definition, you can replace the definition. And so that last bit was replacing the definition. Again, this code is pretty intricate. It's really both the hash table and a singly linked list going on at the same time. So take a close look at this on page 136 of the book. Stir save merely copies the string given its argument to a safe space obtained by a call to alloc. We've showed this code in chapter 5. Since calls to alloc and free may occur in any order, and since alignment matters, the simple version of alloc is just not adequate here. See more in chapters 7 and 8. As an aside, one of the reasons that the authors make vague forward-looking statements whenever they talk about dynamic memory is that large-scale memory management in a programming language is still a subject of active research 40 years later. Back in 1978, it was absolutely not a settled topic. You can see this when the authors build a simple non-production memory allocation scheme with their own alloc and free routines backed by a fixed-length static extern array of characters. Dynamic allocation is essential to writing competent C programs, but it is likely that the production-grade dynamic memory support was still somewhat non-portable when the book was written, so they used simple, self-contained implementations in this book. Modern dynamic memory support is through the malloc, calloc, and free functions in the standard library. These functions request dynamic memory blocks from the operating system and manage those areas on behalf of your C code. On Unix and Unix-like systems, the memory allocation layer asks the underlying operating systems for blocks of memory through the SBRK interface. Even with virtual memory, programmers must carefully manage their use of dynamically allocated memory because memory is never unlimited.
Section 6.7 Fields. When storage space is at a premium, it may be necessary to pack several objects into a single machine word. One especially common use is a set of single-bit flags in applications like compiler symbol tables. Externally imposed data formats, such as interfaces to hardware devices, also often require the ability to get at pieces of a word. As an aside, we are going to go now from low-level programming to even lower-level programming. The Unix operating system is written in C, and Unix needs to have, for example, an implementation of the Internet Protocol so it can be connected to the Internet. One of the most important Internet protocols is the Transmission Control Protocol, TCP. In order to implement TCP, you need to send very precisely formatted data across the network. The data is very tightly packed in order to save precious network bandwidth. The exact format of a TCP header is described in the TCP Wikipedia page. If you look at the header, you will find that at bits 96 through 99, TCP expects a 4-bit integer that defines the data offset. Exactly what this data means is less relevant unless you're actually writing the TCP implementation, but it does demonstrate that we need to control our data layout at times on a bit-by-bit basis.
This section covers how we can use struct to build up a TCP header in C, which can be parsed and set without using masking and shifting operations with hard-coded numbers. The section below is simpler than constructing a valid TCP header using a carefully packed struct, but it does lay the groundwork for these more complex situations. Now back to the text. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it, for example, whether or not it's a keyword, whether or not it's external and/or static, and so on. The most compact way to encode such information is a set of 1-bit flags in a single char or int. The usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in pound-define keyword 01, pound-define external 02, and pound-define static 04. The numbers, of course, must be powers of 2 so that the shifting works. Then accessing the bits become a matter of bit fiddling with shifting, masking, and complementing operators, which were described in Chapter 2. Certain idioms appear frequently. Flags, vertical bar equals external, vertical bar static. Turns on the external and static bits in flags, while flags ampersand equal tilde open paren external or static close paren semicolon turns them off. And if open paren flags ampersand paren external vertical bar static close paren equal 0 ... is true if both bits are off. Although these idioms are readily mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly, rather than by bitwise logical operators. A field is a set of adjacent bits within a single int. The syntax of field definition and access is based on structures. For example, the symbol table pound defines above could be replaced by the definition of 3 fields. Struct unsigned is keyword : 1 semicolon. Unsigned is extern : 1 semicolon. Unsigned is static : 1 semicolon. Close curly brace flags. This defines a variable called flags that contains 3 1-bit fields. The number following the colon represents the field width in bits. The fields are declared unsigned to emphasize that they are really unsigned quantities. Individual fields are referenced as flags.isKeyword, flags.isExtern, etc., just like other structure members. Fields behave like small unsigned integers and may participate in arithmetic expressions just like the other integers. Thus, the previous examples may be written much more naturally as flags is underscore extern equals flags is static equals 1 semicolon. Turn the bits on. Flags is extern equals flags is static equals 1 semicolon to turn the bits on. Flags.isExtern equals flags.isStatic equals 0 turns them off. And if open paren flags.isExtern double equals 0 and flags.isStatic double equals 0 close paren ... to test them. A field may not overlap an int boundary. If the width would cause this to happen, the field is aligned to the next int boundary. Fields need not be named. Unnamed fields with a colon in width only are used for padding. The special width 0 may be used to force alignment to the next int boundary. There are a number of caveats that apply to fields. Perhaps the most significant, fields are assigned left to right on some machines and right to left on others, reflecting the nature of different hardware. This means that although fields are quite useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Other restrictions to bear in mind: fields are unsigned. They may only be stored in ints or equivalently unsigned. They are not arrays and they do not have addresses, so the ampersand operator cannot be applied to them. Section 6.8 Unions. A union is a variable which may hold at different times objects of different types and sizes, with the compiler keeping track of the size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. For example, again from a compiler symbol table, suppose constants may be ints, floats, or character pointers. The value of a particular constant must be stored in a variable of the proper type. Yet it is most convenient for table management if the value occupies the same amount of storage and is stored in the same place, regardless of its type. This is the purpose of a union, to provide a single variable which can legitimately hold one of several types. As with fields, the syntax is based on structures. Union, utag, open curly brace, int ival semicolon, float fval semicolon, char star pval semicolon, close curly brace, uval. The variable uval will be large enough to hold the largest of these three types, regardless of the machine it is compiled on. The code is independent of hardware characteristics. Any one of these types may be assigned to uval and then used in expressions, so long as the usage is consistent. The type retrieved must be the type most recently stored. It is the responsibility of the programmer to keep track of what type is currently stored in a union. The results are machine dependent if something is stored as one type and extracted as another type. Syntactically, members of a union are accessed as unionname.member or union pointer right arrow member, just as for structures. If the variable utype is used to keep track of the current type stored in uval, then one might see code as if open paren utype double equals int, close paren printf paren double quote %d backslash n double quote comma uval dot ival close paren semicolon, else if open paren utype double equal float close paren printf open paren double quote %f backslash n double quote comma uval dot fval close paren semicolon, else if open paren utype double equals string close paren printf double quote %s backslash n double quote comma uval dot pval close paren semicolon, else printf open paren double quote bad type %d and utype backslash n double quote comma utype close paren semicolon. Unions may occur in structures and arrays and vice versa. The notion for accessing a member of a union in a structure or vice versa is identical to that for nested structures. For example, in the structure array defined by struct open curly brace char star name semicolon int flags semicolon int utype semicolon union open curly brace int ival semicolon float fval semicolon char star pval semicolon close curly brace uval semicolon close curly brace symtab open square bracket nsim close square bracket semicolon. The variable ival is referred to as symtab sub I dot uval dot ival, and the first character of the string pval by star symtab sub I dot uval dot pval. In effect, a union is a structure in which all the members have offset 0. The structure is big enough to hold the widest member, and the alignment is appropriate for all types in the union. As with structures, the only operations currently permitted on unions are accessing a member and taking the address. Unions may not be assigned to, passed to functions, or returned by functions. Pointers to unions can be used in a manner identical to pointers to structures. As an aside, the above limitations on unions are just no longer accurate. Like structures, modern C compilers can assign the contents of the union to another union variable. You can also pass unions into functions by value and receive a union as the return type of a function. The storage allocator in Chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. Section 6.9 Typedef. C provides a facility called typedef for creating new data type names. For example, the declaration typedef space int space length semicolon makes the name length a synonym for int. The type length can be used in declarations, casts, etc. in exactly the same ways int can be. Length, len, comma, maxlen, semicolon. Length, star lengths, open square bracket, close square bracket, semicolon. Similar, the declaration typedef char
star string semicolon makes string a synonym for char star, or a character pointer, which then may be used in declarations like string p, line ptr, open square bracket, lines, close square bracket, alloc, open paren, close paren, semicolon. Note that the type being declared in a typedef appears in the position of a variable name, not right after the word typedef. Syntactically, typedef is like the storage class, extern, static, etc. We've used uppercase letters in these examples to emphasize the names. A more complicated example, we could make typedefs for the tree nodes shown earlier in the chapter. Typedef struct tnode, open curly brace, char star word semicolon, int count semicolon, struct tnode star left semicolon, struct tnode star right semicolon, close curly brace, tree node, star tree ptr. This creates two new type keywords called tree node, which is a structure, and tree ptr, which is a pointer to the structure. Then the routine talloc could become tree ptr, talloc, open paren, close paren, open curly brace, char star alloc, open paren, close paren, semicolon, return, open paren, tree ptr, close paren, alloc, open paren, size of, open paren, tree node, close paren, close paren, close paren, semicolon, close curly brace. It should be emphasized that a typedef declaration does not exactly create a new type in any sense. It merely adds a new name for some existing types, nor are there any new semantics. Variables declared this way have exactly the same property as variables whose declarations are spelled out explicitly. In effect, typedef is like define, except that since it's interpreted by the compiler, it can cope with textual substitutions that are beyond the capabilities of the C macro preprocessor. For example, typedef int open paren star pfi close paren open paren close paren semicolon creates the type pfi to mean pointer to a function returning integer, which can be used in contexts like pfi strcomp, numcomp, swap in the sort program in chapter 5. There are two main reasons for using typedef declaration. The first is to parameterize a program against portability problems. If typedefs are used for the data types, which may be machine dependent, only typedefs need to change when the program is moved. One common situation is to use typedef names for various integer quantities and then make an appropriate set of choices of short, int, and long for each host machine. The second purpose of typedefs is to provide better documentation for a program. A type called tree ptr may be easier to understand than one declared only as a pointer to a complicated structure. Finally, there's always the possibility that in the future the compiler or some other program such as lint may make use of the information contained in typedef declaration to perform some extra checking on the program. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. Their book is copyright all rights reserved by AT&T, but is used in this work under fair use because of the book's historical and scholarly significance, its lack of availability, and the lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in a historical context amidst the major changes of the 1970s and 1980s as computer science evolved from a hardware-first, vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn C programming because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.
Hello, and welcome to Object-Oriented Patterns, a historical perspective. We're going to cover a number of different things in this lecture. First, we're going to do a bit of a review of object orientation from previous courses. Then we're going to take a look at historical perspective across time and a bunch of different programming languages. The important part about that is that object orientation is a concept. It's not just a syntax. And so by looking at different syntaxes, we'll have a better understanding of the underlying concept. Then what we're going to do is we'll look at how one might have used C to build object-oriented support into a language like, say, Python, for example, or C++. And then we're going to look at building a Python string class in C, a Python list class in C, and then a Python dictionary class in C, sort of showing how C is also the foundation of most modern object-oriented languages. So if you take a look at the other courses that I've taught, I have been teaching object-oriented. If you've taken my courses, I have been teaching you object orientation for a long time. One of the things you'll notice is that I just keep coming back to it. If you look at Python for Everybody, Chapter 14 is about object orientation. I claim that Django for Everybody is really a class in object orientation because Django itself is a collection of cooperating objects. You create Django applications by creating objects that are being sent messages, which is very much a purely object-oriented concept. I cover object-oriented JavaScript, particularly because JavaScript is a little bit different. I cover that in both Django for Everybody and in web applications for everybody. And so we're going to take a look at all these different syntaxes of object orientation, and then we're going to try to build our own objects, but in a non-object-oriented language, i.e. C. I am not going to teach you object orientation in this lecture. I am going to do a very, very brief review. On my other lectures, mostly what I wanted you to know was terminology. So the most important terminology is a class. A class is not an object. It's a template to make objects. It's like the cookie cutter in the cookie methodology. An attribute is some data that you can contain in each instance of the class, and a method is some code like a function that operates within the context of the instance of the class. The object is a particular instance of the class stamped out from the class when a new instance of the class is requested. So you have one class, then you have many, many instances. So if you do a user-defined class in Python, you see that we have a special keyword class, which is different than def, and within it we have attributes and we have methods. So the methods look like functions, but in particular, the methods inside of a class always have this first parameter, which by convention we call self. You could call it literally anything else, but if you did, people would be confused because the convention is so strong that SELF is always the first parameter of every method inside of Python. So in it is the instance and then two parameters. And then we can look at attributes like self.x and self.y and then assign them in this case to the x and y from the call. So we have a couple of methods like def dump, and again, a dump itself is a zero parameter method, but it always has the instance. And then we look within it, we can say self.x and self.y and look at all the attributes, and we can use the ID function, which we learned in the last chapter, which is kind of like an address lookup function in Python. And so what we have here is we have a little method called origin, which takes the distance for our point from the origin to our point and takes the square root of the two sides of the triangle squared. So if we then get out of the class definition and move into the actual code, we call pt equals point4050. That is how we call the constructor. Point is the class name, and then the parameters to the constructor are 4 and 5 in that example. Point.dump, that's the dump method inside a point. And you can pass the parameter pt, which is the instance. So pt ends up being the instance of this point object. But the more common syntax is to not use the class name and the method name and explicitly pass self in, but instead in the next line we see print origin and then pt.origin. Well, pt.origin is expanded to point.origin, and then the first parameter is kind of added on, which is pt, which is the instance. Now, I've got a del parenthesis pt close parenthesis, and that is the destructor. Now, in Python, the destructor would get run automatically at the end of the program. So in this case, that destructor is a little bit redundant. So now I want to take a bit of a historical look at object orientation. So if you've seen any of my other classes, I try to put the programming languages that we're learning in context. And these are the common programming languages like Python and PHP and JavaScript. And now we're teaching C. And so if you look at this, the idea is you can see that the language C has been the inspiration for virtually all of the modern languages that we use today and that I've taught you. Python while the syntax of Python doesn't look like C, Python has been inspired. We see things like there's formatted printing that talks directly to the underlying C implementation because C Python, not every Python, but the C Python that we normally use is written in C. So C, as we've said many times in this class already, is profoundly influential in the syntactical evolution of procedural programming language. So we've seen this before. But if we think about object orientation, the inspiration and evolution of object orientation really took sort of a different path through a bunch of languages that you may or may not have seen or heard. So the oldest language on this is Fortran in 1955, and Algol 60. Algol 60, I don't have it marked as like that Algol 60 was inspired by Fortran, but probably the better thing to say was that Algol 60 was created in spite of Fortran. So Fortran was loved by some and not loved by others, and Algol 60 is more what the computer scientists of the day in 1960 decided. So there's a series of languages that were popular in computer science, but not necessarily popular in general purpose programming, like Simula 67, which took a lot of the object-oriented ideas from Algol 60, and Pascal, which is a procedural language, which is another language that I learned in the 70s when I was going to school. And if you look for, so Algol and Simula were languages that were mostly procedural but had object-oriented concepts in them. I always think of the most object-oriented languages as Smalltalk. It's not necessarily the first one, but it feels like it's the one that developed the notion of object orientation the most. But it really took inspiration from an earlier language, which was Lisp. And so Lisp was an early 1960 interpreted language. Lisp was often thought of as the foundations of artificial intelligence. Now, Scheme in 1975 was a derivative of Lisp, inspired by Lisp, kind of the next generation of Lisp 15 years later. And it had a bunch of object-oriented concepts in it as well. And so you can kind of see where the object-oriented notions were evolving kind of independently from the preferred syntax. And then in the 70s, when C came along, it really changed the way we think of syntax. And so it inspired C++, inspired Java, JavaScript, C#, and PHP. But then what happened is each of these things kind of took different inspiration from different object orientation. So there's really almost an independent inheritance of where the inspiration for the language came from versus where the inspiration for the object-oriented pattern. And probably the biggest thing that you see is C++, which is early 80s, took its inspiration both from Simula and from C. So it was a hybrid language that tried to take the object-oriented notations from Simula and layer them on top of the procedural syntax of C. Now, another interesting thing here is that Python in 1991 was quite aware of C++. And so if you look at PHP, which in 1995 was not at all object-oriented, it wasn't object-oriented until 2000, Python was object-oriented in sort of almost 1991-92 because the computer scientists of the day were quite aware of these kinds of things, and so Python sort of implemented object orientation almost as soon as Python was implemented. And so, like I said, Python 1991 implemented object orientation, and I really like the object orientation in Python. PHP implemented non-object oriented in 95, but then added objects in 2000. Java took a lot of inspiration from C++. Java was trying to be the next C, and so it's got a lot from C, it's got a lot from C++, And then C# was inspired by C++ and Java. But then JavaScript is kind of like the outlier. JavaScript, even though it came out in 1995 and was very much informed by Java, it took its object-oriented pattern more from Scheme, which is a more pure object orientation rather than an object-oriented layer. And so JavaScript, among all of these things that we'll look at, JavaScript is sort of the outlier in terms of its object-oriented approach. And if you've taken classes from me in the past, I've mentioned that before, because JavaScript has first-class functions and the way you create things, etc., etc., etc. So we're going to take a look at some of these object-oriented implementations over time. I've already talked about the Python inspiration. I flipped Python and C++ in the early days because at least Python we kind of know. C++ is 1980, Java in 95, JavaScript in 95, PHP in 2000, and then C# in 2001.
It was highly collaborative in the sense that this was a group of, make up a number of 30-ish people who were all interested in much the same kinds of things, although with tentacles off into, theoretical computer science, math, and so on, physical sciences kind of thing. But mostly, a lot of us at least, were basically software people. Bjarne came to Bell Labs, I think, in 1979 after getting his PhD at Cambridge. And he was interested in simulation. He'd known Simula in particular, which was probably one of the very first object-oriented languages. And he wanted to do simulation, but C was kind of the language that people used at Bell Labs. And so what he did was to try and take some of the good ideas from Simula, in particular class ideas, and put that on top of C. And for a long time, the implementation of C++ was basically translate C++ into C, and then you could run it anywhere. So it's one of many pragmatic engineering decisions that Bjarne made, that if you want, it's hard to get people to buy into a new language if they have to carry an enormous amount of infrastructure and support and other baggage with it. Whereas if it's one more program that then fits perfectly into your existing environment as a language, as libraries, and all the rest of it, much easier. And so C went through a period of evolution. Well, it's still evolving. But starting there in the very early, 1980, 81, something like that, the two languages were very much together because we're all in this one group at Bell Labs. It would fit comfortably in this corridor, this building. And Bjarne certainly knew C inside out, and then was developing this new language that ran on top of it that stressed C compilers, so that was useful because the code that his preprocessor generated was astonishing. And I think some of the ideas in C++ then retrofitted back into C, in particular the obvious one of how you declare the arguments for a function. I mean, that was better. And a handful of other things. So for a while, the two languages, you could say that C was a pretty close to perfect subset of C++. I think that's evolved in both directions, and so it's less true now than it was. But for a long time, you could take a C program and just run it through a C++ compiler, and it would work. There's a general observation that people write code differently than computers write code. And so machine-generated code tends to stress, in particular, the compiler or the language for which you're generating. And so in the C++ to C example, they were incredibly deeply nested constructs of one sort or another, parentheses that made Lisp look tame, and then very convoluted pointer kinds of computations as well, function pointers, all kinds of, and so it was definitely a stress test, and also generating things that had odd sizes and so on that were not expected, or at least paths that had maybe not been thoroughly tested in a given compiler. I think a lot of people did not think that C++ was right in some sense. It had various warts, blemishes, and so on. Many of those were, again, a direct result of Bjarne's engineering judgment. If you want this thing to take off, the more culturally compatible it is, the more likely it will do that. If you make something that's wildly different, people are going to kind of ignore you. And so some of the syntactic problems of C++ that are still with us are, the same syntactic problems that you see in C. For quite a while, when I was trying to teach C++ to people, I would show them the translation that goes from a C++ object into C. And, it's basically just pointers into structures with the compiler kind of keeping the names apart so you don't have to think about them. And seeing that translation, you could see how object-oriented programming could be done at essentially no overhead, because it's just structure pointers and funny function names, and you can pass function pointers around. So it was all pretty well behaved, and I think that it helped me understand what was going on in C++ and object-oriented programming and so on. I think in modern languages, and Python, a fine example of that, there's an incredible amount of magic going on there, and I don't quite know how it's done as well as it is. I can sort of imagine, but the mechanisms to make some of those things, list comprehensions with lambdas in them and so on, how the heck does that work?
I was trying to characterize what is C++ particularly useful for, what did I actually build it for, and what is its strength today after almost 30 years of evolution, and also where's the limits to where it is. So the way I see it is there's a core domain for C++, and that's what you would call traditional systems programming, but that's not the right term, because it's just a style of language and a style of programming. So I go a little bit further. I said, what is it that requires the kind of services that C++ has? What is the sum of all these applications I've been dealing with? Where did it work and where was it essential? And I came up with the phrase infrastructure, and I roughly define it as if it breaks, somebody gets hurt or somebody gets ruined. These are the kind of foundational things in our systems that must work for the system, for the society to work. The question I'm trying to phrase is what matters in those areas. And I've come up with some notions of compact data structures, very strongly typed interfaces for maintainability and for minimizing errors, a heavier emphasis on algorithms over random code, because we need reliability, we need the stuff to be comprehensible, analyzable. We want to make sure that it's actually correct. And so the paper I was writing come from that kind of thinking. What is the right style, and what are the supports for that style we need for infrastructure software, for software that must be dependable? And we can get real examples, sort of the keys of some of the modern operating systems, the basics of our phone system, the brakes in my car. How do we make that dependable?
how do we make sure that the space probes don't get the logical equivalent of your blue screen of death halfway to Mars, where we can't send a repairman? How do we make sure that they actually go into the right orbits? And JPL lost a probe off Mars because two groups had communicated nicely, they thought. But in fact, one of them spoke imperial measures and the other one spoke the SI system, the MKS system. And the result was a misnavigation that sent more than $500 million worth of equipment into the wrong orbit. Not a good idea. It was the work of 200 good engineers, lifetimes work, down the drain. And that could have been avoided by ever so slightly improvement in the interfaces between the parts of that program. So things like that I'm interested in. So there's a core area where I think the facilities for C++, they're not perfect, but the kind of things I would like, the kind of things I work on are essential. And then there's a huge gray area where you have choices. They can help, in my opinion, but they're not essential. And then you have areas where it probably is unsuitable to apply that kind of stringency technique. I mean, I want to essentially get 100% reliability. If I'm putting up a small application for my own use, or if somebody is trying to push out a little cute web app, they don't need that kind of reliability, and maybe what I'm talking about in terms of programming is not for them. But I think the really important thing here is to realize that there are different techniques, different languages that apply to different areas, and we have to recognize this. We can't have a single language for everybody, a single technique of using that language for everybody. We can't have a single tool chain or a single kind of system. And from there, we can go a little bit further. We probably don't need the same kind of training for education for everybody. The engineer, software developer, or whatever, that is building infrastructure, say the mechanism that automatically updates the software on a cell phone, has to have a different education, different knowledge, different training from the one that makes a little game. Because the one can actually destroy a whole day or a whole week for millions of people by a little slip. Maybe even somebody gets hurt. If the 911 calls don't get through, bad things happen. And it's not just the software that runs on it, it's the update software, it's anything in the chain of safety critical issues that has to be dealt with. But somebody doing that has to think differently from somebody who writes a little application, maybe to make a couple of bugs quickly. There's nothing wrong with that, but they have to think different. As a matter of fact, if you apply this very stringent engineering-oriented thinking to little commercial apps, you'll probably be a year late to market, and it'll be irrelevant. On the other hand, if you took the attitude of first to market is the only thing that happens, and apply them to the steering wheel of my car, no, that's not a good idea. These people have to think different, and the way you get people to think differently is to give them different educations. We don't have an ANSI standard programmer, and we shouldn't have. If it was, we should have several. And I think the field has to, in some sense, clean up its act before somebody else comes in and try and cleans it up for us.
This notion that you can sort of make your own constants and have the seconds after the constants, is that a feature that you added at some intermediate stage, or is that simple sort of operator overloading?
We were observing that we were getting a whole zoo of little suffixes out of the various fundamental types. So the U suffix is for unsigned, and L is for long, I think, and I can't remember them all anymore. And we thought, you can do anything in C++, but you can't make your own literals. And then I'd observed separately that there was techniques that were effective, except that people would not use them because the notation was too ugly. The Unix example is Unix example is one of those. You've been able to do everything in the Unix example I showed. Not quite as elegant, but you can do everything I showed for the last 10 years. Libraries have been available. There was a nice one from Fermi Labs, back to nice places and nice people again. But it wasn't used as much as it should because the users didn't believe in the notation. They didn't like it. And so we were looking at how can you basically clean up people's source code. How can we make code look the way it would look in an ideal language? How can we make code look much as it does in the textbooks? So the Unix example is simply a way of getting your code to look the way the equations look in your physics textbook. I mean, we know how to avoid that Mars climate orbiter problem. Everybody had been taught it in physics in high school. First, make sure your units match, then do the detailed calculation. So why didn't people do it? It was too cumbersome and it was too ugly when they did it, or too costly if they used runtime techniques. So I, together with friends, we thought this problem was worth addressing, tried to figure out what solutions we had, went through several evolutions. I think the last finishing touches was done by David. And it's now standard. This is one of the features that is not shipping widely today. But wait a year and that example will probably run on your computer too.
Are there other kind of examples where you've let people from within a class create their own literals beyond sort of suffixes?
When I started out with C++, I provided constructors, which allows you to construct objects of a certain type from arguments. And that has been very effective, and people have used constructors as if they were literals, but they weren't. There was a runtime cost. So the first thing we did with C++ OX, C++11, was we introduced constant expressions as a more fundamental unit. This was work between me and my colleague Gabriel das Reis. And we have const expr functions that can be evaluated at compile time. And we have const expr types so that you can use type-rich programming at compile time. This is very important in sort of the high-performance computing and in the embedded systems world. That was what we did to address that. Constant expression evaluation is much more general, much easier to use, and yes, more pretty in C++11 than in earlier versions. So that just strengthens what the direction we've gone before. So you could write complex 1, 2 to make a complex number in C++ in 1984. Today you can write the same thing and have the complex number created at compile time, and therefore say put in ROM. I don't know why you would want a complex number on ROM, but you might want a point, which is the same thing, point of 1, 2. Now, you still have to write point or complex. And the other thread of thinking in C++ was to generalize and make safer the initialization. And so it happens that if you know the type you need, like you have a function returning a complex number, you can simply write open curly 1, 2, and it says, oh, 1, 2 is supposed to make you a complex number, and it will make a complex number and return it. And if you happen to be at compile time, it'll do that at compile time. So things work together, you get better notation, you get better performance, and anything you can do at compile time works even better in a concurrent system because you can't get a race condition on a constant. If it's been calculated before the program starts, you can't get the threading problems.
So open curly means find a constructor for the thing that I'm about to put this in.
Yes.
It looks at where the destination is,
Yes.
and it says, is there a two parameter constructor or a 3-parameter constructor or whatever?
Or if it's just a struct, it'll take the first element and put it in the first element and second.
It does it for a struct as well?
Oh yeah.
See, I haven't played in C++ in a while. That's a great
I
idea.
refer to this as uniform and uniform initialization. It'll initialize if it can. And if there's any ambiguity, it of course finds the ambiguity. If you're in a context where like you're calling a function, and the target could be a point or a complex number, it's a tough luck. Go and
Tell
try
me,
again.
or tell me.
So the error checking has actually been improved. C++ 11 is slightly better at finding bugs than C++ 98 was. I mean, I come from the school of philosophy that says that the compiler is your best friend when you generate code, when you build programs. And to make it your best friend, you actually have to have more types. If everything is an integer, well, what can the type system help you there? No, it can't. If everything is a floating point number, it can't tell you whether it's imperial or SI units, and you get bugs. So you need type-rich interfaces, and for that you need to be able to build cheap types, basically, and flexible types.
And convenient.
Types that's easy to use, simple. And so we worked from complex of 1, 0, 1,2 or something like that. So curly is 1, 2, and the type is optional, it's only needed when it's needed. And then finally, we can now write, if we wanted to, 1 plus 2i. Define I as the unit for the imaginary parts, and you get complex arithmetic without ever saying complex. It's down in the definition of the I suffix.
So we're going to take a look at some of these object-oriented implementations over time. I've already talked about the Python inspiration. I flipped Python and C++ in the early days because at least Python we kind of know. C++ is 1980, Java in 95, JavaScript in 95, PHP in 2000, and then C# in 2001. So here's the example that I showed you before. Talked about it before. You have a constructor, double underscore init, double underscore with self as the first parameter. Self.x, again, the key thing is self is by convention. Self is not a language construct. It just so happens that the first parameter of method calls is to the instance, and we almost exclusively use the word self for that. That is a very early 1991 implementation of an object-oriented syntax on top of a mostly procedural language. Now if we take a look at C++, C++ was initially implemented as a pre-processing pass, and it did one-for-one textual transformations, and so class was not a keyword in the C language. Public, that's not a keyword in the C language. There was syntactic transformation that kind of transformed it into C and then ran it through the C compiler. And so we say, and this is pretty elegant, and you can absolutely see how Python was inspired by C++. So class, point, open curly brace, double X and Y are the attributes, and the constructor by convention is it's a function that has no type. The constructor is the exact same name as the class. So in this case, I've got point with an uppercase P. And then the constructor parameters come in. Now, the interesting thing is you have to declare as double X and Y as the attribute variables. And then within the function, you can think of the double XY as almost like extern scope, means they're global across all functions. So you have this weird thing where you can't have a parameter like you could in Python You can't have a parameter the same name as an instance variable or you'll be confused. And so you'll notice I called the xc and yc as my parameter variables so that I know that those are parameters in a constructor. And so I can copy xc into x and yc into y. And it also means if you look at the dump code, you see like you don't have to say self.x, you just say x and y, because x and y are doubles. They're instance-wide extern variables, as it were. And the same is true in the origin function that's returning the square root of x squared plus y squared. You don't have to have self or this or anything else. So if we take a look at the main program, on that first line, point, pt open paren 4.0, 5.0, we are both allocating a point instance and calling the constructor and setting it up. Then we use the dot syntax, pt.dump, open paren, close paren, semicolon, to dump it out. And then we can call pt.origin, and then that will return us a double. And so you'll see this sort of dot syntax that becomes pretty common in every language that comes afterwards. So let's take a look at Java. Now recall that Java was inspired both by C and C++ and really wanted to be like the super language. And you see that it looks a lot like C++, but it does introduce the concept of this, so that it scopes the external variables that are the instance variables. You access an instance variable by saying this.x and this.y, rather than just x and y. And I think it's actually more elegant this way. So we say public class point, and then double x comma y, which are the instance variables. And then the constructor is using the C++ convention of point with no type. Double x and double y are the two parameters. This dot x equals x, and this dot y equals y. Close curly brace. Now I like this better because using this does not keeps me from having to make weird function parameter variable names. I can make them what I want to be, and this is the way, using this is the way that we contextualize that. So if we look at the dump method, we see the use of this, and this is not just by convention, this is a language element. So this is the pointer. You can see from the output, it actually prints out the class that it is and some kind of reference like ID-like thing. And so Java actually, if you start printing objects out, it tells you what its type and what instance it is. It's not necessarily an address, but it probably is related to the address somehow. But then we print out this.x and this.y. And then if we look at the double origin method, we see it's this.x times this.x plus this.y times this.y. So you see the sort of use of this throughout. And then if we look at the main program, we see point pt equals new point 4.0, 5.0. This is where we see the use of this new operator, where you're saying, look, call the constructor. And I like this. I like the sense that you're calling the constructor on purpose. You're not calling it implicitly. And then you end up with pt as the instance of this object. And so for me, this feels pretty good. pt.dump is a good example of calling a method within the instance, and pt.origin is similar. If we take a look at JavaScript, and recall that JavaScript is the weird one. JavaScript did not take its inspiration from C++. C++'s syntax was kind of influenced by the fact that it was initially a preprocessor to the language C. And some computer scientists would think that that's a rather impure way to think about object orientation. And so the JavaScript, when it was created, the idea is to be more pure in object orientation. And so the concept of first-class functions, because it has first-class functions, there is no class keyword. The class keyword was really useful when it was a preprocessor. The thing that JavaScript does take is the concept of this. Now, the interesting thing is if you look at everything on the screen from function point to the closed curly brace, this is the constructor. The constructor constructs everything. It constructs the attribute variables, and it actually constructs all of the methods as well. So if we look at the line this.party equals function open paren, close paren, open curly brace, we are setting, in a sense, an attribute variable to source code. This is an anonymous function. There's no name to the function, so most functions are named, but this function has no name. That's a JavaScript thing. It's a first-class function thing. We are basically not running that function with the 2 lines of this.x equals this.x plus 1 and console.log, blah, blah, blah. Those lines aren't running. They're being compiled, and then the code to execute that is being assigned into the attribute variable party. So it doesn't run it. It reads it and stores it in party. You can literally later print out this.party, and you will see the source code to that function. And the same is true for this.dump. It's an assignment statement, and then similarly this.origin. And you see within those methods, you see this.x and this.y, which is taken directly from Java. We also see the concept of new in PT equals new point 4.0, 5.0. We're explicit, and I like this. I like the idea of saying, please call the constructor from the point class and pass these 2 variables in. And then we see the C++ inspired syntax of pt.dump to call a method in the pt instance and pt.origin to call a method in instance. If we look at PHP, now the key to PHP is PHP is a procedural language when it was created in 94, and then it became an object-oriented language in PHP 4 and then 5. It was late to the party, so it could be inspired by everything, by JavaScript, by Java, by C++, by Simula, by Scheme, all of those things. And so the PHP object orientation is kind of pretty as a result of that. Now, one of the things that happens in PHP is it's got some weird language syntax things, in that variables have to start with a $sign. Thank you, Perl, for that. And the dot operator is used for concatenation in PHP, so we couldn't use the dot operator to look up instance variable or a method inside of an instance. PHP borrowed the C arrow operator, which is -sign greater than. Now, the interesting thing is if you go back to pointers, the arrow operator is what you do when you have a pointer to a structure. And so in some ways that is a throwback to C in a beautiful way, because I think kind of under the covers, and as we shall see when we are starting to implement object orientation in C ourselves, we're going to see that pretty much we get pointers to, an instance is a pointer to something rather than a thing. And so we see this arrow x equals $x in the constructor. We see the constructor is a _ construct, so that PHP kind of used the single underscore and double underscore as sort of metadata about the meaning of things, and double underscore are things you're not supposed to call, they're supposed to be private. And then we have a function dump, and you see the concepts of this inside of dump. In origin, you see this. In the main code, you see $pt equals new point 4050. Well, it's following the new from Java and others. And then we call pt arrow dump, and then $pt arrow origin. It pretty much works like most of the other ones, except that you'd never use dot, because dot is concatenation in PHP. And I'll be honest, I love dot for concatenation, except for the fact that PHP is different than every other language that I use. Every other language uses plus for concatenation of strings. Now, C# is 2001, so C# was inspired kind of by everything. And so you see that C# is clearly a very C++ oriented, but with some Java-ness to it. So you see the $xy in the class, which is the 2 instance variables. You also see that there's no use of this, and so you see that we have to name the parameters differently, because x and y are in effect global across the entire class. And then we have, void dump there, and then we see that it's just using x and y, no need to use this. It's tough for me to decide which of these 2 ways I like better. I guess that this feels more explicit to me. So I like Java and JavaScript in that respect. I like self also. If we look at the origin function, we see x*x plus y*y, and so we don't need to use this. We again see a very Java-oriented point pt equals new point open paren 4.0, 5.0. Point.dump, we're using the dot operator to look at instance variables and methods within the class, and then point.origin. So now that we've looked at sort of a survey of the different kinds of object-oriented languages that are today, and we can sort of see how they derived ideas from one another, now we're going to actually try to build an object in a non-object oriented language. So we're going to build like a Python object in C. So now what we're going to do is we're going to try to build objects in C. C doesn't have object-oriented support, so in a sense we're going to do it by writing functions and using structures and pointers, etc. So we're kind of answering the question about how was Python's object-oriented layer layered on top of a C structure. So we can kind of put ourselves in the position of Guido van Rossum as he was building Python in 1991, and say, how are we going to make this syntax work? How are we going to, in C, which is underneath all of this, how can we make this syntax work? And so this is just review. You know, we got class point, we got a constructor, takes two parameters, self is our instance pointer, and we got dump and we got origin. And then if we look at the main program, we create a new point, call the constructor. We can see that point.dump, that is the function name dump inside a point, but then we've also got to pass the instance in, or the shortcut syntax. And so the pt.origin open paren close paren, that is kind of paying more homage to the way C++ would have called methods, and then of course the del operator at the end. So let's build ourselves some code in C. We are building, in effect, a point object in C. So we're going to just start with a structure, and the structure is going to be point, and there's some instance variables. We're going to just allocate a double x and a double y inside of it. But then the methods are kind of weird. We are going to take the del method, the dump method, and the origin method, and we're going to define them as pointers to functions. So void open paren star del close paren open paren construct point star self close paren semicolon. The void is the return type of this function. Star del means a function named del that the code is not here, but this points to a function somewhere else. And then the const struct point star self, that's the first parameter, right? And so construct point star self is the fact we're going to have one parameter. It's going to be named self, and it is a pointer to a structure. And we've got something similar to in dump. The origin is pretty much the same, except it's got a return value. Okay, and so that now is a structure. This is C, so the structure is going to allocate two doubles, which is should be 8 bytes each, and then 3 pointers, which is 8 bytes each. So we got 8 times 5. That's going to be 40 bytes. It's not a dynamic structure. It is exactly 40 bytes of allocation, because C structures are just memory, and so it's not like you can sort of throw more stuff in there. You got to define it, you got to define what type it is, and it's going to allocate space. We are going to use a naming convention for now, and we're going to create the dump function. And the dump function is going to take a self parameter, and we're going to name it point_dump. That's just a naming convention. And we're going to name the first parameter as it comes into our function self, just like Python. We're going to print out object point at and then %p, which is the way we print a pointer out. So self is a pointer. X equals %f, y equals %f. And then we're going to print out self, and self arrow x and self arrow y. Now remember, that kind of looks like PHP because self is a pointer to a structure, not a structure itself. So we use the arrow operator to both dereference self and then look up the attribute variable x. So if you look at the output, you see it's object point at big long hex number for the address, and x equals 4, y equals 5. And then we have the void point del, which is very similar. Construct point star self. So the first parameter to del is self, and all of the first parameters are always going to be self when we create these functions that we're going to treat as methods. And then we're going to free. That's all that's going to do is call free on the pointer where we originally allocated it. Then we're going to create the origin method, and again take a single parameter self, and we're going to return the square root of self x times self x plus self y times self y, and that's going to have a return value. And then we're going to go and do the constructor. And the constructor is going to return a pointer to a point, and it's called point new. We're going to sort of follow the new convention, and it's going to take two parameters, an x and a y. So the first thing we've got to do is we've got to allocate the 40 bytes, size of star p, which is a double, two doubles, and two pointers to functions, which I think I've got it right, is 40 characters. And then we're going to we'll get that address of 40 characters back, and we're going to set the x value to be x from the constructor, the y value to y from the constructor call, and then we're going to set the dump pointer to ampersand point dump. Now this is done on purpose, where point dump is defined earlier in the file, and then p origin is the same thing, point ampersand point origin. So in each object that we're creating, we are going to record the address of three in effect global functions, right? They're named point underscore, but these are just regular old functions in the global function namespace. Right now we don't have namespaces. We're in C, folks. We can't sort of do that fancy stuff, so we just use a naming convention to accomplish it. And then when we're done with the constructor, we do return P, so that whatever is calling us gets their instance back. So P is the instance, but we are in the constructor allocating and filling the instance up with data. And it's just a struct. It's just 40 bytes of memory with some labels. So in the main code, we say struct point star pt equals point underscore new, and then paren 4.0 comma 5.0. And this looks a lot like OO code, except it's not. We're using a pointer to a structure, and we're calling a global function called point new. We just happen to have named it in a way that looks a lot like object orientation. And so now what we can do is we can say pt arrow dump, which means go look up the dump variable inside the point object that's pointed to by pt, and then call it. But we still have to pass in pt as that first parameter, because that is self. That is the instance. So all these functions, dump, del, origin, all need to have as their first parameter self. And so pt dump looks up dump, but then we still have to put pt in as a parameter. And that syntax, we're going to do the same thing for pt arrow origin, open paren, pt close paren, and then to clean things up. And in this case, we need to, well, the program is done, but you need to free up allocated memory. So the memory is allocated in the constructor, 40 bytes is allocated in the constructor, and then those same 40 bytes are deallocated by calling free in the destructor. And so we for all intents and purposes, there is, other than conceptually, there is no objects involved in this. There's structs, there's pointers, and there's functions. The fact that you can get a pointer to a function means that we've kind of imitated it. And again, I look at this as how Guido van Rossum actually was like facing this and thought to himself, how am I going to figure this out? How am I going to make it look like this is object orientation? So this is kind of probably some of the code looked a lot like this in the early days of Python. And then there was kind of a simple syntactic transformation layer in the Python sort of parsing to call these things with naming conventions. So you can do a lot of object orientation with naming conventions. And if you recall, C++ started as a language preprocessor. And so again, you could almost look at this as, how did C++ get built? Right? C++ had some OO syntax that then transformed the OO syntax into C code that looks a lot like this, which is, we got some functions. The functions have naming conventions, and we create a struct, and that struct has data in it, but it also has pointers to function in it. And we'll call the data the attributes, and we'll call the pointers to the functions the methods, and voila, we have object-oriented programming. So up next, we're going to actually implement the Python string class, or at least a little bit of the Python string class. So now we're going to switch from my little point class, which is just two doubles, to an actual string class. So what's interesting about the Python string class is that you can extend it. And so we've been talking a lot about pointers and arrays, and even when you call malloc, you can't just keep extending things. Whereas in Python, thankfully, we can just extend things. We create a string, we can append a h to it, and we can print it, append hello world and print it, and then assign it to some other string, and then print that and get its length. And we never had to allocate or deallocate any memory during this time. When you get done looking at the code, what we're going to have to do to allocate and deallocate memory, what you should be thinking is, wow, I'm glad I'm programming in Python. I'm glad that Guido van Rossum gave me a string class rather than a character array of fixed length, an expandable string class rather than a character array of fixed length. So we're going to create in C, using our little convention of naming, a string class. And so if we look at the code, what we're going to try to do here is we're going to basically emulate the Python syntax, but in C. So we're going to start by making a structure, PyStir structure. We're going to get a pointer back. We're going to name that X, and we're going to call the constructor PyStir new. We're going to dump it. We're going to have a little dumper. We're going to append an H to it. We're going to dump it again. Then we're going to append a whole string. Now H in C is a character, and hello world is a multi-character string, and so we're appending many characters. We're going to dump that. Then we're going to assign it to a completely new string, and then we're going to print it out. Like Py, give me the string version of this object, or the length of it. And then we're going to delete it, throw it away. So you can see all of the Python operations are sort of mimicked, but with naming conventions in C. Now the one thing you'll notice here is in this main code, we never allocated any memory and we never deallocated any memory. That is within the object. Now within the object, we have a responsibility to properly allocate and deallocate. But one of the interesting things here is I haven't shown you the code to do any of that. And so you don't know that. But that's cool because we can use this as long as we do a new, play with it, and then do a del. We can do stuff with it. Underneath PyStir, it does all of that memory management for us. And that's one of the beautiful things about an object-oriented approach. Again, the syntax on the one side in C is pretty heavy, but in the syntax on the other side, which is the Python, is pretty light. But the idea is that in Python we never had to worry about making a string too long or too short or having buffer overrun or anything like that. So as we dive in, we have to realize that part of the job of this PyStir object is to handle all memory allocation on our behalf so we as programmers can write much simpler code. Okay? So now we are going to build the PyStir class. We're going to create a structure called PyStir, and in that we're going to have three things. The length of the string, we have how much data we've got allocated in the string, and then char data is the actual character array. And so we have to have a character array inside of it. We're not going to let the outside code touch this character array directly. We're going to completely manage it inside this object. We draw a little bubble around us, and it's like, you can do stuff, you can use my object, but I'm going to deal with everything for you, so don't mess around with my internal stuff. So what we would think of is all of this instruct PyStir is sort of private. In C, we don't have a good way to force it to be private, but in the concept of object orientation, length, alloc, and data would be something we'd think of it as private. In our constructor, we are being asked to create a new Python string, and we're going to return a pointer to that structure when it's done. So the first thing we do is we alloc it. Now int is usually 32 bits, so that's 4. Alloc, there's 4, 8. There's probably 16 characters in PyStir. When we do malloc, size of p is 16. That's the number 16, and so it's going to give me 16 characters. Now, the key thing is that is not allocating the actual string data. It's just allocated 8 bytes for a pointer to the string. Start data is a pointer, and that first malloc is only giving us the pointer, not the actual data. So then we just sort of set it up. We say our length of the string is 0. There's nothing in it. Our allocated length of the underlying data string is 10, and then we immediately call malloc to get 10 characters. So now data is a 10 character array, And alloc tells us how much we've allocated, because it's our job inside this thing to keep track of that stuff. And then just to be good, we throw \0 at the 0 position in that allocated character. We don't know what the rest of them are. We just know that the first one is 0. And then we return the pointer to the structure, not the pointer to the data, the pointer to the structure. And this gets called inside the main as struct pi_* x equals pi* new. And when we're done, we get back this cool little 2 pieces of data that have been dynamically allocated, and it's all ready for us to do cool stuff with. We got the struct, we've got the constructor, and then we've got the destructor, which is pi* del, and that again passes in self. Now we're calling free. Now if you recall, there are 2 allocated things. One is the data, which is the character array that we've got. We've got to get rid of that. And then we got to get rid of the object itself. And so at the end of del, we have given back all of the data that we've alloced. Now one thing important here is the order of these 2 statements matters a lot. So when we free self, we're not supposed to access self anymore after that point. I'm sure there could be some data just laying in there that's not been ruined, but you just don't know. And so that's why we have to free self arrow data before we free self, just because it's just wrong to do that in the other order. And so we do a pi* dump, and in that we dump out the length, we dump out how much we've allocated so far, and what the data is in it so far. And then pi* len returns an integer, and it takes self as a parameter. The key to this is it returns self length. And you might ask why it is that we don't just let our calling code access self length. And this again is encapsulation. We don't want to reveal the fact that we're keeping track of length in this variable, because we don't want the calling code to be messing with it. Remember that length, data, and alloc are kind of private. And so instead of saying just go look at self length, no, I would like you to call my function and I will give you the thing you want. So you just call the len function to pass in the instance, and that allows me to change the name of length. It allows me to interpret length differently, allows me to do all kinds of things, but at least the object writer is in control of the contract with the outside world. So by hiding all the data and giving methods to we call these accessors, to access this data is a good idea. Now the _stir, if you think of Python, it's like you can say stir, open paren, close paren, anything inside the parentheses, and it converts it to a string. Well, it just so happens that we're going to maintain self.data as a valid string. So when you say take this string object and convert it to a string ready for printing, I'm just going to return the pointer to the string we've been maintaining all along internally. We have some other methods that we've got to add. We've got to add an append to add a single character. You can see that it's got 2 parameters. It's got self and a single character ch. You got append s, which is got 2 parameters, the self, the instance, and a whole character string, which is a pointer to a character. Then we have assign, which is got 2 parameters. One is self and one is a pointer to a character string. Now, I'm not going to give you these lines of code. I'm going to give you an assignment to write these lines of code. I'm going to show you how they're supposed to work, but I'm not going to give you the code. So I'm telling you that pi* append is about 10 lines of code. Pi* append s is just 1 line of code. It's a for loop. Pi* assign is about 3 lines of code. So pi* append s calls pi* append, and pi* assign calls pi* append s. And so we do a lot of reuse here. So let's take a look at how these are going to be used in our main program. We say struct pi* x equals pi* new, which is give me a new string object. And then we're going to append a single character h to it. And then we're going to append s, a multi-character string. And we're going to dump it each time. And then we're going to overwrite our object with a completely new string. And so the key thing is you have got to build this. This is what you're going to build. Okay? But I'm going to talk a little bit about how to do it. So let's walk through what you might need to do in pi* append. Now recall that when we set this thing up, we created length, we allocated 10 characters and a 10-character array and had data point to that 10-character array, and we remembered that we had 10 characters. So the first thing that append does is it checks if the length is greater than what we've allocated, meaning that, if we're going to put in character 0, like the letter H, we can just append it and then update length. We still have 10 characters allocated and we've used 1 of them. And so we can just start appending into data, right? And we have to put a 0 after it so that the data is a valid string all the time. And so if you kind of imagine that we create the new object, we have a new object that has a length of 0, and it has 10 character array, and it has a string end character in the first character, we're good, and we have 10 allocated, and we know we have 10 allocated. Then if we add an H character, a single character H, all we have to do is add H into that array, data sub 0 in that case, and then update length to be 1, and then say data sub 1 is \0 so that we terminate it correctly. So after that first line, the data is H, it's a valid H string. So we've appended a single character, we've updated the length, and then we have terminated the string. And then we go to the next line in C, where we're just, in this case, we're going to append the letter E. And we look at the length of it, because it tells us where to put it. The length is 1, so we put it in sub 1 and add \0. And then we check to make sure that we have space for it, because we've got 10, but we've only used 2. We really used 3 because HE, end of character string, so we really used 3, but the length of the string we've got is 3. So as long as no one asks us to append more than 10 characters, append is a pretty simple operation. You just add to the character array that we've already got allocated. Okay? But, of course, it gets interesting. You can append HELLO space WOR, and at that point we have 9 characters in, our length of the string that's in data is 9. We've got it properly terminated, so we have used the 10th character to terminate the string, so we're really good. Things are great. But now the problem is we have got to append the L after the R. So we have to append the L after the R. So what we have to do is we have to call a function. We called malloc in the constructor, and now in append we're going to have to call realloc to say, ooh, I asked for 10 characters, but now I want to extend that from 10 to 20 characters. And realloc does that. Realloc says, here's a pointer, and it knows how many characters it is. Please reallocate this pointer, take this data in this pointer, and make it 20 long instead of 10 long. It might have to copy it. So let's take a look at what realloc does. So we can extend the size of a dynamically allocated area by calling realloc with the current pointer to the area and the new size. So in the constructor you see that we malloced 10, and then we're in the append and we say if the length is greater than self-alloc minus 2, we don't have space for 2 characters left, then we're going to have to realloc. So what we're going to do is we're going to change this from 10 to 20 characters. So we're going to take self-alloc, which is 10, and add 10 to it, so now self-alloc is 20, and then we're going to set self-data to realloc the old self-data 20 characters. So this realloc takes a pointer and a new size and gives us back a new pointer. Now it actually may have to move it in memory, so you can't assume that self-data is the same before and after, but you can assume that if it had to move the data to find you a 20 character slot in its free space, that it will have copied all the first 10 characters will be copied, and then you'll get a new parameter. And that's why you see self-data on both sides, both in the call to realloc and as the assignment statement. So we go back here and we can see that, oh yeah, now we have 20, and it's got plenty of space for the L and the D and the \0. So now we're going to show the code that's going to basically test our class. We're going to create a new, we're going to dump it, we're going to append a single character H, we're going to dump it, we're going to append a string. One way to make this simple is just have append S, call append repeatedly for 9 characters, because appending 9 character string is the same as appending 9 characters, not appending 1 character at a time 9 times. Then assign. Assigning a completely new string, which means that you gotta take length back, and you gotta set some things, and you gotta check the size and do a whole bunch of stuff. And then we're going to ask the pystir_stir to give us back a printable string, And then we're going to ask the PyStir_len to tell us how long this thing is. And so you get to write some code. Not too much code, probably 15 lines of code, but it is code that you will need to think deeply about, and you're going to need to understand the structures, you're going to need to understand the pointers, etc., etc., etc. Up next, we are going to make a list class. So the next class that we're going to build in C is an emulation of what you would do if you were building the Python list class in C. So let's just start by taking a look at sort of a Python and C version of this thing. In Python, we create a new list, then we append a whole string, then we print it, then we have another string, then we print it, we have another string, we print that, we ask how long is the list, we do an index, which is a positional lookup, saying where is the string Brian. Then we say if Bob's in the list, where is it? Or we say we can't find Bob. So we have to do an if then else and use in, because otherwise we'd have to use a try catch. Because if you do an index with a string that's not there in Python, it's going to blow up. So we can either do an if then else or we can do a try catch. It's sort of 6 in one, half a dozen in the other. But in C, we're going to effectively call pylist_new to create a new list. We're going to call pylist_append. And again, remember, all the time we're calling these things that are like methods, we're always putting the instance as the first parameter. In this case, LST is the instance. So we're going to append hello world. We're going to print it. We're going to append catchphrase. We're going to print it. We're going to append Brian. We're going to print it. Then we're going to look at the list, length of the list. Then we're going to look up Brian, and we're going to look up Bob. And in this case, I made it so that the index just gives us back -1 to say I didn't find Bob, so that I didn't have to try catch, because it's like a little bit more C-like. And then we do a pylist_del to clear up the memory. We are about to switch from being the consumer of the list object to the builder of the list object. And our job as the builder of list object is to dynamically allocate all the data that we need to make this thing work. And so we don't get to see the details of that. All we know is there's these functions that we can call and this structure that we can use, and if we call the functions right, somebody else is going to deal with all of the dynamic memory that makes this work. And you've done linked lists in previous assignments. So linked lists should not be completely foreign to you, but now we're taking an object-oriented approach to implementing a linked list and hiding the implementation detail within the object, which is an important part of object-oriented programming. So here's like some basic stuff, and some of this should start looking pretty familiar. We got a L node, which is short for list node. We got a pointer to a character string, and then we have a pointer to the next one. So we call that one next by convention. Next is not a keyword. Next is just a really common convention when we're making linked lists. And that's just the node. So linked list is a list of nodes, but then there's kind of the list itself, and that's what the struct pylist is. And it's got a pointer to the head and a pointer to the tail and just a counter. And so if we create the new list, pylist_new, we are going to allocate the pylist object, which is a pointer, which is 8, 2 pointers 16, and 4 should be 20 bytes. And then that's what star p is going to be. Then we're going to set the head to null and the tail to null to indicate that we have an empty list. We're not creating a list with things in it. And set the count to 0, and we're done. So it's pretty straightforward. In some ways, this list is easier in some ways than the Python string was. Now the destructor is a little trickier because we actually have to go through the list and we have to free up all of the text areas, not just the struct L nodes, but we've also got the char star text that we've got to get rid of. So what we'll see here is we're going to, in the pylist_del, we're going to carefully start at the head and then loop through. And remember that freecur has got to be the last thing we do with cur. Once we say freecur, that's the L nodes, we got to do the freecur. We're not supposed to touch cur ever again. So you'll see I say freecur text, which is the string that's pointed to in the current node. Then I look up next, and I'm looking up next before I call freecur because I'm not supposed to use cur afterwards. So I say next equals cur next. Give me the next pointer, before I wipe out cur. I wipe out cur, and then I say cur equals next. And so I created that next variable inside that function just to kind of get past the free cur, so I didn't have to say cur equals cur next after I called free cur. And then loop goes through, and it slowly but surely cleans up all of the L nodes. It might be 0, there might be no L nodes, and head will be null at that point, and while won't even run. But you got to free the text, then you got to know where the next pointer is, then you free the current one, and then you advance to the next pointer and jump up to the while loop and then do the rest. And then and only then afterwards do you free the self, which is the actual PyList object. These structures tend to point to structures that tend to point to structures, and you got to, when you're delling them, when you're freeing them, you got to free them from the outside of think of it as a tree. You've got the leaves and the branches and then the trunk and then the roots. You got to free them from the leaves inwards. And so just be real careful about this. That's part of the reason that I give you so much sample code where I do the del for you, because I just don't want it to mess up. If we take a look at the step of freeing the dynamic memory, you're going to see that it's going to, if we have a head and we have a tail here, the first thing it's going to do is it's going to the L node that is the head, and then it's going to, the first thing that's actually going to be freed is the text, and then it's going to free the L node, then it's going to advance to the next L node, which has is, and it's going to free the is, then it's going to free the fourth thing, which is the second L node, and then it's going to advance to the third L node, and then it's going to free the fun, which is the fifth thing freed, and then it's going to free the last L node, and it'll notice that next is null, and so we're done with, there's a 3-node list. And then the last thing we do is we free the PyList itself. So that the order in which we free these things is really, really important. And you think of it as the leaves outwards, right? The C is fun. Those are 3 strings that have been allocated. Those have to be freed first before we free the L node that happens to point to them. So every little bit of order matters. The one thing I want you to do in this one is I want you to make the list output, instead of it being dump, you'll notice I called this one print, not dump. And I want it to look exactly like Python's list output, which means it's got an open square brace, it's got the strings in single quotes, comma space in between them, etc. And don't try to use string concatenation to do this, because you're in C, you're not in Python. You don't even know how long these strings are going to be. What you need to do is you need to cleverly write a loop that uses printf. So think of this as you can only use printf. Don't use a string because you don't have strings. Just use printf. And remember that printf doesn't add a new line unless you actually put the new line in. So it's pretty easy to do printf open bracket, then printf single quote, printf the string, printf single quote, printf comma, etc., etc. So you gotta, it's about 10 lines of code, and enjoy yourself. I think you'll do a pretty good job of this, and you'll be impressed when you're all done, and then you'll think, oh, I'm walking down the path of Guido van Rossum, because Guido van Rossum had to write exactly these lines of code. Now, he actually was probably using a string class, which I just told you not to use, because he didn't want to call printf directly. So he wanted to make it so you can convert to a string. But whatever. You're walking the path that Guido van Rossum walked while he was building the list object. That's what I want you to do. Here's some more methods. Some are easier, some are hard. Len is really easy. Index is not too bad. It's a for loop, which you loop through, you look for a value, and then you just return -1 if you don't find it. You just return the position. You got to kind of add to go 0, 1, 2, 3, 4, 5, 6, 7, and return the 7 if you find it. Append is a bit tricky, but hey, that was chapter 6. You should know how to do that. You've actually, by this point in chapter 6, you would have written one of these things, so go consult your own code at that point. And so here is the ultimate test case of our list class. We're just going to mimic that Python code. We're going to append a hello world string, append a catchphrase string, append a Brian string, print them all the time. We're going to print the length, and we're going to do an index lookup for Brian and Bob, and then we're going to delete it. We always delete it because we're not in Python, so we're carefully deleting it. And other than the -1 for Bob being 404 in the Python, because that was kind of a joke, it is identical. right? We're really starting to build what looks like a Python list. So up next, it's pretty much, you guessed it, we did a string, we did a list. Yep, it's a dictionary. We're going to actually build a dictionary in our next bit. So now we're going to build a Python dictionary class. And here is the code that we would put in our dictionary. I kept the strings really short because of all the, I want the examples to be pretty short and easy. So what do? We create a dictionary, and we use the, bracket, square bracket operator to create a key. It's a key value pair. The key Z goes to catchphrase. We print it out. The dictionary Z goes to W, which is replacing catchphrase with W, because if you overwrite the same key, you have to put the same value. You have to replace the value. And then we're going to throw three more things. Y maps to B, C maps to capital C, and A maps to D. That's just so that it's not sorted too badly. And then I print it out, and then I print the length of it. I do a get, and with a default value of 404, so sometimes for Z I get the W, and then for X is not there, so I get the 404. Again, kind of an homage to the HTTP error code 404 not found. And then I write a little for loop for key and dict, etc. And I can print the key value pairs out. We'll do the same thing in C. And again, this is almost a perfect transformation, literally. We first create the dictionary with calling a new. Then we put the word catchphrase in the Z key. Then we print it. Then we put a W in the Z key, which should override it, and we print that. And then we set the Y key to be B, the C to be capital C, the A to be capital D, and then we print that. And then we ask, how long is it? And then we do a get to look up under the Z key and the X key, one of which is there, one of which is not there. And I get a null back in that situation. I guess I was a little C-like in my get code. And then I dump it out, and I do a struct dnode loop, go from the head until it's null, and I print out the key and the value from each of those dictionary nodes, and then I delete it at the end. So this is the code. Now again, notice we don't know much about looking things up. We don't know how the length is maintained. We don't know how the static and dynamic allocation is going to happen. We now have a contract with a bunch of library code that is going to implement this dictionary object for us and do all of the memory manipulation on our behalf. Again, we start with the basic stuff. The big thing we're going to do is we're going to not just have a value. It looks a lot like a linked list. We're going to have a key value pair. The PyDict has a head and a tail and a count, just like the PyList. And if you look at the constructor, it's pretty much like the constructor for the list. We allocate the PyDict structure, and we set the head and tail to null to indicate empty, and we set the count to 0, and we're done. And the same with the del. The del is very much like the linked list del. Because we've allocated the key is also going to be a dynamically allocated pointer to a character array. So we got a free cur key along with cur value, but then everything else is the same. We preload the next value, then we free cur, then we move to the next value, and then when it's all said and done, we free self, which is the PyDict value. When it's all said and done, we can call the new, and then we can set a key, like catchphrase. And the key thing there is the key and value are both malloced bits of memory. Just like, before we had the text, which was a malloced bit of memory and copied, and we had to free it. But now we just have two things. And so the key and the value are two things that are going to be malloced and then copied into the malloced area. So some methods for you to build. The len should be pretty easy. Similarly, we have a print that's going to be pretty, and I want you to match exactly the output of the Python. And so it turns out that we can make a method called find, which returns a dnode, rather than get returns a string, and find returns a dnode. And then we can use find both in get and in put. Now we use it pretty much in get to go find it and then return the value, because we have the key. We look up, find it by key, and then return the value. So that's pretty easy to do the get once you have find. So the find is a for loop where you're going to go and you're going to find it, and if you find it, you're going to send it back. Okay, and if you're not, you're going to send a null back. Now you better check if it's null, right? Including in the get, you gotta check if it's null. But then in the put, what you do is you look up the old one with pydict_find, and if you get one, if old is not equal to null, then you're updating the key, updating the value for the key, and if not, you're adding it. Now the thing about the else clause here is it looks a lot like a linked list, because really if you look at this thing, it is a linked list. It's just there's two values in each one. We're not doing anything magical. Now, more advanced dictionary implementations might use hash maps or binary trees or other things like that were in Chapter 6 that we didn't talk too much about. But for now, we're just going to make our dictionary be a linked list, but instead of just a value, it's a key and a value, so we can look it up by key. And so we're not doing too much tricky stuff to make our dictionary really by just adding a bit to a list. So let's just take a look at how this is going to work in sort of the real world as it runs. So remember, we have kind of the dictionary itself, which is a head and a tail and a count. And then we have the dictionary nodes, which is our key and value, and the next one. Now the key and the value are not the actual strings, they're just pointers to strings, which means we're going to have to use malloc to, when we get a key and we get a value, we're going to have to malloc and copy both of those things. So if we start and we see pydict_new, we're going to get a dictionary with head and tail that point to null. And then if we add catchphrase, well, we allocate the z, we allocate and copy the key, z, and we allocate and copy the value and put those in key. And then next is null, and head and tail point to this thing. So we've allocated three things. We've allocated a D node, and we've allocated two character arrays using malloc. Okay? So then, let's say we're going to run the next line of code, which is setting the key Z to W. Now, when you're in the put code, you go and you call find, and you see that there is a thing. There is already a Z in there. So what you've got to do is you've got to replace catchphrase. So you actually, before you go and make a new value, you have been copy W into it, you want to free the old stuff. And so you tend to free the value that was in there before, and then you malloc and copy in for the new value. So if you're done, at the end of this, you will have catchphrase somewhere in magic free space. We don't know how C does magic free space, but it does do it. So at the end of the second put, you still have one entry, but the value has been changed from pointing at catchphrase to pointing at W. Then we add y equals b. Well, you do a find, and there is no y key, so now it's more like a linked list. You create a new D node, and you append it to the end, just like in a linked list, and then you save the key and point key at it, and then you save the value into new malloc space, and then point value at that. And then we go to the next one, where we point C. We don't find C in there, so we create a new D node, and then we do a malloc of the key and a malloc of the value, and we point to those, and then copy the data into those two malloced areas, and then point key and value at those malloced areas. And you can kind of see that this is really, at this point, it's unless we find the key in there already, it's just a linked list that happens to have two character arrays that are dynamically allocated and copied, one for key, one for value. That was a bunch of object orientation. It was kind of a walk down the path that Guido van Rossum took probably in the first few weeks of him building the string class, list class, and dictionary class. Chances are good he built something very, very similar, and then he's like, okay, now I got to make this better. But if I was just writing this thing, he'd probably just type this out. It's kind of pretty for computer scientists who've been doing algorithms and data structures their whole lives. It's like, well, why don't I just make a class that does this? Now that I've got sort of an object-oriented universe, let me hide all of the dynamic memory. And that's really what we're doing. We're hiding the dynamic memory and the implementation details and all the for loops and while loops. They're being hidden. They're important. And if you were to look at the source code to stir, list, and dict in Python, you'd see they're allocating and reallocating. They're doing it a lot more cleverly than what we did. You don't want to call realloc too many times, but for now it works. We're doing small stuff. There is an infinite array of optimizations to make all of this way faster and more impressive. But that's really for another time. So we've kind of got the idea of the baby steps from a procedural language with pointers, structures, and dynamic memory allocation, how you would take the step using those underlying things in a procedural language to build basic objects and support those objects, perhaps as you're building a new language like Python. Hello, and welcome to our continuing series of lectures on improving our implementation of a Python object. So what we've been doing is we have been building a series of implementations, of approximate implementations of some of the things that we find in Python, like the Python dictionary. And so the last thing we worked on was this Python dictionary class, and the previous implementation was just a linked list with a key. Now we're going to eventually have to build all kinds of different implementations, and so the part of what we're doing is we're working toward abstraction, where we're separating what the object is that we're interacting with from how we build it underneath. And so we're going to do things like move our methods into the structure instead of just using prefix style naming conventions, and just reduce the need to look inside the class or inside the structure that is holding our class for code that's in our calling code. So we don't want to have to look at the class the class values inside the class. So this is just continuing along understanding object-oriented principles. The three principles of object orientations are encapsulation, abstraction, inheritance, and polymorphism. And so for now we're bundling more things together. That's encapsulation. And we're working on abstraction, and that is thinking about separately how we are going to use this object from how we're going to build the object. We're going to reveal less and less of our implementation details to the caller. Okay? And so for a while we just said, well, we'll just take the class and add like an underscore and name it, etc., etc. And it seems absolutely simple enough, and in some ways you see that C++ does exactly that when it's compiling C++ to C code. But it seems like it's simple enough, and it seems like you would keep it straight, but it turns out to be a bad idea in practice. So Python strings, which I can write Python code and not have to look up documentation, are real objects that follow the principle of encapsulation. Everything that you touch is inside of the object, like uppercase, searching for something. PHP strings are kind of more archaic in that PHP is more of a C-like way of thinking about things, and they're a type, and then there's a bunch of libraries that know how to use this type. And so I'm going to show you some ickiness in PHP, but I do love PHP, so I'm not just criticizing PHP. PHP has a lot going for it, but in the language and the library there are some annoyances. So let's take a look at a little bit of Python and some equivalent PHP. And so you sort of see this notion that naming convention seems tempting, but it's not necessarily a great idea. So in Python we say x equals a string. We call x.find and have the first parameter the thing we're looking for. And then we have y equals x.replace old new. And so the first parameter is the old string and the second parameter is the new string. And then we say how long this thing is. And so everything's very consistent. But if we look at PHP, it's almost identical, except it's calling libraries, right? So $x equals a string with old in it. And then we're going to use stirpose. That is the position in a string. And the first parameter is what they call the haystack. And then the second parameter is width, which we call the needle. But then we look at the replacement, which is equivalent of x.replace in Python. And it's not stir replace, it's stir underscore replace. So do we use underscores or do we not use underscores? And then the thing that just drives me crazy is what would you expect the first, second, and third parameter of PHP stir replace? Well, if I was writing it, it would be the source string, the old search string, and the new thing to replace it with. But that's not what it is. The stir replace says old string, new string, and then the string we're doing the searching in. You can go look this up, but PHP talks about how there were generations of things, like stirpose, I think, is one of the earlier ones. Stirlen basically that's one of the older ones, and so it's consistent with stirpose, but not consistent with stir replace. And so the naming conventions is just less than ideal, and you can just see from a programmer understanding, it's just really simple that if we look at the Python, it says y equals x dot replace old new. I can remember that calling sequence, and I can never remember the stir underscore replace in PHP. So the thing we're going to do here is we're going to put the methods in the structure, and so that we see some of our C code before and after. And so we create a PyDict, and then you'll notice that just like what PHP did, I called those PyDict underscore put, PyDict underscore len, and PyDict underscore get. I was consistent because I always used underscores, and PyDict is the name of the structure, PyDict underscore del, and so I was pretty consistent with that. But now what we're going to do in the name of encapsulation is we are going to take all those methods, make them be part of the structure. We're going to find that they're just pointers to the methods, but we are going to have global methods. We're just not going to access them through their global names. So we're going to create a new PyDict saying PyDict underscore new, but then we're going to call, to put something in, we're going to call DCT arrow put. And remember, we have to make this first parameter like the self parameter DCT. That's just always going to be that first parameter because we're sort of doing it Python style. And then you kind of know that Z is the key and catchphrase is the value. And so that's the calling sequence. And again, that DCT comma is just because we're not an object-oriented language, and so we put self in there. Again, homage back to exactly the way that Python did it and why they did it the way they did it, because they were creating an object-oriented framework on top of a non-object-oriented environment, just like we are. And then you look at DCT arrow len, and of course putting DCT in as the first parameter is redundant but necessary. And we can do a DCT get, and we, in effect, other than the first parameter, which is DCT, we are putting the key in, and away it goes, and then we could call the del method. But now you'll notice that every single method that is associated with a PyDict is in the PyDict structure. So let's talk about how we're going to do that and why. And so this all kind of falls under leaky abstractions, meaning that when we're in the main calling code and we sneak in and peek at the data attributes inside the class, we call this leaking. And later we'll talk about iterators and why iterators seem inconvenient and clunky, but what their whole job really is to hide implementation details to make a cleaner abstraction. When the calling code depends on the internal implementation names and approaches, that's what it is to be leaky. So we need to define a contract between the class and its calling code from above that we won't change. And we're going to call this contract an interface. Another kind of word for that is abstraction. And so if we look at all the code in our earlier implementation, the whole thing is leaky, right? Especially if you look at that for loop where it says for struct dnode cur equals dct arrow ahead, cur not equal null, cur equals cur next, print cur key and cur value. And so what happens is that should trigger a little like that says don't look inside these things. And this is what later we'll talk about iterators, how far we go and how we actually, this code that we're looking at right here, I think it's pretty, but it kind of violates the abstraction boundary because we're looking too deeply into the fact that this is even a linked list. We don't know there's a linked list. It may not be a linked list. It may be some other kind of a structure. It may be a tree or whatever. And we will later get to the point where we will make these things different implementations, not just a linked list. And so that's this idea that like you should be like, oh no, there's this little wall, but now I'm looking inside. And then when you're looking inside, that's when you kind of are violating the abstraction boundary, or we call it a leaky abstraction. What this leads to is the notion of not all object attributes are the same. And so when we're going to build an object, we are going to decide what parts of these things are the contract and what parts are leave us alone. We're going to hide this stuff. And so the concepts in object-oriented programming are that things that the calling code is allowed to see, whether they be data or methods, are called public. Things that are like reserved for class use only are private. And then when we start talking about inheritance, which we won't talk about too much, there is this middle class called protected, and that is stuff that classes and derived classes can look at, but not the calling code. So protected is sort of more like private from the point of view of the calling code. So if you look at the abstraction boundary that we have here, we see that the place where the abstraction boundary is sort of failing is that head and tail. We want to make an abstraction boundary and say that, look, that the notion of head and the tail, that's going to be all ours, and that's going to be all inside. And that's inside the abstraction boundary, and you're not supposed to mess with it. So if we look at how we do this in Java, there is a keyword called private. And so Java, we're making a point class, and we're making it two double values that we're saying X and Y are private, which means you can't access it outside of this class. The constructor is public and the dump is public. And so you see that that just means that you can't access X and Y outside of the class, but you can access dump and the constructor. In C++, you see a private and a public. And so private says this double X and Y are things that can only be used inside the class, and public is the constructor can be used outside the class and the dump can be used outside the class. And this is just syntax that they put in. Now, interestingly, access control in Python is a little sort of wonkier because Python doesn't really put things like public and private. So what Python is doing, and you've seen these across all the Python you've done, where you see these double underscores, dunders, as it were, like the constructor, you're not supposed to call the underscore and init underscore. That's just when you create an object, that's what happens. And so the init is an internal method. It's a private method. Underscore X and underscore Y are totally valid variable names, except we're marking to the outside world, hey, you're not supposed to access these. And then def dump, the fact that we didn't put double underscore in front of it means that it's public. And so double underscore is the signal inside of Python to do access control. And we look at some of the stuff that C++ really does. This was borrowed in many ways from how C++ does things internally. So up next, we're going to talk about this map and the abstraction and the kinds of things that we do under the covers of the implementation details of the abstraction. So now we're going to dive into the notion of abstractions. We're going to take an interface and kind of compare it across a number of different languages. We're going to call this abstraction a map. A map is a common term that we use kind of abstractly to describe key value collections. And each different language tends to have a different name for that. In C++, they actually call it a map. Python calls it a dictionary. Java also calls it a map, but with an uppercase. And in PHP, we call it arrays. And in JavaScript, they're actually objects. And then we're going to look at the iterator pattern as an abstraction for looping across multiple implementations. So let's take a look at some sample Python code that's playing with a dictionary class. So we created a dictionary at the very beginning. Then we fill it up with some key value pairs. And so you'll notice that like d sub z equals 8 and d sub z equals 1, that's got to be a replacement. So there's no 8 in there after that second replacement. We then print it. Then we do a get of z to see if it's there. And then we do a get of x, and it's not there. So we see x equals 42 when it executes. Then we say, give me an iterator of the items in this dictionary. And so what that basically is going to do is the iterator itself is not a list. In earlier versions like Python 2, when you asked for the items, you tended to get a fully filled out list, but that's a waste of memory. So the iterator is simply a data structure that is keeping track of where in the list we are, and then we call it next over and over and over to advance through the iterator. So we don't have to make a complete copy of all the data. We just have a little pointer that advances through. So items is a relatively small data structure. I mean, it doesn't include all the data in the dictionary. It just is itself a pointer to something. It's all internal. Remember, abstraction is like, hey, I can give you the next thing. Internally, there's pointers and all kinds of crazy things inside these iterators, which we shall soon see. So if you print out items, you will see that it's like an item iterator for dictionaries. That's what that class dict item iterator is telling us. But then we can call the next function, which is built into Python, and say, hey, iterator, do your job and hand me back the next thing. Or if we've reached the end of the dictionary, false. Now, they come in any order. These have any ordered dictionaries, of course. But we get back the entry or we get back false. So we say while entry, then we print the entry, and then we say, hey, give me the next one, and then loop up to the top, and when it becomes false, we're all done. And so what you see, because this is an ordered dictionary, is you see Z1, X9, B3, A4, and then it finishes. So this, we don't know about next, arrow next. We don't know even in this case, we're just getting a tuple back, so we do know that. But if we take a look at this same kind of concept in PHP, we make an array and we fill it up. Z gets to be 8, Z gets to be 1, and that's an overwrite. And then we put 3 more things in and we can print them out. And we see that it's kind of an ordered dictionary, as it were, X, Z, Y, B, A. And then we do a get, and we're using the null coalesce operator, which is the double question mark. So we say, give me A sub Z, and if that doesn't exist, then give me back 42. So it's kind of like a get, but that's a PHP 7 and later. So we look up X and we don't get it, so we see X equals 42. And then we run through an iterator. And again, there's structures inside of arrays, but we know nothing about how PHP implemented the arrays. We just know that if we say for each A as key is assigned to value, we can print out K and V. And so this is a very abstract way of saying, I want to go through all of them. I want the keys and values. Give those back to me, but I don't care how you do it, whether you make extra copies of data, etc. So that's another iterator pattern. Now in C, the data structure we create is a map. And if you read this, you'll see that it talks about how the implementations work, etc., etc., etc. But the C++ equivalent of a dictionary is in effect a map. And so this is some C++ code. The first thing we see is we're going to create a map, and in this less than greater than syntax, you're seeing that the map is mapping a string to an integer. So the key in this case is a string and the value is an integer. The previous two languages didn't care so much about types, and so that's why but now we're in C++, which cares greatly about types. And so now we say MP sub Z equals 8, then MP sub Z equals 1, which again is a replace operator. Then Y, B, and A are set to 2, 3, and 4 respectively. And then we do like a get operation. And this one is a little funky in C. Why they didn't give us a get operation, I do not know. But what this is using is a ternary operation. It's saying MP count, how many Z keys are inside this thing. And if it's greater than 0, we print out MP sub Z. And if it's not greater than 0, or if it's 0, then we print out 42, which functions like a Python get on a dictionary. So this syntax is funky. You can go like Google it. There's just it's like there's 2 ways you can do it, and neither of them makes me particularly happy. Because I think that for a map-like object, a get with a default is pretty valuable. The notion of running through and counting means you found it or didn't find it. And if you found it, why don't you give it back to me? But they just don't have a get. But now we see an iteration. So it says for auto. Auto is a type, but it's an automatic type, and it knows that this MP is a map string int, and so it creates this current pointer, which is a pointer to not exactly a map string, it's a map entry. But we don't have to care about that. There's actually a type. Cur, the variable cur, has a type. Whatever the MP begin is going to give us back as a type, and it knows that based on the map string int. and it makes cur the right type. So this is like whatever type you want, but it is not any type. It's a very precise type, and that's a sort of a hallmark of C++, is all the types are very, very precise. So it's a for loop. You see the 3 semicolons? The initialization clause, auto cur equals MP begin, says, hey, we've got our iterator. Get me started. Begin. Go to the beginning of it and give me the first one. And as long as cur is not equal to MP end, the end, there are no more. That's kind of like they're null. And then plus cur. So we're incrementing cur. And then there's a key and a value, and they don't call them key and value. They call them first and second. That's the thing coming back from MP begin has a attribute first and an attribute second, and we call the C underscore str to convert that to a C string, so I can use printf, so I don't have to use C out, just because I don't know why I didn't want to use C out in this one. But you see an abstraction where the first and the second are known, but because this is a key and a value, that's not such a big deal. Okay, and so that's doing the same thing in C++. In Java, they have a interface, and you see the word interface here, an interface named map, less than greater than k comma v. And just like in C++, this is saying a map is a key and a value, but what we're putting in here is the type of the key and the type of the value. So we're going to make a map that has a string key and an integer value. You might say, why didn't I do string? And that's because it makes it just easier when I'm writing so much C code. It also will be fun when we actually count things, if you remember. From a long time ago, we did counting. But map is the class, and string integer, there's that. This is kind of polymorphism where it can be a map that maps strings to integers, or integers to strings, or strings to strings, or who knows what to who knows what else. Meaning this map is exceedingly flexible, and it doesn't care what kind of type it's using, as long as the type meets some basic criteria. So here's a bit of Java code that does the same thing that we've been doing. And so we see that we're going to make this variable map, lowercase, is of type map of strings to integers, and we're going to create a new tree map of strings to integers, and the new creates a new object. Now the difference between a map and a tree map is a map is an interface and a tree map is an implementation. The tree map says we're going to build this key value store, but we're going to store our data in a tree, and that says to a computer scientist that it's going to have a certain performance and memory footprint. Trees are a great way to store key value data, but they take a little bit more memory than a linked list, as we will later see. And so we're choosing an implementation. The other thing where it says tree map that you might use is what's called a hash map, which is a simpler map implementation, but doesn't keep things in order. So you can choose, the map doesn't change, but you can say, I'd like this to be a tree map or a hash map. They're both key value stores. One is an ordered key value store, and a hash map is an unordered key value store. And they both have different performance behaviors and internal implementation details, but it doesn't matter because they're both maps. In this code that we write, we could literally change tree map to hash map and the code would work exactly the same, but the order of the key value pairs might be a little bit different. Now you'll notice that when we're putting stuff in, we call a method map.put. So everything we've seen so far says like map open bracket quote z quote close bracket equals 8. Java chose not to do what's called operator overloading, and so it really does everything in a method. So the kind of things that you think are going to be done with an assignment statement or some other syntax tend to be done. It's like, okay, we're going to do everything with methods and parameters. Now map is the object instance that's being worked on, and z, where that's basically saying map sub z equals 8. And we'll do an put of z1, which is going to overwrite. You'll see I'm doing the same thing in each one of these things. And then put in y, b, and a with 2, 3, and 4 respectively. I can print it out, and if you look at the printout, it looks a lot like what it looks like in Python. There's this thing called get-or-default, map.get-or-default, which is, if the key z is in there, give it to the value, or just give me 42 as a default. And in the first case, z is there, and the second case, x is not there, so you see x is 42. That's not a bad name for it. It's a little more verbose than get, It's pretty much the same as what we do in Python. And then we have an iterator. And now you see in this for loop, you see kind of the notion of the fact that the iteration variable has a type. So we don't have this auto. Later versions of Java may have an auto, but now I'm explicitly showing you. It's not a map string integer, it's a map.entry, which is an entry inside of a map. It's an abstract interface to the entry inside of a map. Each entry that's got to match the string integer that's in the map. And so there's a map string integer, which is the whole map, and then there's a map entry, which is one of the entries. But this map entry is also kind of an iterator, right? So we're going to iterate and move forward. So it's not just the key and the value, it's really the key and the value and the position. But we don't see the position. All we know is we use this for syntax, which is kind of like a for in Python, and we call map.entrySet, which is I want a set of all the entries. And that map entry set does not construct a giant in-memory list and then go through it. That actually creates a single map entry with the key and the value of the first one, and then you hit it again and it gives you the second one. You hit it again, it gives the third one, and pretty soon it gives you null, which means that the loop is going to stop. And the entry itself does have a key and a value. Now, key and value are known in the map entry interface. So you say entry.getKey and entry.getValue. Now that they're using methods to give us back the key and the value versus in the previous things you saw attributes being used in the iterators. And that's because Java is obsessed with preferring to use accessor methods like getters and setters versus just grabbing attributes. And the key thing is they can add just a little bit of business logic if they want, rather than having to do something and then have the key and the value already completely computed, sitting in an attribute for you to use. Entry get key, sometimes it just grabs something that's already got computed, or it might actually go do something or do some work. And so by putting these things in what Java calls getters and setters, in this case we're not seeing a setter so much, but making it so that instead of it being entry.key, it's entry.getKey, open paren, close paren. That's a very Java way of thinking about this. So we started by talking about a simple Python dictionary where we fill it up, we use get, then we create an iterator, and then we abstractly loop through that iterator. And that's what we wanted to accomplish in this section, just to see how that is done in a wide range of different languages. Because the map abstraction is kind of like this thing that we use as software developers, and then it's a kind of a sealed thing, and then underneath it all the magic happens. So I want to talk about the C++ programming language for just a bit, because C++ plays a really, really important role in the development of object-oriented programming. C, of course, came out like 72 through 78, and then C++ came out in 80, and then both C++ and C co-evolved through the early 1980s. And then you see things like C# and Java and Python and PHP all informed heavily by C++. If we look at how object-oriented was happening kind of before C++, it was like C++ wasn't really appreciated by the typical mainstream procedural programmer of the day. And so things like Algol and Simula, it was kind of like there were tribes that liked procedural and tribes that liked object-oriented. But then C++ came along and sort of pretty much unified it, which meant that you probably learned Python as your first programming language, and you were using object-oriented programming from the time that you started. And C++ is what sort of unified that. And it was the C++ as the quickly #1 procedural programming language, and then C++ as the #1 object-oriented programming language that kind of brought order to the notion of procedural, object-oriented, hybrid, etc. And sort of everything that kind of came after 1980 was really strongly influenced and informed by C and C++. So let's take a look at how this sort of changed over time by looking at some syntactical influence. So C++, which was the earliest, which is a preprocessor plus a compiler, it turned into a compiler on its own eventually. But it has this concept of a map that has a separately selectable type of the key, type of the value, and it uses the square brackets, map, open square bracket z, close square bracket equals 8. And that is in effect a put, right? That's like an insert into the map or update of the key, and it's a pretty succinct syntax. And so Python came up with a way. Python really didn't want to make a more complex syntax than C++, so Python worked on its language to make it so that you could just say d equals dict, and it was a typeless language, and so we don't care the fact that it's going to be strings mapping to integers, because you can map lots of things to lots of things in Python. But it did follow the d sub z equals 8. And again, you used this from the beginning when you first started programming in Python, and you thought that was just natural. But what's really going on is more like what Java did in 1995. We're not going to use the square bracket to put stuff into a map. We're going to be more pure here, and we're going to create methods. Now, if you look under the covers in Python, you see that that is really a method that does that insert of the key of z and the value of 8. But if you look at Java, it says map string integer. So we again have this notion of a generic class, capital map string integer, map, which is our object variable, equals new tree map string integer, which of course is choosing the underlying implementation. And then they have the syntax of a setter style, map.put. And then they're giving the key and the value as two different parameters. There's choices that each of these languages are making, and I'll try to highlight them as we go through it. I want to talk a little bit about how C++ and its object-oriented approach and design made it so that a class like the map works almost the same as like a sort of a low-level class like a float or an int, and has access in particular to kind of the special characters or operators like square brackets or plus or minus, how that happens. And it is that you can create a specially named method inside of a C++ class that the compiler will consult and call when it encounters certain what you think of as language syntax. Meaning that as it's parsing the language syntax, like square brackets, it's like, oh, I've got some code to do some work here. This concept is called operator overloading, meaning that the behavior of the operator is controlled by the writer of the class. You are writing a class. So in this bit of code here, I've created, for no particular reason, a class that I call 10 integers in a row. And I have an array of 10 integer values, but that's private. So that's something that the outer class can't talk to, right? So you can't say 10 int 10 like in the main, 10 dot values is like, no, you're not allowed to touch that because it's private. But then what I do is I create a public method, which is the square brackets operator method, the method to be called when the compiler encounters square brackets, my class name, my object name, followed by square brackets, call me. Now the first thing we see is the return type of this operator, square bracket operator code, is an integer reference, an integer that can either be read or written, which means it can be on the left or right hand side of an assignment statement. And the parameter that it's being given is an integer index, which is the thing inside of the square brackets. Now, it is a reference because of the ampersand, but it is a constant reference, meaning we're not allowed to change it inside of this function. Okay? So const means we're leaving it alone, which means we're not allowed to say index equals 42 inside the square bracket operator method. And so what we're returning is that private variable values sub-index, but we are returning a reference to it. So wherever it appears in the original C++ code in the main, what happens is that reference can be, like I said, on the left or right side of an assignment statement. So let's take a look at how this works in the main code. I am going to create a variable called 10 of type 10int, and then I say 10 sub 1 equals 40, which means I'm storing 40 in position 1. But when it sees that 10 sub 1, it says, oh, this little class has an operator, square bracket operator, so I better call that little method, pass the 1 in, then that returns a reference to values sub 1, and then into that reference the 40 is assigned. Now Python doesn't have return a reference, and it doesn't have a call a reference. C kind of does, but they're pointers, and so references and pointers are different. References, you'll notice there's no special syntax to dereference a reference, whereas when you get a pointer, you got to have special syntax to dereference a pointer. So this notion of call by reference and return by reference is like impressive in C++ and allows it to do a lot of things and allows us to have this seemingly native line of code, 10 sub 1 equals 40, which is really just a bunch of method calls. Amazing. And then we immediately say print 10 sub 1 contains and then 10 sub 1. And again, this is kind of a right-hand side of an assignment statement. It's looking it up. It calls the method, the operator, the square bracket operator method, passes 1 into it, and then we return value sub 1, and then that's what gets printed out. And so then we say 10 sub 5 equals 10 sub 1 plus 2. And now we see 10 sub 1 on the right-hand side of an assignment statement, which calls that same code in the operator brackets method within the class, passes in the 1, returning the reference to value sub 1, but then that reference is just 40, and then we add 2 to it, and then we assign it into 10 sub 5, which is again calling the int operator method to get a reference to values sub 5. And that assignment happens. All I really did was kind of faked it, but I used it to show you this like lovely ability to do operator overloading. When I first found my way into Java, my greatest disappointment, because I taught a C++ class and then I learned Java. I wasn't a whiz at C++, but I really thought it was pretty elegant. So for me, my brain was, so I didn't learn Python first. I learned C++ first. And I'm like, hey, that's what object-oriented ought to be. And then I'm looking, go in Java, and Java didn't do that. Java basically does not want and did not want as a choice to take values by reference in method calls, and even more, it did not want to return references in the return values of method calls. Those two things, the ampersand in the return type and the ampersand in the call, parameter call, those are essential for C++ to accomplish this. And Java did not want to return references, in particular because it has to do with garbage collection, variables going out of scope, etc., etc. And if you return a reference, you don't know when it's out of scope, etc. These are powerful, complex, and potentially quite dangerous things, right? But the C++ design was, hey, you are a samurai warrior, and you are going to use these very wisely, and we don't want to take power away from you. We want to give you all the power that you might want, and just trust that you're not going to make mistakes, right? And so choices that Java make and Python make are like, no, we don't want you to make mistakes, so we're not even going to give you this kind of thing. There are other ways to do everything. Things like tuple returns in C is a good example of kind of an homage to this notion of returning things is not always just a single thing. So, but C++ is kind of unique. Now, again, Python emulated the C syntax that was quite beautiful, that was a result of C's support for operator overloading. And here's the thing where like it all comes together. So Python saw the beautiful syntax that C++, when you did the right things, the compiler would give you this, let you use this beautiful syntax and still call your methods inside the object. But they didn't want to do the call by reference and return reference that the C++ did. And so what they did is they did basically a syntax transformation. If you look, Python is, in a sense, very Java-like in that everything has to happen through methods. But then there's these hidden methods. Okay, let's take a look at the code. So I'll create a dictionary named X, and then we say X sub 1 equals 40. And again, we know what this means. That means somewhere in the key, under the key 1, there's 40. Now, I can print this out by saying X dot double underscore get item double underscore open paren 1 close paren. That's taking the index inside of the square brackets and passing it to a predefined Python understood rule for what get item, the square brackets turn into double underscore get item double underscore, where the X is the object and the parameter is the syntax. So if we think about it on the right-hand side of an assignment statement where we're just reading it, it's just doing a get, right? It's kind of doing a getter-like thing. Give me item 1, and then out comes the 40, and that's how the print of X sub 1 is a 40. That's really what happens under the covers. Is there is a class which has underscore get item underscore defined in it as a method, and that's how it loads X sub 1. So if we go down another line and we say X sub 5 equals X sub 1 plus 2, seems simple enough. And literally for years, Python software developers don't even need to know that this is miraculously and beautifully complex. But what this translates into at runtime by compiler syntax transformation is the X sub 1 on the right-hand side turns into a X.getItem paren 1, which pulls up the 40, and then plus 2 gets added to it. But then that expression is passed into X.setItem in position 5. So the left-hand side of the assignment statement is the X sub 5 equals part, and that's calling setItem. So if it's doing a square bracket lookup on the right-hand side, it's calling getItem. And if it's doing a square bracket on the left-hand side of an assignment statement, it's doing a setItem. So this means that there was no need to return references, no need to process references, none of the hoops that C++ went through. And so you see that Python did not choose to implement the way C++ did, but they supported the very elegant syntax. Now, and then you'll see that Java in 1995 takes it, or 94, takes it one step further in that they're not even going to give you that cool syntax. They're like, no, we're going to say just do x.put and x.get and call it good. If you know that x is an object and you need to do a get and a put, do the get and the put. We're not going to do this little syntax transformation that makes it pretty. And we're also not going to give you operator overloading because, again, operator overloading requires references because it allows the class to return a thing that can be used on either the left or right-hand side. And again, Java did that because they did not want to make their memory management more complex. So it's hard to argue. But what this kind of shows you is like the amazing interplay between these languages. Bjarne Strostrup went to school in Denmark and started working on C++ in Denmark, but then was hired to go to Bell Labs in New Jersey, where he met and worked with for a number of years. Bjarne Strostrup and Dennis Ritchie and all the folks at Bell Labs that gave us Unix and C over the decades. And so C++ kind of came to the world from Bell Labs, from Murray Hill. And Guido van Rossum, who was in Netherlands at the time, really was just looking at all this stuff and using all this stuff and an expert in C and C++. And back in those days, we tended to look a lot at like the code that C++ generated. And Guido's like, I'm gonna borrow. These are really good patterns. And so that's how we see so much influence of not just the syntax, but the actual runtime conventions. And like, if you look at some of the generated C++ code, the concept of private is often done with underscores. They use underscores a lot. Python's like, yeah, I'll just borrow that. I'll just use double underscore as my signal as this private, and away you go. So to show the influence that C++ and C had over Python, both in the syntax and in the runtime, we can take a quick look at some internal details of how Python works. And Python turns out to have almost identically implemented operator overloading in as C++, but we don't see it. It's all internal. You have to kind of look. So on the left-hand side, that's the code that I just got done going through. That's the C++ code that has the private values and then the public operator overload. And now if we look on the right-hand side, we see a class 10int, and I'm creating a double underscore values, which is values private, as a dictionary. And then I'm going to define the set item. So this is like a private method called set item, and then a private method called get item. Python basically has the left side and right side assignment of bracket lookup operators different. And the set item is the left-hand side, and the get item is the right-hand side. You'll see that in the set item, I'm just taking self values, subindex equals value, and I'm in the getter, I'm returning self underscore values subindex. So that's the right-hand side. So if we look at the code, I see, let's make a 10int on the variable 10. 10 sub 1 equals 40. Now Python transforms that 10 sub 1 syntax into a set item of 10, comma the number 1, comma 40, and then calls set item. And you can see, of course it worked, right? The three values are self, index, and value. Well, self is 10, which is the object instance. The index is the thing inside the square brackets, and the value is the result of the expression on the right-hand side. It's not just 40, but it's the expression on the right-hand side. And so that goes in, right? We see the print, 10 sub 1. Well, that is a right-hand side reference to 10 sub 1. So that's going to call get item. Self is 10, and then index is the 1. And we're going to just return it, and that's going to print out a nice little happy little integer, which is exactly the variable 40. So it says 10 sub 1 contains 40. And at this point, it should be obvious what's going on. When I say 10 sub 5 equals 10 sub 1 plus 2, well, the 10 sub 1 on the right-hand side turns into a get item that gives us back the 40 value. Then the 40 and the 2 are added together to finish the right-hand side of the expression. Then we're going to assign that into 10 sub 5, which then turns into a set item of 10, comma 5, comma 42. And then that stores 42 in position 5 in our private variable values. Private values variable. And then I print it out, which is a left-hand side lookup of 10 sub 5, which calls get item again with self is 10 and index is 5, and so we get the 42. And so you see how they're so similar inside. I mean, again, like if you look at generated C++ code from early C++ code compilers, you'll see these double underscores used in various places, which means that Python in its internal implementation used the same patterns as C++ did in its internal implementation. Python chose not to do call by reference and return by reference. Java chose not to do call by reference and return by reference, and Java chose not to do the fancy syntax transformation. But you know, who knows? Maybe one of these days Java could do that syntax transformation and be like, whoa, Java has everything. And then to some degree, Python has shown the way about how you do this without doing call by reference. And again, that ampersand operator and ampersand index on the left-hand side, that's the like scary part where language designers are like, I'm not sure I want to go do that, because C++ is not a garbage collected language, but Python and Java are garbage collected languages. And that's not the only reason that Python and Java didn't want to do call by reference, but it is one of the reasons that you kind of, it just simplifies to know that when a function is done, it's done, and there's not like sneaky little pointers inside that function that need to stay alive. So it allows you to throw stuff away when functions are finished. Okay, enough of that. Just again, I'm just trying to show you in the simplest possible examples the kinds of design decisions that all these language and library designers were doing as they built the languages that we know, love, and use today. So it's time to stop deep diving into object-oriented theory and get to writing some code. And so we're going to start with something simple. we're going to do encapsulation. The second thing we're going to do is iteration, but for now we're just going to do encapsulation, and then in the next section we'll do iteration. And really, most of this code you've already done. We're just kind of refactoring it and moving things around and taking these, functions that we named by convention and we allowed the calling code to use, and moving them into the class using some pointers. So a real accomplishment here is the map arrow put, the map arrow get, and the map arrow del. These things are now named and accessed in such a way that they are attributes. The functions we're calling are attributes in the class itself. And so other than that, it's not that different. And so it's not that big of a deal. The other thing we're going to do is be a little more explicit about what things in these classes are public and what things in this class that we're building are private. So we'll start with the map entry. This is the structure that makes up the nodes of the linked lists. The key is a character string, and the actual value is an integer that we're just going to make it simple. We got to dynamically allocate the key like we've been doing, and then we have a prev and a next. The key there is the prev and the next are double underscore, so that means they're private. But we are going to decide that key and value are public, and we just indicate that much like Python would do by not putting double underscores in front of it and remembering in our mind that they're allowed to be used in calling code. The map structure, most of it looks pretty simple. We have a head, we have a tail, and we have a count. You've been maintaining those for some time now. Those are private attributes, so we've renamed them in such a way that they have double underscores in front of them. And then we have a series of public methods. We have 5 of them. The key thing is these are pointers to functions. And that's what void star put, that's parenthesis star put. That means that we're allocating a variable in the structure named put, and it is a function pointer that will return a void. It's a pointer to a function that returns a void. So not only are we defining the attribute that we're going to use to access the function, we're also defining the calling sequence. It returns a void, and it takes 3 parameters, a struct map pointer to self, char star key, and int value. So when it's all said and done, this is not putting the code in here, as it might say in JavaScript, for example. What is a single 64-bit number, which is a pointer to the beginning of a function. Now the function method signature has to match. So we're defining the method signature, but in terms of allocating, we're really allocating 1 pointer for put, 1 pointer for get, 1 pointer for size, 1 pointer for dump, and 1 pointer for del. And again, you look at get. Well, get takes as its first parameter a pointer to the map, which is self, a key that we're going to use to do the lookup, and then a default value to return. And then get returns an int. And so that's pretty straightforward. It took me a little while to get the pattern right because the parentheses here are really, really important because we're both defining the attribute name and the rules of its use and the method signature of the function that we're eventually going to point to. Okay? But that's pretty much it, right? We're just going to put these things in. And so the constructor is pretty straightforward. It's not that different than the constructor that you did. We got to build these functions, double underscore map put, double underscore map get, map size. They're outside of this. They're above us in the source code somewhere. And we're just saying p arrow put, which is an attribute put, public attribute put, is equal to ampersand, the address of the double underscore map put function. Super simple. Ampersand is address of that function. Get is address of that function. Size is address of that function. Dump is address of the function. And we're done. And this is kind of showing you that this is, let's see, head is a 64-bit pointer, tail's a 64-bit pointer, count is probably a 64-bit integer or a 32-bit integer. Put, get, size, dump, and del are all 64-bit. So the size of the map itself, the map structure, is about, 10 words or less. And that, again, has to do with efficiency, right? But you probably have most of the code you need for map put, map get, map size, map dump, and map del. So map dump is pretty simple. you know, if we look at this, you know, the self is the pointer to the map, so it has a head and a next, and we're going to just go through it until cur is equal to null. We got a map entry, which is the type. Now we don't double underscore the cur because that's really just an automatic variable inside this function. That has nothing to do with the outside world. And you'll notice that we're just access double underscore head. We're accessing double underscore next because we're in the class, right? And so those are private, but they're totally legit to access them when we're building a dump tool inside the class. So private things are accessed in the methods in the class. That's normal, right? We don't have to hide those. I'll tell you, when I'm building something like this, the first thing I want to get to work is some kind of a dumper, because when I write this code before I hand parts of it over to you, I have like map dump, map dump, map dump, map dump. Every line I put a map dump, and eventually when stuff starts working, I start taking the map dumps out. So just debug, 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 always. So that's why I'm just like, I couldn't write this code if I didn't have a map dump, and so I'm going to make you guys do it as well. So the destructor, like most destructors, the key thing is to draw the picture and figure out what parts were dynamically allocated and then call free, or which parts came from malloc, and then make sure you free them. And so we're just going to loop through, and again, we're in the class, so we're happily using double underscore attributes. We're going to loop through, and the order of this is always important, but by now it should make sense. We're going to free the key, because remember that's a string pointer that we malloced. We do not need to free the value. That's just actually part of the map entry struct, and we're going to get rid of that in a second. We're going to advance to the next one first, and then we're going to free the current map entry, and then we're say cur next, and we're going to loop up. And so eventually we're just going to go through the linked list and free the key, and then free the entry itself, and we've given back all of our data. And then we're all done with that. We actually free the 10 words or so that is the map structure. Again, this should start to look familiar to you. So get is pretty simple as long as you have some code that like is map find. Map find is going to do all the hard work, but map find can look at underscore head and all that stuff, and next, and look at all that, write some for loops. It should be not too hard. And again, underscore map find is private, but we're in the class, and so just have fun talking to the private stuff. Map put is something you're going to have to write, but if you think about it, if you get map find and it returns and you've done this before, you've used a find-like method to find the thing in the linked list, and you update it. If you found it, it's really simple. You just change the value in return, and if not, you add it to the end of the list. You construct a new map entry, and you add it to the end of the list. And so again, I just hope by now you can knock these things out. And so that's basically it. I mean, if you really think this was a very simple section where all we're doing is changing from globally named functions, we're enforcing the rules of private with double underscore, and then we're taking those pointers. We've declared pointers to functions in our map, and then our constructor sets them up, and the rest is really just refactoring code that you pretty much already have. So now we come to the last section of this module, and that is iterators. It's all been building up to iterators. And this is a situation where you might say, wow, I don't like iterators. Iterators seem like a more complex way to write loops than just looking at like head and next and sneaking in and violating the abstraction boundary. But as you'll see in the overall next module, you're going to have very different underlying data structures, and we want to be able to write the same code over and over again. So at some level, what we're doing here is we're building a map implementation that can be a linked list, a hash map list, a hash-based map, a list-based map, or a tree-based map. And what we want is this code right here this code should not change. We should say, hey, give me a map. We got a map entry, we got a map iterator. Those are all part of the contract that we have with the object, be it a linked list, tree, or map, or hash. We're going to do a put, dump, get. Now we're going to iterate. The hash won't even have it doesn't have a head. And the next, it's not going to work, right? So we're going to have to say, hey, there's this abstraction. Give me an iterator for your map, okay? And we don't know what's in the iterator. We don't need to know what's in the iterator. The only thing we need to know is it has a method called next. That's it. So we're basically saying, let's get started. Give me an iterator from the map. Call the iterator method, passing the map instance as a parameter, and give me back iterator. And then we write a while loop, and we say, hey, iterator, give me the next thing. It is up to the iterator to start at the beginning and then advance and move down. And when we get null, we break. If not, we print key and value from the cur. Now cur is of type map entry. There's a map iter next, and then cur is what we get back from iterator. So we get from iter next, we get back a map entry. And so if you recall, key and value are public in the map entry. So I could have had you hide those behind sort of getters and have a get key and whatever and name those underscore, but we're just going to leave them public attributes for now. If we were really going to if we were implementing Java, I mean, right now we're kind of hard coding this string key integer throughout, so it's going to be okay. And then of course we call the destructor on the iterator once we're kind of done with that loop, and then we call the destructor on the overall map. And this code should be roughly the same when we go from linked lists to hashes to trees. This is the moment, and it's this iteration pattern. So I'm going to do a bunch of pictures, and so I just want to, I've been drawing some pretty complex pictures on these things, but by now the whole pattern of what next means and prev and these things being null, a doubly linked list, and the key pointing to another little, a char star key, which points to another little statically allocated thing, and the head points to the tail, and the head and the tail, and all that stuff. I'm just going to, for this section, really simplify these pictures. It's to say, look, there's a variable called head somewhere, and it points to a z equals 22, then it points to a w equals 42, and then that's the last one, and that points to the next there points to null. And so I'm going to really use a succinct representation of linked lists going forward. If we review what we don't want to do, right? We do not want our calling code to know about count. We do not want it to know about head. We don't even want it to know about next within the entries, right? We don't want to know that. We do want it to know about key and value. And so the calling code where map arrow number underscore head current underscore next, no, that's not allowed, right? Those are private. So in our calling code, if we're looking at things have underscores, technically we could do it because there's nothing in C that's stopping us, right? We create those things, right? So we don't want to call head or count, because then if we change when we're doing a map, head's not there anymore. I mean, a hash, head's not there. Next doesn't work. I mean, we got to hide that. We got to wrap it. We got to create a strong abstraction around this notion of starting a loop and then iterating one iteration of a loop, and then ending the loop. We have to abstract that away. This is the concept of separation of concerns. Our calling code does not need to be concerned about how the object can be looped through, right? So we need a generic notion of looping. So you can think of the iterator object itself as a thing you create, and it sort of starts at the beginning, and then you hit it, boop. Next, give me another one, give me another one, give me another one. And inside the iterator, the state is changing. It's like advancing. And it just gives them to you one at a time. You can't ask it for the same one. Once it's been given to you, it's sort of like ratcheted down to the next one. So if we look at this Python code, we'll start with a dictionary. A maps to 1, B to 2, C to 3, and we print it, and there's the dictionary, and we say, oh, let's convert that to a list. And that list is the keys, which is A, B, C, and then say, give me an iterator from that dictionary. We print that out, and we print the type of it. It is of type dict_key iterator object. And so the iterator itself is not the entire dictionary. It is not a list of all the keys. It is an internal structure that Python is going to maintain, and then we're going to poke it by calling next, next, next. Now the whole next thing, that's probably calling an internal method like double underscore next double underscore. So next is part of the Python language. So if you look at the while loop, it's a while true loop. We say item equals next. So that means give me the next available item in the iterator and then advance it. And if we're past the end, return me false. Then I say if item is false, break, and otherwise I print the item. And so I'm getting the item is A, B, and C. But the key thing here in Python, we're using Python to keep it as simple as possible, is the iterator is something that's created. The iterator doesn't contain all the data. The iterator contains pointers inside of it so that it knows what to do next. And we repeatedly probe the iterator with the next call to get the next thing. And that both advances, returns, and indicates when we have run out of things. So it's weird because we're so used to say like for blah in blah or for this, that, but that's not how iterators work. Iterators want this next thing to happen. In the C code to do the iterator, you create it, you loop next through, and the C one is going to look pretty much the same as the Python one. So if we look at the map iter structure, it is going to have the kind of things that we've needed. We just are going to pull them in. So the concept of current, like we've used the variable cur in the past for these loops, is in the map iter structure, and it's private. So we've moved that from a sort of a variable that was in the main scope to inside this and made it private. The only public things we have are a next method and a del method. And so now what we have is a simple contract. You can see our kind of outside contract for this class is it's created by the map class, but once it's constructed, next and del are the only thing that you can do with this, and that's that. And then we get to decide inside this class. And so when we construct it, we're basically going to start it. We're going to allocate the right size. We're going to take the current and point it at the first item, pulling from the head of the linked list. And then we're going to set the two methods next and del based on the address of the implementations of the functions that implement it, and then we're done, right? And so because we're inside of the map, and that's map iter, so this is what you get when you go map arrow iter, you get this code. And so we're totally allowed to do everything private with map because, again, the developer of the map class is the same person or team that's developing map iter. And if we wanted to change head to, X, we could, because we would just go inside all our code and change it, but head is not exposed to the calling code, so they wouldn't notice that change. Again, that's the key. At the moment the constructor is called, before the first call to next, this is what the map iter looks like. Current is pointing to the first item in our linked list. Then the while loop starts and it calls head. Now you'll notice that it's kind of got this weird thing where it grabs the current, and that's because current starts at, we could have implemented this differently, but the way I did it was current is pointing at head, and I have to, for the return, it's got to return at the first call to next. I grab current, and then I advance current. So that at the moment that it returns, the return value is b equals 14, and current now points at 21, d equals 21, preparing for the next call to the next function. Okay? So then it comes in, and retval grabs 21, and that's what we return, and then we advance to 19, and you can kind of see retval and current chase each other down this linked list. So we return f equals 19, and then current points to null, and then we notice that current is null, and then we return null to tell our calling code that we are finished. So to start the iteration, to prime the iteration, we call the map object and say, hey, give me an iterator for the map. And we get that back, and we're going to store that in our variable iterator. Then we're going to start an infinite loop that says while 1 or while true, cur equals iter next. Give me the next one, which the first time 2 is going to give me the first one. Then if I got a null, I'm done with the loop. Otherwise, I print the key and the value of the one I got, and then I go up and I iterate to the next one, print it, up, print, up, print, up, print. Oop, I got a null, and then I delete the iterator. And this is super equivalent to what we do in Python, where we say x equal, give me the iterator for the dictionary x in the variable it. Then while true, we advance to the advance next of it, otherwise give me false. If we got a false, we're done, and otherwise we printed it. So these two are very, very parallel. And you'll notice that Java and C++ don't do iterators the same thing, but I wrote this C code to mimic Python's way of doing this. So it's been quite a long journey. We really focused on abstraction and encapsulation, and we've done it with iterators. And all we've done now is we've laid the groundwork for multiple implementations of the map. We shouldn't have to change our main code anymore. We should be able to put we build a list map, and then we're going to build a hash map, and we're going to build a tree map. Those have increasing complexity and improved performance characteristics. And now you really are going to start seeing why we say have abstraction, so that we can fool around underneath the abstraction and accomplish really cool things and get closer to what Python really does underneath of a dictionary implementation. Hello, and welcome to the last lecture in this course. We're going to talk about tree maps and hash maps. Up till now, we've built a map abstraction. We've looked at how iterators work. We've created a linked list implementation of the hash abstraction. And now we're going to go and build a hash version and a tree version of that same thing. If you recall, some lectures ago, I read a Robert Frost poem, miles to go before I sleep. Well, that's where we're at now. We're coming to the end of this miles to go, although, as you'll see, the end is really just the beginning of the next phase. And with a little foreshadowing, if you have been with me for a very long time, all the way since Python for Everybody, which for me was recorded a number of years ago already, this is the first complete piece of code that I showed you, and that was the code to count the number of words in a file by splitting them, then creating a dictionary, and then counting them. And we're going to finish this lecture by implementing this in C. But I'm getting ahead of myself. So the idea here is we're exploring different key value implementation alternatives. We built a unordered Java-based hash map, which is like a Python 2 dictionary. If you recall, Python 2 had unordered hash maps, which meant you sort of ended up with your stuff coming out in a random order. It was the same order, but every time you inserted something, the order might change. Now, Python 3, later versions of Python 3, they tend to be ordered, which are more like the list map that we did. We're going to have a map that is sorted, that's more like Java's tree map with an iterator, and it is sort of chapter 6.5 or section 6.5 of the book. And it is a combination of a tree map and a linked list map, but Java doesn't have such a thing, which really kind of surprises me. They got a tree map and they got a hash map, but they don't have a linked tree map or a linked map. So here we go. Now the two abstractions, two implementations we're going to build, you see them in Python, you see them in C++, and you pretty much see them in Java as well. But we're going to do our own thing. So I would say to you when you're writing this code, I don't want you to think that when I wrote this code that I gave you as samples, or when I wrote these slides, that it was easy for me. The concept of trees and hashes are pretty straightforward, but then you got to solve the little problems of how to take the previous and hook it to the current and hook the next to the next, the current next to the next from the previous. And so you got to draw pictures, and this is actual picture that I drew. I really wrote all this code from scratch. I mean, I didn't come up with the idea of a tree from scratch, but I wrote this code from scratch. And you can see that like when I was building the tree map, my goal was to find the right place in the tree to insert the next item. And so you see I've got this 1, 3, 5, 7, 9, 11, 13. So I kind of constructed this tree that was right. It was in order. And then I was trying to figure out where I might put 4 and where I might put 8 and where I might put 14. And then I kind of had this notion when I was writing the picture that you'll see I had the words lowest node greater than. And then I crossed them all out because that wasn't enough. And you'll see when we get there that I have the lowest node greater than and the greatest node less than. And I've got to get both of those things. And so as we work our way down the tree, we got to keep track of this. I'm getting way ahead of myself. Like many data structure programming tasks, if you can draw the picture and it makes a lot of sense. You see the hash map, which is the first one we're going to do. That's really just nothing more than a bunch of linked lists with a hash function picking the head. Instead of one head, it has, in this case, 4 heads. So that one turns out to be easy, and that's the first one that we're going to do. But when I wrote this, I mean, I knew what I was doing. I knew what a tree was. I knew what a hash was. That's the easy part. The hard part's writing the code. Now, taking the code from someone else, like if you're taking it from Python or C++ or Java, that's easy. Thank heaven they wrote it and they tested it. And we have a nice tested working implementations. So you shouldn't have to write this stuff in most languages. And so we're just understanding how to write it. But if you do it right, you're going to make mistakes. And you're gonna be 80% right, but then it's going to be real hard to debug this stuff. So part of what you need to accept the fact that you're not likely to write it perfect the first time, and debugging is difficult. You're going to print out a bunch of like %Ps and hex values and stuff, and you're going to just go through it slowly, like, what did I do wrong? Because the main programs for the programming assignments that I give you are really kind of like unit tests. They're sort of pushing your implementation to see if it's capable of handling all of the common situations. And so don't stress if it doesn't work right away. My implementations didn't work right away. They failed. You can, if you can go to some website and get the solution. I mean, if you're going to do that, just go to Python and make a dictionary if that's your goal. Your goal is to struggle with doing something that you understand. You know how to do it. You know what a tree is. You kind of know that you got prevs and nexts and lefts and rights. But you still got to write the code, and making 1 or 2 mistakes and then fixing those 1 or 2 mistakes is essential to understanding. So with that, up next, we're going to talk about the hash map. So now we're going to talk about a hashed-based implementation of our map. And this is the answer to the world's most common programming interview question. But we're going to do hash maps and then tree maps. Tree maps are harder. So hash maps turn out to be beautifully simple, and that's kind of the reason that everyone likes these as interview questions, because the interviewer can remember the answer. A tree map, they might have trouble remembering. And so it's the perfect thing in an interview to say, draw me a hash map, because they know they still remember the answer from when they went to school. They'd have to do a little review to get the tree map right. So here we go. So let's talk a little bit about our hash map implementation. It's got a weird order, and once you see the data structure internally, it'll be clear why there's a weird order. It is like a Python 2 dictionary, and it's like a Java hash map. It's very similar to both of these things. I'm guessing the code we're going to write is very similar to when Guido made his first dictionary. It's going to have extremely fast insert and lookup, just like Python 2 dictionaries and Java hash maps. It's going to be iterable, like Java's Python 2's dictionaries and Java's hash maps, and it builds on linked lists. Surprisingly, it's really easy to build a hash map if you understand linked lists. And so it's covered in chapter 6.5.1 and 6.6 in Kernighan and Ritchie. 6.5.2 is literally the hardest part of the book. And that's why we kind of start with 6.6 and then kind of go back to 6.5. Okay, so let's take a look at our data structures and how we're going to go from the list map to the hash map. So our list map is pretty simple. We've got the entries in the map, which are key value, which we've decided are going to stay public. We've got the prev and the next for the map entry, which is just, we're going to link these things together. And then the list map itself, it's got a head and it's got a tail and maybe a count and a few other things, and then the methods, etc., because we've done encapsulation. So the hash map entry, if you look at it, it's pretty much identical. And that's because the entries in a hash map are just part of a linked list. The key to the hash map is there's multiple linked lists, and we see that in struct hash map. And underscore buckets is how many buckets we have. In a more sophisticated hash map implementation, we would have the number of buckets grow as size grew and the list got too long, but we're going to keep that. So that's called rehashing, and we're going to keep that out of our conversation. So, but we're going to have a number of buckets, and in this case, it's going to be 8. So those are called hash buckets. And then we're going to have heads, plural, we're going to have 8 of them, and tails, 8 of them. But within a particular head and a tail, it really is a hash map. So as you're writing the code for the hash map, go back to the list map. I mean, literally copy the list map code and then change the singular to plural. And you'll see some of the things I show you in the actual code. So if we look at how a list map looks, it's got a head, and it's got a bunch of entries that have prevs and nexts. I'm not even showing the prevs and the arrows. I'm just showing the next, but assume there's always prevs there because it's a way for us to link things in. But if you look at the hash map, so you take the actual key, you run it through a hash function, which creates some big number, no matter how, but it is just a number. No matter how long the key is, it can be 1 character or 2,000 characters. Eventually the hash runs a calculation that gives us back a number, sort of a pseudo-random number that has, equally likely, and there's a whole science of hashing. And then we take a modulo, and in this case we have 4 buckets. So we take this hash calculation, modulo 4, and that gives us a number from 0 through 3. And with that number, we pick the linked list, and then we add it to the linked list, just as if we were doing this with a linked list. So once we've done the hash and we picked a bucket, it really is exactly the same as a linked list. So a hash map with 4 buckets is the same as 4 linked lists. And you pick the linked list by the hash computation. And the hash computation is deterministic and predictable. So wherever we put D, it's going to be in bucket 1. And we can look it up in bucket 1, we can store it in bucket 1, etc. And so for inserting m equals 90, that's going to hash into bucket 2, and we're going to put it in that linked list. Okay? So it is beautifully simple. Now what is a hash calculation? This is actually from my Postgres for Everybody course. Basically the hash maps large data items to a single number, basically, and these are called hash values. So the whole concept of a hash function, when used with a modulo, in this case I've got 16, modulo 16 in this picture, it maps a big string into some fixed number of buckets, and often the buckets are power of 2, but they don't have to be. It's really a modulo operation. And so there's a whole science of hashing and hash functions. And it turns out the hashing and hash functions are a big part of security and digital signatures and all that stuff. And so there are people who spend their whole lives researching how to build good hash functions. And so there's this SHA-256 compression function. You can go look it up. You can see what's going on here is like the arrows are shifting, and the plus with a circle is exclusive ORs, and they sort of both show you the shifting and the exclusive OR, and they give you a diagram of how these things, and they shift an exclusive OR, yada yada, and they're taking the pieces of a value. It's computed in a loop and updated, and what they're showing you is what happens each iteration through the loop. And so the idea is we are going to take a string array, and we're going to take a number of buckets. And the idea of a hash is it is just some integer number, and we're going to go through each of the items, each of the characters in the string. That's the 4 star stir star plus stir plus plus, and we're going to take the current value of hash. In this case, we're going to shift it 3 to the left, and then we're going to exclusive OR it with the character we're looking at. So you can say shift 3, exclusive OR, shift 3, exclusive OR. So you can think of it as like an accumulation. But the exclusive OR is a nice form of accumulation in that it increases the randomness, the pseudo-randomness of this thing. And so exclusive OR just turns out to be a super valuable calculation. And so this loop is going to run so many times. And so we're going to print it out. You're going to see the hex. If we're just taking the letters HI, you can see kind of the internal hash value growing and changing. And you can kind of see it going from right to left as it sort of grows. And there's new data being put in bitwise. It's a bit exclusive OR. But at the very end, it says return hash % buckets, which takes the modulo operator of the number of buckets. And in this case, I'm going to be using 8 buckets just to run the hash function, right? Give me the bucket for this string. So you can see me running different things on the right-hand side and getting back the ultimate final bucket. So hi goes in bucket 1, hello goes in bucket 7, and world goes into bucket 4. This is really inspired by the shifting and the masking, but I've simplified it so you can kind of see what's going on. And in our particular hash, it's good enough for our purposes, but it's probably going to have collisions when treated against a whole series of random data. It's not going to be as good, and that's where a fancy hash like SHA-256 would be helpful. So now that we understand the basic data structures and how hashing functions work, up next we're going to take a look at actually building a hash map, or at least adapting our list map and turning it into a hash map. So now that we understand what a hash function is, we're going to actually build our hash map implementation. But what we're really going to do is make a copy of our list map code and change as few things as possible. You'll be impressed with how easy this really is if you have a bit of working list map code. This is the new constructor, and I can call your attention to the changes, right? Remember, we have a number of buckets. We have however many buckets we have 8 heads and 8 tails. So we're going to look at the constructor. So we're going to allocate a hash map. It's not that big, right? It's still got the functions for our encapsulation to put, get, size, dump, and iter. That's not changed at all, except it's called hash map instead of list map. The buckets is set to 8. We're going to initialize all 8 buckets to have a head of null and a tail of null. Because remember, this is just 8 linked lists, and the count we set to 0. Pretty straightforward, especially if you understand the hash list. And if you don't, go back and watch that lecture. Don't just like go, oh, I didn't understand what a hash list was. I'll just keep on not understanding and use ChatGPT. It's like, well, I don't know what to do if that's how you're going to go through this assignment. But if you have and understand a working hash list, this is easy, easy, easy. We've been using list map find before, and all it does is it finds a hash map entry if it's already there. And so we send in the whole hash map self, which is very, Python object-oriented pattern where the first parameter is always self. We have a key we're looking up, and then we're telling it to start in a particular bucket. And that's the real change. If you have hash list find, it doesn't have a bucket. Hash map find has a bucket. And so this code is exactly the same as hash list find, except instead of starting at head, we have an array of heads, and we use bucket to figure out the thing, and then we loop through it. We're in the right bucket. Something above us figured out what bucket it go through. And so if we look at hash map get, which is taking a key and having a default and having a self, we say, hey, compute the bucket from the key and however many buckets we have, which in this case might be 8. And then we do a struct hash map star retval, go find it, passing in the bucket. If the return is null from find, we return the default, otherwise return the value. So again, there's one line changed between the code from list map get to hash map get. So let's do a quick review of what we do in map put. Now this is not the hash map put, this is map put. This is our list map put. So we call find. If we find it, then we're just going to update the value and we're done. If we don't find it, we allocate the new entry, we set its next to null, and we link it into the list. And this is the place where you should be drawing a picture. If the head is null, that means we have an empty list, then self head is this new thing. If the self tail is not equal to null, we've linked it at the end, then we're going to update the tail, etc. So draw these pictures, and these are the parts where you'll mess it up. You will get these wrong, and it's okay to get these wrong. Put like a print statement in every line here if you're having trouble. Right? And you got all the cases, and this nice little 4 lines of code captures the cases. Okay? So remember, we're inserting at the end. So what do we do for hash map put? We have a bucket. We're going to run a hash computation to figure out which bucket it is. Then we're going to call hash map find, and we just tell it to find it in the bucket. So in the linked list, sub 3 or sub 4 or whatever. And if we found it, we update the value and return. Otherwise, it's time to insert. So we allocate a new one. We set its next to null. And then we know which bucket it is. So in this, we looked at the previous code. It was for 1 linked list. And for this current code, there's 8 linked lists. But we already know which linked list we're dealing with. And so literally, you can take the word head and change it to head subbucket. Everywhere you see head here, you can change it to head subbucket, tail subbucket. And literally, when I wrote this code, that is exactly what I did. I did it slowly not to mess up, and of course the compiler helped me if I forgot something. But that's as simple as it is to transform the put from a list map to a hash map. Of course the dump, we have to do a little bit differently. We want to show all the buckets, and so we were showing what bucket it is, the key value pair, but other than that, it's really pretty straightforward stuff to do the hash map dump. Remember I told you that writing a debug tool is essential, so you can change your main code to dump, because you'll mess it up, right? You will not write this code perfectly, and you need to be able to debug it. So now let's take a bit of a review of the list map iterator. So recall that the iterator is its own object. We've got the entry, we've got the iterator, and we got the map itself. And the map iterator is allowed to do all the internal stuff because whoever's writing these things is writing them in a group, so we can think of it as like a protected value. And so really the essence of the map iterator is a current. So we're going to call it, the public part of it is next and del, and the private part is what the current thing is. Because we don't get to see the current, but we can use next to get the current back. And so the idea is we can call next rather than looking at current. Recall that the way the iterator works is you ask for the iterator, and then you hit the iterator with the next, and you go until you're done. And when you find something, you print it out. And we can do the same thing in C and as well as Python. If we think about how to do the iterator for a hash map, it's a little different. Generally we start the first bucket, and we must move through all the buckets. Eventually we got to get to, because we got 8 or 4 linked lists, we got to go through all of them, and we got to go down each of them. But if we're looking for the next item, and we got to skip empty buckets. So we kind of got a bit of a complex while operation. And so one of the things we're going to do is when we create the map iter, we are going to store a reference to the hash map. So when we construct the hash map iter, we're going to know which bucket is an internal value, current is an internal value, and map is an internal value, which we're going to use to remember that map that we're an iterator for. And then we're going to have a next and a del. This is the constructor, and we're saying make an iterator given a hash map. We make the iter structure. We remember a pointer to the map in case we're going to need it later. The current bucket we're going to look at is 0, and the current map entry is the head of the 0 bucket. And then next and del are just encapsulated methods, basically, and then we return it. Now that first bucket may or may not be an empty list, right? So that first, there might be just one bucket. The third bucket might have a list in it, and 0, 1, and 2 won't have anything in it. So remember, so we're starting at the top bucket, and our current is pointing to the head of the first bucket, which may be null. The tricky bit is the iter next. And we remember we've given the map iter, we don't get map, but we've stashed map in _map. If self current equals null, in the old days, in a list map, we knew we were done and we could just return null. But now we have to go down a bucket. So this is the iterator's bucket, goes from like 0 to 1, so we increment it. And if the current bucket we're looking at in the iterator is greater than or equal to the maximum number of buckets, we have now got to the last bucket, and we return null. And then what we do is we say, okay, that must mean we have more buckets, so we say self-current is equal self-map, that's our little stashed version of the map, and we're going to go, we've already incremented self-bucket, and so we're going to grab the next head, and then we're going to loop up to the top. Now at this point, if that bucket is empty, we're going to do it again. And we're either going to go through this while loop enough times until we either have exhausted the buckets or we have found a bucket that has an entry in it. Then we got to do a little trick, grab the current. So the only way we're coming out of this loop is if self-current is not null. Because if self-current was null, we would have whiled our way through and then returned null eventually after we exhausted the buckets in the while loop above. So the ret-val is self-current. If self-current is not equal to null, we're going to go to the next and then return ret-val. I've given you the code. Go through it carefully. It's tricky to write. What I would do is I would print this code out and draw the picture. Okay? Draw the picture. So let's take a look at a hash map iterator in action. So this is what it looks like when we just got constructed and we're in the first call to next. Current is pointing at the first item in the first link list, the link head sub 0. We'll fall through, we look at this self-current value, and it's not equal to null, which is great, which means we have something to return. So we don't have to go through the sort of scanning across null entries. So we skip the while loop, and we simply set ret-val to self-current, and if it's not equal to null, we advance that, and then we return ret-val. And so at the end, it looks like this. The current has been advanced to the next thing we're going to return on the second call. So the first call returns f equals 19, that's the ret-val, and the next thing is going to be h equals 17. But now we give it back to the calling code, and away we go. So now we come in the second call, it's going to do kind of the same thing. Current is going to have pointed to h equals 17. It's not null. And so we simply take ret-val and be self.current, and then we advance it as long as self-current is not equal to null. And because it was pointing to h equals 17, we're going to advance. But now, as we exit this second call, current is going to be null. But we're going to take care of that on the third call, so don't worry about that. Ret-val is h equals 17, and current equals null. So now we're done with the second call. So now we come into the third call. And in this situation, we are pointing at the 0 bucket, and current is null. So the while loop is going to take over. So while self-current equals null, which is true right now, we are going to run the code. Say self-bucket plus plus, which is the bucket number in the iterator. And we're going to ask, is the bucket number in the iterator greater than or equal to the number of buckets in the map? If we are, we're done. We're at the last one, but we're not. So we're not going to return null. And we're going to say self-current equals self-map head self-sub-bucket. So we're going to go down to bucket sub 1 now, and we are going to make current point at bucket, whatever the head of bucket 1 is. And that's okay. We found an empty bucket, because remember I said you got to skip empty buckets. But we're still in the while loop. So the while goes up, says, self-current is still null. I mean, I just moved to the next bucket, but self-current is still null. So I add 1 to the bucket becomes 2. We check to see if we're done, right? If it's greater than or equal map buckets, return null, which it's not, because we're at bucket 1. And self-current is equal to self-map. Remember, map is our remembered version of the whole map, so we can see all the heads, because we've got to work through the heads. So now self-current points to b equals 14. And now the while loop goes back up, and now self-current is not null because it's pointing to the b equals 14 item. So it pops out of that while loop and drops down and says ret-val equals self-current, which was b equals 14, and then it advances self-current, and self-current becomes null again, but that's okay because we're going to return b equals 14 on the third call. So just to review, returned f equals 19 on the first call, we returned h equals 17 on the second call, and returned b equals 14 on the third call. And now it's going to loop back up, and we're going to see the fourth call. And so the fourth call is going to come in, and current was d equals 21, and so it's pretty simple. We're not going to run the while loop at this point. We're going to return d equals 21, and we're advanced current, so current is now pointing to null. And now, in the fifth call, current is null. But now, that's going to trigger us working in the while loop. We're going to add 1 to the bucket. The bucket is going to become 4. And we say if this bucket inside this iterator is greater than the total buckets in the map, return null. And we're now done. The fifth call returns null that tells the calling code that we are at the end of the list. So if you keep yourself straight and you draw pictures like this and you think it through, this is a surprisingly small amount of code to build a complete iterator for a hash map. I kind of mentioned this in passing, but we still have more work to do, a thing called rehashing. It's not that hard, and feel free to try it. At some point, if these linked lists get too long, our performance starts to suffer. And so one of the things that hashes do is in the middle of an insert, they'll have something we call a load factor. And it's like, whoop, these buckets, each bucket would have a length, and we might check all the bucket lengths, and if it got to be like over 10 or 15 or something, we would have to rehash these things. You don't have to reallocate, you just have to go from 4 buckets to 8 buckets, and then you recalculate the hash modulo 8 and figure out which bucket it belongs in and reconstruct all these things. And so it's not impossible to do a rehash, doubling the bucket and reducing the average chain length. But we are not going to do that in this particular thing because we're going to keep it simple. So the hash map iterator, while complex, is surprisingly simple. It's really very similar to the list iterator. The key thing is that we've got to have that while loop that sort of skips. If we're at the end of one list, it's got to get to the beginning of the next list, and it's got to skip empty buckets. Now, this is why you can see, because the things in the list are in somewhat random order. The buckets, the mapping of any key to any bucket is in random order. And this is why when you think of Python 2, we can look in Python 2 and we say, oh, if you iterate through a map, they come out in the same order, but there is no predictable order. But if you do it twice, you're going to get the same order. And the fact that the order might change if you do inserts or deletes, that has to do with the rehashing. And so we're kind of at the point where we have built the 2 foundational types of Python 2.0. We've built a list, and we've built a dictionary, Python 2.0. But next we're going to move to Python 3.0 and start creating a linked list that maintains sorted order and can be iterated in key order. And so that's going to be our treatment. So up to now, we've done all the easy stuff. So it's time to do the linked tree map, which really is kind of a modern, flexible key value store. This is a nice key value store that you would want to use if you were a software developer. Our linked tree map is ordered, like Python ordered dictionaries. It stays sorted, meaning that not only does it stay in order, it stays in sorted order. We insert things and they go in order like a Java tree map. You can be iterated like a C++ map or an ordered dictionary, but not a Java tree map. This just boggles my mind why you can't. Well, we'll talk about actually why they didn't do it, but it's not that hard. Why they so. And we're going to have fast lookup. So the problem with a list map is it's got a lot of nice features, and we can make a sorted list map, and we're going to in this section. But the problem with a list map is lookup is slow. And so we're going to actually pretty much use the tree part to do fast lookup. And you can see this in 6.5.2 of the textbook. So we are going to do something that's pretty common in data structures, and that is we're going to maintain wherever the entries, and they're going to maintain simultaneously a sorted linked list through the entries and a binary tree. And so we're going to look at them separately, and then we're ultimately going to find them together. We're going to put them together. So let's talk about what a tree is. A tree is a structure that the tree map entry you see has a left and a right. So the things to the left are things where the key is lower than the current, right? So H equals 42. The question is, where would A go? Well, A goes to the left. Where would T go? Well, T goes to the right. So the idea of the tree is that whatever entry you're in, there's a key in that in the entry, and then you can either go left or right based on the comparison of the key. And instead of having a head and a tail, there is just a root. So the root is the top entry of this tree. And then there's a series of left and right choices that you make. And each entry has a left and a right. And the tree map entry has a key value pair. And we're going to keep key and value as public because it's just an entry. But now there is no next, right? This is why we are using abstraction, because we're not even going to give them a next. We're going to have a left and a right, okay? And we're not going to show that. We're not going to let people see that. We're just going to give them a set of methods to mess with our tree map, and we're going to deal with all this stuff, and we need a left and a right to do it. So just taking a look at how it works is, let's just say we're going to, in this current tree that I've sort of built, they're not always balanced. I happen to balance it just because it looks better on PowerPoint slides. But let's just say we're going to insert in this tree a G equals 25. So it's got a key of G and a value of 25. So what you do is you start at the root and you compare it. And you say, oh, G is less than H. So we're going to go down the left-hand side. So you can think of it as you're walking down the left-hand side. Then you are encountering D equals 8. And then you're like, okay, G is greater than D, so we got to take it's like driving a car. Turn right at intersection D. And so we do. And we're working our way down. And now we're looking at intersection F, and we've either got to go left or right. And so G is greater than F, and so we're going to go to the right, not the left. And so we do. And so that basically is the path that we took. And so to insert G into the tree, we find the greatest value less than, which is F. And you're kind of inserting it, if you think about it, between F and H, right? So the next higher one in the tree is H, and the next lower one in the tree is F. And that was the trip we did. I like to think of this sort of trickling down the tree and making these decisions as almost like a pachinko machine, where you hit the balls, they go ding 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 ding. It's not random, of course. It's very precise, but it is kind of like you stop at the top and you make a bunch of binary left-right decisions, and eventually you find yourself somewhere at the bottom. And so if we kind of look at the tree map put, and we are going to start at the root, and then we're going to do a comparison. And if we find it, the comparison is going to be 0. We update the value. And if we don't find it, and it's less than, we're going to go left. And if it's greater than, we're going to go right. And so this is basically the idea. This while loop will trickle down the tree, going left and going right, and it will either find the value if there's a match. Like if we're looking for F, we'd have found it, and we'd have stopped, and we would have returned. If we're looking for G, we won't find it, but we will find where we're supposed to insert it. Okay? So the last thing that we talk to, which G will find its way down to the right of F, we will find where to put it. So as long as the tree is correctly maintained, you will either find a match or you will find the right place to insert it. And the tree it's not guaranteed to be balanced. There's further algorithms that can make the tree balanced. But the key thing is that the order will be right. Okay, so by following these rules, following this algorithm, the order will be right, and you will always find the right place to put it. Or you will find a matching place. And think about how dictionaries work, right? You say X sub hello equals something. Well, there's either going to be a hello key in there or not. If there's not, we're going to put it in. If there is, we're going to update it. And that's what this code does. We're going to create a new tree map. We're going to put h equals 22, and then we're going to do h equals 42, which replaces h, right? Then we're going to do d equals 8. Then we're going to do b equals 1, 2, 3, and then we're going to do f equals 6. And it turns out I'm kind of doing this in order so it doesn't get too long on the page. And then I'm going to do a dump. And remember how important a debug is. When I first wrote this code, you can darn well bet you that I had map dump. It was map put, map dump, map put, map dump, map put, map dump. So I could see what it does. And so the dump, if you look at the dump, then we put in K and M and J, and then we dump it again. And so what I've done is, if you look at the map output, you see that the map output has these h equals 42, and then it's kind of trying to give you some sense of the treeness of it. Okay, meaning that the b equals 123, f equals 6, and d equals 8, the number of vertical bars tell you how deep in the tree you are. And so you can see that the immediate child nodes of h in the second dump are d and k, and the child nodes of k are j and m. So you could draw this all up. And so the idea of my dump code is I'm trying to sort of draw you a tree. So here is the dump code. Now this is very, very different. And literally, this is the first time, well, I talked about recursions and functions, talked about stack frames and stuff like that. But if you go all the way back to Python for Everybody, I delay talking about recursion until there's a real value for it. And it turns out this is a beautiful use of recursion. And if you didn't write this recursively, you'd probably have to write your own stack. And that would be like a bummer. We're going to recursively go down the tree, and we're going to keep track of the depth. And the idea of the depth is it tells me how many vertical bars to print. So we come in, and we're pointed at a particular place in the tree. Maybe the root, maybe the top one. And depth is going to be 0. And so if cur is null, we're done. A key thing to recursion is you've got to have a way to get out. So if we get to the end of some tree, subtree, and we get to a null, we go left or right and that it's a null, don't print anything out, just you're done. You've gone one beyond the leaf of the tree and cur is null, so just return. Then what we do is we have a for loop, depending on depth, that prints vertical bar space. That spaces it over. And we're going to go down the left tree, and then we're going to come back and we're going down the right tree. And this is what's called a depth first search for those computer science nerds, right? And so we're going to go down the left, and you'll notice that when we go down the left, if the left is not equal to null, we are going to dump the tree on the left with depth equals depth plus 1. And so if we start with a depth of 0, that's going to become 1. And then if we recursively go down further, then it's going to be 2. And then then that when that recursion comes back, if cur right is not equal to null, we're going to dump the tree on the right. So what you see is dump the tree on the left recursively, which means go all the way down the left, then come back up, then dump the right node, then come back up, go up again, and dump the right node. And so you see this like how the order. This is a depth first search of H. We're going down past D. Then we're going even further past B. And then we're coming up from B, and we're going back down from D to F. We're coming up from F, then we come up from D, then we go across H, and then we go down to K, but then we go to the left of K, which is J, we go back up, and then we go to the right of K, which is M, and then we go back up, and we're done. So the calling sequence to this is tree map, dump tree, self root with a depth of 0. I will say this, when I wrote this code the first time, I had printfs all over the place. Now I pretty much know how to do a depth first search of a tree, but still, in a debugging, sometimes sometimes you make your tree incorrectly and your debugging is like, huh, that doesn't look like what I thought it was gonna be. And so I don't be ashamed if you have to put print statements in all over the place. First, get your dump working. Just make sure your dump works, because then you can debug everything else with the dump. And the get's pretty simple. And we've got the default, we got the key, and we've got the tree. So we're going to start a while loop where we're going to go down left, right, left, right, left, right, right? So we're going to start at the root. We're going to compare the key to the key we're searching for, the current key. If they're the same, then return the value. We could do this recursively, but that you don't do recursion if you don't need to. If the current key, if the key we're looking for is less than the key we found, we're going to go down the left. And if the current key, otherwise we're going to go down the right. And so you can see this thing is just going to pachinko its way down, ding, 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 to the right spot. And if it gets to null, then we return the default, right? Remember, this is like a dictionary. If the key's not there on a get, we return the default. You can see why Guido van Rossum in Christmas 1987 created a function called get, which looked for a key and took a default value. Because this code is what you write. What, I'm going to return null and then I have an if statement? Heck no. Just pass in a default. If you get to the bottom of the tree and you haven't found it, return the default. If I want it to be null, I can make the default null, right? Away we go. So this is beautiful. This is beautiful. So, from that beauty, both the dump are beautiful and the get is beautiful. Iterator is a pain. You just can't easily build an iterator for a pure tree if you have nothing more than that tree. So a list map can support an ordered iterator. We saw before a hash map can support an unordered iterator, but a tree map cannot support an iterator without building some kind of a stack. And the problem is that the concept of current is just so complex. When we're doing recursion, the concept of current is just so implicit. It's actually in the call stack, the notion of current, because there's really, when you're doing the map, the dump, you have a call stack of currents, and then when you go back up the call stack, you're getting a different current, so you're switching back. And so you either have to make your own stack of currents. You could build an iterator for a tree, but you'd have to build a stack. So a lot of folks sort of don't want to do that. We could build a stack, but we're not going to. So what we're going to do is we're going to do a technique for our iterator that is a common technique. When you have a data structure that almost does what you want, and then you have another data structure that does what you want, you combine them. So if we look at this tree, there's a lot of nice things for searching, for replacing, for inserting, and it does all that very fast because it's actually log n, because the height of the tree is log base 2 of the width of the tree, right? The number of items in the tree. So it's log base 2-ish. So it's super fast. All my trees are small, but if these trees get big, they're super fast. It goes down, the pachinkos its way down to the bottom really fast. But I can't easily build an iterator. So what I'm going to do is I'm going to add to this a linked list. But I'm going to have the linked list simultaneously working with the tree. So each of these items is going to have a next and a prev and a left and a right. And we're going to almost write the code mentally independently for the tree code and the linked list code. Okay? So we're ultimately going to combine these things together. There's not a separate linked list and a separate tree. It looks like this in a linked tree map. So think of each one of these things having a next and a prev and a left and a right. And we maintain them in such a way when we're doing inserts that everything works perfectly. So we're going to simultaneously maintain with the same entries a tree and a list, but we're only going to use the list to build the iterator. And we're going to make this a sorted list because these things are in order. the tree is helping us quickly find the place to put it, but also where to put it in order. So let's take advantage of that. So this is a sorted, ordered dictionary in Python lingo. Okay? So just remember that these entries, these list tree map entries, are simultaneously participating in a tree and at the same time in another layer, as it were, participating in a linked list. The tree map, which is the tree map structure, has a head and a root, because at the same time, tree map is both a tree and a linked list. And the map entry is going to have a next and a left and a right. And again, you just almost keep these things separate, right, in your mind. When we're doing tree things, we're going to use left and right and root. And when we're doing list things, we're going to use head and next. And these are things by now that should be sort of familiar to you. So this is the structure that we're going to build and maintain. And up next, we're going to build the put code, or this combined two-layer data structure that has a tree and a sorted linked list all at the same time. So this is an entire lecture on the put method of our tree map. And the essence of this is we're going to be simultaneously updating two data structures at the same time. I guess that's the definition of simultaneously. So just before we start, this is not easy. I think it's pretty much impossible to do exactly what I'm asking you to do. Just use a bunch of Google searches or asking your AI bot. Maybe you can. You need to really understand what you're doing, and this is where a picture is so valuable. Once you understand it, the code should look very clean and very simple to you. My put code, as I was writing it, was like broken. And like I tried to fix it, and then it was broken again. And I threw it away, and I wrote it again, and I drew a new picture, and I wrote it, and it was broken, and I threw it away again. And then like, poof, it was perfect. So as you're writing data structure code, the notion of like, it's broken, just accept that it's broken. It's going to be broken. You're going to throw it away. That's the point. Because you know that this algorithm is eventually going to work. The algorithm is not the problem. It's your implementation that's the problem. Okay? So if we take a quick look at the performance of put, and I've mentioned this, the binary search is log n, while a sorted list search is order n, meaning that if you have a search list of 500,000 or a million, it takes on average 500,000 lookups to find it. Whereas a million entry tree search, you take the log 2 of a million and you get about 20. And so the key thing is we're going to use the tree anytime we're searching. And we're going to only use the list when we're iterating. But we're going to, while we're doing put, we've got to maintain both the tree and the list. Okay? So we are going to have to be real careful to keep in our mind, and this is where I drew all those pictures. We've got to be able to insert into an empty list, which is easy because root is null and you just put the thing in. Then you got to find a right gap. A gap to the right is something, and then find a left gap, and then insert at the beginning after you go down a bunch of lefts and go down a bunch of rights, and then replacing is the easy part. As we've seen in put, you say if it's equal, change the value. Okay? So let's just take a look at our data structures, and then we talked about these before. We have simultaneously in the entry, we have a left and a right, and we have a next, because we are simultaneously maintaining a sorted linked list and a sorted tree. The tree map has a head and it has a root, and that's pretty much it. So in our constructor, we set the head to null, we set the root to null. We're empty, we don't have anything in the tree, we don't have anything in the linked list. So the empty list is easy, right? And so we have to scan to see if it's in the list, right? And if first we can just say, hey, if self head is null, and it'd be the same as saying if self root is null, well, we just point head and root to the new item, okay? Because we're inserting h equals 22. I'm going to insert these in order so the list, so I don't run out of space on my PowerPoint slides. And so when we're done with this, root is going to point to h equals 22. The left is going to point to null. The right is going to point to null. The next is going to point to null. And head is going to point to the item. So we have a valid linked list and we have a valid tree at the same time. Okay? So again, this is not the whole put code. This is just the first part where there's some dots in there where you're putting all the data in, putting the key in, and setting next to null and left to null, etc. So that's in there. But the first one is pretty easy from the head and the root. Okay? So we keep doing that for a while. Let's just take we put some things in there, and we've got our linked list going correctly. You can just verify that. You run through, they're all in order. You can take your lefts and your rights, and all the things that are less than h are to the left of h, and all the things that are to the right of h are greater than h. Away we go. So we're going to write some code, and what we're really going to look for, and this is the tricky part, is to find the item or the gap where the item belongs. Now the problem is we're going to have to link these things back up. When we were just doing a tree, it was easier, because you would either find the item or find the place to link it. Okay, so trees are easier, easy to maintain. The linked list is harder to maintain because you've got to keep track of the item that is the largest item less and the smallest item greater, and that's what I call the gap. So this left and this right are as we're walking down the list, we're going to keep track of the smallest greater item and the largest less item. Okay, and that's what this left. So we got cur, we got left, and we've got right. And you can think of left and right as like breadcrumbs. Like we're going to throw breadcrumbs. When we're going to turn to the left, we're going to remember the right. When we turn to the right, we're going to remember the left. And you'll see it in action. So here we go. Here we go. So we got this tree, g equals 29. We're going to insert it. So then what we do is we compare it to h equals 42. And then we say, oh, that's a turn to the left. So now we know, at least at this point, the smallest greatest value is h. And so we point right at h as we are moving down the tree. And you see that. You do the stir comp. You see what it says. If comp is less than 0, we're going to turn left, and then right is going to point at cur where we were. And now the next time when we're going to turn right, which is what we're going to do next, it's going to remember where left was. So we're now comparing g to d, and g is greater than d. So now we're going to turn right, but now we're going to update left. So d at this point in our search, d is the largest number less than, or the largest key less than g, and h is the smallest key greater than g. So you see how left and right are like breadcrumbs as we're sort of pachinkoing our way down this tree. So then we compare g to f, and g is greater than f, and so we're going to take a right turn, and whenever we take a right turn, we update left. So now we have actually found the place that g belongs. And if you look, left and right are perfect for the linked list, because now we know that left next is going to point to g, and g next is going to point to h. So left next won't point at h anymore, it's going to point at g, and new next is going to point at h. Okay, so when we do this, because we've got left and we've got right, we just link them in. And then we insert it into the tree, and away we go. And so now you look, what we have done is we have now, left and right were just temporary variables that we had during this tree map put code. But if you look at this and look at carefully, we have a correctly formed linked list that's sorted in order, and we have a correctly formed tree. And we use the tree to get to F fast, and we use left and right so that once we got to the right place, which was to the right of F, we could just hook it into that linked list with no additional cost. Okay? See how pretty it is. So now let's take a look at some other of these things. So let's take a look at inserting J. Well, J is going to go right when it sees H because it's greater than. It's going to go left when it sees K because it's less than. I mean I. I'm inserting I, not J. It's going to go left when it sees K, and it's going to go left when it sees J. And when it's done, you've got left is H and right, the right value in the I shouldn't even name these left. I should call them the smallest, wait a sec, the largest value less than and the smallest value greater than. That would probably be a more mnemonic name, is largest value less than and smallest value greater than instead of left and right. I'm thinking of it as the thing, it's like a bracket. You got a gap. And what's your immediate left and what's your immediate right? And so now we know exactly where this belongs, and we know how to update both the linked list and the tree. So, boink, update the linked list using left and right, and then update the tree using cur, right? And so away we go, and we've got ourselves in that gap. And so we can insert to the left, we can insert to the right. Now remember that if our key was J, we'd have found it, and then all we'd have done is updated the value. So remember, and my brain does this a lot when I'm looking at this code. I'm like, but will I find it? And will I find the right one? What if it's already there? Well, already there's the easy part. Okay, so there we go. So let's take a look at inserting A equals 17 and how this works. Remember the use cases. We've got to do the beginning, the end, left gap, right gap, empty list, and then pretty much we'll have it. So A equals 17, that's going to end up all the way down. So we are going to compare it, and we're going to turn left, to the left, to the left. I think there's a song and a dance about that. And so we remember right, which is the smallest number greater than. And it's not going to be right is not going to stay H equals 42 because we're going to compare A and D, and then we're going to go left again. And now right is going to follow us. And then we're going to compare A and B, and we're going to go left again, and right is going to follow us. Now the interesting thing is left is now null. We have found the place. We're going to insert to the left of B, but we're also going to insert through the head because we know that left is null, which means that we just found the lowest thing in the current, something lower than anything in the linked list. So then we just hook A in before B right after head, and then we hook it in to the left of the B. Going with a larger than anything else that's in there, we're going to end up with this at the end of the linked list. We're going to compare X to H and going to go right. And remember left, the largest value less than for now. We're going to look at K, we're going to go left again, and left is going to be updated to be K, the largest value less than. Then we're going to compare X to M, and X is still greater than M. So we're going to go right again, and left is going to be M equals 67. And you'll note that the thing we detect here is right equals 0, which means we have no value greater than X in this list. So we just say X next, the current thing next is null, and the cur next is, points to the X entry. And then we hook it in on the right side of the M equals 67, and then we are done. So if we're going to do a replacement, remember I told you this was the easy one. So, and again, in my brain when I was writing this code, I'm like, but what if it's already there? It's like, calm down, that's the easy one. Okay, so we're comparing F to H. Well, it's to the left. We're going to keep track of right, but we're not going to use them because we're going to find it. And then we have a match. And then we just see it and go like, oh, fine. F is 16. We're done. Life is simple. If they're equal, we found it. We don't have to keep looking. We found it. We just change it. And again, think of how fast this works when the key's already there. It's like nothing to allocate, no links to make. You just change the value, and you're done. So it's important to test all of these cases. And I just went through every single one of the cases and showed you what they're supposed to look like. And I will tell you that you will make mistakes. And I will tell you that asking Google for help, as long as you read what they say, will inform you. But I doubt that Google's going to just give you the whole code of something that is as intricate as this. I would say a simultaneous sorted linked list and a tree at the same time. Maybe it can do that, because that's what you're really doing. So up next, we are going to go back to the beginning and go back to Python for everybody to wrap things up. Well, it's been quite a journey. We have built in C a whole object-oriented pattern, reviewed all of object-oriented programming, implemented a number of different Python objects in C as a way to understand how C++ works, how Java works, how Python works, how they all work under the covers. And so we come to the end of this sort of walk through all these amazing data structures, and I hope you've had fun. But one of the things I like to do at the end is I like to go back to the beginning. So some of you have been with me from the very beginning. Python for Everybody may be the first programming class that you ever took. And I want to now finish by reviewing the very first program that I ever showed you in Python for Everybody. It is from chapter 1. I love this example, and this is counting the most common word in a file. So it's in Python. We read a file name, we create a dictionary, we read all the lines, we split it. I think we don't do conversion to lowercase, but then we're going through all the words, and we're saying we're going to set the counts to counts.get word comma 0. Remember when you first saw that, 0 is the default, and then we're going to add 1, and that's the way when we see the first word, we sort of bootstrap whatever the word is that we're looking at. Then we have a max loop, so we're going to iterate with items. We're going to look for word comma count in items, and we're going to do a simple max loop, and then when it's all done, we're going to print out the largest word and the count of the number of times that large word was shown. So fast forward. Here we go. Now you by now have built a tree map, hopefully. And so now what we're going to do is we're going to use your tree map code, and we're going to implement this count. So we're going to have a tree map, call the constructor for it. That's our dictionary. We're going to have the tree map entry that we're going to need to use to go through the iterator. We're going to have a tree map iterator. We're going to create, because we don't have strings, we're going to create a 100 item array name, char array, and word. And yes, it's dangerous. We're just not going to be too mean to our code and blow it up, but we could. And then variables like I and j and count max value and char max key. That's all of our setup stuff. So we're going to open the file name using scanf. Now we're in C. It's not Python anymore. But you can see the similarity. So then we're going to do an fopen of the file using read. And again, you can see the similarity. We're going to do a scanf through fscanf with a file pointer. And we're going to do a %s, which gives us a word. And word there is a pass by reference, because remember, word's an array. If we don't get an end of file, we're going to write a for loop to go through word and call toLower, which is in ctype.h. And then we are going to carefully put a new line at the end of word. And then we're going to get the current count with map get. Ask for map, which is like self. Word is the key, and 0 is the default. And then we're going to do a map put into the word position with count +1. And then we're going to close it, or close the thing, and we're going to dump the map. Then what we're going to do is write a max loop. Max key equals null, max value equals -1. It's a count, so I guess we can assume that -1 works here, because there's only positive integers in our dictionary /tree map. We're going to ask for an iterator. We're going to create an infinite loop. We're going to ask for the next item from the iterator. If it's null, we're done. And if max key is null, or the cur value is greater than or equal to max value, the one we're looking at is greater than our current max, we retain max key and max value. And when we're done, we give back the iterator, and we print out the max key and the max value, and then we delete the map. And so that's the miles to go before I sleep. Been a long time, but the end is really the beginning. These are the most basic data structures. These are the classic data structures. These are the data structures from Chapter 6 of Kernighan and Ritchie. These are the data structures for 40 plus years that people have been learning about. Once you get good, and I hope you have taken the time to get really good at these data structures, because what these are is they're like the omelet of cooking. They're easy. It seems like everyone knows how to do them. But until you know how to do the easy stuff, you can't understand the large, fancy stuff. In a recipe, you need foundational notions, and you can create something amazing. If you have done all the work in this course and you've done it well, your journey can continue with many great cookbooks. The one I'm showing you now is what we called CLR, because of the authors. When I did it back in grad school, there was only 3 authors, not 4 authors. CLR, and this is a thick book, a very thick book. And what you're going to find is this is a very well-written book. And if you know everything in this course, you should be able to open this book up to Warshell's algorithm and write an implementation of C, of Warshell's algorithm. Because you know how to allocate things, you know how to create structures with pointers in them, and you know how to deallocate them. And if you learned every lesson in this course, you can almost open anywhere, alpha, beta pruning, all kinds of things. You can just open it up and go 4 or 5 pages, look at how they describe the algorithm, and then implement it. So I'm not going to teach you every one of the algorithms in this book. What I've taught you is what an algorithm is and what the foundational pieces of all algorithms are. Okay? So I wish you luck, and I encourage you to keep going on your journey. Your journey is not ending, it's beginning.
Hello, and welcome to the lecture in C Programming for Everybody that I call the Epilogue. And that's because this lecture happened after the course was completely finished. I have a saying in my life that basically says that when you think you are finished with a journey, often that's when you finally know where the journey actually begins. And that applies in C Programming for Everybody, because C Programming for Everybody for me was a 4.5-year project to create the book, create the autograders, create the lectures, get it up on Coursera, get it out on the internet, etc. And so I just was going through the class, and at some point I ran into Chapter 6 of Kernighan and Ritchie, and I'm like, what will some good examples to use? What are some good examples that I can use that will be relevant to the students who perhaps have taken Python for Everybody? And I'm like, well, why don't we just implement some Python classes? We'll see how complex they get. And if it works out well, it talks about the concept of interfaces and implementations. And so I think it worked out really, really well. And so as we were going through Chapter 6 of Kernighan and Ritchie, I built us a Python string class. And you can go back and you can watch those other ones as an extendable character array with some chunking, where it would allocate some space and then fill that space up, and as that space filled up, it would extend it. And I made a list class, and I used the linked list from Kernighan and Ritchie Chapter 6. If you recall, I made an extra little bonus section 6.5.1 where I talked about linked list explicitly, because in the original Kernighan and Ritchie 1978 book, and I believe it's the same in the 84, but I'm like, I'm going to show you linked lists first, and so I added this little piece to
the canon, the Kernighan and Ritchie canon. I added that. I implemented the Python dictionary using the technique of Kernighan and Ritchie 6.6, pretty much straight on. When I built the Python string class, you'll notice that there's a structure that has a length and an alloc, and the alloc is how many characters we allocated, and the length is how many of those we've used, and we're putting automatically a 0 byte at the end of it. As you add things together, eventually you get the length to be 9 with a 0 byte, and the alloc is 10, which means we can't add the letter D. And so we use realloc to extend it and make it be 20, and then we have space to put both the letter D and the end of string. We built a Python list class. It was so natural to just make it be a linked list, and linked list has two structs. One is the linked list itself that has a head pointer and a tail pointer, and a number of items that like lets us give back len when we need to give len back. But then every node, we're going to just have a list of character strings or character arrays, and so we have a pointer to a character array, and then we have a pointer to the next. And so when we sort of do our constructor, we allocate the object, and then we set the head and the tail to null to indicate that the list is currently empty, and set the count to 0, and we're done. And then as we add things to the list, right, we have these pointers, and we point to the head to the beginning of the list, the tail to the last item that we added, and we store using malloc the strings so that we get a pointer to a string that the list owns rather than the parameter, which doesn't belong to us. And then we hook the next up, and there's a little tricky stuff, right? If the string is empty, which means head is null, then we just point head at the newly allocated node. If the tail's not null, we take the last thing and point it to the one we just made and set tail to new, and then we allocate the string and then copy the text from the parameter into text, and then we store that as a pointer, and then we update our count. Like if we add another one, you have to kind of graph the new one in beyond the tail. So the tail, instead of being null, now points to the one we just created, the fun. And then we update tail to point to that, and then the next on that one is 0, because that's our way of ending the list. And if we're going to iterate through this list, we start at the head, look at the item, then we go to next, and then we'll look at that item, and then go to next, and look at that item, and go to next, and it's null, and we're done. Again, we were able to build a quite competent Python list object from that. And as you might expect, when we switch to building the dictionary class, we just go into section 6.6 and go in and make a hash table with buckets. And it's literally the bucket-based hash map is probably the most common programming interview question. Perhaps it's less common now because everyone knows that it's a programming interview question, right? And so, I just figured, of course, a dictionary is going to be a set of buckets that are a set of pointers to lists. Recall that hashes are some function that takes the key and creates a large pseudo-random number, which means it's deterministic, but it's widely distributed with the idea to limit collisions. So John Smith and Joe Smith hopefully will hash differently, even though they're very close, right? And so the way we did this, again following Kernighan and Ritchie, is we used the key computed a hash, which is a large integer generally, but then we modulo it based on the number of buckets. And so the buckets are, in a sense, 4 linked lists. And if we wanted to write this code in a way, we could have kind of used the list object and said here and be a little bit less repetitive, but we just implemented the whole thing. So if you look, we start with a struct krdict, which has a number of buckets. It has 4 heads and 4 tails and a count. And so it's just heads and tails of the way you do linked lists. And if you look at the node, we're going to do key and value, and I'm going to make it be a string key and an integer value, again to simplify, right? And the char star key is a pointer to a key that we're going to save. And if we look at the new operation, we allocate the actual dictionary object. We decide how many buckets we're going to have. The way I define struct krdict, it's just a 4-element array. Then we set them all to null so that we know that they're empty, because it's important to know if the heads and tails each of the linked lists are empty. Now one of the things is this doesn't have any expansion mechanism. And so I just wanted to keep it really simple to show you the data structure, so I kind of like punted on rehashing an expansion. And then we set the count to 0, and then we return it. As we're inserting things in, right, we use the hash to figure it out, and then we simply have 4 linked lists. So if you were to compare the KR list code to the KR dict code, you would see that a lot of it looks the same, except we're starting with a head that has been chosen by a hash computation along with modulo based on the number of buckets. As I finished all that up and I finished the class up, I began to really wonder. I started looking at it less from a C and a K&R, Kernighan and Ritchie perspective, and more from a Python perspective. And I'm like, did I just inadvertently do exactly what Guido van Rossum did? Did Guido van Rossum read this book like most of us did in the 70s and 80s? And did he just say, you know what, I'm going to make a list object and it's going to be a linked list, and I'm going to make a hash object and it's going to be a set of buckets, linked lists and buckets like everybody would do? So I decided I would ask Guido if I could come out to him, see him, and talk to him about the influence that Kernighan and Ritchie Chapter 6 had on his design of Python. And in particular, was my guess, because I didn't look at the Python code to do this, I was really teaching Kernighan and Ritchie Chapter 6. And so up next we have the first of 2 interviews with Guido asking about how he built his structures and whether or not my structures that I had just guessed and assumed were even close. And so we started the interview with me handing him a copy of the Kernighan and Ritchie C book, which was signed, and I left it with him, and saying, skim through Chapter 6 and tell me how Chapter 6 affected how you built the original version of Python. Python 001 did you start building the objects? And where did the objects come first and then a syntax came, or did you build a syntax and then the objects?
I think in my head I had both.
Okay.
Because I was building a stripped down version of ABC, and I was very familiar with how ABC implemented its data structures. And I had pretty well developed ideas about how I would do it instead of the ABC way, both for the syntax and for the data structures. So for the syntax, actually, my main gripe about ABC was that it used uppercase letters for the keywords of the language. They had a reason for that, but I didn't think it was a good reason, and it just looked horrible to a Unix hacker like myself. So that's what I wanted to change for the syntax. But I knew that I wanted to do the indentation, and I had already participated in the parser for ABC, so I knew how to do that stuff. I had some of my own ideas, but I knew what I wanted. I literally actually started with a parser, and actually I started with a lexer and a parser. Those were actually the first bits of the language that I wrote. But before I started, I knew I had very specific ideas on how the primitive data types would be implemented. I would use the same reference count mechanism that I knew well from ABC. I would implement integers in a similar way because I wanted.
That would be an easy, integers would be an easy choice not to put in the object field.
Yeah, no, I wanted everything to be an object. That was also a thing I approved of about ABC. And I think I have to take it back about the arbitrary precision integers. Mm-hmm. Those came quickly, but I don't think that they came immediately. There was an integer type which was 32 bits. There was a separate long type which survived until the end of Python 2, which was arbitrary precision, and there was a float type. Then for the sort of more complex data structures, and sort of the int and the numeric types were not all that different or interesting not that different from ABC. But for the rest, I sort of had seen what ABC did, which was that everything was implemented as a tree, even strings. And I did not like that because I wanted to interface with system calls and C libraries. And I said, I want strings to be arbitrary length, but I want them to be a linear buffer. And so too bad if a long string sort of requires allocating a large buffer at once. Most strings aren't that long. I'll make sure that it works for any size, but I'll optimize for the short strings that are the bread and butter of so many programs I imagined would be written in Python.
That is a brilliant choice, but not automatic or intuitive that would be the right answer.
Having sort of written a lot of C code and knowing that I wanted Python to be extensible with C, that was also one of the very early choices. I wanted to sort of link back to C code in a natural way. So the import system was part of that.
So when Python was a month old, or maybe 2 months old, if you were appending to a string and a loop, was it basically extending, reallocating, and copying?
No, strings were always immutable. So yes, it was calculating the size of the result, allocating a new string object, and then copying the two originals into that. There is a string resize internal operation that is sort of intended to be only used when you're building up a string before you've shown it to anyone else.
Right.
And I needed that because I was envisioning an I/O system where you say, oh, I'm going to read a line and I don't know how long that line is going to be, or maybe I'm going to slurp an entire file into a single string and I don't know how long that file is. So I'm allocating a large enough buffer. I'm reading into that buffer, and then if it turns out that I allocated 1,000 bytes, but what I read was only 15 bytes, I reallocated to give the sort of remaining 85 or whatever 900 bytes.
Are we talking about your thinking before you released the very first version of Python? Meaning you didn't at some point you came back from vacation and you handed it to somebody at work. This is your thinking when there's only one person before even the 0.01.
Oh yeah. I wanted strings to be done that way, including like the little detail that if you have a string of, say, 10 bytes, you allocate 11 bytes and you put a null byte at the end, just so that if you happen to want to pass that string to a C library function that expected 0 terminated strings, null byte terminated strings, you wouldn't have to copy it. There might be a null byte in the middle, so you might things might still go wrong, but if you sort of knew or trusted that wasn't the case, you wouldn't have to make a copy with 1 extra byte just to make sure that null byte was there. The null byte is part of the data structure. only of course visible on the C side. So for lists, I had a similar idea. Again, lists in ABC were a tree structure that was sort of super efficient, even if you grew a very large list from small ones. And I thought the tree structure was way too complicated, so I said, okay, a list is a mutable data structure. That was sort of a concept that didn't really exist in ABC. In ABC, everything was immutable. I thought, well, pragmatically speaking, I prefer my larger data structures, meaning lists and dictionaries, to be mutable. And so the implementation was always just a pointer to a buffer that could be reallocated. We call it list in Python. It really is an array. That is an array of pointers, and each pointer points to an object. We know how long that array is. That's in the object header. And so if there's no room, we reallocate it. And if we throw something away from the middle, then we shift everything over and we also reallocate. The only improvement that happened to that data structure in the last, well, let's say 34 years, is that the original implementation did not have over-allocation. I was relying on realloc doing some kind of chunking. So if you realloc something from 1,000 bytes to 1,004 bytes, I imagine, well, internally realloc probably aligns everything in chunks of 16 bytes or more, and so it's not going to move that memory. And that sort of, eventually that was shown to be either false or just inefficient.
You and realloc would do it as well as you would have done it, but eventually it didn't.
It didn't, yeah. And so eventually they're sort of internally, there are two sizes that are held in the list object header. One tells you what the length of the array is of the list is to the Python user, and the other one tells you how much space there is in the array, and the second is always larger than the first. And
I'm shocked that it wasn't a linked list.
Oh, really?
Yeah, I'm shocked.
I'm sorry.
It's named list.
But
okay.
Yeah, no,
I get what you're doing. So then talk through, as you built the earliest dictionary structure, what's different between that?
So again, in ABC, dictionaries were trees, and in the case of dictionaries, they were kept in sorted order by the key. The key was always some orderable object. Well, I think in ABC, everything was comparable.
Yeah.
At least two things of the same type.
Were trees.
So ABC, and again, I thought that was too complex, and I had skimmed at least Knuth Volume 3, which explains the concept of hash tables. And I was familiar with hash tables in Perl, where I think they're cold hashes. And so I just I leafed through the table of contents of Knuth Volume 3, and I picked a hashing algorithm and sort of a hash table organization that felt right. And so I chose open hashing instead of sort of having separate linked lists for buckets. And the original hash algorithm for strings, at least, was something, I don't know if I picked the hash function out of Knuth also, but I probably did.
Between Python 3.7 and Python 3.8, dictionaries kept their order. Like, what happened? Was it the revenge of ABC? Meaning that the trees...
No. It's a different kind of order. In ABC, the keys were sorted. So if you have numeric keys, if you have the 112 and 500 in your dictionary, in ABC at least, the keys are ordered 1, 12, 500, or 1, 2, 3, or whatever.
Yeah.
And if you insert 11, it gets inserted between 1 and 12. On the other hand, in the newer Python dictionaries that preserve order, it is insertion order.
Right.
So it is not because the sort of Python dictionaries don't require that the key type is sortable, is comparable. It only needs to be hashable. And so we can, well, and of course it needs to be, you need to have an equality comparison. Is this string equal to that string? But you don't need, you never need to look at is this string less than that string.
So what did you do to make it keep insertion order?
So that was in a time when I had long relinquished or delegated development of most of the basic data types. I think we had a developer in Japan who sort of for years had been improving the efficiency of the dictionary type. Mm-hmm. And sort of one of the problems of the original design with open hashing that I picked from Knuth is that it's pretty space inefficient. Right. Because if you have let's see if I can reconstruct. For each key value pair, you have to have a pointer to the key. Let's be old-fashioned and say that's 4 bytes. You have a pointer to the value, that's another 4 bytes. Then you have the hash, which is another 4 bytes. So now the hash table is an array of structs that are each 12 bytes long. And for the hash table algorithm to the lookup and insertion and deletion algorithm to work at all, you can't have the table be more than 2/3 full. So that means that if you have an array of 1,000 entries, you can store at most 600 or 700 key value pairs. And so you have 300 or 400 times 24 bytes wasted space. And so our Japanese core dev figured out a way to have separate tables where the sort of the hash table only contained one thing, and the actual key value pairs and hashes were kept in a table that had no holes in it.
So they were basically like kind of growing, filling, remembering, everything is remembering where things are laid out.
And so first he stumbled upon sort of, I think he refined the algorithm a few times, having these separate arrays, and then he stumbled upon the property that, oh, hey, it happens to preserve insertion order.
In the second table for sure, right?
Exactly. In the second table, because the sort of the table in which you jump around based on the hash value now just has an index into the other table. And so there is an additional space saving, because if your hash table has less than 256 elements, that array only needs to have 1 byte for the index. And so there's like all kinds of cleverness there.
It comes as a surprise to me that you don't do linked lists.
Really? I could have told you that 10 years ago.
That it doesn't do linked lists. I mean, I guess, and that has probably to do with your desire to interoperate with C. Kind of just percolates throughout that. Blocks of things that can be extended and then filled in seem to be better than generic linked lists.
What I didn't know at the time that's also a good architecture for modern hardware, because you have better cache locality.
Exactly. I would have thought.
which is not a concept that I think I
Certainly
even
linked
knew
lists.
existed in '89. So I think I just avoided linked lists because I didn't like them for some other reason.
That's cool. That's exactly, well, it's not exactly what I hoped you'd say. I'd hoped you'd list over and over and over again, because I just have assumed all my life that linked lists were the, linked lists and hash maps and linked lists on top of hash maps and linked list, linked list, linked list. Because computer science thinks about linked lists all the time.
There are plenty of pointers in Python.
Yeah.
But sort of the classic linked list is not used much.
So I hope you watch that interview carefully. One of the things that I do when I edit the interviews that I have with luminaries is that it's not uncommon that the questions that I ask them are not perfect questions. And then you kind of, what I do at that point is I'm like, whoops, my assumptions were incorrect. And so one of the things I did in the editing of the interview that you just watched, and you'll see it in the interview, the next one, is that I didn't cut out all of my confusion. And that the reason for that is that I wanted you to see the moments where I had an assumption that turned out to be wrong, and then I'm kind of mentally scrambling to ask a good question, and I'm asking for clarifications. And so during that video you can see me learning from Guido. The summary of this is that Guido really didn't use the linked list much at all. He didn't use the linked list for the list object, and didn't use the linked list for the string object, and didn't use the linked list for the dictionary object. Surprise, surprise, I was completely wrong. The Python 1.0 list and dictionary objects were extendable arrays of pointers and not linked list at all. While Guido was an expert in K&R Chapter 6, like most of us were, his much more recent work was in ABC and C++, and so he really wasn't looking at K&R for his data structure implementation. And more importantly, he was looking at ABC for his data structure implementation. Or more specifically, he was looking at ABC and saying, I don't like the way ABC did its data structure implementation, but he didn't then go back to Chapter 6 of Kernighan and Ritchie and say, well, I'll just do it this way, which is, again, I'm a computer scientist, and my instinct is like, Chapter 6 of Kernighan and Ritchie is just the ground truth. Why wouldn't you do that? So I think he started with lists as simple extendable arrays, which makes a lot of sense because you're either linearly looking them up, which is not the fastest way, or you're looking them up by position, like sub 5, and why not use arrays? So that just, once you talk to him and he walks you through it, and you're like, oh, yeah, I get it. But then the other thing is he didn't even use linked lists and dictionaries, and you can see me as I'm asking that question, like incredulously saying, like, please tell me that you use linked lists and dictionaries and buckets, like all the interview questions for the last 35 years. And the answer is no. So he looked at an earlier document, and this was the truth of algorithms for all of us in the 70s. And that is Donald Knuth, volumes 1, 2, and 3. And right here is Donald Knuth, volume 3, the one that I scanned to get what's in there. And here in, where are we? Yeah, collision resolution by open hashing. So what he was doing was what good computer scientists did of the day, and that is read through this kind of a book and found inspiration for how to build a hash map, because he knew we wanted to do hashing. So we did hashing in K&R Chapter 6, and he wanted to do hashing, but he did it a very different way. And it has to do with the collision resolution and the linear probing. And so again, there were no real linked lists in the core data structures. It turned out that, and we talk about this a little bit in the video, that there are performance advantages to not using linked lists. And the interesting thing is, if you look at when Guido was actually building Python Python, we were all using computers that didn't depend heavily on cached memory architectures, meaning that the CPUs that we were using and the memory that we're using had a speed match much better. And that's because all of it was in refrigerator-sized computers. And things were just slow enough that the CPU was not that much faster than the memory. But when the CPU became a single chip CPU in the late 1980s and early 1990s, when the floating point, fast floating point, even ended up on a single very large, very hot chip, the memory could never keep up, because what happened inside the chip, which is maybe 3/4 of an inch to an inch, or more likely more like a half inch, that was so fast inside the CPUs that the memory just couldn't keep up, and so they put caches inside the CPUs that could keep up with the CPUs. But linked lists caused this bouncing through memory that blew the cache. And so if you were to try to run a pure linked list based operation with a 10,000 long list, it would perform terribly on a 1992, 93, 94 computer. But Guido wrote this thing in 1989 and 90, and so he wasn't thinking I got to make a cache efficient data structure. He's just I like arrays, but they turn out to be really good for cache architectures. And so to some degree, if you were to go back and look at it and say, well, let's go back and add linked lists, you'd say no, because linked lists would have a really bad performance impact if we did them in a sense the way I did them when I was teaching you Chapter 6 of Kernighan and Ritchie. And so that's why you see the delight. I mean, I'm wrong. When I'm talking to Guido, I'm wrong the whole time, but I'm learning. And I'm like, oh, that's so cool. So let's do a little bit of a review, and this sample code is available to you. So let's take a look at my re-implementation of a Python 1.0 list, not the Kernighan and Ritchie way, but the Guido way. And what you find is you look at this code, and I'll get some code walkthroughs and you can look at those later, but if you really spend some time and compare the linked list implementation to the extendable array implementation, you'll realize it's simpler. So, for one thing, we only have one structure. It's the list. We have, again, how many allocated spaces are in the list, much like the string that we did. I did the string pretty close to how Guido did the string, but the list I got wrong. So you have an allocation and a length, which is very much like the string that I did, and then an array of pointers. Okay, so that's what this char star star says. That's an array. The first star is an array. The second star is an array of what? It's a pointers to items. Okay, and that is an array of pointers to characters. That's what that's saying. And so if you look at what we do, we allocate the thing. We set the alloc to 0, and alloc to 2, and the length to 0, and then we allocate a 2-item array of pointers. We know that length is 0, so we know that none of them are used. And so that's the data structure. In a sense, it's already simpler than a linked list. And if you append, first you got to see if you've got space to append, right? And if you've got space to append, well, that's okay. You just allocate the new string, you copy the parameter into that string, and wherever the end is, and length tells you where the end is, you put it in that position and add 1 to the length. And so at the end of the first one, you've got a half full linked list now with a 0th item pointing at the character array that you just saved. And then if you put the second one in, you do the same thing. And we don't have to do anything right now because the length is 2 and the alloc is 2. We've got a completely full array because our list has 2 items in it. But then the next time you come in, self length is greater than or equal to self alloc. So we're just going to extend it. So I just added 2 entries for simplicity, and then I do a realloc. And what realloc does is for the things that were in it before we realloc, they get copied if we get a new pointer back. Sometimes you get the same pointer back with a little more space allowed at the end. Sometimes you get a new pointer. You can't tell with realloc. Computer scientists like myself who were trained on linked lists really tried to avoid realloc. And maybe that was a good idea, and maybe that was because realloc wasn't such a great implementation. And Guido and I talk a little bit about realloc let Guido down as Python progressed and became more and more significant. So he tended to start doing his own memory management and not depending on realloc, which is a combination of the C runtime and potentially the operating system. But the key to realloc is if you got 2 items in there, you might get a new pointer back, and that's why I've got to reassign it. A new pointer back, but it'll copy the ones that are there, but you're responsible for setting up the ones that are new. Now for us, because length is all we need, we don't even have to set like 2 and 3 to 0. We don't have to do that. So we just now have 4 spaces, and we save the malloc, we malloc it again, and we copy the saved thing in, and we put it in at the end. Now we have space, and then we add 1 to the length. And I have some code walkthrough that goes into this in more detail, but let's just take a quick look at the shapes of these 2 approaches, right? And again, I just assumed linked lists, but I'll tell you that I apologize to you. I'm like, well, some of these for loops in linked lists are not the greatest thing, blah, 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 right? And if you just look, you can kind of see how the Python in the lower right that just has an array of pointers is simpler than the linked list on the left. And again, we computer scientists have always taken pride in the fact that we understand linked lists. But that doesn't mean that just because it's something we know how to use, that it's the right thing in all situations. And Guido chose to go elsewhere. And then if we look at the code, in the upper left, we're dynamically extending the pointers. There was no reallocation in my KR list append because I didn't need to, because it would always alloc a new node. So there's 2 mallocs in here. In the Kernighan and Ritchie one, you malloc the node and then you malloc the string. Whereas in the Guido one, you just malloc the string, and every once in a while you realloc the items. The part of linked lists that always gets me, and I just have to draw a picture every time I do it, is that part in the middle of the KR list underscore append, and that's if self head equals null, self head equals new. If self tail not equal null, self tail next equals new, and then self tail equals new. I get it every time, right? But those don't roll off the tongue nearly as easily as saying self item self length equals saved, self length plus plus. For all of the years since 1972, we just use linked lists almost in some ways as a badge of honor, and Guido felt no real urge to do that. And inadvertently, his approach to extendable arrays is great for caching, and it's great for fast lookup, because you can never look up a linked list by sub 27, whereas if you do it Guido's way, sub 27 is a very cheap operation. So up next, we're going to dive into what Guido did as he implemented the Python 1.0 dictionary.
Hello, and welcome to a code walkthrough for C programming for everybody. The code we're walking through is some of the Epilogue code, where we're comparing kind of what I did in my Chapter 6 Kernighan and Ritchie stuff to what Guido tells us was the Python 1, and then later the Python 3.7 approach to dictionaries, lists, and strings. So what I'm going to go through right in this one is the string. So let's take a look at that code. This is basically the code that is the string code. Now, the pattern that I'm using here is a chunked array of characters. And so like if you look at it, the string has some data, but what we're adding for this particular one was something that Guido was very obsessed with in the early Python version, again from ABC. And the idea is that we use this thing called reference counting. And it means that if you sort of assign something, you don't always have to copy all the data. You can kind of copy a pointer instead, but then you have to be careful that reference count, because the del operation has to know when the reference count goes to 0. So this pretty much looks like the code that I wrote, sort of based on for the K&R book to implement it, with some reference counting. And the easiest thing to do is look at the main code here. And so we create a new string, we dump it, we add an H character, we dump it, we add hello world as a string and we dump it, and then we're going to set it to a new value. But then here's the new part right here. We're going to create this assignment. And so this we have a variable called x, which is a pointer to a P1 str. And we have a variable called y, which is also a pointer to a P1 str. So what this is this is P1 str underscore assign, and we're passing in a pointer. And so what's going to happen here is this is like going to increment the reference count. You're going to see this. It's going to increment the reference count because now we're going to have two variables, x and y, that are literally pointing to the same string. So let's even run this code. Okay, so I've got it run here. And so what we see in that last bit, when we make all the top bit here is all on the string x. But the interesting part here is where we say string x equals a completely new string, and we're pointing out the location in memory that is. And then after the assignment statement, we see string y equals a completely new string, and it's at the same location. But what we've done is we have incremented the reference count. Then if you look at the main code, we del x, which was the original P1 stir del x, which is the original one, and all we do is we decrement the reference count, but we don't actually deallocate the data. And then we still have the string y. We shouldn't have the string x. But then what happens when we delete y at the very end here, P1 str underscore del open paren y close paren, then it actually frees the data, okay? And so the idea is we can copy a reference without copying all the data, have x pointing to it, y pointing to it with a reference count of 2, and then we can free either x or y. That'll, instead of throwing away the data, that decrements the reference count. So let's just sort of take a bit of a look. Now, most of this is the same as what we covered. Like if we look at, let's look at sort of the constructor, P1 str new, we allocate a buffer. We allocate the object, and then we allocate 10 bytes, and we tell it that it's 10 long, and we put a new line, an end of string in there, and we set the reference count to 1. So as soon as we create it, we assume that this new is going to be assigned into a variable, and then we make the reference count be 1. And so if you look at the len and the dump and the etc., and you look at the append, we see the append is pretty much a clone of what I did, where, if we don't have enough space, we allocate another block of 10. This is, Guido calls this chunking in the video, and then we reallocate it, and then we've got 10 more, and so we can stick our character in to the end of it and add 1 to it, and then we null terminate the string. So that code is identical to what I did in the Kernighan and Ritchie book. And so let's look at the assign code. So this is the interesting thing, where P1 stir underscore assign, we have one pointer, and we're going to return this pointer, so we have two variables pointing to the same block of dynamically allocated memory. So when we're doing this assignment statement, in effect, y equals x, inside the object, we don't need to worry too much about y or x, but we do need to know that we are now referenced two places. So every time we add a second or third reference, we just add 1 to the reference count. So self arrow refs plus plus, and then we return it. So then if we look at the code in the main program where we're saying struct P1 str star y equals P1 str underscore assign x, we could have said y equals x, but we wanted to record the fact that we've added a reference so that we know that that has a reference count of 2, so we don't inadvertently free the wrong thing. And then the only other place that this gets interesting is in the del method. So if we go into the del method, what's cool about this, and this is where reference counts, and so we in our main code, we just we delete y with the underscore del method, we delete x, we can do all that stuff, and it's inside the object where these reference counts are being resolved. And so what's cool about this is we're saying, okay, we're going to del x, which was the original thing that we assigned it into, and if the reference are greater than 1, we don't actually free any data. We just decrement the reference count and we're done. And so that's where we see in the output, we see decrementing reference. And you see all these addresses are the same, 0x60 blah, 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 91C0, okay? And so they're being decremented, and so the first free decrements it, and that goes from 2 to 1 in this case, because the underscore assign incremented it, and then the underscore del decremented it. But then when we get the ref count to 1, that means we're in effect freeing the last reference. So it prints out freeing reference, and you can see it says free. We're actually freeing the data. And so that's where we do the free of self data, and then we free the self to get rid of it, which is the code we did before. And so the real essence of this code is the obsession, this code is the obsession with reference counting. And that has to do with the fact that you want to be able to point multiple places to the same string without wasting extra memory just to make a bunch of copies for no real purpose. So when you're kind of making a copy that points to the original, then you have to increment the reference count and decrement it. And so in the rest of these sample code, I will not add reference counting to it because we're just going to look at the underlying data structures. But it's really important to understand that reference counting was essential to the ABC implementation and Guido's C++ implementation and Python 1.0's implementation. It was all about reference counting to save very scarce memory so that you could point to the same string many times. And the reference counts could get very high, especially strings that were constants. So reference counting is important, and this is just, you can take a look at this code and compare it to the KR code that I built. Reference counting is an important part of Python. Welcome to another code walkthrough for C Programming for Everybody. In this code walkthrough, we're going to compare how Guido implemented list in the earliest versions of Python versus how I implemented list while teaching chapter 6 of Kernighan and Ritchie. And so this was, if you watch the video of my interview with Guido van Rossum, this was like my greatest revelation. Like, what? And so the big revelation is that Python's list object in Python 0.01 was an array of pointers. And if we look at the Kernighan and Ritchie list item, this was a linked list. I did a linked list. And so the actual KR list struct has a pointer to the head and the tail of its linked list and a count. And again, this is classic linked list. And to some degree, while I was teaching this in Kernighan and Ritchie chapter 6, I was really teaching you linked lists and using the Python list abstraction to teach it. And so we have two data structures. We have this node, which just has a pointer to a text saved and a pointer to the next one. So this is like classic linked list. I'm not gonna go through that again. So you just go back and watch the chapter 6 stuff, and I talk about linked lists all the time. But that's not how Python does it. Did it or does it? And it's not clear to me exactly why, but I think he was just trying to build the simplest possible data structure. And we'll look at some code and you'll see that there is a certain simplicity. Like already in just the struct definition, we see the struct P1 list, there's only one of them. If it's a linked list, you have sort of a struct for the node and a struct for the list itself. The constructor, P1 list new, well, we're just going to malloc the object, and then we're going to say, okay, let's allocate to an array of pointers to characters. And so if we look at the struct P1 list and we see char star star items, that is syntax for a array of pointers. Okay, and so you think of each pointer as either 32 bits in the old days or 64 bits in the modern days. So that's an array. And so what I'm doing in this p items equals malloc open paren p alloc times size of char star, that means I'm allocating 2 elements that are pointers, which means, again, 2 times 64 bits in the modern world, and noting that I have 2 in there, and length, which is the Python view of the number of items, is 0. So we've got space for 2, and we have 0. And that's an array that we know alloc tells us how long the array is, and length tells us how much of the array we've used. And just to go back, I'll try not to compare and contrast too much, but just think about the complexity of linked lists the way I did them in Kernighan and Ritchie, my Kernighan and Ritchie chapter 6. You have this thing called head, you have this thing called tail, which is null, and count is 0. And again, for those of us who know linked lists, this is obvious. It's what you do. But an array is simpler than a linked list. And so, there we go. Okay. So that's what we've got. When we're done with our constructor, we've got an array of 2 pointers to characters, allocated 2 and length 1. So let's take a look at the main code right now. And so the key to this main code is that, in a sense, here's the Kernighan and Ritchie main code. Because this is like an interface and an abstraction, the main code should be pretty much the same. And the main code pretty much is the same, meaning that we create a linked list, we append some stuff to it, we print the list, we check the length, we look something up, and then we delete it. And we do both things because below the abstraction, below the interface, both of these implementations, both the KR list and the P1 list, are supposed to provide to us, the caller, the same abstraction. We can append, we can print, we can check the length, we can check the index, and we can delete it. And it does not matter what the implementation is. And so that's more the builders of the Python runtime get to decide how to do this, because we've got a contract with them, again, an interface. So let's just take a look at the code. We're going to add hello world to our list and print it. Then we're going to add catchphrase and print it. Then we're going to add Brian and print it. And then we're going to say, how big is it? And then we're going to ask, where is Brian in there? And where is Bob in there? And then we're going to delete it. And if you look at the run, you see, the list starts out as hello world, and the list is hello world catchphrase. And we'll see what this extending, because we started with 2 slots in our array. And for the first 2, you didn't have to get bigger, but then we're like, oh, wow, we're running out of space. So we got to extend this array. We'll show that code in a bit. But then we end up with 3 things in the list. Again, that's not our job as the caller. 3 things in the list, and Brian is in position 2, which 0, 1, 2. Hello world is 0, catchphrase is 1, and Brian is 2. And Bob is not there, so we get back a -1. Pretty stuff. Okay, so let's take a look at the append code, because this is where the fun happens. So here's the append code. So let's take a look at now let's go back how I taught you append, a month or so ago. And so again, you got this, the lecture has pictures of all this, right? So if you're appending, if it's empty, your self head is new. If the self tail is not equal null, then self tail next equals new, and then self tail new equals new. So that's just like, you got to draw the picture and add the little arrows, and away you go. And then you allocate save the string itself. But now we look at the P1 list, and we have to extend it if necessary, right? So if self length, i.e., is greater than self alloc, so we allocated 2 in the constructor, and then if the length is 2, we don't have enough space, because our next one would be sub 2, and that you can have sub 0 and sub 1 in a 2 long array. And so all we're going to do then is we're going to have chunking, and Guido mentioned chunking in the video. We're going to chunk it to add 10. And so we're going to basically extend from 2 to 10. So we're going to add 10. We're going to increase the alloc size, and then we're going to call realloc. And realloc is going to take the array of items and say, however big that was, free it, move it, whatever, extend it, depending on what realloc is, how realloc is working. And we're going to say, okay, we want to have 12 of these things now, 12, and that becomes our new items. Now that realloc will also, so if there's 2 things in it, and we extend to 12, realloc will copy the 2 things. So we don't have to do any copying because realloc copies the first 2 things because it knows that items is too long. And so it copies the first 2 things and then gives us 10 more. So there's no copy code here. And so I think, Guido really liked the realloc. And a lot of C programmers don't like realloc, and he did. He's like, look, realloc says it's going to do this, and I want to do this, so realloc, do your job. And so I think back to my own time as a software developer. I just felt, because again, we were taught linked list, linked list, linked list. I just didn't think about realloc as a useful thing, and Guido clearly felt like realloc is the answer. And it lets him have this simple array mentality. So you just reallocate it and say, look, here's an array that's 2. I want it to be 12. Help me, and we're done. And so that's really simple code. I think very easy to understand. And then we make a save string. And then we just add at the end of the array, self-length, which in this case is sub2, is that string. And then we add 1 to the length. So this code is really simple. And if you were doing debug print, you don't really need any addresses, because if you recall, when I'm printing in all my linked list stuff, so that you can debug it and redraw all your lines and figure everything out, I'm printing addresses out all the time. But no, this is just a position. So this is the 0, the 1, and now the 2 in this case. And so that's where you see when it says extending from 2 to 12, that's as a side effect of adding the 3rd item to a list that was pre-allocated with 2 slots. Okay? And that's it. But let's take a look at the print code, right? Let's look at the print code for both of them. This is KR list print. Let's take a look at the print code in Guido van Rossum's version. Okay. So the key to this is the for loop in P1 list underscore print. The for loop is for I equals 0, semicolon, I less than self length. Let's take that blank out. I less than self length, I plus plus. That is like really basic chapter 4, chapter 5 stuff in Kernighan and Ritchie. So it's just an array. So you write a simple incremented for loop. It's fast, cache efficient. It's beautifully simple, right? So in this print, this is obvious. Now, when I showed you this same thing in Kernighan and Ritchie, chapter 6, I just for in KR list underscore print, it says for cur equals self arrow head, cur not equal null, cur equals cur next. And I apologize for this line. I'm like, you will eventually write this because it's an idiom. You will write this quite naturally, and it'll make a lot of sense to you, right? But in Python 1, we didn't do that. It was an array. And the only place that we have to worry about its dynamic nature, is in the append, right, where we reallocate it. So everything we're doing here is a simple for loop. So like even the del command here, the del basically says, let's free all those little items, let's free those character strings with a for loop. For I equals 0, I less than self length, I plus plus. Again, a beginning C programmer can understand this code. And if we look at the C code in KR list underscore del, we just see a while loop. And remember, you had to do these in a certain order. And so the whole free, and I talked about all this stuff. The fact that you got to do it in a certain order, well, this is pretty simple, right? So it frees each of the items. It's for equals 0 in P1 list del. You free each of the characters, strings that we point to. Then we free the array that's got those pointers, which are now valid because we got rid of them. And then you free the object itself. And so to some degree, one can appreciate the simplicity of what Guido did in this by going with arrays. And again, the key thing that misled me, or that Guido just took a different approach, it really came down to realloc. And so he believed in, I was trained to not think about realloc as plan A. And so I thought linked lists were plan A, because then you don't have to do so many reallocs. And Guido's like, I want an array, and realloc says it's going to do this for me. And away we go. So I encourage you to take a look at P1 list and KR list and put them in two windows next to each other and sort of compare and contrast. And what I really want you to do as you're comparing and contrasting is I want you to think about the complexity of writing, debugging, and then later the complexity of understanding, and how much knowledge a programmer has to understand to be able to make sense of these two bits of code. And again, for those of us computer scientists for whom linked lists are very natural, we just write this stuff. I can write it pretty fast, but that doesn't mean that it's the easiest to learn. So away we go. And so I hope you found this comparison interesting. Cheers.
So now I want to talk to you about the Python 1.0 dictionary as built by Guido back in 1989-1991. And this sample code is available under /code, and it's the Epilogue code, and it's p1dict.c. So the key thing is that instead of reading the C programming book and K&R in chapter 6, Guido van Rossum was reading page 518 of a much earlier document, which is more about pure data structures and algorithms. And so this was kind of like our Bible on how to write good, fast code. And this was our Bible on how to write sophisticated algorithms. So Guido found this, and he decided he didn't want to make linked lists, and that's partly because of his experience in ABC. And so this is open hashing using an array. So this is an array-based hash concept. And in the bucket styles, there's an array of hash linked lists. And so this is an array that actually everything is stored in the array rather than a pointer to things that are outside the array. The key in open addressing is how you probe and find open slots when your initial hash leads to a collision. And hashes, we try to make hashes not collide, but they can collide. And so this is basically, it uses a circular iteration. And it actually, if you look at there at L3, it's subtracting 1. And if it's less than 0, set I to I plus M, go back to step L2. It's probably just easier to show you a picture of what's going on. So let's imagine that we've got an array of 8 key value pairs, and this is literally an array. In our case, these will become pointers. Key will be a pointer, value will be a pointer. But Knuth is not thinking about that. As far as Knuth is concerned, everything is just a variable. So it's an array of key value pairs. And the key thing to the hash, it's the same hash computation and the same modulo operation that looks at the number of buckets. But when it picks a slot in the array, that slot is just where we hope to store it. But if that's already occupied, we got to find another place. And we presuppose that there's always space, and we'll talk about how that ends up getting solved later with rehashing. But the key is we got to figure out where we want to put it, assuming that there's space. And linear probing algorithm is you start going backwards. So you go from 3 to 2, and is that available? Great, use it. If 2 is not available, go to 1. go to 0. And if you get to 0, you got to go all the way to the end. This is kind of a circular list. Eventually it's going to visit all 8 entries, but it's going to start at whatever entry the hash indicated it's supposed to start. And the whole purpose of the hash is to get to the entry that has the key and value in question more rapidly, or to know that it's not there. And the way you know that it's not there is you run this loop, and when you find a key and a value of 0, which means it's empty, then you know that it's not there, and you also know where you're supposed to put it. So if we look at the data structures that I wrote to implement this Python 1 dictionary, we have a dnode, which is just a pointer to a key and a pointer to a value, because we're going to do strings, key, value pairs to simplify this. The dictionary itself has the size of the array, the alloc, which we've been using all along, count, or length, I switch back and forth in some of this code, and then an array of dnodes. Now remember that that's a struct. So if we look at the constructor, we allocate the dictionary, we set its length, which is the number of things in it, to 0, and we set the alloc, which is the size of the space we can store things, to 2. And then we allocate our 2-item array of struct dnodes, and then we have to mark them. We can't just assume they're zeros when we get it back from malloc. Some mallocs give us zeros, some mallocs don't, but in this case we need to, no matter what, ensure that we have them marked as null, because our null is an indication of emptiness, so that later when we're looking around we can find which areas are empty. And so if we take a look at the put, the hash tells us where to look, and we put this all in P1 dict find, which does the hash computation and does the modulo of the number of buckets and gives us back a pointer to the dnode in question. Now this pointer is either where that key belongs and already exists, or it's where that key belongs and it's empty. Now if we found an empty slot, we don't have to allocate the dnode because it's already the array. We just have to set up the key with a malloc and a copy, set up the value with a malloc and a copy, and then record the fact that we now have one key value pair in our array. We're going to use this not only to return like len, but also to know when we filled it up, because when len gets to be the size of alloc, it's full, and we'll talk more about that in a second. So that's what it looks like after we've inserted one key value pair. Now let's say we're getting a put request for a key that's already in there. So we're going to say z equals w instead of catchphrase. So we run pdict_find, and it comes back and it says here's your thing. But the difference is you look, and the key, the one it's pointing to, the one it gave us back, the one it found, already has a key. Now you might think that's bad news. No, it's great news. It means z already has a slot, and then all we have to do is update the value, because dictionaries function like assignment statements. If you have z that has catchphrase, and then we get z equals w, you're supposed to store w and then throw catchphrase away. And so that's, you see it do that, right? It frees old value, which was catchphrase, and then mallocs the new one and then stir copies into it. And now at the end of this one, we still have a length of 1, and z maps to w in our hash map. So now let's do another put. Let's say y equals b. We're going to do pdict_find, and it's going to hash the value y. It's going to give us back position 1. Now that could be because it hashed to position 0 and linear probing found its way to position 1, or maybe it hashed to position 1. It just doesn't matter. pdict_find says, look, this is the best possible place to store y in this particular array. So now at the end of that, we will have z and y, and we have an alloc of 2 and a length of 2. But now let's say we want to insert c. So the problem is that we're full, which means that pdict_find is not going to find one. Whatever it hashes to, it's going to look through all the rest of them, but there's no space. There's no space in the array. So what we have to do is, if it's not there and we're out of space, we have to expand items. That is the code, what we call rehashing. So let's take a look at the rehashing code. We'll look at this in some detail. At the high level, we store the size and the array of items in old alloc and old items respectively. Then we double the size. That's just how we do it. And then we allocate a brand new array of dnodes. In this case, 4 dnodes get allocated, and that's in items. And then we do some code that pretty much looks like it came from the constructor. We're going to take those 4 D nodes, and we're going to set their key and value to null. Because at this point, we're kind of like halfway through reorganizing this thing. Our old items are available to us, but new items are empty. That means that we can use find and do inserting into the new one. And so that's what we're going to do. Before we throw old alloc away, we're just going to write a simple for loop to go through them. Now we got to check to see if old item sub I is null, because when we're done with this, we're not just going to wait till it's 100% full. We're going to actually reallocate when it's 70% full. If old item sub I is null, .key is null, that means it's empty. We don't have to reinsert it. That's all we're doing, is we don't have to reinsert it. But if we find one, then we go and ask the p1 dict underscore find where to put it. And in this case, we're only going to always get a new slot, because keys are unique, which means we can go through all the old item keys and never hit the same one twice. And there will always be space, because we just alloced a thing that's twice as big as the thing it's coming from. So there was 2, and we've allocated it to 4. We will always find a place to put it, because the keys are unique. Think about it for just a minute. And then we just say key equal and value equals copy them. We don't have to reallocate them or anything. They're just pointers to the saved strings that are key and value. And then the only thing we throw away is old items. And so, you know, it's kind of pretty. Now the last thing where we say old equals p1 dict find self key, we used old before to figure out that, oh, wait a sec, we need to make some more space. So we have to then find where the incoming key, because we're in the middle of an insert right now. So we have to know in the new items where that belongs. And so that's why we say that. So if we take a look at the moment where we're inserting the C key, we're full up. We've got 2 allocated, right? And we're saying, where should we put C? And the answer is you can't. So now we drop in to the reallocation code. So the first thing the reallocation code does is make a copy of old items and old alloc. So there's the 2 items, Z and Y, are there. And then what we do is we double the size and make an empty array of 4 D nodes and set their key and value to null. And so we kind of have the old array and the new array sitting around right now. So then what we do is we start looping through the old array. And we see, oh, Z equals W. So we just run a simple hash calculation and say, where does Z belong in the new items? And then we put it in there. Now we don't have to deallocate or reallocate the actual Z or the actual W. We just have to change the pointers. Now you'll notice at this moment, we've got a pointer in the top one and the bottom one that's pointing to the same allocated memory. That's a reference count problem, but we're going to throw old items away in just a bit. So we loop through that, right? So we find the Z and we put the Z in the right spot. Remember, we're still in the middle of trying to insert C. We've kind of temporarily paused and cleaning up our hash map to give us space to insert. So then we go through the loop again, and now we find that the Y belongs in position 3. Y equals B goes into position 3, and now we're at the point where what we have done, we're still again trying to insert C, but we have to first make space. Now we're kind of done with old items. We've got pointers in the new items that point to the key value pairs, and we can actually just throw that away. Not only when we throw that away, it not only throws away the array itself, but it really kind of resolves our problem that we had 2 pointers pointing to the same thing, which leads us to like memory leaks potentially. But now we've cleaned our mess up. We've freed the old items. We're still in the middle of inserting C. And this is one of the downsides to hashing, is this cleanup phase can take a little while. I just moved everything around so it looks like what we had before. And now that we've got this thing rehashed and we've got our Z equals W and Y equals B in an array that is 4 long rather than 2 long, we are ready to continue with the insertion of C. So we say, okay, where does C belong? We run the hash again with the pdict underscore find of the C key, and it says that belongs in 2. And again, it might be in 2 because it's empty. It might be in 2 because something was not empty and we did collision resolution. But it doesn't matter. When it comes back from find, remember it's bigger, so there's always going to be space. So we don't have to worry too much about there not being space. But now we got an empty slot, and we can put that value in and put the key in and update it so that there are 3 items. The length becomes 3. So that's how they did it, how Guido did it in Python 1.0. But up next, we're going to talk with Guido. We already talked with Guido about how things changed between Python 3.6 and Python 3.7. The same implementation was like Python 0.1 through Python 3.6, roughly the same shape I just covered. But things changed in Python 3.7.
So welcome to another code walkthrough for C Programming for Everybody. This is another in our Epilogue code where we're comparing and contrasting the way I taught dictionaries, lists, and strings in the Kernighan and Ritchie Chapter 6 with how Guido van Rossum actually implemented dictionaries, lists, and strings. And we're going to look at dictionaries here. So I've got 2 tabs open in my text editor. I've got one that's p1dict.c, which is the Python 1 implementation, which is my approximation of Guido's approach and my simplification of Guido's approach. And then I have the krdict, which is the version that I wrote, kind of cleaned up and adapted for this. The version that I wrote as we covered it in Kernighan and Ritchie Chapter 6. And if we look at the very allocation, and I mean the structures at the top, we have a D node, a dictionary node, and the dictionary node in my implementation is got a next pointer, and so it's got a key and a value. We're going to have character, we're going to have string keys and integer values just to keep our mallocs down. But the difference between the dictionary node in my code is that every one is going to be part of a linked list. Because if you recall, in my code in Kernighan and Ritchie, as it's described, it is an array of linked lists. And so in this case, I just have 4 heads and 4 tails that point to the head of a linked list. And so that means that every D node has got to be either the beginning, middle, or end of a linked list. And so it's got to have, the D nodes have to have a star next in them. So let's go compare and contrast that with how Guido did it. So Guido still has a D node because now we're in dictionaries, and so you need a key and a value. So in my krdict, I made the value be integers just to simplify it, but I'm going to make the values be strings in my Python code to be a little closer to, what Guido did. But then the change happens when we start allocating the actual dictionary object itself. So if we look at what I allocated, I have a number of buckets and I have a count for my struct krdict, but then I have an array of 4 heads, an array of 4 tails, which is basically a way to make 4 linked lists that I will select among the linked lists based on the hash function. But that's not what Guido did. In p1dict, we got an allocation and a length, but then we also just have an array, an array of pointers to D nodes that we'll call items. Now the fun thing is, if you look at this, let me go ahead and show you it's a little bit different. If I look at the P1 list and I compare and contrast, a P1 list has an allocation, a length, and a pointer to an array of pointers to strings. In my P1 dictionary, it's an array of pointers to key value pairs. But the alloc, length, and then an array of pointers to something is a very similar approach. And you'll see when we get to the Python 3 stuff that there's almost a duality in Guido's mind between the dictionary and the list. The dictionary is like just a slightly improved list having to do with indexing. And again, it was a surprise to me. And But the similarity, again, when we get to Python, Python 3.7 version of the dictionary is going to be like, oh, I see what you're going on there. But so just for now, remember the approximate duality between dictionaries and lists in Python 1.0. Okay. So again, we have our linked list nodes that have a pointer to a key, pointer to a value. That'll be a dynamically allocated pointer to a dynamically allocated and saved string. And then we have a dictionary, which is then a one-dimensional array of those pointers to those D nodes. And if we look, so the key thing here is we need to know which entries in this array of D nodes are empty and available and which ones are used. So the constructor is a little more complex. If we look at p1 dict underscore new, of course we allocate the kind of object itself. We set the length because there's nothing in it. And we're going to allocate 2 slots, just like we did in the p1 list. That forces us to reallocate so that we don't have to write too big of a code to cause reallocation, and we can debug our reallocation. And then we basically create an array of D nodes, right? So we're like 2 times the size of struct D node. And the size of struct D node is 2 64-bit pointers. And then what we're going to do is we're going to mark them as empty. We need to know that these items are empty. And so we're going to set the key, which is a pointer, and the value for each of them to null. So you've created a 2 long array of D nodes with keys and values of null. And again, we need to remember which ones are empty and are not. And so then let's look at the main code. So that's the constructor, that's the data, that's the data structures and the constructor. So what we're going to do is we're oh man, I thought I deleted that line. That yeah, let's delete this line because we're printing it. We've added some stuff in the print. That makes it a little simpler. Okay, let's hope it still runs. That would be cool. Let's run it. Let's keep change the code. Yay, it works. Okay. Okay, it's simpler. I like simple. So we create a dictionary calling p1 dict new. We print it. It's going to be empty. Then we put under the key of Z the string catchphrase and print it. Then we put the key of, we put W in. That should be a replacement. And then we put the string Sakai in. Sakai equals B basically. Sally equals C basically. And then A equals D. And then we say how many things do we have in there, and then we do a get, like a .get in a Python dictionary. We're looking for the key Z, and we're looking for the key X. Well, the key X isn't going to be in there, and then we delete it. So let's go ahead and run this code, which we just did. And so what this print does, I've added some stuff to it. So you see the first print is just curly brace, open and close curly brace, empty, and it's also printing out the length and alloc. And so basically what it's saying is there is a length of 0 and we have 2 spaces alloced. So then what we do is we put Z in, and that Z ends up in Z equals catchphrase, and that ends up in position 0 in the array. And then we have a length of 2, a length of 1 because we've got one thing in there, an alloc of 2. Then, if you recall, we replace Z equals W. Now because Z hashes to the same spot, and we'll talk about how that happens in a second, that hashes to position 0 in the array, and then it just replaces it. And so it just replaced the value in that case, and so we still have only one item in there and an allocation of 2. Okay? And so then what we're doing is we're inserting a new, like Sakai equals B. I should probably put some more print statements in there. Let's do that. Let's do the underscore put, and let's put a print statement in here. printf insert %s equals %s \n, comma, key, comma, value. Oops. It'll be just easier for us to debug this. Okay. So we insert z equals catchphrase. That goes in hashed slot 0. We have one item and a length of 2. We insert z equals, no, I want to call that put. I want to call that put because it's not insert. So then we put z equals w, and then it uses the hashing and the lookup and all that stuff to find that that's in position 0, and so we simply replace the value. So we didn't extend it at all. And now it's trying to put Sakai equals b in there, and with the hashing of Sakai finds its way to position 1 in our 2-item array. And when we're done, we've got our 2-item array. Happens to be insert order, but that doesn't necessarily mean, because it's just my hash function is terrible. And then we have 2 items in and 2 items out, 2 items in there and 2 items allocated. Now we're trying to insert Sally equals C. And now the hashing algorithm, which I'll show you in a bit, looks through and says, wait a sec, there's no space here. Usually that hashing algorithm says if it's above 60% full, then we declare it no space. And so we're going to do what's called rehashing. So we reallocate and then we re-add the thing. So we're making the space so it doubles it in size. So when it's all said and done, Sakai ends up in position 1, and Z ends up in position 2, and Sally ends up in position 3, and we have 3 items in a 4-long array. Now here's an interesting thing. You will see here, when we go through the rehashing, Z in the 2-long array, Z was in position 0, but in the 4-long array, Z's in position 2, because this is rehashing. Now what happens is that's because whatever the hash value for Z was, modulo 2 is 0, but modulo 4 is 2, and so the positions don't change, right? It wasn't going to end up in position 1, but modulo 2 and modulo 4 are multiples of each other. But you see in this case here, Sakai, Z, Sally, the position of Z moved. And so again, if you're writing an iterator that's going through this, and you just inserted one and it reallocated in that, that's why Python 1 dictionaries, and literally any hash-based dictionary that's truly using hash, we'll see how it worked in Python 3 in a second, but when we reallocate things, stuff gets shuffled around. So the order is different. So we made space for Sally, and then we put A equals D in. Now the thing we're triggering is if it's greater than 60% full. When you have 1 and you got 2, that's 50% full, and that's why the Sakai equals B did not trigger a reallocation. But if we have 3 items in 4 slots, that's above 60%. And so we're going to reallocate. And so even though we could have snuck it in that last spot, that's not good for hashing. So we're going to say, you know what, it's time to make this bigger again. So we're going to so A equals D, we're going to make space for A, and then we're going to double the size of the array to be 8. And let's see, we got Sakai equals B in position 1, we got Z equals W in position 2, we got Sally equals C in position 3, and A equals D in position 4, and we're half full at this point. So we're done now. We have a length of 4, and we say, hey, let's look up Z, and yes, we get W, and let's look up X, and the answer is there is no X. And so our code is working, doing, our little unit test. Our little unit test is kind of doing dictionary things. So let's take a look at put, okay? Let's take a look at print, because print's easier. Let's take a look at print, because print teaches us a little bit about the data structure. Okay, so, come back. So in p1dict underscore print, the whole little first equals 1, that's just there so that we put the comma out. But the nice thing is it's a for loop. For I equals 0, I less than self alloc. Now, if we look at the P1 list, let's go look at P1 list. The P1 list, the array, it's I equals 0, I less than self length. And that's because in the list, we just append in the beginning of the array, sub 0, sub 1, sub 2, sub 3. That's how lists work. But because we're using hashing, our array is like sparse in that it starts out empty and we start using slots, but we don't use every slot in order. So we got to go through all the slots to iterate through a dictionary array. And if it's null, remember if self item sub I dot key equal null, continue, which means skip empty slots. Skip empty slots. So this array could have 100 things in it, and if we only put one where the thing is inserted, which we're going to see in a second with insert, is dependent on the hash function, because we're not just inserting them linearly, we're inserting them based on hash function using open hashing. And so we have to skip the empty items. But after that, it's okay. We just print them. And so we're iterating through this array of pointers, skipping empty entries, and printing out the entries that exist every time we're doing an underscore print. And so we're seeing them in the order that they got spread out using the hashing function. Okay? And so you can see that it prints the key and it prints the value and then it prints the I, the position. And so that leads to, very, very pretty stuff. And then we print the length and the alloc. And so this is great for debugging. Great for debugging for us. Okay, so that kind of reviews that the items is a sparse array with nulls being our way of marking emptiness. Okay, so again, if you go back to the underscore new, we allocated it and we set everything to null. Okay, so let's go look at the underscore put, because that's where all the good stuff happens. It's a bit of work. Yeah, can I get it all on one screen? No, I can't get it all on one screen. Okay, so we'll just work through it. So the first thing we have to do is we have to figure out which of the slots in this array the key belongs in. Which of the slots in the array does the key belong in? So we're going to use a utility thing we wrote called p1dict underscore find to say, find me the entry in the array that is the right entry for this particular key. Okay, so now I got to go look at that. P1dict find. Okay, so this is pretty straightforward. And so this is open hashing. And so the way open hashing works is it starts by doing a hash computation to figure out a position in this array of items. And getBucket, you've seen this in other code that I wrote. getBucket is just a crappy little hash function that does a shift and an exclusive OR repeatedly going through the entire string, with the idea of creating a pseudo-random number that is deterministic based on the string that I can then take the modulo of the number of buckets. So this ends up with a relatively large integer that in long strings might even overflow. And again, computing hash functions is a research area unto itself. This is a terrible hashing function, but I've used it over and over and over again because it's short and gives me some pseudo randomness, but it's probably highly collision resistant. So the whole idea is, if I have two buckets, that gives me a deterministic number between 0 and 2, but not including 2. Okay, so let's go back to the find operation. So we get the bucket, and that bucket might be, let's say it's bigger. Let's say we've got 16 slots and they're all empty. The way it works is bucket will say, okay, you're hopefully you're slot 5. The problem is then there's what's called collision resolution. And if slot 5 is already filled, you got to find another slot. But you got to find another slot in a way that later, after it's in there, you can find it again, find the key again. And so we do linear hashing, we do linear collision resolution, which means if we find ourselves hashing to position 5 and position 5 is full, we say, oh, well, let's just linearly go forward. Let's look at 6, let's look at 7, then 8, 9, whatever. And then when we get to the end, we go 0, 1, 2, 3, 4, 5. And if we get to the point where we have checked all the slots and they're all full, then we kind of have to blow up. And that's where it says printf could not find slot for key. That would be like throwing an exception. We'll just print it out here, but that'd be like, something went wrong, because you're never supposed to 100% allocate a hash. About 60 or 70% is when you're supposed to quit and double it or expend it in some other way. So let's look at the code that hunts for a starting at position 5, hunts for a free position. And so we say offset equals 0, offset less than self-alloc, offset plus plus. So that's going to go, if we have like 8 entries, that's going to go from 0 to 7. But we really want to start that iterator in 5 and then wrap around when we get to 8, okay? And so I call it offset, but then I calculate the position in the array as offset plus the number of buckets, offset plus the bucket, which is 5, and then modulo self-alloc. So if we got 8, offset's going to go from 0 through 7, and the bucket is 5, that's going to go from 5 through 7 and then 0 through 4. Okay, so I is the circular look. So we're doing a circular lookup in an array starting at 5. We're going to look through if necessary, every single position in that array is going to be checked. So we're starting at like 5, where the hash function told us to go. And if self items sub 5 dot key is null, it's a great spot. That means that the hash function pointed us to a available entry, and we're done. So we return the address ampersand self arrow items sub I. Otherwise, we might have found something that's full, and we don't know right now if we're going to replace this value or not. But if the key matches what we're looking for, we actually found the right one. And so we return the address of self items I. And if we didn't find an empty one, and we didn't find one that was full with a matching key, then what we've got to do is go back up into the for loop and go down 1. So if we were at 5 and it was full, but the key didn't match, then we would go to 6. And if 6 was full and the key didn't match, we go to 7. If 7 was empty, then we're done. So we say, oh, 7 is where we're going to go. And so you can see, if you think about this for a little while, and you can go read the lecture slide on open hashing, you can see that as long as there's space in this array and it's not completely full, eventually we're going to find a place. Okay? We're either going to find a place that matches the key, or we're going to find an empty place. And that's what find's job is to do. And again, as long as resize is working and we never let it get to be above 70%, we can always find a slot for the key. Okay? So this, again, when we say printf could not find slot for key, that's really traceback time, because that means that the thing above us, which we're going to look at now, is going to be going to blow up. Okay, so let's look at underscore put again. So come underscore put. So a lot of work gets done in underscore find where we hash the key and then we do the linear look up if it we do the linear lookup for collision resolution, and we either have an empty entry or we have the actual entry. And so the first if statement we have afterwards is if old is not null and the key is not null, that means we just found it, which means all we got to do is replace the value. We don't have to add any entries. The index is great. The array is great. So we just free the old value and we alloc the new value, and then we just string copy it in, and away we go. So that's when we did the z equals w. That was the code that ran to basically say, oh well, we found z, so we just have to free the original string, and the original string is catchphrase, and the second string is w. So we're replacing catchphrase with w, and this little bit of code right after the underscore find is the thing that does, here we found it. Okay? But so that's the second one. Let's go back to z equals catchphrase, because z equals catchphrase is not found because we're starting with an empty array. So that means that old key, we're going to get an old because the hash will find a slot and that slot will be empty and it'll give it back to us. But old key is going to be null, which means this one is available, which is cool. Okay? Now, actually, this to do is not a to do anymore. Right now, it's going to be an ignore. So this is the bit. Okay? I'll come back to this. Okay? This is the tricky bit. Now, I never did this in Kernighan and Ritchie. I don't think. I have to check. But this is called rehashing. And this is when our length is greater than or equal to 70% of our allocation, which means this array is more than 70% full. That's when we're going to do this reallocation. Okay? But I'm going to ignore that whole if statement for now. I'll come back. So we're processing z equals catchphrase here. And z ends up, we can even look, ends up in sub-0 of the array. And so if it's time to insert, this part is really easy. So it's time to insert. We're going to allocate the key, the value, malloc the value, and malloc the key, and string copy them in. The old already exists. Old is a pointer into an entry into an array that's got a key and a value. Okay? So there's an array of key value pairs, and so we don't have to allocate the old itself because the old is already in the array, but we do have to allocate the strings that we've been passed as parameters, and then we add one to the length. And so that's basically how it ran when we're doing z equals catchphrase. At the end, we had z in position 0, we had a length of 1 and an alloc of 2. Okay? So now we're going to look at where we've got a, and you'll notice in my 0.7, let's go back to that now because we're going to look at that. This is kind of tricky. Okay, so this whole self length greater than or equal to alloc 0.7, it allowed me, because it was only 2 items, it allowed me to fill it up completely because one item is only 0.5. And so when I put Sakai equals B in, I didn't trigger the reallocation. So it just put it in position 1. I don't know if, oh, Sakai did go into position 1. So, but now we're doing C. And it's like, I could not find a slot for key Sally. And so that means could not find slot for key Sally. So that means that it searched. Let's go back to find. I guess this is not really a traceback. This is just a fact. So it went and looked at hashed the what's the key on that again? Sally. That key is Sally. It hashed the Sally, found a starting point with bucket. That hash just found a bucket. And where did Sally want to go? Sally ends up, well, in 3, but it would probably have been a 1. Sally would have been bucket 1 before it got expanded. And then it looked through the whole thing, which in this case was only 2, and it couldn't find either an empty 1 or one that matched Sally. And so we say, can't find it, return null. Okay. And so now we get back to put. So we're doing Sally now, and we find old is actually null, so this code doesn't run. So we didn't find an entry. Old key is not even allowed. We're not even allowed to say old arrow key because old is null. And now, find didn't find it, which could be bad, but we're going to fix it. Come back. We're going to fix it. So we're coming through here, and we're saying if self length is too full, greater than 70% full, then we're going to make space. So you can see here in the output, it says we are making space for Sally. We're still in the middle of the put of Sally equals C, right? And so we're going to grab a copy of the old allocation number and the old items. Those are just integers. And then what we're going to do is we're going to make a brand new empty items. And so we're going to double the size of our array. And then we're going to set the new items. That's why I had to store old items here. We're going to set the new items to be 4 D nodes. It's an array of 4 D nodes. Now we got to be really careful. This is kind of like a constructor for that items. We're going to set the key and the value of the newly allocated 4 items in that array to null because they start empty. You'll see in a sec that we got to re-add them. So we're kind of creating an empty array that's twice as big. And now what we got to do, and this is why we call this rehashing, is we got to go through the old array and find all those items, and then we got to add them in the right spot. And this is where you'll notice that Z was in position 0, and Z ends up in the reallocated, rehashed array in position 2. So you really have to rehash it because all the rules in the new one have to be followed. The initial hash, the linear resolution of conflicts, of collisions, etc. So you really think of this items as a brand new one, and we've got the old items sitting there, not much longer, but we're going to go through them all, and we're going to just add them again. Okay, now, yeah, so we're going through all of the old items. If the key is null, that's one of the empty slots in old items. Continue. Then we're going to call find again. And the key thing there is that's why we made self items be the new thing, is so we could call find. So that's the first time it's being called in this loop. The new items is completely empty, but old items I sub key is the key. And then, and so let's see what we got here. Yeah, so new item, if new item is null, that means it didn't find space. Now we just doubled the space, so that shouldn't happen. And given that the keys in old items are already unique because this is a dictionary, we should never find in the new empty the key twice. So that basically says, oh, it's already in there. And the answer is, wait, we started with an empty one. So new item key not equals null is a bad thing. But it should never happen because we have a unique, each key is unique. There are no duplicates. And so as we're inserting them again into a new hash map array, that we should never get it. So that's why it says very bad news. That means that we either couldn't find space because I don't know why, or it's already in there, which I don't know why either. That means that this is like traceback time. This is like the runtime library is not well formed and we made a bug in our runtime library. So then that means that new item should be non-null and it should be empty, which means we can just like copy. Now this is just a pointer copy. It's not actually the stuff because the key is the pointer to the key, the string array, and the value is the pointer to the string array. So we say new item key equals old item sub I dot key, and the same thing for value. And so now what we've done is we've copied all of the old items and we've positioned them correctly in the new items. So at this point, we're done. And the free here is simpler because we're not freeing the strings because we just copied those. We are freeing the array. Okay, so we're freeing the old array. Free old underscore items frees the old array. Now what we need to do is we need to search for the position because we're going back to put Sally equals C. And so Sally is the key that we're putting in. So we just made space for Sally. Now, again, if Sally was already in there, this code would have run and we'd be done. And so we have to re-look in the newly expanded array. We got to find the right spot. And again, if Sally was already in there, this code would have been run and we'd never be down here. So we have to redo this and say, okay, where is Sally? In this case, where should Sally belong? Because we just made more space. And so old equals null would mean we still don't have space for Sally, even though we doubled the darn thing, we doubled it. And old key not equal null, that means that Sally's already in there. Well, wait a second. If Sally was in there, we'd not even come down here. So again, the Sally old key not equal. Again, you put out these kind of tracebacky, very, very bad news. That is like somebody, our code, we're the library writer, our code is messing up. So old is really supposed to find, no matter what, we're adding Sally to the dictionary. Old's got to find a slot for us, or our code is broken. So this is me debugging and leaving this in, just to make sure, like, oh man, that is impossible. Should never happen. But I'm going to say, very bad news. So it finds a slot, and then we just copy the key and the value and increment the length. And so this whole realloc thing is kind of new. I don't think I did this when I did the Kernighan and Ritchie, because the way Kernighan and Ritchie does it, you can just keep extending those linked lists. Like if you look, so if we look at the underscore put in the Kernighan and Ritchie code, you'll see I do a get bucket, right? And I find a bucket, and if it matches, there's always a bucket in this one because the buckets are pointers to linked lists. So there's always a bucket. There's no resolution by linear collision resolution. So if we find it, we just copy the value. In this, I had integer values. And then otherwise, you just append to the end of the tail of the bucket using, self-head sub-bucket equal null, new, and then it's just, at that point, this is just in KRDict, we don't have to reallocate. Now, you would want to reallocate at some point because then these chains get too long, and so it's not like you don't have to reallocate with these chains. I didn't write it, so the reallocation would be sort of in the middle of put, and it'd be very complex code, and it would be actually probably be about the same complexity, maybe a little bit more complex than what the Python 1 implementation was. And so with that, I think I pretty much have covered the essential differences between the Kernighan and Ritchie dictionary code that I wrote and the basic approach, the basic approach using an array of dnode items. And if we look at find a linear collision resolution, and the linear collision resolution, let's do this. I'll put a comment in here. Linear and underscore find. I can't. I gotta figure out how to spell collision. Well, the version you see will have how many S's? No, how many L's? Okay, I'll fix that for you. And so this is linear collision resolution, and that's tricky stuff. And so you want to take a look at that and understand that very carefully. So I hope that you found this lecture useful. I think the next thing we're going to talk about is how dictionaries changed from Python 1 through 3.6 all the way up through Python 3.7, because the dictionaries did change and got a lot better. So we'll talk about that soon. Cheers. Hello, and welcome to another programming walkthrough for C Programming for Everybody. This is one of the last walkthroughs for the Epilogue code. And in this walkthrough, we are going to look at how dictionary, the internal data structures in Python for dictionaries changed between the first version and the 3.7 version. And so we talked previously P1 dict.c about, in effect, Python 0.01 through Python 3.6. And then Python 3.7 and later has a new dictionary that maintains insert order. But it also saves a lot in terms of efficiency. So here is our approximation and simplification of the Python 3.7 dictionary. And so let's talk a little bit about the problem that the Python 3.7 dictionary solved by looking at the Python 0.01 dictionary. Now, if you listen to the Guido van Rossum video that I've got, these key value pairs, in the real version of the dictionary, it stores the pointer to a key, pointer to the value, and the hash value. So it doesn't have to recompute the hash. Now, I kept it simple, and all my stuff was going to be small, so I didn't do this optimization to recompute the hash. I could have, but I just kind of want to keep the code as small as possible, so I just recompute the hash in the few places I need it. But this means that in a 64-bit system, this is 3 times 8 or 24 bytes. And the problem is, let me delete this line so I don't break my code, the load factor. Now, we never let the load factor get above 0.7, which means that by definition, and the larger the structure gets, the larger the wastage is, 30% of the entries have to be empty in the key value pair array. And again, that's 30% of 24 bytes wasted. 30% of the size of the array times 24 bytes, that's always wasted. You cannot not waste it. And so what happened is that in the Python 3.7 version, in effect, items was treated more like a simple linear array of pointers to key value pairs. So now you got your key value pair, and in Python is key value hash and a few other things. So this is a larger data structure. Dnode is a larger data structure. And then we have a separate simple integer array that is the index, because items is an array and index is the offset into that array, but that's just one integer. And so we're going to do all the hash indexing and resolution and conflict resolution and collision resolution in this index array, which itself is a much smaller item. And I'm going to just make it, and I don't know if Python does this, I'm just going to let index be twice as long as items, which means from an indexing perspective, we never get a load factor above 50%. And we're only going to extend the array when we run out of space in items. And we're going to store the key value pairs linearly 0, 1, 2, 3, 4, 5 in items, and then we're going to just reallocate. So in many ways, all of a sudden, the kind of reallocating, let me open a new tab here, p1 list.c. The reallocating code, if we go back to the p1 list, extend if necessary, you're going to see that in p1 list append and p3 list append, we're going to see that it looks a lot like the realloc pattern in the Python list, because it is an array. Okay, the actual key value pairs are stored linearly in an array, and that's also how you end up with maintaining insert order. It wasn't, they tried to maintain insert order, but at some point, if you're just using a linear list, 0, 1, 2, 3, 4, insert order is going to be maintained. And if you delete one, you shift them all up, and it just treats. So I would guess that ultimately inside of Python itself, after 3.7, there might be some overlap in the code between dictionary and list because they pulled out the hashing lookup in this separate data structure, which is an array of integers. Okay, so then if we look at the get bucket is the same. It's a lousy hash function. I did it as small as I could just so it didn't take up a lot of screen space. If we look at the constructor, p3 dict underscore new, we see we're allocating the actual dictionary object, and then we're allocating 2 key value pairs, 2 struct D nodes, and then we're allocating 2 times the alloc size of integers. And so our index is 4, and our D node list, our D node array is 2. And we don't have to initialize the key value pair array, the items array, because we know with length which ones are valid and which ones aren't valid. But we do have to take this new index and put -1 in there. We did this a little differently in Python 1. Dictionary, we use nulls, but right now it's an array of integers, and the -1 is going to be my marker. That's going to be my marker to say this is an available index slot. Okay, so that's what the data structures look like. Let's go ahead and run the code. Now you'll note that this code is in effect exactly the same as the P1 dict code that we went through before. And so we'll run it, and it will look stunningly familiar, meaning that we have an empty dictionary. We're putting Z equals catchphrase, and putting Z equals W, Sakai equals B, Sally equals C, A equals D, and we're printing it out. So now we're printing it out. This is like an iterator. So Z catchphrase, and then 0 is the position in the index, not the position in the items. It's the position in the index. So this is in index position 0. And so we see Z maps to W, Sakai maps to B, and they're in index positions 0 and 1. It's kind of hard to hash, because we don't have to rehash until it's completely full, and we have 2 items. The alloc is 2, so we can put Z equals W and Sakai equals B. Remember that index is 4 when alloc is 2. So index has 4 integers, so we still have a load factor of 50%. But now what happens, we're going to put Sally equals C in, and now we have to extend the items, and we automatically extend the index. So we have a 50% load average before the extend, and then we have a 50% load average after the extend. Well, actually less than 50% load average, but the point is because I just, by definition, had my hash index be double the length, I never get to a load average of 0.5. Above 0.5. And again, you can make this more complex and let the load average get to 0.7, but I'm keeping it really simple. The other thing that you'll notice is in the rehash, again, thinking back to the Python 1, so you'll notice that the hash position of Z, just like in the previous one, after it went from 2 to 4, went from position 0 to position 2. And I talked about how it's not going to completely move randomly, but it hopped in this case because whatever the hash value, modulo 2 was 0 and modulo 4 was 2, and that's because 0 is modulo 2. So these things kind of go by powers of 2, but B equals 1 stayed in the same place, et cetera, et cetera, et cetera. And so, but here's the thing. Notice the order of the things printing out. These 0s and 1s, et cetera, that's the hash position, but it's not the position in items. So Z equals catchphrase is item sub 0. Z equals W is in item sub 0. Sakai is B, that's in item sub 1. Hash position. So Z equals W in this output is in hash position 2, but items position 0. And so you'll notice that insert order is maintained in this, unlike the P1. Again, this wasn't to make insert order work. It was a side effect of changing the data structures to make items be just an indexed array starting at 0. And again, pulling the hash computation, items is an array that's linear, and index is an array that is looked up by a hash. Okay, So let's take a look. So let's take a look at put. And of course, the first thing we see is P3 find. And just underscore find. So recall from the previous one that the goal of find is to find a bucket position that's free and available. Okay? And so remember that get bucket is just the hash computation for that particular key we're looking for. And we have the same kind of circular, this will give us a number between, 0 and 8, like 0 through 7, if there's 8 entries, or 0 through 3 if there's 4, or 0 through 0 or 1 if there's 2. And then we have to go with the circular look, okay? But you'll notice now when I say for offset equals 0, offset less than self-alloc times 2, I am now looping through the index array, not the items array. And I do the same little trick to do the modulo so that it goes like 5, 6, 7, 0, 1, 2, 3, 4. So I goes 5, 6, 7, 0, 1, 2, 3, 4, which is exactly what you need to do collision resolution using linear probing, which is the way we do it. And it's very simple. If we find an empty spot in the index, now the data is not an index, the data is still in items, right? So if we find an empty spot in index, meaning it's a -1, that's a free one, and that's what we're going to return. Notice that in this one, I'm returning an integer rather than a pointer. I probably should go back and change all those others to return integers instead of pointers, because I think it makes the code easier. It looks a little more complex in some places, but easier to understand in other places. If it's -1, we're done. If we look at the key and we find in items now this one's a little trickier. We're comparing the key to self items, which is the key value pairs, right? But it's self-index sub I. Self-index sub I is the position within items of a particular key value pair. So we have to look up using self-index to find the right spot, because self-items is like a linear list. It's not really a hash map. The only thing that's hashing here is the index. And then we go grab the key out of the thing. And if we match it, we're like, oh, this is the position. Oh, by the way, I found it. So in our calling code, we'll check to see if it's empty or not. But right now, if it's empty, we turn I. And if it matches, we return I. Otherwise, we keep incrementing. Now, the key thing is, because the load factor is only 0.5, this is always going to succeed. That's another nice thing about this. It always is going to succeed, because when we increase the size of items, we also increase the size of index, so that index is always 2 times the size of items. So we never get a load factor above 0.5, which means this feels to me like a lot more reliable code. And if we don't find an empty slot, which in the other one that was a trigger for reallocation, but in this one we reallocate differently. So returning -1, that's just like not a good sign. Okay, so let's take a look again at find. At the put. So this code here, when we do the find, position equals P3 dict find of the inserted key, we basically say, if the position is not equal to -1, that means this is a valid entry, which means we're replacing the value. And again, that's the scenario where we have z equals catchphrase, and then we say z equals w. We're just going to replace the value. We're not going to change the key. The key is already in the right position. The key is already hashed properly. The index is correct. The items is correct. And all we need to do is grab the value and get rid of it, and then alloc the new value and stir copy it in, and we're done. So we're done. So if we find it, that's great. Okay? So we don't find it, we have to insert it. But we know where to insert it right here. But now what we do is we simply say if self length is greater than or equal to self alloc, that's when we're going to expand it. So here we're saying if self length is greater than or equal to self alloc 0.7. Now the alloc here is the number of things in the items, which we're using linearly, which means we can fill it up 100% before we have to extend it. So we're looking to see if the length is greater than or equal to self alloc. Here we were looking at, is the length greater than or equal to self alloc times the load factor 0.7. That's when we triggered in Python 1 dictionaries. But if we look, this append says if self, and now we're in P1 list. This is again that duality between Python 1 lists and Python 3.7 dictionaries. Because in a sense, the items is just a list, right? So if self length, which means now it's full, it's 100% full, it's 100% utilized, there are no spaces in items. If self length is greater than self alloc, we're going to extend it. So that means that this code here, self length, self alloc, is really quite simple, right? So we just realloc the items and realloc twice and realloc whatever. We're going to do twice as big in this case. And so that is like exactly copied from the list. We just realloc. Okay, so but now we got a little bit more work to do in Python 3 because the items was easy. We just realloced it. We did exactly what lists would do in this situation. But now we got to fix the index, okay? And so, so self items at this point is right. Okay, so self items is right because realloc did all the work for us. You know, we doubled the size of it, but then it copied all that stuff. Okay, and the other thing we don't have to do here, which we did have to do in Python 1, is we didn't have to set all these new items that have been allocated because in items, because it's like a list, alloc and length is all that matters. And we haven't changed length yet. We have changed alloc. So the fact there might be garbage in all that new data, it might be zeros, might be garbage, is okay. Now what we're going to do is rebuild the index. Items hasn't moved. And so we don't need it. We just free index right now. Remember, index is that integer array that's twice alloc, right? So now we just allocate another integer array that's twice the size of whatever we've got allocated in items, an integer array. So self arrow alloc times 2 times size of int. Boom. And then we just have a little for loop for I equals less than or equal to self alloc 2i plus plus, set it to -1. Because what we're doing is we're creating a new completely empty index. The key value pairs are just sitting there happy as a clam in items. But now we got to make a new index. Okay? So we're going to refill this index, but it's really simple. So now we're going not to alloc for I equals 0, I less than self length. Now we're going to go through the items, and that's length. And then we're going to call the find operation based on the key of each of the items. And that's going to give us a position. And it's going to do conflict resolution, collision resolution using linear probing. And so at that point, all the index at that position is, the position is where in this array should it go. And that means that, you know, if it's in the 3rd position in the hash map and we're looking at the 0th position in items, I is 0 and position is 3. And so this code, if you compare this code, again, it's better memory-wise. If you compare this code to the code inside, if you compare this realloc code between the Python 1 code and the Python 3 code, and I don't even do it in KR because it was going to be so ugly I didn't want to show it to you, right? So it's ugly in Python 1. It is pretty in Python 2. I mean, seriously, this, you look at this code in _put for a while, and you'll be like, why didn't they think of that back in 1989? Why did it take them till whatever 2018 or something to see this? It's a beautiful data structure, right? It is a beautiful data structure. Okay, so here we are in this code where we have refilled the index, and again, self-index is changing, right? And because that's how the conflict resolution works.
and positions in the index might be different before and after. So after that, we're done extending. We're going to have to do the actual insert, because the reason we extended was we were going to insert a new thing. In this case, if we look at, we're trying to put Sally equals C in, then we extend from 2 through 4, and now we're like done extending, and so we got to put Sally in, right? So Sally's going to go in, and this is the insert code that we've already looked at, right? But we do have to go find the position of Sally, because we found it before in the pre-expanded index/items, and now we're finding it in the post-expanded index/items. But then we just allocate the key and the value, copy them in, and then add the key value pair at the end of length, which is not alloc, but length is like the next position in that linear array of items. So we're new items. We set the new key, the new value, and then we set the index to be pointing at this entry in self items, because index is an integer. So it's like if we're putting it in, so if we're expanding from 2 to 4 and we're going to now use 3, position 2 actually, self index, whatever the position is computed by hashing and linear collision cleanup. And then we set it to length and we add 1 to the length. So if you watch kind of all this stuff, it just, of these 4 lines of code, only one of those lines has to do with hashing, and that is the self-index position equals self-length. We're recording, it's kind of like recording a cookie crumb in the Hansel Gretel. So we're just remembering in the index where that is, so we can jump to the right position in index quickly using hashing, rather than doing a linear scan of the key value pairs. But literally, if you took this index away, you have just a list. And so again, let's look at Python list. Yeah, this is simpler because I'm not, yeah. But all it does is it extends, this was a list of strings, so it's actually a little simpler. But all it does is it copies the string and then puts it at the end and then adds 1 to the length, and it's done. And so the Python 3 dictionary does that. It's kind of cool. So as we put Sally C, it extends it. It recomputes the index, and that's why the hash position of Z moved, but not the position in items. The position in index moved because this sub 2, Z maps to W in position 2. That's the index position, not the items position. The items position is just like a linked list. Z is in 0, Sakai is in sub 1, and Sally is in sub 2. And so that's insert order, and everything works pretty well. And so for me, as I think about like the Python 3 dictionary and compare that to classic Kernighan and Ritchie dictionary, where the classic Kernighan and Ritchie dictionary was so complex on rehashing that I didn't even write code for it. I'm like, oh, let's pretend that's not a problem, okay? And now I can tell you in the Python 3 code, I can go all the way through the rehashing and tell you that it's some of the more beautiful code that I've seen. So I hope you found this valuable. Cheers, and I hope to see you online.
So now let's talk about what happened between Python 3.6 and Python 3.7, where dictionaries began to maintain insert order, not key order, but insert order. So it really, what the basic idea here is that the hashing is a quick way to find a starting position in an array, but it doesn't necessarily mean that everything has to be stored in hash list. So now what happens, and you saw this, the code we wrote with trees, the tree map exercises. You can have sort of more than one data structure that you're maintaining at the same time. And so that's what's happening in Python 3.7. Now in Python 3.6, we made a big fuss about how there was no order. And when you go through the code walkthroughs, you'll see that sometimes the order changes at the moment of rehashing. So the order is pseudo-random, as it were, but the order can then change at any moment because of rehashing. And but the pseudo-randomness is because of hashing, and it's not even consistent from insert to insert because rehashing and not database hash map reorganization. So, like I said, Python 3.7 separated the notion of the hash index from the key value store. And so this leads to the fact that iterators that go through Python 3.7 dictionaries function much more like Python lists, which are iterated in key order. Now, you don't have a sub-0 or sub-1 because that dictionaries don't want to give you that semantic. But it basically is a Python list plus a hash index for quick lookup and quick for inserts and gets. And iterating through the dictionary is just like the Python 1.0 list. And key lookup by key and insert by key is still very quick. Now, I have a whole long walkthrough that goes through all this, and I'll just kind of give you the high-level picture, and that will help you when you go through the walkthrough. So if you look at struct pdict, it's got an allocation, and it's got a length, and it's got a struct dnode that is an array of items. Okay? But now we have an integer array that's index. And in the code that I wrote, I just made index be twice as big as the number of items in index was twice as big as the number of items in items. And that basically meant that I always had space. And so I ended up with a load factor of 0.5. And so if you look at items, it's a list, meaning that we insert z equals catchphrase, z equals w, y equals b, and c equals 42, and they maintain insert order. And a new insert is just done at the end. So what we're seeing here is a list that's 3/4 full, but we don't care about that in the same way as we did in the Python 1, because the load factor of the items is irrelevant. It's the load factor of the index that matters. And because I'm making the index twice as large as items, it never reaches a load factor above 50, meaning we reallocate when we need to make the list bigger, but then we also make index bigger too, and so we never exceed a load factor of 50%, which makes things really smooth and really easy. Now the key thing is the index is an array of integers, and what's stored in each integer, as you can see with these arrows, is simply the index that the key value pair lives in the items. So again, this is kind of two simultaneous data structures. The index is a hash. Items is a list. And index points to the offset within the list. Now, I didn't do it, but Guido could easily have shared some of the code between, and some of the optimizations between list and the items in a dict. So I'm not going to go into it. I do have a code walkthrough that takes a good bit of time that goes through all this code. Just remember this picture, but it's really kind of extracting the hash index into its own table. So in summary, we learned from Guido, surprisingly, that he loved realloc and expandable arrays of structs with pointers to his objects. Linked list is not hardly used in Python's core data structures, and it turns out to be a really, really good choice in retrospect. The code is surprisingly simple once you start taking a look at it, and you're kind of glad. I was kind of glad to leave linked lists behind, even though I'm pretty good at linked lists. And moving memory management into Python from realloc was something that happened like 10 years later that Guido mentioned, because the realloc wasn't as predictable as he wanted it to be, and eventually there's this concept of garbage collection, which is underneath realloc, and it was too difficult to hope that realloc was going to do the things that Python wanted done. So the places in the code that you've looked at here that use realloc now use a Python allocator. And realloc what happens is realloc gives us bigger chunks of memory, and then Python manages those and garbage collects them and cleans them up, etc. And so that's the modern era of Python really depended a lot less on the cleverness of realloc, because it just turned out to not always be as clever as we thought. But there's more. Guido and I didn't stop talking after we talked about the data structure shape. The whole surprise linked list thing. I'm like, oh. And so if you recall, I had this picture, which was kind of like not just how things worked. I was placing, in this picture, I'm placing C in the context of all the languages that influenced C and all the languages that C influenced, right? And so this is you've seen this picture before. But what I wanted to talk to Guido about is I wanted to talk to him about what were the influences on Python. C, C++, ABC, and as you will see in the video, Modula. I wasn't expecting that. But I don't know what I do know what I was expecting. I was expecting that he didn't like C++ and he loved C, and I didn't know as much how strongly ABC had influenced him. So in ABC there was much to like and for him much to dislike. So C++, something Guido used it. He wrote code in it. He wrote a series, sounds like a series of experimentation as to to some degree, I guess maybe his question was, is C++ so awesome that I can get done what I want to get done in Python and C++? And so he did some C++ experiments that he found somewhat disappointing. And so that's why he used C instead of C++, because he could get done what he wanted to get done. And so Guido chose C as a language to build Python, but Guido learned a lot about how to layer object-oriented concepts on top of an otherwise procedural programming language. And so C++ had a big influence, and I bet at some point he thought C++ was the answer and then said, no, I got to use C. And of course, ABC, if you look at the Wikipedia entries, like ABC influenced Python, and the answer is yes, but it influenced it more than you might think. And that is that there were things that Guido liked and things that Guido didn't like about ABC, places he wanted to improve. So ABC had a lot of cool types. ABC handled allocation and deallocation using reference counting. Guido liked all that stuff. But it used B trees internally, and B trees are not binary trees. B trees are a thing that's most commonly done on databases. The other thing is it had no mechanism for user-defined classes. All the concept of object orientation was in the language itself and in the language implementation itself, and there was no chance for users to define their own objects in ABC. And so, ABC did what it did well, and Guido knew ABC well and worked on ABC and knew what he wanted to take from ABC and knew what he wanted to build beyond ABC. I think that in some ways the language ABC is kind of pretty. I can read that, and you can see things like split and in and other concepts, the for loop, the sort of implicit iteration in the for loop, for line in document. You can see that just came straight to Python, except he made it all lowercase, of course. ABC was kind of COBOL-like, where you wanted how to return words, document as parameter. That first line is a little bit tricky, right? He also wanted real object orientation, and he wanted to stay much closer to the C libraries, because ABC didn't really care about being able to call like C string libraries or C socket libraries or anything like that. And he wanted lowercase keywords. Another thing that surprised me was the fact that Modula 3 was a significant influence. So Modula 3 was a rather European-centered language. It kind of came from Pascal, which came from Zurich, ETH and Zurich. And so this was the kind of thing where folks like myself in the United States really didn't think too much of Modula. But Guido was clearly investigating how to do things, and there were some really good ideas in Modula 3. And he went and talked to the folks at Modula 3, and the concept of self as the first parameter is a way to layer an object-oriented mechanism on top of a procedural language. Really, the concept of self was inspired by Guido's interaction with Modula 3. I'm going to give Guido the last word here. So I'm going to put the second half of my interview and just let Guido talk about what inspired him as he was designing object orientation in Python.
Can you walk us up to the inspirations and the history of how perhaps ABC got so good at OO?
So ABC was actually not object-oriented.
Okay.
ABC had a fixed set of data types. Well, the data types were composable. Like you could have, say, a list of integers or a list of strings, and those would share the operations on lists, but sort of there was no concept of class, there was no concept of users defining classes, there was no concept of subclassing either in the implementation or for the built-in types.
So
there was like
ABC had a bunch of really convenient to use primitives.
Yeah,
They did a lot of work for you, but they weren't really OO.
that's correct. And they insisted that there was only a single numeric type. So in part so that they could sort of not deal with the complicated hierarchy of integers and floats and rationals and sort of
But when you started Python,
Yeah.
you had like object orientation very front of mind, not just a convenient set of primitives, but a convenient set of object-based primitives. Where did you read that in it?
Yeah.
Or did you read that somewhere else?
I was familiar with C++.
Okay.
Yeah, and I think that might have been the only object-oriented language that I knew at the time. At least I can't think of any. Well, I own a big book about Simula, which is the sort of the granddaddy of all object-oriented languages. I don't think I ever managed to get my hands on a Simula compiler. And I have to admit, I also only skimmed the book because it was actually sort of...
Had you written C++ before?
Yes.
Like how much have you written C++?
Enough to invent automatic, or I forget what they're called, the pointers that are like automatically ref counted. So yeah, I forget.
So you layered
there are standard
ref counting on top of C++ so that you would not lose your sanity while working in C++.
No, because I was very familiar with ref counts, because ABC's implementation is written in C and everything uses reference counting. And it works out better in ABC because there are no cycles possible in the data types, because there are no mutable data types. You can't have an object that contains itself or references itself directly or indirectly in ABC. I don't think that I sort of realized all the details of why that is important, and I didn't care because pragmatically those things aren't always as important as they seem to be theoretically. But anyway, I was very familiar with reference counting in C, sort of for how it was used for ABC. I think that's where I learned about it, and I didn't sort of hear much about it elsewhere. Then at some point when I was teaching myself C++, this must have been in the mid-80s, one of the things I tried was, my experience with ABC and reference counts in the implementation was that it was very error-prone. we regularly had to sort of deal with bugs in the implementation where we either leaked memory or sort of crashed because we had freed things early, and it was always like, oh, there's a missing incref or decref. And of course, the missing decref is much harder to debug because you leak a byte here and you leak a byte there and nobody notices because people didn't write large applications in ABC. So anyway, someone probably put me on the idea of in C++, you can override primitive operations to the extent that you can build automatic reference counting. And I built that for some toy application and played with it and realized that it didn't work right. The problem was that it was like, and I probably didn't know enough C++ at the time, or possibly C++ hadn't developed certain subtle mechanisms like move operations. It was very crude, like overloading assignment. That was basically what I did. And so I found that where if I had handwritten reference count operations, I would sort of know, okay, this object is owned here, so we pass it to some function. That function doesn't have to increment the reference count just because it's using that object, because it's not going anywhere as long as the caller of that function has a reference to it. On the other hand, the automatic reference counting, as I had implemented it using C++, would say, oh, we're passing this thing as an argument to a function, so increment the reference count. Oh, that function returns, decrement the reference count. So there was much, much, much more reference counting activity, and sort of that part I didn't like, and so Python still does it manually and is written in C, not in C++. But somehow I picked up the idea of vtables, or at least arrays of pointers to functions, as a handy way to implement objects. And actually, initially, for the first probably 6 months, Python was not object-oriented. And so very few people saw that, like a handful of my coworkers saw that. And the sort of the implementation had this notion of you can implement an object type by putting a bunch of function pointers and a bit of other information in a standard structure that describes the type. I called it a type, not an object.
So in a way that you were emulating C++'s way of kind of like creating a perception of object-oriented programming without truly being an object.
Yeah. Oh, and wait a second. There is another step that I just missed. So in around 88, I spent a summer as an intern at DECCirc, and I talked to the designers and inventors of a language named Modula 3, and they were like putting the last proofreading efforts for the Modula 3 report, but they had built a Modula 2.5 compiler. They called it Modula 2 Plus. And in their documentation, either the draft of the Modula 3 manual or the internal Modula 2 Plus manual, I learned this concept of how Modula 2 Plus and 3 do kind of not quite object orientation, and I think they meant it as sort of a reaction to how it was done in C++. They said Modula 3 is not actually an object-oriented language, but the key part of object-oriented use, where you define a class through a bunch of functions, and the notation where you say object.method and then the argument instead of function and then the object and then the rest of the arguments. They said if you use that notation, object dot or thing dot method paren and then arguments, thing had to be something that had a type. I think it was a structure type that had a bunch of pointers, function pointers in it. And so the method names were simply fields or members of that structure in modular 3. And so to create the equivalent of a class, you defined a structure. You defined a structure that had a bunch of function pointers. They were all typed, so you could say this is a function that takes one argument of this type and it returns blah blah, and then a bunch of those with names. And the trick was if the compiler sort of noticed that you were using that and then you were calling it, it would say, oh, we're going to insert the thing whose method you just used as the very first parameter to the function. This is where Python's explicit self comes from.
Exactly.
And so that is all modular 3's design that I copied. And so originally in Python, I didn't have a user level notation to even do that. The type system was only extensible by writing a C extension.
Oh.
And so the author of
class keyword, what we think was the class keyword, was not there.
That was
a month and a half.
That in the first probably 5 or 6 months it wasn't there, and I think we had an intern who knew C++ better, or who somehow had the right.
Liked it better.
Who knows? He was younger than me, and he said, "Hey, if you want to give users the ability to define their own classes, here's a hack how you could do it. You add this little bit of syntax, and then you map it to this structure at the implementation time, and it all works."
And that's 5 months in.
And yeah, and so everything else was working. We had like a working interpreter with a REPL and integers and floats and strings and tuples and lists and dictionaries and functions and types that were sort of internal things. I think even then you could ask for the type of an object.
Did you, at the time, in these first 6 months of Python, did you feel like you were doing core research on what object orientation was going to mean in the future?
No.
Or were you just students? No?
I was just hacking together an implementation of a language that I didn't know where it was going. I obviously spent enough time on it that I was hoping it would go somewhere. But
you didn't think of yourself as like that you were going to someday like write a paper about like how object orientation should be done. You weren't thinking like a researcher would think.
definitely not that.
You were just solid problems.
I was not a researcher. I was a programmer. I do not have a PhD. I was employed by CWI as a programmer.
Do you now even think maybe that you made a profound contribution?
You're the first person to tell me that, and I'm not sure that I totally believe it. I would say that the Modular 3 inventors sort of made that contribution, because they were much more sort of researchy types, theory types. They thought long and deep about all the sort of theoretical and eventual repercussions of designs like that. And I was happy to implement something even even if there were edge cases where it would just not do the right thing at all. Like, until we finally, after about a decade or so, added a cyclic garbage collector to the language, Python would leak memory irretrievably in many situations where you had created a cycle and then lost the last pointer into the cycle from outside it. And it took a very long time before our users convinced us that there were some edge cases where that was actually a real problem and there was no good existing solution.